This new mathematics was not about things, that is, objects with their properties and relations, nor even about those properties and relations independent of any objects. It was, or at least seemed to its practitioners to be, about concepts, concepts of objects of various sorts, concepts of various sorts of relations and functions, concepts of properties of objects and of functions, and eventually, concepts of a radically new sort of thing, namely, a structure. The whole of mathematics was in this way to be reborn as a purely conceptual enterprise, one that unlike earlier mathematics, which was conceptual but unknowingly so, was explicitly and self-consciously conceptual. This new subject matter was further understood to bear no intrinsic or internal relationship to physical reality, that is, the world revealed in sensory experience. The world of the mathematician is rather a self-enclosed, autonomous realm of meaning subject only to its own internal demands. Point 24 Because traditional abstractionist conceptions of concept formation can have no place in the domain of mathematics as it is now to be understood, this new subject matter required also a new account of the mathematician's intellectual access to the subject matter of mathematics. It is very natural to think, as Aristotle did, that our concepts of such things as circles, triangles, and numbers are the result of a process of abstraction that begins with our sensory experience of instances of circles, triangles, and collections of objects. And although the relations and functions of concern to Descartes and 18th-century mathematicians following him are not in the same way abstracted from our sensory experience of objects and collections of objects, nevertheless it was possible, as Kant shows by example, to maintain this kind of naive abstractionism even in the case of early modern mathematics insofar as, at least in principle, relations that are displayed in the symbolic language of arithmetic and algebra can also be exhibited in geometrical figures. One cannot in the same way display the concepts of concern to modern mathematics, for instance, the concept of a function conceived as a mapping or that of a group. Point 25 And in any case, we have seen, in the work of mathematicians such as Riemann and Dedekind, there was a self-conscious turn away from representations of numbers and functions on the grounds that particular representations introduce something arbitrary and inessential, something merely external, into what ought to be the study of the internal, constitutive features of things. Thus, although one might first discover, say, the group concept by consideration of cases, by a kind of Aristotelian naive abstraction, the concept in its mathematical use is instead to be given by a kind of top-down characterization in terms of the properties that are constitutive of a group. Point 26 The fact that the instances have these properties is to be seen as secondary. On the view of naive abstractionism, the concept is what it is because the instances are what they are, it is the instances that are explanatorily basic. This is, furthermore, explicit in ancient thought. One can give a definition only of what exists because what the definition serves to do is to set out the essence of things of that kind. It sets out what it is to be that kind of thing. One must then start with instances of the kind as the basis on which to develop one's definition. On the new approach, the explanatory order is reversed. The instances are instances of the concept because the concept is what it is, constitutively and intrinsically characterized by higher order properties. The concept comes first, in the order of being if not in the order of knowing. And it must come first if mathematics is to be freed of the limitations that would otherwise be imposed on it by what is intuitive. A simple example illustrates the essential point. One begins in arithmetic by considering cases, particular sums, products, and so on, and on that basis comes sooner or later to notice that the order in which one, say, adds does not matter to the result, that adding 2 to 3 is equivalent to adding 3 to 2, and so on for any pair of numbers one cares to consider. Abstracting from the particular numbers, one might then say that a plus b equals b plus a holds generally, that is, for any pair of numbers one cares to consider. But now we can invert the order of explanation, see this equation not as expressing a general feature, that is, a property, of particular sums of numbers, but instead as disclosing a constitutive feature of the operation of addition, that, as we in fact say, addition is commutative. Point 27. That is, we read the equation not now as about numbers but as ascribing a property directly to the operation of addition. Numbers do not come into it at all. And once having taken such a top-down approach to addition in terms of its intrinsic properties, we are free to apply the notion in contexts involving numbers that are quite unlike traditional numbers so long as they behave well enough with respect to addition as it is now to be understood. Consider now not only the commutativity of addition but also other familiar fundamental laws of elementary algebra, namely, these. 1. Commutativity of addition and multiplication, a plus b equals b plus a times b equals b times a. 2. Associativity of addition and multiplication, plus c equals a plus, times c equals a times. 3. Distribution, a times equals plus. 4. The existence 28 of 0, there is a number 0 such that a plus 0 equals 0 plus a. 5. The existence of unity, there is a number 1 such that a times 1 equals 1 times a. 6. The existence of additive inverses, for any number there is a number a such that a plus equals 0 equals plus a. All these laws, although first formulated for ordinary numbers, soon came to be seen to hold of other systems of numbers as well. Any system S of numbers that is closed under addition and multiplication and satisfies these laws is a commutative ring with unity. A ring is a structure that satisfied through, save for the commutativity of multiplication, plus. And other similar mathematically interesting structures exist as well. Obviously, any theorem that can be proven on the basis of just these basic laws governing addition and multiplication, will hold in any system of numbers that satisfies the laws from which the theorems are derived. Point 29. The concept of a group, the central concept of abstract algebra, takes things a step further. It concerns not the arithmetical operations of addition and multiplication but instead the concept of a collection of elements C together with some operation asterisk on those elements where C is closed under asterisk that satisfies the following three constraints. The operation asterisk is associative asterisk C equals A asterisk. There is an identity element I in C such that I asterisk A equals A asterisk I. Each element A in C has an inverse such that A asterisk A equals I equals A asterisk A. That is, much as Descartes abstracts from particular measurable quantities to focus on the relations such quantities can stand in, so in group theory one abstracts not only from any actual collections of elements but also from any particular relations. Ontologically a group is a kind of an object, but it is a peculiar sort of object insofar as it is not merely a thing with a nature or a subject of predicates, a primary bearer of properties. It is instead a kind of structure, where a structure is a system of elements in a certain relationship. The concept of a group, as set out above, is the concept of such a system or structure. Although at first abstracted from particular mathematical instances of groups, the group concept comes in this way to be understood top-down, as given by its constitutive properties, the associativity of its operation and so on. In the concept of a group there is no reference either to any particular elements or to any particular operations but only to certain properties of collections of elements and of operations. And the elements in the collection need not even be objects, though they can be. In Galois's work, for example, the elements are the various permutations that are possible on roots, and the operation asterisk is composition on permutations, that is, one permutation followed by another, which is associative. The identity element is the do-nothing permutation, and because for every permutation there is one in reverse, the last condition is satisfied as well. The collection of permutations together with composition thus form a group. The integers similarly form a group under the operation of addition because, any two integers can be added together to form another integer, the addition function is associative, there is an identity element, namely, 0, and for every integer there is an inverse. If 0 is excluded, the rational numbers likewise form a group under multiplication. These facts about the integers under addition and the rationals, excluding 0, under multiplication furthermore explain the fact that linear equations of the form a plus x equals b and x equals b are inevitably solvable. A simple example illustrates the point. We begin with a linear problem, say, 7 plus x equals 12. Because 7 has an additive inverse, namely, minus 7, we can add that number to both sides, 7 plus equals 7 plus 12. Because addition is associative, we can infer that plus x equals 7 plus 12, and by a simple computation get that 0 plus x equals 7 plus 12. Because 0 is the identity element for addition, it follows that x equals 7 plus 12. Simple computing yields the result, x equals 5. And the same point holds mutatis mutandis for the case of the rationals under multiplication. Much as the law that x2 plus y2 equals r2 underlies and explains the characteristic look of a circle, so we see here how fundamental properties of groups can underlie and explain characteristic results of early modern mathematics. The mathematical concept of a group has proved extraordinarily fruitful. Beginning with only a few explicitly defined concepts, mathematicians have proven a whole range of important, and sometimes surprising, theorems. Group theory has furthermore revealed important connections between different parts of mathematics. Felix Klein, for example, used group theory to show why the quintic equation, which as we saw is not generally solvable by radicals, is solvable if appeal is made to a certain sort of complex function, the elliptical function, and he did so by showing deep interconnections between the quintic, the theory of rotation groups, and the theory of complex functions. Nor is the interest of group theory confined to mathematics. Group theory has important applications in, for instance, physics, chemistry, and engineering. The notion of a group is exemplary not only of the sorts of entities that are studied in modern mathematics but also of its extraordinary fruitfulness and power. Point 30. The concepts of modern mathematics, although they may first be discovered by reflection on instances, are to be understood independently of any instances, by appeal only to various properties and relations as set out in definitions. Something is an instance of the concept if, and only it has the features stipulated in the definition. This begins to explain why the concepts of modern mathematics have sometimes been described as Kantian ideas, that is, as concepts of reason rather than concepts of the understanding. Hilbert, for example, famously begins his Grundlagen with an epigraph taken from Kant's first Critique: all human knowledge thus begins with intuitions, proceeds thence to concepts and ends with ideas. Whereas ancient Greek mathematics, at least on Aristotle's account of it, begins with intuitions, sensory experience of objects, and on Kant's account begins instead with concepts that can be constructed in pure intuition, Hilbert's mathematics, so Hilbert seems to suggest, begins with ideas, that is, concepts of reason to which no corresponding objects need be met with in experience. Husserl similarly, writes in his Ideen, quoted in BOI, that geometrical concepts are ideal concepts, expressing something we cannot see, their origin, and also therefore their content, differ essentially from those of descriptive concepts. Exact concepts have as their correlation essences which have the character of ideas in the Kantian sense of the word. What Husserl here refers to as descriptive concepts are Kant's concepts of the understanding, concepts of objects, properties, and relations that can be met with in experience. Geometrical concepts are not, Husserl suggests, such descriptive concepts but instead Kantian ideas, that is, concepts of reason. Modern geometry thus achieves, according to both Hilbert and Husserl, the standpoint of pure reason. It completes and fully actualizes the science first developed by the ancient Greeks. Its concepts are now explicitly understood to have their contents independent of any and all relation to any object given in intuition. But Kantian ideas are not only concepts of reason rather than concepts of the understanding. They also, Kant tells us in the Jask logic, cannot be attained by composition, for the whole is prior to the part. 31, that is, as Husserl puts it in the passage just quoted, their origin, and also therefore their content, differ essentially from the origins and contents of the concepts of the understanding. Kantian ideas are in this latter regard more like Kantian intuitions than they are like Kantian concepts. In the transcendental aesthetic, for example, Kant appeals to the fact that space as a whole is prior to the parts of space to argue that space must therefore have the form of an intuition rather than that of a concept, in which the part is inevitably prior to the whole. Kantian ideas, like Kantian intuitions, are wholes that are prior to their parts. Hence, if modern mathematical concepts are Kantian ideas, or at least something very like Kantian ideas, they possess a kind of organic or essential unity that is quite distinctive of them. By contrast with the accidental unity of a concept of the understanding, whose parts are intelligible independent of the whole, the parts of a Kantian idea can be understood only through the whole, much as, so it would seem, the parts of an essential unity can be understood only through the whole. In fact, the concepts of modern mathematics are neither essential unities, at least in the way that living beings are essential unities according to Aristotle, their parts intelligible only in light of the form of life taken as a whole, nor accidental unities, as Kantian concepts of the understanding are according to Kant. Concepts of modern mathematics are instead intelligible unities, wholes of parts that are nonetheless not reducible to their parts. Such unities have independently intelligible parts, as accidental unities do, but as in an essential unity, the whole is more than merely the sum of the parts and cannot be attained by composition, just as Kant says. Were the concepts of modern mathematics merely composites of parts that are antecedently available, then once mathematics is freed of any relation to intuition there would seem to be no constraints on what might count as a concept of modern mathematics. Any structure would be as good as any other provided that it could be treated mathematically. And many take this to be the way things actually are in modern mathematics. If mathematicians distinguish, as indeed they do, between real mathematics and mere play with made-up, or at least non-mathematical, concepts, then that can only be out of some sort of prejudice or some not strictly mathematical sentiment. But again, mathematicians do not understand mathematics as a mere game with arbitrarily formed concepts. They treat the concepts of concern to them as intelligible unities whose natures we can discover, analyze, and sometimes fail altogether to grasp. If these mathematicians are right, if the concepts of modern mathematics really are intelligible unities, real wholes of real parts, then mathematical concepts have their own discoverable contents. Kant thought that in mathematics definitions are synthetic, that one puts together concepts to form new concepts in mathematics rather than having to analyze given concepts, as in philosophy. But as Bolzano seems to have been the first clearly to recognize, the sort of mathematical practice we have been here concerned with requires precisely what Kant had claimed has no place in mathematical practice, namely, the analysis of concepts. Instead of beginning with clearly understood primitives that can then be combined in definitions on the basis of which to construct instances in pure intuition, Bolzano's practice requires that one first analyze the concepts actually in use, concepts such as that of a function, of continuity, and so on, and on that basis form adequate definitions of those concepts, definitions that in turn enable derivations, deductive proofs, of various properties and relations of those mathematical concepts. This by itself does not show that characteristically modern mathematical concepts are intelligible unities, however. Because, according to Kant, all concepts of the understanding, those of philosophy as much as those of mathematics, are composites, the fact that some need to be analyzed into their parts, which for the case of concepts of the understanding is a reductive process, one that reduces the relevant concepts to their parts rather than built up out of parts, is not enough to distinguish modern mathematical concepts from Kantian concepts of the understanding. If, however, we combine this notion of analysis with another feature of Bolzano's practice, a very different picture begins to emerge. If, as Bolzano does, one aims to derive theorems on the basis of defined concepts, then one needs to appeal also to primitive propositions. Bolzano's search for adequate definitions of fundamental mathematical concepts goes hand in hand with a search for adequate foundations, a set of primitive propositions on the basis of which to derive theorems. And as Rusnak argues, for Bolzano the adequacy of both his definitions and his primitive propositions is determined not by their intuitive appeal or their evident truth, but experimentally. A search for the grounds of a given proposition will begin with a determination of which concepts it contains. The grounds which one adduces for the proposition should be other propositions involving the concepts contained in it. Then the problem becomes one of reverse mathematics, to find a set of premises using only those concepts from which the given proposition is exactly deducible. At a certain point, one will, Bolzano thinks, arrive at propositions which, due to their degree of simplicity and their deductive relations, appear as grounds but never as consequences of the other propositions of a science, and these are axioms. By their nature axioms cannot be proved. They must nevertheless be justified, not, however, by their self-evidence, rather, because after repeated trials of various possibilities, a given set seems to do the job of supporting the deductive structure of a science best. This conception of the nature and role of an axiomatization is resolutely anti-foundationalist and fallibilist. Riemann in his habilitation lecture similarly underscores the need for the analysis of concepts in mathematics. The task of the lecture is to set the practice of geometry on a new, self-consciously conceptual foundation and thereby to supersede Kant's account of geometry as a body of synthetic a priori truths about physical space. Riemann's first task, then, is to clarify the concept of a multiply extended quantity, and this task is of a philosophical nature because the difficulties lie more in the concepts than in the construction. Indeed, the whole of the first section of the lecture is primarily philosophical insofar as its concern is to clarify the concept of an n-dimensional manifold as the foundation of a general theory of the concept of space. Riemann was furthermore profoundly and self-consciously historicist in his conception of mathematics. For him mathematical concepts and axioms are immersed in a historical process of change. Far from the usual idea that there exists a ready-made theory of everything, in his view all concepts of natural science, and of mathematics in particular, have evolved gradually from older explanatory systems. Scientific theories are for Riemann the outcomes of a process of gradual transformation of concepts, starting from the basic ideas of object, causality, and continuity. Development takes place under the pressure of contradictions or else implausibilities revealed by unexpected observations unexpected in the light of the hypotheses proposed by reflection at some particular stage. That is, as Freya would more exactly put it, not our concepts but instead our grasp of concepts evolves and is transformed. Over time, with further inquiry, we thus can come better to understand concepts that we had been concerned with all along. Mathematics is not an empirical discipline but it is, for both Riemann and Bolzano, nonetheless in a way experimental. There are no given first principles from which to deduce consequences, rather, it is developments within the discipline that reveal new concepts, and indeed new kinds of concepts, which once they have become available can be refined and their consequences explored. As Bolzano's are, the foundations that Riemann proposes are and must be provisional. They have, as he puts it, the status of hypotheses. Like any other form of intellectual inquiry, mathematics as it came to be practiced over the course of the 19th century is in this way constitutively self-correcting. The search for foundations is not, for these 19th century mathematicians, the search either for certainty or for ontological grounds that it would become in the 20th century, but instead a search for the proper conceptual foundations of the discipline of mathematics as it had by then become. 32. According to both Bolzano and Riemann, the science of mathematics does not rest on any given foundation but nor is it merely a game. There are concepts that are proper to it as its subject matter, concepts such as that of an infinite-dimensional manifold, of a group, of a Lie algebra, and these concepts are to be intrinsically characterized in definitions on the basis of which theorems are to be proved or to be shown to be in need of more careful articulation. It is the course of proof and refutation that enables us to extend our knowledge about those concepts, in some cases by revealing connections among them and in others by revealing our errors and misunderstandings, the fact that we had not after all understood them as well as we ought. And this, sketchy though it is, suggests that the concepts of modern mathematics really are quite like Kant's concepts of reason, both in their independence from anything given in intuition or sensory experience and in their characteristic unity. Much more will need to be said to fill out this picture, but already we can begin to see how profoundly different developments in mathematics in the 19th century look to 19th century mathematicians from the way they would come to seem to philosophers in the 20th. 5.4 Prospects for the philosophy of mathematics. An adequate philosophy of mathematics ought to clarify the nature of mathematical knowledge, both what it is we know in knowing some bit of mathematics and also how we know it. That is, it ought to explain the interconnection between mathematical truth and mathematical knowledge, to combine a plausible metaphysics of mathematics with a plausible epistemology of it. But as the practice of mathematics is transformed over the course of its history, so, we have seen, the nature of the philosophical problem it presents is transformed. For the ancient Greeks, we saw, the problem concerns the ontological status of and our epistemic access to the geometrical and numerical objects that ancient Greek mathematicians and philosophers assumed were the subject matter of mathematics. And many still today take the problem of mathematical truth and knowledge to concern its objects. The standard view is that there are mathematical objects. 33 The problem, then, is to understand the ontological status of those objects and the nature of our epistemic access to them. Already in the 17th century Descartes came to think that mathematics is not about objects but instead about relations that objects, more exactly, measurable quantities, can stand in. And the way to account for this sort of mathematical knowledge, he thought, was by appeal to God-created clear and distinct ideas that we find innate in us. We discover new mathematical truths by reflecting on those ideas and determining what must be true in light of them. But that, Kant saw, is not only inadequate as a philosophical account of truth and knowledge in mathematics, it also falsifies Descartes' actual mathematical practice, which constitutively involves the symbolic language of arithmetic and algebra. Does Kant's alternative account in terms of constructions in pure intuition, in terms, that is, of the activity of paper and pencil reasoning that is made possible by the forms of inner and outer sense, resolve the problem of truth and knowledge in mathematics? The answer seems obvious. Kant's philosophy of mathematics in terms of the construction of concepts in pure intuition, whatever its virtues, has no application to a mathematical practice in which one reasons directly from concepts. Mathematical practice, as it emerged over the course of the 19th century, does not involve the construction of concepts in intuition, but instead deductive reasoning from concepts. But how can one learn anything new by reasoning from concepts? How can a deductive proof extend one's knowledge? Already in 1894, Poincaré raises the essential difficulty. He writes in the opening paragraphs of On the Nature of Mathematical Reasoning. The very possibility of mathematical science seems an insoluble contradiction. If this science is only deductive in appearance, from whence is derived that perfect rigor which is challenged by none? If, on the contrary, all the propositions which it enunciates may be derived in order by the rules of formal logic, how is it that mathematics is not reduced to a giant tautology? The syllogism can teach us nothing essentially new, and if everything must spring from the principle of identity, then everything should be capable of being reduced to that principle. Are we then to admit that the enunciations of all the theorems with which so many volumes are filled are only indirect ways of saying that A is A? No doubt we may refer back to axioms which are at the source of all those reasonings. If it is felt that they cannot be reduced to the principle of contradiction, if we decline to see in them any more than experimental facts which have no part or lot in mathematical necessity, there is still one resource left to us: we may class them among a priori synthetic views. But this is no solution of the difficulty, it is merely giving it a name, and even if the nature of the synthetic views had no longer for us any mystery, the contradiction would not have disappeared, it would only have been shirked. Syllogistic reasoning remains incapable of adding anything to the data that are given it, the data are reduced to axioms, and that is all we should find in the conclusions. 34. Notice that Poincaré's concern is not with the starting points, whatever they are, of mathematical reasoning, but instead with the reasoning itself, and the apparent sterility of purely logical reasoning, its inability to realize something new that was not contained already in one's starting points. His concern is that if mathematics were a practice of reasoning from concepts by logic alone, then its results would be, at least in Kant's view, which Poincaré clearly seems to endorse, analytic, that is, merely explicative rather than ampliative, which is to say, not knowledge properly speaking at all. How by way of strictly deductive, truth-preserving proof is it possible to discover truths, that is, to extend our knowledge? We will consider 4 possible answers. According to Kant, deduction, because it is by logic alone, is merely explicative. Nothing new can arise from such reasoning, one only makes explicit something that was implicit already in one's starting point. One might then argue that because modern mathematics is a practice of reasoning by logic alone, it is merely explicative, not a science, an investigation into the truth of some matter, at all. If there cannot be knowledge by means of deductive proof, then, given that mathematics is a practice of deductively proving theorems, what is proven in mathematics does not amount to knowledge. All the mathematician does, on this account, is draw out the logical consequences of whatever axioms and definitions mathematicians care to consider, thereby making explicit something contained already implicitly in those starting points. One may seem to learn something new, but really it was all there already, one just did not know it. So, while there may be a psychological sense in which one acquires new knowledge, logically speaking one does not, because that which has been extracted in the course of the reasoning was already there, as beams are contained in a house. Much as one can dismantle a house and use its beams to build a fence, so using logic one can dismantle the premises and put the parts back together in a way to form the conclusion. In that case, all that has been achieved is a reorganization of something one already had. One has not extended one's knowledge but merely reorganized it, and useful though this reorganized knowledge may be, it should not be confused with actually achieving something new. 35. Alternatively, one could argue that because mathematics is a science, an investigation into the truth of some matter, it cannot proceed merely logically, by deducing theorems on the basis of axioms and definitions, but must involve something other than pure logic. This was Poincaré's view, that mathematical reasoning is not merely logical but instead distinctively mathematical. This is also, though in a different way, what Kant had thought, that mathematics involves a distinctive use of reason, one that is different from reason in its discursive use. According to Kant, what is characteristic of the mathematical use of reason is that it involves constructions in pure intuition. What Poincaré thinks is characteristic of distinctively mathematical reasoning is not that it involves Kantian constructions but instead that it involves, in addition to strictly logical modes of reasoning, also mathematical ones. There are 2 different ways this might go. First, it might be the case that although some mode of reasoning could be broken down into a series of strictly logical inferences, in mathematical reasoning it is not so broken down but treated as immediately valid. Poincaré seems to suggest such a view in the following passage. Our body is formed of cells, and the cells of atoms. Are these cells and these atoms then all the reality of the human body? The way these cells are arranged, whence results the unity of the individual, is it not also a reality and much more interesting? A naturalist who never had studied the elephant except in a microscope, would he think he knew the animal adequately? It is the same in mathematics. When the logician shall have broken up each demonstration into a multitude of elementary operations, all correct, he will still not possess the whole reality. This I know not what which makes the unity of the demonstration will completely escape him. Although it may be possible to break down a mathematical mode of inference such as mathematical induction into a multitude of elementary and strictly logical steps, much as an animal's body can be broken down into the cells of which it is composed, to so break it down destroys what is in fact an essential unity. One can no more learn about mathematics, or indeed learn mathematics, by focusing on the strictly logical inferences of which its modes of inference are in some sense composed, then one can learn about an elephant by focusing on the cells of which it is in some sense composed. Suppose that the mathematician infers some conclusion from a set of premises by means of some form of inference that the mathematician claims is mathematically valid, and that our mathematician can convince other mathematicians that the conclusion does indeed follow. That is, our mathematician can get other mathematicians to see, to grasp, the validity of the inference. Others, those who are not mathematicians, we will suppose, are utterly baffled. They simply cannot understand or grasp how the conclusion follows. So the logician breaks the inference down into a series of strictly logical steps, and now even a non-mathematician can understand that the conclusion can be derived from the premises. The problem is that what the non-mathematician is now seeing is not mathematics but only logic. The mathematics has been lost in the course of the dissection of its modes of inference into their logical parts. What is distinctive of mathematical ability, on this account, is that it enables one to recognize irreducible mathematical wholes, valid mathematical modes of inference that can be broken down into strictly logical steps but qua mathematical are essential unities and cannot be so reduced to logic. On this view, what the non-mathematician lacks is the ability to discern these unities in addition to the logical steps they can be broken up into. The non-mathematician is like one who can see only the cells of the elephant as a collection of cells, but not also the elephant, that is, the essential unity in virtue of which it is an elephant, an animal of a certain sort. 36. The idea that there is an irreducible unity to a mathematical mode of inference despite the fact that it can be broken down into a series of purely logical steps in much the way there is unity to an elephant despite the fact that it can be broken down into a mere collection of cells is not merely frivolous. An interesting theorem is just such a unity. We know that in a sense a theorem can be broken down into a series of little steps, that is, that it can be proven. But although we are interested in the proof, all the little steps, we are also interested in the theorem. Looking at the theorem is analogous to looking at the elephant because the theorem, in its way and qua theorem, that is, as something that has been proven to be true, holds all those little steps inside itself. Looking instead at the proof that gets you from the antecedent to the consequent of the theorem is like looking at the collection of cells that in a material sense makes up the elephant. But although this may help to explain the nature of mathematical understanding, it is not clear that it helps with the issue of mathematical knowledge. If mathematical induction, say, can be broken down into a series of logical steps, then it would seem that using the rule of mathematical induction cannot extend one's knowledge because in fact the conclusion is derived by what has been revealed to be a strictly deductive procedure. 37. The second way there might be distinctively mathematical modes of reasoning in addition to logical ones is if there were modes of material inference in mathematics, for example, in eliminable relations of entailment among the concepts of mathematics. Suppose that being F entails being G, not logically, but because of what it means to be F, that is, in the way that one thinks being larger than another entails that the second is not larger than the first. A mathematical inference would then be an inference that depended in this way on the meanings of the mathematical ideas involved. To understand those ideas would enable one to recognize the validity of the inferences, and although one could always express those relations of entailment in conditionals and treat them as premises, thereby turning one's materially valid inference into a formally valid inference, to do so would again be to lose sight of the mathematics involved. Ditlevson provides this explanation. Even though the warrant for if P, then C may be based on a grasp of a mathematical architecture linking C with P, the modus ponens counterpart nonetheless abstracts away from this grasp of architecture itself and focuses instead on its net classical effect, that is, on the classical semantico-epistemic status and logical form of the belief which it warrants. It treats grasp of an architecture as merely the means by which the classical semantico-epistemic status of if P, then C is established, while viewing the semantico-epistemic status itself, rather than the means of establishing it, as the matter of primary epistemic importance. Although the materially valid rule that enables one to infer C on the basis of P shows that knowing that P provides a good reason for inferring that C, If the inference the rule governs is replaced by another, strictly logical inference involving also the conditional if P, then C, then P no longer serves as the ground for C. What one now has is a logically valid inference, and what one now knows is only that given that the premises are true, the conclusion is also true. One has lost sight of why the conclusion is true. That P no longer can be seen to serve as one's reason for inferring that C. And this happens because what had been functioning as a rule of inference regarding what is a reason for what is reduced to a merely truth functional conditional, that this is true if that is true, thereby robbing the original premise of its status as a reason. What had been a good mathematical ground for inference is reduced to a merely logical ground. Interestingly enough, Descartes' account in his second replies of the analytic and synthetic methods of demonstration in geometry seems to make essentially this point. 38 As he explains, the order of argumentation in the two cases is the same. The items which are put forward first must be known entirely without the aid of what comes later, and the remaining items must be arranged in such a way that their demonstration depends solely on what has gone before. Whether the method of demonstration is analytic or synthetic, it is deductive, at least in a broad sense, and non-circular. Nevertheless, Descartes thinks, the two methods are very different. Analysis shows the true way by means of which the thing in question was discovered methodically and as it were a priori, so that if the reader is willing to follow it and give sufficient attention to all points, he will make the thing his own and understand it just as perfectly as if he had discovered it for himself. But this method contains nothing to compel belief in an argumentative or inattentive reader, for if he fails to attend even to the smallest point, he will not see the necessity of the conclusion. Moreover, there are many truths which, although it is vital to be aware of them, the method often scarcely mentions, since they are transparently clear to anyone who gives them his attention. In the Meditations, Descartes tells us, it was the analytic method that was followed, and the method is a priori because, as Descartes indicates in his account of synthesis, it is prior to the method of synthesis. Synthesis, by contrast, employs a directly opposite method where the search is, as it were, a posteriori. It demonstrates the conclusion clearly and employs a long series of definitions, postulates, axioms, theorems, and problems, so that if anyone denies one of the conclusions, it can be shown at once that it is contained in what has gone before, and hence the reader, however argumentative or stubborn he may be, is compelled to give his assent. In a synthetic demonstration, everything on which the proof depends, save for the rules of formally valid inference employed, is explicitly stated in advance in axioms, definitions, postulates, theorems, and problems. Because it is, the proof compels assent by anyone, no matter how argumentative or stubborn, who accepts those axioms, definitions, postulates, theorems, and problems. But of course one can set out everything on which a proof depends only after one has the proof itself, only after one has achieved, analytically, knowledge of the primary notions and has drawn conclusions from them. It is for just this reason that the analytic method requires, in a way the synthetic does not, the closest attention to each point, and enables, in a way the synthetic does not, a reader to make the thing his own and understand it as perfectly as if he had discovered it for himself. The analytic method employs rules of material inference to draw conclusions from evidently true premises. In this case, one is to see that the truth of the premises entails the truth of the conclusion, but in order to see that, one must actually think about what the premises mean, and thereby about what they entail. The synthetic method, because and insofar as it relies only on formally valid rules of inference, does compel assent, but because it does not require that one actually think about what is being claimed in the premises, it does not ensure understanding. 39 It follows, Descartes thinks, that the synthetic method is not as satisfying as the method of analysis, that the analytic method is the best and truest method of instruction. Point 40. According to the view under consideration, there are rules of material inference, that is, relations of entailment among concepts, that although they can be stated as premises, instead function in mathematics directly as inference licenses. Again, This is different from claiming that what mathematicians treat as distinctively mathematical inferences can nonetheless be unpacked in ways that reveal them to be purely logical. When one makes a rule of material inference explicit as a conditional in a premise, one does not thereby show it to be purely logical. It is one thing to claim that, say, mathematical induction is a distinctively mathematical mode of inference, though of course one can include it as a premise of an inference modus ponens, and something very different to claim that mathematical induction, though it appears to be, and even perhaps is, distinctively mathematical, can nonetheless be broken down into a series of strictly logical steps. But although these are different claims, either way the thought is that while one can make everything explicit and hence logically valid in a mathematical proof, either by including as premises all the materially valid rules involved or by breaking all the mathematically valid rules down into their strictly logical parts, this destroys the mathematical reasoning, and destroys as well mathematical understanding. Rav seems to take essentially this view insofar as he argues that the mathematician's proof is irreducibly meaningful and so cannot be identified with a derivation in some formal system precisely because such a derivation is merely syntactic. Although, according to Rav, most of our current mathematical theories can be expressed in first-order set-theoretic language, a mathematician's proof cannot be formalized in such a language because it depends on an understanding and on prior assimilation of the meanings of concepts from which certain properties follow logically. Our question was, how can one's mathematical knowledge be extended if one's reasoning is deductive? If we assume with Kant that deductive reasoning cannot extend one's knowledge but only make explicit something that was implicit already in one's starting points, then there are only two possibilities. Either reasoning in mathematics is strictly deductive and hence cannot materially extend one's knowledge, or reasoning in mathematics can extend one's knowledge because it is not strictly deductive, because it involves modes of inference that are peculiar to the discipline of mathematics. But we can also question Kant's claim that by logic alone there can be no extension of knowledge. Perhaps one can extend one's knowledge by purely logical, deductive reasoning from concepts. Because Kant provides two different characterizations of the analytic/synthetic distinction, there would seem to be again in this case two ways to develop the point. One might argue, first, that Kant was wrong to have thought that analytic judgments, by means of reason alone, are inevitably explicative because there can be judgments that are by means of reason alone but in which the predicate is not contained already in the concept of the subject. According to this approach, Kant was right about what logic is but wrong about what it can achieve. Alternatively, one could argue that Kant was wrong to have thought that by reason alone only analytic judgments are possible because there are purely logical ways to go outside my concept, ways that do not involve any reference to any objects. On this view, Kant was wrong about what logic can achieve because he was wrong about the nature of logical reasoning. According to Kant, the analytic/synthetic distinction exactly lines up both with the explicative/ampliative distinction and with the by logic alone/involving objects distinction. Analytic judgments are known by reason alone and are merely explicative, and synthetic judgments are ampliative because reference to an object serves in such judgments to connect the predicate to the concept of the subject. Perhaps what the new mathematical practice of reasoning from concepts shows is that this picture of the analytic/synthetic distinction is wrong. What it cannot settle is how the picture is wrong. The logical positivists drew our first conclusion. They took it that what modern mathematical practice shows is that some judgments that are known on the basis of meanings by logic and reasoning alone, and hence are analytic, are nonetheless ampliative, not merely explicative, because the predicate in such judgments is not contained already in the concept of the subject. Peirce drew the second conclusion. According to him, the lesson of modern mathematical practice is that even reasoning from concepts by logic alone can involve something like a construction and so is, or at least can be, synthetic, hence ampliative. As we can think of it, although for Kant reasoning that is ampliative involves thereby constructions, and so also reference to objects, the positivist argues that there can be ampliative reasoning without constructions. Peirce instead accepts Kant's first move, that ampliative reasoning is constructive, but denies the second, the idea that constructions inevitably involve reference to objects or forms of objects. According to the positivists, developments in mathematics in the 19th century showed that there can be judgments that are true in virtue of the meanings stipulated in one's axioms, and so analytic a priori, but which are far from trivial, which can be proven only from a whole collection of axioms in what is perhaps a quite complex series of steps. Although concepts do often contain contents that can be made explicit in trivial analytic judgments, concepts can also acquire meaning through their logical relations one to another, relations that can be made explicit in an axiomatization. Theorems that can be derived from a set of such axioms, solely in virtue of the stipulated logical relations, thus follow by meaning alone and so are analytic in Kant's sense, but they are also, the positivists argued, ampliative, that is, significant extensions of our knowledge. Where Kant went wrong, on this view, was in thinking that there is no difference between what is true by definition, and hence trivial, merely explicative, and what is true in virtue of meaning, or on the basis of concepts, which can be ampliative despite being derived on the basis of logic alone. Point 41. For the positivists, mathematical knowledge can be ampliative despite being analytic because not all meaning is given by an explicit definition. Meaning can also be determined for a collection of expressions, assumed to be otherwise meaningless, through an axiomatization involving those expressions. What is deduced from such an axiomatization is analytic, by reason alone, but also ampliative, that is, knowledge properly speaking. As already indicated, Peirce's response to 19th century developments in mathematics was very different. His thought was not that what those developments show is that constructions are not needed in mathematics, but instead that even logic, even reasoning from concepts alone, involves constructions. He explains in The Logic of Mathematics in relation to education. Kant is entirely right in saying that, in drawing those consequences, the mathematician uses what, in geometry, is called a construction, or in general a diagram, or visual array of characters or lines. Such a construction is formed according to a precept furnished by the hypothesis. Being formed, the construction is submitted to the scrutiny of observation, and new relations are discovered among its parts, not stated in the precept by which it was formed, and are found, by a little mental experimentation, to be such that they will always be present in such a construction. Thus the necessary reasoning of mathematics is performed by means of observation and experiment, and its necessary character is due simply to the circumstance that the subject of this observation and experiment is a diagram of our own creation, the condition of whose being we know all about. But Kant fell into error in supposing that mathematical and philosophical necessary reasoning are distinguished by the circumstance that the former uses constructions. This is not true. All necessary reasoning whatsoever proceeds by constructions. On Peirce's view, the lesson of the developments in mathematical practice in the 19th century is not that mathematics, which can involve reasoning from concepts alone, is for that reason analytic, rather than synthetic as Kant would have thought, nor even that it is ampliative despite being analytic as the positivists argued, but instead that reasoning from concepts alone is, like earlier forms of mathematical practice, synthetic, that is, ampliative, albeit necessary, because even deductive reasoning can involve constructions. Whereas positivists focus on the starting points of deductive proof to explain their capacity to extend our knowledge, Peirce in this way focuses on the activity of proving, arguing that such activity can realize significantly new results. Both the positivists and Peirce sever the connection between deductive reasoning from concepts alone and mere explication that one finds in Kant. But they do so in quite different ways. The positivist argues directly, given that not all reasoning from concepts is merely explicative of their contents, but can be on the basis of a whole collection of axioms that only implicitly define the non-logical concepts involved in those axioms, reasoning from concepts can be at once analytic, by logic alone, and ampliative, a real extension of our knowledge. Peirce's response is different insofar as he severs the Kantian connection between reasoning from concepts and explication only indirectly, by severing the Kantian connection between the activity of construction and intuition of objects. Again, on Peirce's view, even deductive reasoning from concepts involves constructions and so is, or at least can be, ampliative. Indeed, even pure logic is not, Peirce thinks, merely formal but is instead a science, that is, experimental, and hence inherently fallible. The possibility of Peirce's response, in addition to the positivist one, has not been sufficiently recognized. Kafka, for instance, seems simply to assume that what the positivists, following on from Hilbert's formalist project in geometry, were claiming about the possibility of knowledge through proof just is what Bolzano, Dedekind, Freya, and others had in mind. But although Bolzano's old dream of knowledge by purely conceptual means can be pursued along positivist lines, it need not be. It can also be pursued in line with Peirce's suggestion that reasoning from concepts is ampliative, despite being deductive, because even reasoning from concepts is in some way constructive. And we need to recognize this because, as Quine showed, the positivist response is fatally flawed. We have seen that according to the positivist the truths of mathematics are ampliative despite being analytic, they are contentful, non-trivial truths that, like any analytic truths, are known by appeal to meanings alone. Quine shows that this cannot be right because if the judgments of mathematics really are analytic, that is, founded on meaning alone, hence incorrigible and unrevisable, then they are not and cannot be true. 42 Alternatively, if they are true, then they are not founded on meaning alone because in that case they can be revised as needed. No truth is or can be immune to revision, because if it really is impossible to get it wrong, then there is no objective or truth evaluable content to the claim at all. This is most obviously true of simple analytic judgments such as that all humans are rational. If that judgment is true by virtue of meaning, because being human is by definition being a rational animal, then the judgment that all humans are rational is not a piece of knowledge of any kind. It is nothing more than a substitution instance of the logical schema all is a, and this substitution instance must not be confused with the truth, however trivial, about humans, for if it were really a truth about humans then it would be possible that it be mistaken. And the point holds equally of a theorem that is deduced from axioms. Insofar as it is not possible that one is mistaken, it is also not possible that what one has is an item of knowledge. This point can be hard to see, and it can be hard to see at least in part because there is a perfectly good distinction to be drawn between claims that are believed on the basis of meanings and claims that are believed on the basis of fact. I might, for example, believe that humans are rational on the grounds that in the language that I speak part of what it means to be human is to be rational. Quine's essentially pragmatist point is that either sort of belief, either belief on the basis of meanings or belief on the basis of fact, can turn out to have been mistaken and require revision. Again, there is no truth in virtue of meaning, nothing that is given, unrevisable in principle. 43 The positivist's idea, that the practice of proof can realize mathematical knowledge because some analytic judgments, true in virtue of meanings, are ampliative, cannot be made to work. There neither is nor can be any truth in virtue of meaning. What then of Peirce's idea that even deductive reasoning can involve constructions and hence be ampliative, albeit necessary? Can the problem of mathematical truth be made to yield to this approach? Kant's account of the practice of mathematics, in particular, his idea of constructions, provides, at least in certain respects, a very plausible explanation of how and why the practice of mathematics as it was in Kant's day works, how the mathematicians play with symbols and diagrams enables the demonstration of new truths. Kant saw, as no one before him had, that both Euclidean geometry and arithmetic and algebra essentially involve systems of marks that involve three levels of articulation, and that it is by reconceptualizing at the second, intermediate level various collections of signs in the display, in an ordered, stepwise fashion, that the truth emerges with the proof. 44 The problem for Kant's account is that since the 19th century mathematics has come to seem to be discursive rather than intuitive. In Kant's sense, it does not use any specially devised system of marks in its demonstrations, and so, It seems, Kant's philosophy of mathematics is simply irrelevant to this new practice. We are left with no account of how and why modern mathematics works. Modern mathematics, at least according to its early practitioners, is a kind of thinking in concepts, but given Kant's division of the uses of reason into discursive and intuitive, it seems impossible so much as to conceive how such a practice might enable the demonstration of new truths. Peirce rejects the division. According to him, as we have seen, all necessary reasoning whatsoever proceeds by constructions. This is quite implausible for the case of natural language reasoning. One does not need to have so much as the idea of writing or of notation generally in order to reason in everyday life. But the case of mathematical reasoning seems to be different. Much as we can think of Kant's notion of construction as extending the domain of Euclidean diagrammatic reasoning, which in many cases provides explicit constructions, to include also computations and calculations in arithmetic and algebra, so we can think of Peirce's suggestion as aimed at extending Kant's notion of construction to include also reasoning from concepts in mathematics. We know that Peirce came to think that an adequate understanding of reasoning in mathematics requires not an algebra of logic but instead a more diagrammatic notation such as he aims to provide in his system of existential graphs. As he explains in an essay introducing his system of existential graphs written around 1903, our purpose is to study the workings of necessary inference. What we want, in order to do this, is a method of representing diagrammatically any possible set of premises, this diagram to be such that we can observe the transformation of these premises into the conclusion by a series of steps, each of the utmost possible simplicity. Peirce's thought seems to be that if we had such a notation we could see, as Kant helped us to see for earlier forms of mathematical practice, how reasoning from concepts alone could be ampliative. If Peirce were right, and assuming that such a use of constructions is distinctive of mathematical reasoning, as Kant had thought, then it would follow that Poincaré was right as well, that there are distinctively mathematical modes of reasoning even in the case in which the reasoning is strictly deductive, that is, truth-preserving. We have canvassed 4 possible philosophical responses to the problem of truth and knowledge as it arises for the practice of Denken in Begriffen that emerged in mathematics in the 19th century and remains standard today. None are wholly satisfactory. Although it appears to be the case that by reasoning deductively from concepts mathematicians such as Riemann, Dedekind, and others discover significant new mathematical truths, we do not yet have any adequate way of thinking about this. Nonetheless, there has been progress insofar as Poincaré and Peirce, both of whom focus on the activity of the mathematician, seem less obviously to be wrong than either the positivists or those who deny that mathematicians ever achieve anything new at all. Poincaré does accept Kant's account of logical inference. What he argues is that mathematical inference is different from logical inference. Peirce instead takes Kant to be wrong about the nature of logical inference. Even logical inference is, he thinks, more like what Kant thinks of as distinctively mathematical, constructive inference. This seems bizarre. In so seeming, it highlights just how profound are the difficulties in thinking about this new form of mathematical practice of reasoning deductively from concepts that became the norm in the 19th century. 5.5 Conclusion. Mathematics, Grabiner remarks, is that area of human activity which has at once the least destructive and still the most fundamental revolutions. Nowhere is this more evident than in the 19th century revolution in mathematical practice, the revolution that was, as Stein describes it, a second birth of the subject. Mathematics was not merely to be done in a new and better way, as Descartes had shown with his method that it could be. It was to be raised anew on purely conceptual foundations by means of reason alone. 45 What Kant had declared impossible was now enacted. Indeed, it almost seems in retrospect, that Kant had only to make explicit that early modern mathematics, like its ancient counterpart, constitutively involves something we can call pure intuition for mathematicians to rise up and prove him wrong. The revolution, I have suggested, unfolded in 2 distinguishable waves. First, from reasoning in the symbolic language of arithmetic and algebra, mathematicians began self-consciously to reason on expressions in that language, something 18th-century mathematicians such as Euler had in fact already been doing, albeit quite unself-consciously and unsystematically. Indeed, one can find this sort of reasoning here and there already in Descartes' geometry. The symbolism is not only a medium within which to discover new results as Euclid's diagrams are, its equations can also exhibit discernible patterns that can be exploited in the course of mathematical inquiry. At the second stage of the revolution, somewhat ironically, all appeals to symbolisms were to be eschewed. The symbolic language that in the 17th and 18th centuries had opened up a whole new world of mathematics was now to be regarded as providing a merely contingent and external perspective on what now appeared to be the real subject matter of mathematics. What had seemed in the 18th century to be the thing itself, namely, the formula, had been revealed to be only its outer clothing. What matters is not the formula through which we first gain cognitive access to a function, but the function and, in particular, the intrinsic properties in virtue of which it is the function it is. Kant's critical philosophy, although not a prerequisite of the revolution, nevertheless profoundly influenced the articulation both of the nature and fatal flaws of the old regime and of the fundamental character and constitution of the new. Not Kantian pure intuition but Kantian ideas, that is, concepts of reason conceived as intelligible unities, are now to be seen as what mathematics is really about. Finally, after over 2,500 years of growth and development, mathematics has, so it seems, become a self-standing discipline, the work of pure reason wholly unfettered by the contingencies of our form of sensibility. But how can this be? Surely mathematics needs to answer to something independent of its own activity, and if it does not answer to anything independent of its own activity, then it really is, as since the 19th century it has so often been taken to be, nothing more than a mere game. How, by reason alone, is it possible to know anything at all? The straightforwardly Kantian answer is, of course, that it is not possible to know anything by reason alone. There can be no ampliative deductive proofs on Kant's conception of deduction. But perhaps Kant was mistaken about this. He had been wrong about the role of pure intuition, not, perhaps, its role in ancient and early modern mathematics, but nonetheless wrong about its role in mathematics as it had by now revealed itself to be. Perhaps, then, he was wrong as well about the power of reason. If, as Kaffer remarks, Kant was right, concepts without intuitions are empty, and no geometric derivation is possible that does not appeal to intuition. But by the end of the 19th century, Bolzano, Helmholtz, Freya, Dedekind, and many others had helped determine that Kant was not right, that concepts without intuitions are not empty at all. The formalist project in geometry was therefore designed not to expel meaning from science but to realize Bolzano's old dream, the formulation of non-empirical scientific knowledge on a purely conceptual basis. Although one perhaps begins with an intuitive grasp of a domain, say, geometry or arithmetic or analysis, that grasp can be refined through a careful analysis of the concepts involved and strictly deductive proofs of the theorems of that domain. Such proofs, it seemed clear, can extend our knowledge, despite being purely deductive. Because in Kant's logic the very idea of a deductive proof that is ampliative is manifestly incoherent, perhaps what is needed is a new sort of logic, a pure logic that is universally valid but not merely formal, devoid of all content. Naderp, a Marburg neo-Kantian, describes such a hoped-for logic in On the Question of Logical Method. The fundamental problem of logic then concerns the conditions of possibility of science in general, of theory in general, of truth in general, of deductive unity, the necessary generalization of the Kantian question regarding the conditions of the possibility of experience, for this meant, the unity of objective lawfulness. The question therefore arises, what are the primitive essential concepts from which the essential concept of theory itself is constituted? All logical justification of our concepts must go back to this ultimate foundation. Pure logic then is the theory of theories, the science of sciences. Neither Kant's general logic, which is merely formal, devoid of all content and truth, nor his transcendental logic, which is a logic of truth but not maximally general, will do. What is needed instead is a pure logic that is universally valid without being merely formal. Such a logic, and only such a logic, Nader thought, can provide what is wanted, the science of truth. Nader calls for a logic that is at once universally valid and contentful. This is not, we will soon see, the logic that in fact came to be developed. The logic that would be developed, building on the work of Boole in the mid-19th century and culminating in Tarski's work in the 20th, is not a science of truth. Instead, as we will see in some detail in the next chapter, that logic is largely an extension of familiar Kantian themes, just as Russell suggests in the Principles of Mathematics. It is more powerful than Kant's monadic predicate logic but otherwise largely Kantian. Little wonder, then, that logic has, despite a century of effort on the part of some of our ablest philosophers, yielded only very meager insights into the practice of mathematics. 46. 6. Mathematics and language. How does mathematics work? The answer of the mathematical logician is that it works by drawing deductively valid inferences from axioms. A mathematical proof is a sequence of sentences each of which is either an axiom or a consequence of earlier sentences according to some rule of logic. 1 Sup's Introduction to Logic provides a classic exposition of the view. We begin with a set of formulas which we call premises. The object is to apply the rules so as to obtain the sought-for conclusion. Because logic provides a completely explicit theory of inference adequate to deal with all the standard examples of deductive reasoning in mathematics, any mathematician's proof can be reworked into such a fully formal proof. The only difference between the proofs that mathematicians give in their actual practice and a fully formalized proof in the symbolic language of mathematical logic, on this view, is that the mathematician's proof does not lay out every step of the reasoning but instead makes jumps. In an informal proof, enough of the argument is stated to permit anyone conversant with the subject to follow the line of thought with a relatively high degree of clarity and ease. In giving an informal proof, we try to cover the essential, unfamiliar, unobvious steps and omit the trivial and routine inferences. Surprisingly, this seems not to be right. First, mathematicians do not in their actual practice give proofs, even informal ones, in Sup's sense, but instead provide descriptions of how the reasoning goes, or would go were one to engage in it. 2 Furthermore, and even more puzzling, fully formalized proofs are usually unintelligible. If written out in full they are difficult to comprehend, and despite their rigor they are often unconvincing, because although they provide verification that a result follows logically from given premises, they may fail to convey understanding of why it does. We saw in section 5.4 that Poincaré goes a step further. A mathematician's proof cannot, he thinks, be formalized at all. 3 Somehow the act of formalization turns a proof that is, a real proof, the sort of proof a mathematician actually gives, into a non-proof. What can possibly be going on here? It is barely conceivable that the norms governing the reasoning mathematicians actually engage in are simply disjoint from the familiar rules of logical inference. Even if Poincaré were right to think that there are distinctively mathematical modes of inference, either primitive relations of entailment among mathematical concepts or rules of inference that, although they can be broken down into a series of purely logical steps, nonetheless have a characteristic unity in mathematical practice, logic nevertheless ought to be of some use in mathematics, for instance, in what Ditlevson describes as times of epistemic crisis. But it is not. The mathematical logician's formalizations are of absolutely no use in actual mathematical practice. They do not convince, or even clarify, and most often they are simply unintelligible. We need to understand this. We have seen that the profound transformations in mathematical practice over the course of the 19th century showed that Kant's philosophy of mathematics in terms of the construction of concepts in pure intuition as made possible by space and time as the forms of sensibility was fatally flawed. What those developments seemed further to suggest, given the enormous and pervasive influence of Kant, was that it is not reason in its intuitive use but instead reason in its discursive use that is at work in mathematics, that there are not two uses of reason, as Kant had thought, but only one. Supps takes just this view: a correct piece of reasoning, whether in mathematics, physics, or casual conversation, is valid by virtue of its logical form. Point 4. But, as Supps immediately goes on, because most arguments are expressed in ordinary language with the addition of a few technical symbols particular to the discipline at hand, the logical form of the argument is not transparent. Fortunately, this logical structure may be laid bare by isolating a small number of key words and phrases like and, not, every and some. In order to fix upon these central expressions and to lay down explicit rules of inference depending on their occurrence, one of our first steps shall be to introduce logical symbols for them. With the aid of these symbols it is relatively easy to state and apply rules of valid inference. The way the mathematician reasons, Supps thinks, is the way anyone else reasons, whether in everyday life or in, say, philosophy or courts of law. Reasoning is everywhere the same, and it is performed, or at least expressed, in natural language. But because natural language can mask the underlying logical form of a sentence, the nature of this process of reasoning is to be laid bare by introducing abbreviations, simple signs for the logical particle of natural language together with explicit rules governing what may be deduced from sentences containing such signs. Although Kant had held that mathematical reasoning is essentially different from reasoning in other contexts, developments in mathematics in the 19th century seem to show that it is not, that reasoning is everywhere the same. But although the mathematical logician diverges from Kant on this point, in other respects the conception of logic and language that we find in mathematical logic remains fundamentally Kantian. Point 5. Logic, it is thought, is merely formal, without content or truth. And because it is, it seems natural to adopt a model theoretic conception of language according to which there is an absolute distinction to be drawn between, on the one hand, logical form, which is displayed in the uninterpreted formal language, and on the other, the various models or interpretations relative to which sentences of the language have content and are true or false. And because all content and so all truth is taken, following Kant, to lie in relation to an object or objects, generality must be understood quantification ally, in terms of the idea of quantifying over a domain of objects. If all content lies in relation to objects, then there obviously cannot be truths directly about concepts, say, about their logical relations one to another. Although in their mathematical practice mathematicians appear to establish such truths, really mathematics is about objects, at least if it has any content. The failure of Freya's logicism showed that its objects cannot be purely logical, so, it is assumed, there must be other objects that mathematics is about, either that or it really is merely formal, not a science at all, nothing more than a play with empty signs. Almost all work in 20th century philosophy of mathematics is founded on just this assumption. According to the standard view, a mathematical proof is, as any piece of reasoning is, a set of sentences some of which are premises and the remainder of which are derived from those premises according to logically valid rules of inference. Generality is understood quantification ally, language is understood model theoretically, and meaning is understood in terms of truth. What is the case with objects? The task of the first half of this chapter is to examine these last three ideas. We have already seen well enough how the notion of a quantifier arises in the context of Kant's philosophy. Because Kant thinks that concepts are not object-involving but that nonetheless judgment must be object-involving, he adopts a quantificational conception of generality. Our concern here will be with the very idea of a quantifier, and in particular with some unresolved debates about how to think about them. Model theory as an account of how language in general works is different insofar as it is not a particularly Kantian idea but seems instead to have arisen, at least in part, in response to the developments in mathematics in the 19th century. But Kantian ideas are not far away. If one is antecedently committed to a quantificational conception of the generality of, say, the axioms of elementary algebra, then when one realizes that those axioms can be applied also in quite different sorts of cases from those originally intended, it will seem natural to adopt a model theoretic understanding of those axioms, especially if one is also inclined to think of reasoning mechanistically, as a matter of the rule-governed manipulation of meaningless signs. We will see that independent of such commitments that conception of language has little to recommend it, that a quite different view of the significance of the relevant developments in mathematics in the 19th century is at least as plausible. That meaning as it matters to logic and reasoning in mathematics should be understood in terms of truth is, we will see, also problematic. According to the received view, reasoning is everywhere the same, and all that logic, at least insofar as it is the study of valid forms of inference, does is to make explicit what the rules are that govern reasoning. Hence, it is assumed, one reasons in natural language in mathematics, any special signs that are used function merely as abbreviations. But this is far from obvious and in fact seems manifestly false of most of mathematics, for most of its history. The fourth section explicitly addresses the question of the role of writing in mathematics. Four positions are outlined: the Kantian view that mathematics is constitutively written in a way that natural language is not, the documentist view that language is inevitably after the fact in mathematical practice, serving only to report results achieved independently of it, the view of the mathematical logician that mathematics is done in natural language, and finally Jourdain's view, which, we will see, combines aspects of both of the first two. Current mathematical practice strongly suggests that Jourdain's view of the role of writing in the practice of mathematics is correct. But if it is, then although current mathematical practice by contrast with both Euclidean diagrammatic practice and the practice of 17th and 18th century mathematicians such as Descartes, Euler, and Gauss has no specially devised system of signs within which to work, we can nonetheless ask what would be required of such a system of written signs. What would a Leibnizian universal language, designed for the current mathematical practice of reasoning from concepts, need to be able to do? Taking our cue from the symbolic language of arithmetic and algebra, and from aspects of the way interesting new results such as Euler's theorem are derived in that symbolic language, the fifth section aims to provide an answer. 6.1 Quantifiers in mathematical logic. Natural language, we have seen, is inherently object-involving. We speak first and foremost of perceptible things that matter to us. Mathematics is not about such things, and after Descartes it is not even ostensibly about objects at all. Cartesian ideas, paradigmatically those of mathematics, are not, as everyday concepts are, constitutively object-involving. Kant inherits this Cartesian conception. Kantian concepts are also not constitutively object-involving. But, Kant thinks, at least judgment must be object-involving. One very obvious way to combine Kant's idea that concepts do not give objects but are only that through which objects are thought with the idea that for thought to have content is for it to be in relation to an object is with a quantifier, where a quantifier just is a means of referring to objects in general sentences. We read, for instance in the Jask logic, that an example of an analytic judgment is this: to everything X, to which the concept of body belongs also extension. Kant clearly does not think of a sentence such as that all bodies are extended as predicating of bodies, all of them, that they are extended, but instead introduces something that appears to be very like a quantifier to provide something, objects, for the conditional predicate extended if a body to be about. Because all content and so all truth lies in relation to an object on Kant's account, the meaning of a general sentence, whether in mathematics or in everyday conversation, is to be understood in terms of what is the case with objects if it is true. This constraint, that one's account of generality is to apply indiscriminately to our everyday talk about ordinary things in the environment and to the inherently general judgments of mathematics, generates, we will see, enormous technical and philosophical difficulties. Point 6. Frege, one is often told, is the founder of modern logic. It was Frege, we are told, who first discovered the quantifier that we employ in mathematical logic. This is wrong on two counts. First, as we will see in more detail in Chapter 7, Frege's notion of generality is not that of quantificational logic but instead a notion designed specifically for the needs of mathematics, and in particular the needs of the 19th century practice of reasoning deductively from concepts. But even if Freya had developed the notion of a quantifier that Peirce introduced in 1883, it was Peirce's notion, not Freya's, that as a matter of historical fact we have inherited. It was Peirce, not Freya, who, as Putnam argues, seems to have been known to the entire world logic community. First-order logic would have existed without Freya. Although Freya discovered the quantifier in 1879 and Peirce's student Mitchell independently discovered it only in 1883, it was Mitchell's discovery that made the quantifier part of logic. Quine makes the same point. Peirce, not Freya, was indeed the founding father, for Peirce's influence was continuous through Schroeder's work, with side channels into Peano, and culminating in Principia Mathematica. We can trace out a chain of development of logic from Boole up through De Morgan, Mitchell, Peirce, Schroeder, Peano, Russell, and Whitehead, to logic in its modern estate. Where the inception of mathematical logic comes in this chain is in 1883, when quantification becomes clearly articulated by Charles Sanders Peirce. Even the terms quantifier and quantification, thus applied, are his. It is also interesting to note, as Quine does, how arduous is the path to the notion of a quantifier in Peirce, although what is ostensibly that same notion seems to spring full-grown from Freya in his Begriffsschrift. This would be much less surprising if they were articulating quite different notions, as in fact they are. The idea that Freya is the founder of quantificational logic is simply false. It is due, at least in part, to Russell's falsification of the history of logic. Point 7. The basic idea of quantification is very simple. Much as phi is true just in case the object denoted by the letter A has the property f, so fx is true just in case all objects more exactly, as we have to say to avoid falling into a contradiction, all objects in the domain of quantification have the property f and fx is true just in case at least one object has that property. But, although the basic idea is very simple, and appears already in Kant's late lectures on logic, working it up into a theory powerful enough to deal with all cases would be achieved by Tarski only in 1933, 50 years after its first official introduction by Peirce. Nor were there only technical difficulties. Philosophical debates about the precise nature of the quantifiers also sprang up, and although they no longer command any interest, this is not because they have been resolved but instead because they have come to seem unresolvable. Natural language is exceptionally versatile, anything that can be said, one way or another, in natural language. But some things, in particular, truths of mathematics and logic, seem most aptly expressed in written language using the literal notation. For example, we use letters in logic to express the law of identity, that A equals A, though we can also express that thought in English as that everything is self-identical. We similarly use letters in arithmetic to express, say, the commutativity of addition, that A plus B equals B plus A, though this too can be expressed in English, most naturally, I think, as that the operation of addition is commutative, that is, as ascribing a property to the arithmetical operation of addition. Numbers do not seem to come into it at all, any more than any objects are referred to when one rehearses the law of identity, that A equals A. Accidental generalities are very different. If I claim that every saucer in the cupboard is chipped, to use an example of Dumetz, then my claim is true just in case each and every saucer in the relevant cupboard is chipped. The claim that, say, all cats are mammals seems to be different again insofar as we take it to be necessary that cats are mammals. Whereas an accidental, merely contingent generality such as that every saucer in the cupboard is chipped authorizes only what Sellers has called a subjunctive identical, that if anything were one of the saucers in the cupboard then it would be chipped. A lawful generality authorizes a subjunctive conditional. If there is a lawful connection between being a cat and being a mammal then it is true that if anything were a cat then it would be a mammal. As the point might be put, in this case, by contrast with the case involving the saucers, we are talking not merely about all the actual cats but about all possible cats, all the cats there are or could be. Mathematical logic treats all these sorts of cases in the same way, in particular, It treats a generality in mathematics such as that A plus B equals B plus A in just the same way that it treats an empirical, merely accidental generality such as that every saucer in the cupboard is chipped. Both are taken to involve a universal quantifier and so to refer to objects. And as already indicated, it is easy to understand how, given the developments in mathematics in the 19th century and the enormous and pervasive influence of Kant, this might have seemed the right way to go. What we need now to see is how the very different demands of, on the one hand, the empirical, merely accidental or contingent case, and on the other, that of mathematics, pull in different directions. We saw in section 4.2 that Euler and Venn diagrams encode two very different conceptions of judgment. Euler diagrams encode a pre-modern conception according to which judgment is a matter of predicating of objects assumed already given that they are thus and so. On this conception of judgment, which is quite natural in our everyday understanding, one can predicate only of something that actually exists. If there are no SS, then one can make no judgment of the form cis p, which is why it is valid to infer, in Aristotle's logic, that some S is P given that all S is P. Venn diagrams function very differently. They encode instead a Kantian conception according to which judgment acts instead on two concepts that are not presumed to have any instances but are conceived merely as predicates of possible judgment, and relates them to objects by way of something like a quantifier, that all objects are P if S, that some object is both S and P, and so on. These two conceptions of judgment give rise in turn to two very different intuitions about quantifiers, the intuition that they are inherently restricted and the intuition that they are inherently unrestricted. According to the defender of restricted quantification, quantifiers function as determiners enabling the expression of thoughts that are about all, or some, or exactly n, objects of a certain kind. As Brandom has put it, quantifiers quantify, they specify, at least in general terms, how many. As Brandom immediately goes on, the question how many, however, depends on what one is counting on the sortal used to identify and individuate them. Now in Grundlagen, Freya is talking not about generality but about numbers. If I give someone a stone with the words, "Find the weight of this," I have given him precisely the object he is to investigate. But if I place a pile of playing cards in his hands with the words, "Find the number of these," this does not tell him whether I wish to know the number of cards, or of complete packs of cards, or even say of points in the game of skat. To have given him the pile in his hands is not yet to have given him completely the object he is to investigate. I must add some further word cards, or packs, or points. On Brandom's view, this point about numbers applies also to quantifiers. Because the role of the quantifier on this account is to determine, in general terms, how many, for example, some, or all, or at least 23, or most, or exactly one objects of a certain kind have the relevant property, and because the question how many, is meaningless in the absence of a sortal determining what is to be counted, it follows that a quantifier is inherently restricted. Given that it is, unrestricted quantification a dangerous and often unwarranted extrapolation based on a misunderstanding of the way pseudo and prosertals such as thing, object, one, and item function. Thing, object, and so on do not individuate objects, one cannot count things or objects as such. But if quantifiers serve to specify how many, then unrestricted quantification involves just such pseudo-sortals. The apparently unrestricted quantifier is in fact restricted, it is restricted by a pseudo-sortal such as thing or object. Restricted quantification, then, is logically prior to unrestricted quantification. The latter is to be understood in terms of the former point 8. It is quite natural, at least in some cases, to think of a general sentence of natural language as answering the question how many, and so to think of the quantifier as a determiner. Question: how many people now in the room are wearing glasses? Answer: all of them. 9 In other cases, the idea is less plausible. The judgment that all red things are colored, for example, is not easily taken to provide an answer to a how many question. There is no number that is the number of red things, so it would seem that there is no sense to the question how many red things are colored. And yet, it seems obviously true that all red things are colored. Or consider the mathematical truth that every ordinal has a successor. There is no number that is the number of ordinals, and yet we do know that every ordinal has a successor. Similarly for the case of a logical truth such as that everything is self-identical. Here again, it does not seem plausible to take this truth to involve a determiner and associated sortal, that is, as answering the question how many things are self-identical. In these cases it is the Venn-style depiction of judgment rather than the Euler that seems most natural, and with it a conception of quantifiers as unrestricted. Russell, in his Principles, seems to have the Venn conception in mind, and he does so at least in part because he is thinking not of everyday examples but of mathematical ones. He argues that quantifiers are inherently unrestricted. It is customary in mathematics to regard our variables as restricted to certain classes. In arithmetic, for instance, they are supposed to stand for numbers. But this only means that if they stand for numbers, they satisfy some formula, i.e. the hypothesis that they are numbers implies the formula. Thus in every proposition of pure mathematics, when fully stated, the variables have an absolutely unrestricted field. Any conceivable entity may be substituted for any one of our variables without impairing the truth of our proposition. The 1906 essay on insolubilium makes the point more generally. A statement, such as phi x, which is true under an hypothesis can only be stated to be true under that hypothesis if the statement that the hypothesis implies phi x can be made without any limitation on x. Any limitation on x is part of the whole which is really asserted, and as soon as the limitation is explicitly stated, the resulting implication proposition remains true when the limitation is false. Thus a variable must be capable of all values. Russell argues that any sortal restriction can be formulated as a condition on the truth of the generality. The sentence A equals A plus AC, for instance, which is true no matter what numbers are put for A, B, and C, can be expressed unconditionally as if A, B, and C are numbers then A equals A plus AC. This sentence is true no matter what object names are put for A, B, and C, hence, Russell concludes, a variable must be capable of all values. Whereas Brandom argues that restricted quantification is conceptually basic on the grounds that a quantifier requires an associated sortal, so that unrestricted quantification is actually restricted by the dummy sortal object or thing. Russell argues that unrestricted quantification is conceptually basic on the grounds that any associated sortal can be treated instead as a condition on the truth of the sentence, leaving the quantifier wholly unrestricted in its scope. Thinking of a quantifier as a determiner is especially plausible in the case of an accidental regularity. In the case in which a sentence of the grammatical form all S is P is true in virtue of the chance concurrence of facts, that this S is P and that S is P and so on for all the SS there actually are, it is very plausible to take the sentence to have the form of an ascription of the predicate P to the SS, that is, to each and every one of them. For the ground of the truth of all S is P is, in such a case, the truth of the particular instances. But the case of a law, say, a law of algebra, seems essentially different. The thought that A equals A plus AC is not grounded in arithmetical facts such as that 3 equals plus. Although one might first discover the law by reflection on cases, one does not examine cases to determine that the law is true. In this sort of case the generality seems to be logically prior to the instances. Whereas in the empirical case the truth of the generality is grounded in the truth of the instances, in the mathematical case, the reverse would seem to be true. The generality seems to be the ground of the truth of the instances. It is for just this reason that the idea that the quantifier is functioning in this context as a determiner is so implausible, and for the case of a sentence such as that every ordinal has a successor is simply unworkable. The conception of a quantifier as a determiner, while it is clearly cogent for the case of an accidental generality, seems altogether wrong as an account of how quantifiers function in general laws such as the distributive law of elementary algebra or the law that every ordinal has a successor. The Russell-Lien account, which takes quantifiers to be unrestricted, seems more plausible for the mathematical cases, though of course it will lead to contradiction unless a domain of quantification is antecedently specified. But the Russell-Lien account seems most implausible if applied, say, to the claim that every saucer in the cupboard is chipped. As Russell already saw, to make the extension to the empirical case requires that in addition to particular facts, there are also general facts and existence facts, that is to say, there are not merely propositions of that sort but also facts of that sort. In the case of the saucers, for example, the strategy requires not only facts such as that the saucer, which is in the cupboard, is chipped, and that saucer in the cupboard is chipped, and so on, but also essentially general facts such as that nothing else but this, that, and the other saucer is a saucer in the cupboard. The idea that there are essentially general, and yet merely empirical facts of this sort, contingent facts that are nonetheless not reducible to singular facts about particular objects, is the price Russell must pay to extend his analysis to the empirical case. Like Freya's question in Grundlagen whether the units collected in a number are identical or different, the question whether quantifiers are inherently restricted or inherently unrestricted seems to admit of no clear answer. In our case, just as in the arithmetical case, each side supports its assertions with arguments that cannot be rejected out of hand. If it is assumed both that reasoning is everywhere the same and that even truths of mathematics are in some way about objects, that all generality is to be understood quantification ally, then quantifiers must be at once restricted and also unrestricted. Are quantifiers perhaps, then, barely restricted but only by the pseudo-sortal object? Russell's paradox shows that that way out leads to contradiction. We are left, finally, with an irresolvable dilemma. In mathematical logic as it is currently practiced, we do use restricted quantifiers, that is, we specify a domain of quantification, but we do so in order to avoid paradox, not because we think we understand what quantifiers really are, whether restricted or unrestricted. A second debate that our quantificational understanding of generality has generated concerns two very different semantic accounts that can be given of quantified generalities, the objectual and the substitutional. According to the objectual interpretation, a universally quantified sentence fx is true just in case all objects have the property f, and an existentially quantified sentence fx is true just in case at least one does. On the substitutional interpretation, a universally quantified sentence is true just in case every substitution instance is true, and an existentially quantified sentence is true just in case at least one substitution instance is true. An adequate semantics for first-order logic can be given either way. 10. On the objectual interpretation, a universally quantified sentence is true just in case all objects in the domain of quantification have the relevant property. On the formally adequate objectualist account due to Tarski, the truth of quantified generalities are understood in particular by appeal to the technical notion of satisfaction. On the substitutional interpretation, quantified generalities are instead understood truth functionally. Universally quantified sentences are to be taken to be logically equivalent to conjunctions, possibly infinite, of instances, and existentially quantified sentences are to be taken to be logically equivalent to disjunctions, possibly infinite, of instances, and bon vec. On the substitutionalist view, we are to analyze the indeterminate reference of quantifiers and variables in terms of the determinate reference of names. The truth of quantified sentences will be defined in terms of the truth of their instances. Formulas with free variables will receive no interpretation at all. Thus the reference of variables, and in general the quantificational apparatus, will depend on the individual constants. According to the substitutional interpretation, a quantified generality means the same as a truth function of singular sentences. Its truth conditions are just those of a truth function of its instances. On the objectual interpretation of a quantified sentence such as, the letter x functions as a variable ranging over the domain of quantification. The sentence is true just in case the sentential function fx proper superset symbol gx is satisfied by all objects in the domain. The substitutional reading takes X to function schematically, to indicate the structure of the sentences that go to make up the relevant conjunction or disjunction. Sellers puts the point this way. If by language is meant a symbolic system in which all individual constants and predicates are explicitly listed without the use of such devices as, or and so on, a system, that is, in which the expressions which are substitutable for variables are explicitly listed, then it is clear we do not speak such a language, but rather the schema of a language. Only an omniscient being could effectively use such a language. The symbol structure we employ is almost completely schematic as far as individual constants are concerned. We are obliged to make use of general propositions in talking about the world. But an omniscient being, a being able explicitly to state the conjunctions and disjunctions that our quantified generalities are logically equivalent to on the substitutional view, would not. Because we are not omniscient, we employ schemata of sentences to achieve the same end. According to the substitutional interpretation, quantified sentences are to be understood as truth functions of singular sentences, and hence to be about objects in much the way singular sentences are. One does not list all the cases, nevertheless, the truth of the sentence is to be understood as a function of the truth of those cases. The objectualist begins instead with the satisfaction of predicates by objects or sequences of objects. Objectually interpreted, the truth of a quantified sentence is understood not by reference to the truth of its instances but instead by whether or not the relevant predicate is satisfied by some or all objects in the domain. In an adequate formalization of the two approaches, this difference takes the form of the fact that, by contrast with a substitutional account, the objectual interpretation requires appeal to a denotation function in the definition of the truth of a quantified generality. In a substitutional account, open sentences, that is, formulae with free variables, are not assigned any semantic interpretation. Just as Kripke says, on the substitutional interpretation we have no satisfaction, only truth. Later we will see why this debate arises. For now we turn to the technical details. Tarski's 1933 account of quantifiers objectually interpreted provides a structurally analogous account for the substitutional interpretation. According to the objectual interpretation, a universally quantified claim ascribes a property to all objects in the domain of quantification, and an existentially quantified claim ascribes it instead to some objects, at least one, in the domain of quantification. But this alone is not sufficient for an account of multiply embedded quantifiers. The sentence "everybody loves somebody," for example, is expressed quantification ally as LXY and is true just in case everyone has the property of loving someone, that is, quantification ally, just in case every object in the domain of quantification has the property LXY. But what is this property? Even if we know what all our singular terms designate and know the semantic values assigned to each of the n-ary predicates in the language, this will not determine the semantic value of LXY. Because, moreover, there are an endless number of such complex predicates formed from singular terms, predicates, the connectives, and the quantifiers, we need a recursive account. Tarski's definition of truth in formalized languages serves admirably. The task is to extend a simple model theoretic account of the truth of atomic and truth functionally compound sentences to a general account of arbitrarily complex quantified sentences. The means, on the Tarskian account, is the notion of the satisfaction of an open sentence, that is, a sentence containing one or more free variables, by a sequence of objects. We formulate the truth definition for our language as follows. Point 11. 1 names, A designates A, B designates B, and so on. 2 predicates, object satisfies F if alpha is F, alpha satisfies G if alpha is G, and so on. 3 A sequence S satisfies a sentence N if the object N satisfies. 4 A sequence S satisfies an open sentence XK if the KTH member of S satisfies. 5 A sequence S satisfies XK if XK is satisfied by some sequence S that is like S except perhaps in the KTH term. 6. A sequence S satisfies xk if xk is satisfied by all sequences S that are like S except perhaps in the kth term. 7. A sentence is true if it is satisfied by all sequences. Obviously we need to say something more about the notion of the satisfaction of an open sentence xk by a sequence. First, again, an open sentence is not merely a predicate expression, it is a predicate expression all of whose argument places have been filled by variables. Because we will need to correlate our variables with objects in our sequences, we suppose that the variables, x, are numbered 1 through n for arbitrarily large n. That is, we have variables, x1, x2, x3, and so on, and open sentences such as fx1 proper superset symbol gx2, and rx1 x2 x3. Now we assume that we have a function from the natural numbers to objects that generates ordered sequences of objects. The first variable x1 is assigned the object in the first place in a given sequence, the second variable is assigned to the object in the second place in the sequence, and so on. A sequence S will satisfy the open sentence xk just if the object at the kth place in S satisfies, just as in above. But there are of course a vast number of objects about which we might wish to judge. Indeed, there would seem to be non-enumerably many of them given that we make judgments about, say, the real numbers. To guarantee that there are enough sequences to deal with all the cases, the following 3 conditions are stipulated. 1. There is at least one denumerable sequence. 2. For every sequence S, for every natural number I, and for every individual Y, there is a sequence S which differs from S in at most the ith place and whose ith member is Y. 3. For any finite sequence S there is an infinite sequence that results from iterating the last term of S. The truth conditions of quantified sentences of arbitrary complexity are thereby fixed. We have our semantics. Now we need to consider the kind of logical complexity this semantic theory exhibits. We know that there are significant logical differences between, first, simple universally quantified sentences, turned sentences, then, at the next higher level of complexity, sentences that embed an existential quantifier within the scope of a universal quantifier, so-called turned sentences, and finally, sentences that further embed a universal quantifier within the scope of the embedded existential quantifier, that is, turned sentences. The monadic predicate calculus, for instance, is essentially simpler than a polyadic predicate calculus precisely because any turned sentence in the language of the monadic predicate calculus, for example, can be rewritten in such a way that no quantifier is within the scope of another, in our example, fx proper superset symbol gy. All quantifier dependence can be eliminated in such a language, and correspondingly, any set of axioms expressible using only the monadic predicate calculus has a finite model. Turned sentences in which the quantifier embedding is ineliminable are logically more complex than quantified sentences containing no embedded quantifiers. As just noted, axioms expressible without quantifier embedding have finite models. There are only infinite models for axioms that are ineliminably turned in form, such as, for instance, the axiom that every number has a successor conceived quantification ally. Turned sentences, which involve the level of quantifier dependence required in, for instance, the expression of various limit operations, are different again. As Friedman explains, in the case of turned quantifier dependence, for example, in the generation of points on a line by appeal to an axiom to the effect that for every point there is another to its left. Although the total number of points generated is of course infinite, each particular point is generated by a finite number of iterations, each point is determined by a finite number of previously constructed points. In generating or constructing points by a limit operation, on the other hand, we require an infinite sequence of previously given points, no finite number of iterations will suffice. Limit operations, Friedman concludes, involve a much stronger and more problematic use of the notion of infinity than that involved in a simple process of iterated construction. Tarski's account involves, we will see, just this stronger and more problematic use of the notion of infinity. Assuming it is appropriate to interpret the general sentences of his theory quantification ally as it must be if the model theoretic conception of language is to be understood, as it most often is, as a general account of any and all language. Tarski's account makes essential appeal to THIRD-WORLDISM sentences in providing a semantic theory of the classical quantifiers. Point 12. We saw that Tarski's account requires the notion of the satisfaction of a sentence by a sequence with the stipulation that for every sequence S, natural number I and individual Y, there is a sequence S which differs from S in at most the ith place and whose ith member is Y. To ensure that there are enough sequences to yield the right result in all cases, this condition must be satisfied. But, as the at most indicates, this condition has the form of an THIRD-WORLDISM sentence. The ith member of S is identical to the ith member of S and the ith member of S is Y. Quantifiers, we should not be surprised to discover, given that they are to be appealed to in understanding any and all general sentences, both those that are merely accidentally true and mathematical theorems, say, about real numbers, involve something on the order of the logical complexity of limit operations. Quantifiers simply must, if they are to do the job they are called on to do in mathematical logic, quantify over infinite, even non-denumerable, domains of objects, and Tarski's account deals with that fact essentially as 19th century mathematicians dealt with limit operations in calculus. To account even for a simple universally quantified sentence, Tarski must appeal to a condition that has the form of an THIRD-WORLDISM sentence. Mathematically, there is no difficulty with this. Difficulties arise only if Tarski's account is taken, as he himself did not take it, to provide a philosophical analysis of generality for any sort of language, mathematical or natural. Point 13. The quantificational conception of generality aims to provide an account of logical generality that applies both to accidental, empirical generalities and to the demonstrably true generalities we find in mathematics. Intuitively, however, the two cases are very different. Indeed, as I have repeatedly urged, in the latter case objects do not come into it at all. Thus, although in the case of a contingent generality such as Dumet's about the saucers in some cupboard it is quite natural to think of a quantifier as a determiner and hence as inherently restricted, in the mathematical case, if the notion of a quantifier is to be brought to bear, then it seems instead more natural to treat it as inherently unrestricted. Neither view, we have seen, has much intuitive plausibility as an account of both sorts of cases. The objectual/substitutional debate has a somewhat different shape, as we will later see in more detail. It arises because although the truth conditions of a quantified sentence and the corresponding truth function of instances are identical, the inferential consequences are not. We saw, finally, that in order to have an account that is technically adequate for all cases, those that arise in mathematics as much as those that occur in everyday life, something structurally identical to what we find in the case of limit operations is needed. This is unsurprising given that mathematical generalities often concern what, quantification ally, must be thought of as infinitely large, even non-denumerably large, domains of objects. Tarski's work, as an account of how generality works in general, would seem to be obviously incoherent insofar as it explains what an THIRD-WORLDISM sentence means by appeal to an THIRD-WORLDISM sentence. Alternatively, what it can be taken to suggest is that we need to distinguish logically between accidental, merely contingent generalities, which really are about objects, and the apparently very different case of generalities in mathematics. The needs of mathematics, and in particular mathematics since the 19th century, which manifestly has moved a considerable distance from the needs and concerns of everyday life, perhaps should be addressed independently of the resources that are made available by our everyday talk about the things around us. Given that most mathematical truths of any interest are general, and that generality has a central role to play in mathematical reasoning, it is unlikely that we will understand how mathematics works as a mode of inquiry until and unless we have a more adequate conception of the nature of the generality that is exhibited in its judgments, however things work in the case of our everyday talk about things. 6.2 The model theoretic conception of language. According to the mathematical logician, language, any language, involves two essentially different and opposed elements: logical form, which alone matters to the goodness of inference, and content that is given by an interpretation or model. More exactly, on this conception, a language involves four essentially different sorts of signs that Hodges characterizes as follows. First, there are the truth functional connectives. These have fixed logical meanings. Second, there are the individual variables. These have no meaning. When they occur free, they mark a place where an object can be named; when bound, they are part of the machinery of quantification. The third symbols are the non-logical constants. These are the relation, function, and individual constant symbols. Different first-order languages have different stocks of these symbols. In themselves they don't refer to any particular relations, functions, or individuals, but we can give them references by applying the language to a particular structure or situation. And fourth, there are the quantifier symbols. These always mean for all individuals and for some individuals, but what counts as an individual depends on how we apply the language. To understand them, we have to supply a domain of quantification. The result is that a sentence of a first-order language isn't true or false outright. It only becomes true or false when we have interpreted the non-logical constants and the quantifiers. We have already examined the notion of a quantifier that is invoked here, and have seen why it needs also the notion of a variable. Now our concern is with the idea of a non-logical constant. Why should we conceive language model theoretically, and in particular its predicates, as non-logical constants that are meaningful only given an interpretation or relative to a model? One obvious answer is the Kantian one, that without relation to any object given in intuition, one is left with a mere form. Of course, Kant thought that mathematics has a kind of content in virtue of the pure forms of sensibility, but suppose we reject, as 19th-century mathematicians did, the idea of such forms while leaving in place Kant's conception of cognition overall. Then we are left only with empty logical form, on the one hand, and empirical content on the other. Already in 1844 in his Ausdehnungslehre Hermann Grassmann develops such a view. He distinguishes between formal sciences, which do not go outside the domain of thought into some other domain, but remain completely within the field of combinations of different acts of thought, and real sciences, which are empirical. As Nagel explains, for Grassmann, pure mathematics was to be developed entirely with the help of logic alone. Moreover, in order to proceed formally, without a reference to the contents of any science of nature, he recognized that he could not build his system upon axioms, and required instead what he called definitions. These definitions implicitly define the various elements and operations which he introduced, so that Grassmann was one of the first mathematicians who explicitly recognized that mathematics is concerned exclusively with formal structures. Grassmann's formal theory involves concepts without intuitions. But on a Kantian understanding, that means that it is without any content, or truth, at all. Grassmann's theory is, then, purely formal in Kant's sense of formal. Peacock in the 1830s provides what seems, at least on the surface, to be a somewhat different motivation for distinguishing between an uninterpreted language and an interpretation of it. His concern is with the symbolic language of arithmetic and algebra, and it is imperative, he thinks, to distinguish between arithmetical and symbolical algebra on the grounds that although in symbolical algebra it is invariably possible to transform, say, the equation x plus b equals a into x equals a, b, in arithmetical algebra the expression a, b has meaning only if a is greater than or equal to b. Symbolic algebra is, Peacock thinks, purely formal. The only constraint on permissible manipulations of its signs is that provided by the rules. Arithmetical algebra, because it concerns numbers, has additional constraints that are set by its subject matter, for example, the constraint that a larger number cannot be subtracted from a smaller point 14. De Morgan similarly distinguishes between what he calls technical or symbolic algebra, which is an uninterpreted system of signs together with rules of their combinations, and what he calls logical algebra, in which the signs are interpreted. He also takes a step further than Peacock in suggesting that a symbolic algebra might be interpreted in more than one way. In illustration of the idea, he supposes that we have three symbols, m, n, and plus, and one rule, that m plus n is the same as n plus m. Here, De Morgan writes, is a symbolic calculus, how can it be made a significant one? He offers the following 5 interpretations. 1 m and n may be magnitudes, plus the sign of addition of the second to the first. 2 m and n may be numbers, and plus the sign of multiplying the first by the second. 3 m and n may be lines, and plus the direction to make a rectangle with the antecedent for a base, and the consequent for an altitude. 4 m and n may be men, and plus the assertion that the antecedent is the brother of the consequent. 5 m and n may be nations, and plus the sign of the consequent having fought a battle with the antecedent. The first 3 interpretations are especially interesting insofar as Veit had already in the 16th century held a similar view about the symbolic language of algebra. In itself it was an uninterpreted calculus, one that could be interpreted either arithmetically, as concerned with numbers, or geometrically, as about figures such as lines and rectangles. And, we saw, it had to be so conceived because for Veit as for ancient Greek mathematicians one cannot operate with lines the way one operates with numbers. Multiplying one number by another gives a number, but multiplying one line length by another gives instead a rectangle. Multiply means one thing in the case of numbers and something very different in the case of line lengths. It has to be interpreted differently in the two cases. Boole takes up De Morgan's idea and applies it to the laws of thought in his mathematical analysis of logic. As he explains in the introduction, they who are acquainted with the present state of the theory of symbolical algebra are aware that the validity of the processes of analysis does not depend upon the interpretation of the symbols which are employed, but solely upon the laws of their combination. Each system of interpretation which does not affect the truth of the relations supposed, is equally admissible, and it is thus that the same process may, under one scheme of interpretation, represent the solution of a question on the properties of numbers, under another that of a geometrical problem, and under a third, that of a problem of dynamics or optics. It is this idea that is to be extended now to the realm of thought, to logic. In particular, algebraic properties of multiplication and addition that were first formulated for the natural numbers are now to be shown to hold also for the intersection and union of classes and for the logical relations of conjunction and disjunction between propositions. The signs are not, then, to be understood as signs for arithmetical operations, or for operations on classes, or for logical relations among propositions. They are determined only by the rules governing their manipulation, and can be given a variety of interpretations. As Boole shows, by manipulating those signs according to the rules one can derive valid conclusions from classical categorical premises. And here we find a crucial difference between Veit's idea of an uninterpreted formal language and De Morgan's idea as developed by Boole. For Veit, the formal, uninterpreted language is nothing more than a useful tool for solving problems in arithmetic and geometry. For Boole, the formal uninterpreted language and the possibility of different interpretations of it together reveal something fundamental about the nature of thought. Thought has two distinct and separable parts, a formal part and a material part, the difference between which is mirrored in the distinction between an uninterpreted symbolism and an interpretation of it. Reasoning is, in essence, the mechanical, rule-governed manipulation of empty signs. It is nothing more than the workings of a kind of mechanism, something that could as well be achieved by a mere machine. Boole is often looked upon as the founder of computer science for just this reason. 15. An apparently different motivation can seem to pull in the same direction, that is, towards a model theoretic conception of language, namely, a concern for rigor, and in particular, the thought that if one's reasoning really is fully rigorous, that is, completely gap-free, then it will not be necessary to attend to meanings at all. Pasch, the father of rigor in geometry, according to Freudenthal, writes in his 4-Lesson über Geometrie. If geometry is to be really deductive, the deduction must everywhere be independent of the meaning of geometrical concepts, just as it must be independent of the diagrams. Only the relations specified in the propositions and definitions employed may legitimately be taken into account. During the deduction it is useful and legitimate, but in no way necessary, to think of the meanings of the terms. In fact, if it is necessary to do so, the inadequacy of the proof is made manifest. Nagel's characterization of Pasha's view is even more revealing. Everyone is aware, he pointed out, of the dangers which threaten the geometer who uses diagrams and other sensory images, but few seem to be equally aware of the traps which we lay for ourselves when we employ common words to designate mathematical concepts. For such words have many associated meanings not relevant to the task of a rigorously deductive science, and these associated meanings sway us to the detriment of rigor. To avoid these handicaps it is therefore desirable to formalize the set of nuclear propositions, that is, we ought to replace them by a series of expressions in which the geometrical concepts of the propositions have been replaced by arbitrarily selected marks, whose sole function is to serve as places or blanks to be filled in as occasion may warrant. The result of such a formalization is an empty frame, which expresses the structure of the set of nuclear propositions and which alone is relevant to the task of pure geometry. In pure geometry, according to Nagel, all meaningful words have been replaced by meaningless signs, which ensures that one draws no inference grounded in meaning. Pure geometry, like pure mathematics in general, is to be conceived as nothing more than the manipulation of empty marks according to rules. But rigor does not entail formalism in this sense. Rigor requires only that one make explicit all one's presuppositions, everything on which one's reasoning depends. And yet Nagel clearly seems to think that the way to avoid being swayed by associated meanings is by jettisoning meanings altogether. Why? Why does Nagel slide so easily from the demand for rigor to the formalist requirement that all meaningful expressions be replaced by empty signs? A plausible answer is that he associates rigor with mechanism. To be really rigorous is to think like a machine, impervious not only to associated meanings but to any meanings at all. We have seen already that this is a characteristically modern idea, whereas the ancients modeled even the workings of inanimate nature on the animate. The modern turn was to model the animate on the inanimate, that is, the merely mechanical and law-governed. Descartes famously held that non-rational animals are nothing more than complex machines. Perhaps even minds, at least insofar as they are logical, are nothing more than complex machines. Only so, as far as I can see, can someone like Nagel take it to be obvious that rigor can be achieved only by formalism. But if so, it is not the needs of mathematics that is driving the push towards the model theoretic conception of language, but instead tacitly held assumptions about what it means to be rational at all. We turn, finally, to the most directly mathematical motivation for the model theoretic conception of language, namely, the new use to which axiom systems are put in modern mathematics, the fact that different systems of objects can be shown to be isomorphic, and hence can serve as models for one and the same set of axioms. This is explicit, for instance, in Whale's discussion in his Philosophy of Mathematics and Natural Science. An axiom system, a logical mold of possible sciences. One might have thought of calling an axiom system complete if, in order to fix the meanings of the basic concepts present in them, it is sufficient to require that the axioms be valid. But this ideal of uniqueness cannot be realized, for the result of an isomorphic mapping of a concrete interpretation is surely again a concrete interpretation. A science can determine its domain of investigation up to an isomorphic mapping. In particular, it remains quite indifferent to the essence of its objects. The idea of isomorphism demarcates the self-evident boundary of cognition. Pure mathematics develops the theory of logical molds without binding itself to one or other among possible concrete interpretations. The axioms become implicit definitions of the basic concepts occurring in them. We have seen already that a fundamental idea in the progress toward abstract algebra was the realization that the familiar axioms of elementary algebra, although formulated first for ordinary numbers, can be applied to other systems as well. Because whatever theorems can be proved on the basis of the axioms must hold also for any system that satisfies the axioms, it came to seem that the axioms of algebra should be understood as mere forms and its non-logical constants as uninterpreted signs that could then be assigned various interpretations. But, as already indicated, that is not the only way to think about what is going on here. Consider again the familiar axioms of algebra, for instance, these. 1a plus b equals b plus a. 2 plus c equals a plus. 3a times b equals b times a. 4 times c equals a times. 5a times equals plus. Given these axioms governing permissible rewritings, one can further derive various theorems, which similarly govern permissible rewritings, for instance, this, 2 equals a 2 plus 2 of plus b2. The question is how exactly we should think of these axioms. One way is quantification ally, that is, in terms of the conception of generality that we find in standard logic. On this way of thinking, the axioms are implicitly universally quantified claims about ordinary numbers, basic truths about numbers, all of them. But we know that these axioms can also be interpreted differently, that is, applied to different systems of things. Although we can read the axioms as truths about numbers, as on the quantificational reading, those same axioms can also be interpreted differently, as truths about quite different sorts of objects. So long as the axioms are satisfied in a given domain, then the derived theorems will hold in that domain. And this is, of course, an important, and importantly mathematical, insight. What it suggests, if one is working with the quantificational conception of generality, is that we instead understand the axioms model theoretically. We find just such a line of reasoning, for example, in Hodges, who argues that for mathematical purposes, we need non-logical constants whose interpretation is fixed in a structure but not fixed in the language. We want to say, for example, that two structures have some property in common. One method is to write the property as a first-order sentence and say that it is true in both structures. And that is indeed one way to achieve the desired result. But there is also another. On our first, quantificational reading, the axioms, and the theorems derived from them, are conceived as expressing truths about numbers, facts about how things stand with those objects. On the second, model theoretic reading, they are conceived instead as uninterpreted stipulations for which many models might be given. The third way to conceive those same axioms, and the theorems derived from them, is as basic truths about the operations of addition and multiplication, as ascribing properties to those operations, here, commutativity, associativity, and distribution. On this reading, the axioms and theorems are perfectly meaningful, but they are in no way about numbers. What the axioms and theorems concern on this third reading are certain arithmetical operations and particular properties of those operations. On this reading, the axioms set out basic properties of those operations, and on that basis one derives theorems that ascribe other, non-basic properties to those same operations. Point 16. These properties serve, in turn, to ground and explain the goodness of various inferences. It is, for instance, because addition is commutative that the inference from, say, 7 plus 5 equals 12 to 5 plus 7 equals 12 is a good one. This third reading of the axioms as ascriptions of higher-level properties to the operations of addition and multiplication helps to clarify the first two readings as follows. First, if, as the third reading has it, addition has the property of being commutative, then it obviously follows that for any two particular numbers, 3 and 4, say, 3 plus 4 equals 4 plus 3. It follows, that is, that the quantificational reading of that same axiom is true. But now, as we can see, that universally quantified generality is not known to be true directly. Instead, that quantified generality is known to be true because addition is commutative. It is not merely an accidental truth about numbers that as it happens for any two of them the first plus the second is equal to the second plus the first. It is necessary that this be so. And this necessity at the level of individual, particular numbers can be explained by the fact, one level up, that is, at the level of operations on numbers rather than at the level of the numbers themselves, that the operation of addition has the property of being commutative. Point 17. The second, model theoretic reading is also explained because what that reading can be seen to reflect is not a distinctively model theoretic insight, but instead the fact that valid inferences are instances of something essentially general that can be applied to other cases. Suppose, for example, that I infer from the fact that Felix is a cat that Felix is a mammal. If that inference is a good one, that is because it is good in general to infer from something's being a cat to its being a mammal. Any actual inferences are like this, they are instances of something more general, a rule that can be applied also in other cases. Applied now to the case of our axioms, the basic idea is this. If, as on our third reading, we take our axioms and theorems to be ascriptions of properties to the operations of addition and multiplication, then we can see as well that the inferences from the axioms to the theorems are not good in virtue of the fact that they are about addition and multiplication. They are good because having those particular properties that are ascribed in the axioms entails having certain other properties as well. That is just what the derivations of the theorems from the axioms shows. It follows directly that any other function or operation having the same particular properties as are ascribed in the axioms will also have the properties that are ascribed in the theorems that are derived from the axioms. The insight that the axioms and theorems can be applied in other cases does not show that the model theoretic conception of language is the right conception to have. That insight is simply a reflection of a fundamental feature of inference, the fact that any particular inference is an instance or application of a general rule that can be applied also in other cases. On our third reading, the axioms of elementary algebra are contentful truths about the operations of addition and multiplication from which other truths follow. All these truths function in turn to license inferences in particular cases, that is, in demonstrating theorems, for instance, this. If two numbers are each a sum of two integer squares, then their product is also a sum of integer squares. We begin by formulating the starting point in the symbolic language. We have two numbers that are each of them a sum of two integer squares, which we express in the symbolic language thus, a2 plus b2 and c2 plus d2. What we must show is that their product is also a sum of integer squares. So we write down the product of our two sums thus. Notice what we have done here. We began with a certain mathematical idea, the idea, or as we can also say, the concept, of a sum of two integer squares. The content of that concept, what it is to be a sum of two integer squares, was then expressed in the language of algebra, a2 plus b2. This expression, a2 plus b2, does not merely abbreviate the English phrase, though one could imagine so using the signs, but instead formulates in a specially designed system of signs the content of that English phrase, what it means mathematically. To express the idea that we have two such sums, we then use different letters in place of a and b, and on that basis we are able to exhibit the content of the idea of a product of two numbers that are, each of them, a sum of two integer squares. Having thus formulated the content of the concept product of two sums of integer squares in an arithmetically articulated complex of signs in the language, we can now apply the rules given in the axioms and derive theorems. Leaving out obvious steps that we could easily put in, tedious though it would be to do so, the fifth axiom licenses the move from a2 plus b2 to a2c2 plus a2d2 plus b2c2 plus b2d2. Notice, first, that although the rule applies to a certain form of expression, it is still perfectly possible to keep the content expressed in view as we apply the rule. As an indication of this, we can express the rule in axiom 5 in words: if you have a product of a number and a sum, then it can be rewritten as a sum of the products of the number together with each of the summands. It is also worth remarking that although we generally think of inferential articulation as something that involves a relation between concepts, here we are dealing with an internally articulated idea. It is the whole expression that sets out the idea with which we are concerned, the idea of a product of two sums of integer squares, and because that expression is internally articulated, we can apply the rewrite rules of elementary algebra to it. Now we need to reorder to get A 2C2 plus B2D2 plus a 2D2 plus B2C2. At this point a student might wonder why that was a good move to make. The reason, however, becomes clear at the next step in which we both add and subtract 2ABCD to give, after some reorganization. A 2C2, 2A plus B2D2 plus a 2D2 plus 2AD plus B2C2. And now even the student ought to be able to see that this last expression can be rewritten as AC, BD, 2 plus 2. But that, we can see, is just what was wanted, a sum of two integer squares. We have the desired result. Point 18. By formulating the content of the concept with which we began, the content of the concept product of two sums of integer squares, in the formula language of algebra, we were able to reason in the language, by putting equals for equals, to obtain eventually the result that was wanted, that product is a sum of integer squares. That reasoning was, or at least could have been made to be, fully rigorous, every step licensed by a basic or derived rule in the system, but it was also fully contentful. In proving the theorem that the product of two sums of integer squares is also a sum of integer squares, using the language of elementary algebra, one does not abstract from content, instead one expresses content in a mathematically tractable way, in a way enabling reasoning in the system of signs. Of course the beginning student will operate with the language in a fairly mechanical way, much as the beginning chess player operates with chess pieces in a mechanical way in the course of a game. It takes time and practice to become literate in the system, to learn to see the meanings in the signs, the contents they express, and this is not surprising. The symbolic language of elementary algebra is quite unlike natural language. It is a specially designed system operating on its own distinctive principles, and it takes practice, and some skill, to learn to use it to its full potential, just as it takes practice, and skill, to become a really good chess player, to learn to see the opportunities and hazards in particular configurations of chess pieces. There is a further lesson in this example as well. As Avogadro, from whom the example is borrowed, notes, the proof uses only the commutativity and associativity of addition and multiplication, the distributivity of multiplication over addition and subtraction, and the fact that subtraction is an inverse to addition, hence it shows that the theorem is true much more generally in any commutative ring. The little chain of reasoning rehearsed above in the symbolic language of elementary algebra is valid, and so we know that it is an instance of a rule that can be applied also in other cases provided that the requisite properties hold in those cases. This chain of reasoning does not show that we are, in this case, not in fact reasoning about products of sums and sums of squares. What it shows is that the reasoning can also be applied in other cases as well. Again, any actual inference is an instance of something more general, something that can be applied in other cases as well. It is just this that explains the fact that, as Avogadro notes, our theorem about integer squares holds in any commutative ring. We saw in Chapter 3 that Veit understood the language of algebra as an uninterpreted formalism because although it could be interpreted either arithmetically or geometrically, that is, as about numbers or as about geometrical objects such as squares and rectangles, there seemed from Veit's essentially pre-modern perspective no way to give a unified treatment of the signs, one that would embrace both arithmetic and geometry. Descartes, by contrast, was able to give a unified reading of the language because according to him mathematics, at least universal mathematics, is not about objects, whether numbers or geometrical figures, but instead about relations that such objects can stand in. What an equation expresses is, in his view, an arithmetical relation. By moving everything up a level in this way, from consideration of objects to consideration of relations that objects can stand in, Descartes is able, as Veit is not, to provide a univocal meaning for the signs of the language. Similarly, if one thinks of a general sentence such as an axiom of algebra quantification ally, as about all objects in the domain of quantification, then it will seem impossible to give a unified treatment of the signs employed in our axiomatization above, one that will embrace all the models to which those axioms can be applied. If one thinks that what the axioms are about are objects, that they have certain properties and relations, then it will seem that given that different objects, properties, and relations are also correctly described using sentences of the same form, we can, and should, treat the form separately from the various structures that have that form, and the language as a whole model theoretically. The alternative, corresponding to the move Descartes makes, is to move everything up a level again, to conceive the axioms not as about objects but instead as about the operations designated by plus and times, as ascribing to them various properties on the basis of which to draw inferences. This is made explicit in abstract algebra, in the definition of, for instance, a group. In that definition various properties are stipulated of an operation not further specified, and various things are shown to follow from that definition, perhaps together with others. Much as the subject matter of mathematics was changed in the 17th century, so it was changed in the 19th century. And in both cases something new had to be recognized as a locus of the truth of mathematical judgments, first-level relations and functions in early modern mathematics, and higher-level properties and relations in the case of contemporary mathematics. And in both cases one might, for whatever reasons, resist the move or simply fail properly to understand it. If, for example, one thinks that all content and all truth lies in relation to an object, then, given that the axioms hold in different domains of objects, it will be natural to distinguish the forms of the axioms conceived as collections of uninterpreted signs from their contents on an interpretation. But we have seen that there may be other forces at work as well, in particular, an essentially reductive, mechanistic conception of thinking and reasoning. If reasoning really is rule-governed, on this line of thought, then it can have nothing whatever to do with meanings, and must be something even a mere machine can do. The alternative, that reasoning is a capacity of a certain sort of living being in whose nature it is to be rational, is not so much as considered. We are left with the model theoretic conception of language, a fundamental opposition of form and content, and no prospect of understanding the striving for truth in the practice of mathematics. 6.3 Meaning and Truth. We have seen that modern mathematics does not require that we adopt a model theoretic conception of language. Nor is it obvious that we should adopt the quantificational conception of generality, though the two ideas are in certain respects mutually reinforcing. They are also both fundamentally connected to a third, the idea that meaning is to be understood in terms of truth, ultimately, given our understanding of quantifiers, in terms of truths about objects. To know the meaning of a sentence is to know what is the case with objects if it is true. But this apparent truism leads us also to accept something that is less obviously true, and in fact, we will see, false, that sentences that have the same meaning in the sense of truth conditions, what is the case if the sentence is true, thereby have the same meaning in the sense of inference potential, what follows if the sentence is true. Because we equate the two notions, we think that a language that tracks truth conditions provides everything that is needed in inference. This is codified in the mathematical logician's relation of logical consequence. A sentence is a logical consequence of some other sentence or sentences. Just in case if the latter sentence or sentences are true, then the former is as well. This seems unproblematic in the case of the truth functional connectives. That is, it is not unreasonable to suggest that the inferences from, say, A and B to B and from A, B and A to B are good, because if A and B is true then B must be as well, and similarly for our second inference from A, B and A to B. And if one interprets generality quantification ally, then all inferences should be explicable this way, whether one interprets the quantifiers objectually or substitution ally, inferences involving them should be, as our simple inferences above are, merely truth functional. Thus it comes to seem that in order to express everything necessary for a correct inference it is enough to track truth conditions. What is the case if a sentence is true? We will see that both the familiar debate between Millians and descriptivists about proper names, and the debate outlined above between objectualists and substitutionalists about the quantifiers, suggest instead that two different notions are at work, a notion of meaning in terms of truth conditions and another very different notion of meaning as it matters to inference. Meaning is understood in terms of truth in quantificational logic, and because it is, the notion of sense that we inherit from Freya cannot be conceived as a properly logical notion at all. It must concern instead the cognitive value of a sentence for a thinker. Two sentences that have precisely the same truth conditions can differ in cognitive value for a thinker if that thinker, without manifest irrationality, can assent to one but not the other. Sameness and difference in semantic value, in truth conditions, is a logical difference, a difference in the meaning expressed by a sentence. Sameness and difference in cognitive value for a thinker is not a logical difference. This much is clear. What is less obvious in particular cases is whether a difference is semantic or whether it is instead cognitive, whether, that is, it is a logical difference properly speaking at all. Consider, first, the case of proper names. It is very natural to think of a proper name merely as a label for an object, as a means of referring to the thing named in order then to go on to predicate something of it. This is the Millian view of names. That it is the correct view is suggested, first, by the fact that one's beliefs about a given object can be radically revised over time while remaining thoughts about one and the same object, and also by the fact that two different people can have wholly different beliefs that are nonetheless about one and the same object. Both these considerations suggest that names have no descriptive content, that they are merely labels. Furthermore, where two ordinary proper names are in fact names of one and the same object, whether or not anyone knows this, then the truth conditions of two simple sentences that differ only in their involving one or other of the two names will be identical. If A and B name the same object, then A is F and B is F will both be true just in case the object named has the property of being F. One and the same object is the locus of the truth of both sentences and one and the same property is ascribed. The two sentences have the same truth conditions. A thinker may not realize that it is one and the same object that is the locus of the truth of the two claims. Nevertheless, it seems correct to say that where two names designate one and the same object, sentences involving the two names that are otherwise identical have the same truth conditions. But what, then, are we to make of the fact that it does not immediately follow from, say, the fact that Hesperus is a planet that Phosphorus is a planet? The inference from Hesperus is a planet to Phosphorus is a planet is not valid. Nor of course is it valid to argue that Hesperus is Hesperus, therefore Hesperus is Phosphorus. What is needed to turn such invalid arguments into valid arguments is precisely the identity, that Hesperus is Phosphorus. The explanation for this, the descriptivist argues, is that names are really disguised descriptions, and different descriptions in the case of different names. That is why the sentence Hesperus is trivial, although the sentence Hesperus is Phosphorus can constitute a real extension of our knowledge. The argument is often attributed to Freya, but Freya, we will eventually see, is not a descriptivist about proper names, though Russell is, at least about ordinary proper names. We can understand this debate between the Millians and the descriptivists as follows. We assume for the purposes of the argument that if two sentences have the same truth conditions then they have the same inferential significance, the same consequences, and use as our example the familiar pair of sentences, Hesperus is a planet and Phosphorus is a planet. According to the Millian, this pair of sentences shows that proper names are merely labels for objects because, after all, both sentences refer to one and the same thing, namely, Venus, and say the same thing about it, that it is a planet. One might not know that they have precisely the same truth conditions, but they do. The differences between them, for instance, the fact that one does not infer one from the other, is to be explained by appeal to the notion of cognitive value. It is possible to know that Hesperus is a planet without thereby knowing that Phosphorus is a planet because, although the two sentences mean the same thing, they can have different cognitive values for a thinker. In sum, on the Millian view the two sentences have the same meaning, the same semantic value, but can have different cognitive values to a thinker. Where the Millian argues modus ponens from our assumption, argues that the two sentences have the same truth conditions and hence the same inferential consequences, the descriptivist argues modus tollens, the two sentences do not have the same inferential consequences, as is shown by the fact that there is no valid inference from one to the other without the additional premise that Hesperus is identical to Phosphorus, and hence the two sentences also, the descriptivist concludes, do not have the same truth conditions. The difference between the two sentences, in other words, cannot be merely cognitive but is semantic, a difference in meaning, in what is the case if the sentences are true. And yet the Millian seems to be right about the truth conditions of the two sentences, they are identical. The descriptivist nonetheless seems to be right about the inferential consequences of the two sentences, they are different. But if so, then it is the conditional that both agree on that is wrong. A specification of truth conditions is not thereby a specification of inference potential. The second debate has just the same structure but concerns the nature of the quantifiers, in particular, whether a universally quantified claim is logically equivalent to a conjunction of instances, and an existentially quantified claim logically equivalent to a disjunction of instances, or whether they are logically different. Let us stipulate that terned AX and X be given the objectual interpretation and pi X and sigma X the substitutional interpretation. It is clear that in the case in which the domain is finite and surveyable fxiffffx and gxiffgx, in both cases the two sentences are materially equivalent, the one true just in case the other is. Indeed, it can be argued that no matter what the domain, the truth conditions of the two sentences are the same. Although in different ways, they ascribe the same properties to precisely the same objects. So, the substitutionalist argues, a quantified generality is logically equivalent to a truth function of instances. Only they do not seem to be if one considers also their role in inference. It is a matter of logic that fx implies fx, which is the schematic form of the relevant conjunction of instances, and correlatively that gx, schematic for a disjunction of instances, implies gx. If a universally quantified sentence objectually interpreted is true, then one can validly infer any conjunction of its instances one cares to name, and if a disjunction of instances is true, then one can validly infer the relevant objectually interpreted existentially quantified sentence. That much is clear and uncontroversial. The problem is that the converse inferences seem to be invalid, or if not invalid then enthymematic. In both cases a further premise would seem to be needed to the effect that the given cases are all the cases there are. Fx is stronger than any conjunction that can be formed of sentences of the form ft, while fx is weaker than any disjunction of such sentences. If that is right, then a quantified generality cannot be logically equivalent to a conjunction of instances as the substitutional interpretation claims it is. The substitutionalist, seeing that the truth conditions are the same in the two cases, argues that there is only a cognitive difference between a quantified sentence and the relevant truth function of instances. The objectualist, seeing that the inferential consequences of the two are different, argues that there must then be a semantic difference between the two, a difference in meaning, in the truth conditions in the two cases. Only there does not seem to be, and so neither side is able to convince the other. Again, one wants to conclude that both are half right, the truth conditions of the quantified sentence and the truth function are identical though the inferential consequences are not. Again, it is the assumption that sameness in truth conditions entails sameness in inferential consequences that seems mistaken. There is a further wrinkle. The substitutionalist holds that there is only a difference in cognitive value between a quantified generality and the relevant truth function of instances. And this, we saw, seems plausible if one is focused on what is the case if the generality is true, on its truth conditions. If the substitutionalist is right, then, the two sorts of theories, the substitutionalist and the objectualist, are themselves merely cognitively different, two ways of saying the same thing, though one might not realize that they are. The objectualist, focused instead on what follows from a quantified generality as contrasted with the truth function of instances, takes there to be a semantic difference between the two, because the inferential consequences are different in the two cases. The objectualist infers that the truth conditions must also be different in the two cases. For the objectualist, then, there is much more at stake in the debate. From this perspective, the substitutional interpretation, while it may be technically adequate, is simply wrong about how quantifiers work. It may yield the results that are wanted, but its methods obscure what is really going on. The language of standard quantificational logic was designed to track truth conditions. Indeed, as Quine remarks, a good notation of logic, as he understands logic, is designed with no other thought than to facilitate the tracing of truth conditions. And it is tacitly assumed that in tracing truth conditions the language will trace everything necessary for a good inference. But if, as the above considerations suggest, the notion of meaning as it matters to truth needs to be distinguished from the notion of meaning as it matters to inference, then we need to ask what our logical language ought to trace, whether what is the case if a sentence is true, or instead what follows if it is true. Given that the concern of logic is inference, one would presume that it is the latter notion that is needed. 6.4 The role of writing in mathematical reasoning. We saw that Supps assumes, as is common, that mathematical reasoning is just like reasoning in everyday life. This is a surprising thesis if one thinks of the long history of mathematics. Certainly diagrammatic reasoning seems very different from the sort of reasoning one engages in when one is trying to come to some conclusion about, say, the relative merits of two candidates for a position in one's department or what sort of car one ought to buy. The computations of 17th and 18th century mathematicians similarly seem quite unlike everyday reasoning. For most of its long history, mathematics has been distinguished by its use of written marks that do not seem merely to abbreviate words of natural language, and much of mathematics would be paralyzed without those systems of marks. One does not need any system of written marks to reason in everyday life. Everyday reasoning did not wait on the development of a written language. But as we have seen, the mathematical practice that emerged over the course of the 19th century is also not constitutively written. Indeed, the new mathematical practice of reasoning from concepts championed by Riemann aims quite self-consciously to be freed of the constraints of the symbolism of 17th and 18th century mathematics. What then is the role of written marks in mathematical practice? We know already that according to Kant, writing broadly conceived as the inscribing of marks is a constitutive feature of mathematical practice. By contrast with the practice of philosophy, which makes a discursive use of reason in accordance with concepts, the practice of mathematics makes an intuitive use through the construction of concepts. And constructions, as Kant conceives of them, essentially involve some sort of writing, actual or imagined. I construct a triangle by exhibiting an object corresponding to this concept, either through mere imagination, in pure intuition, or on paper, in empirical intuition, but in both cases completely a priori, without having to borrow the pattern for it from any experience. Similarly, in elementary algebra, mathematics chooses a certain notation for all construction of magnitudes in general, as well as addition, subtraction, extraction of roots, etc., and, thereby achieves by a symbolic construction equally well what geometry does by an ostensive or geometrical construction. Reason in its discursive use through concepts, Kant thinks, does not in the same way rely on a system of written marks. Indeed, Kant thinks that reason in its discursive use does not rely on any sort of language. As he explains in the Inquiry, the signs employed in philosophical reflection are never anything other than words. And words can neither show in their composition the constituent concepts of which the whole idea, indicated by the word, consists, nor are they capable of indicating in their combinations the relations of the philosophical thoughts to each other. Hence, in reflection in this kind of cognition, one has to focus one's attention on the thing itself. Point 19. Unlike the written marks that mathematicians use, the words of natural language, whether spoken or written, are of no use in philosophical reasoning. Kant thinks, the philosopher must consider the universal in abstracto. Kant's idea that writing, inscribing marks, is somehow constitutive of mathematical practice has its defenders still today. Rotman, for example, argues in Mathematics as Sign that mathematics is a form of graphism, an inscriptional practice based on a system of writing. According to him, Mathematics is essentially a symbolic practice resting on a vast and never finished language. One doesn't speak mathematics but writes it. Equally important, one doesn't write it as one writes or notates speech, rather one writes in some other, more originating and constitutive sense. Mathematical signs do not record or code or transcribe any language prior to themselves. They certainly do not arise as abbreviations or symbolic transcriptions of words in some natural language. The symbol square root is not a mathematical sign 4 is the square root of, neither is equals the sign 4 is equal to, rather, these English locutions are renderings of mathematical notions prior to them. Others, we will see, maintain just the opposite. They hold that mathematical symbols are merely convenient shorthand much as Supps holds that the signs of logic are a convenient shorthand. A second view of the role of writing in mathematical reasoning is what Rotman calls the documentist view, which he ascribes, for instance, to Husserl. This is the view that language, whether written or spoken, is inevitably after the fact in mathematics, serving only to document or report results obtained independently. This documentist view of the role of language in mathematical reasoning is, that is, essentially Kant's view of the role of language in reason's discursive use. Although words can be used to report a finding of reason in its discursive use, the words are of no help in the reasoning itself. Thurston seems to defend such a view of the role of language in mathematical practice insofar as it is, he suggests, one thing to do mathematics, quite another to communicate, or at least to try to communicate, one's mathematical ideas, whether verbally or in writing. The way mathematicians write is not, Thurston argues, the way mathematicians think. There are, he suggests, big differences between how we think about mathematics and how we write it. And as he indicates, it is just this that explains why mathematical ideas can be communicated so much more effectively in face-to-face conversation than in writing. One-on-one people use wide channels of communication that go far beyond formal mathematical language. They use gestures, they draw pictures, they make sound effects and use body language. With these channels of communication, they are in a much better position to convey what is going on, not just in their linguistic faculties, but in their other mental faculties as well. The practice of mathematics, the doing of it as Thurston understands it, is clearly not essentially written. Yet a third view, common among philosophers and assumed also by some mathematicians, is, as already mentioned, that mathematics is not merely reported, after the fact, in some written language as Thurston suggests, but actually done in natural language, and hence is not essentially written at all. 20 According to Benacerraf, for example, mathematics is done in a sublanguage of English. For the later Wittgenstein similarly, the languages of mathematics are a suburb of the town that is language as a whole, one distinguished only by its straight regular streets and uniform houses. And Supps, we have seen, takes this view in his Introduction to Logic. It is also rehearsed in some college-level mathematics textbooks. Mathematics, we are told in one such text, is done using a specialized dialect of English, that is, in natural language. The symbols are simply a convenience. It is easier to write x2 than the square of x, and x euro is more compact than x is an element of the set A. In each case the meaning is the same. On this view, which manifestly contradicts not only the Kantian view of mathematics defended by Rotman but, along a different dimension, Thurston's documentist view as well, all the signs that are used in mathematics are merely shorthand. Though it would be more tedious, one could do all of mathematics in natural language. 21. We have distinguished three views of the role of writing in mathematical practice: the Kantian view according to which mathematics is constitutively written, the documentist view according to which writing or indeed any public record or communication of one's results is essentially after the fact, and what we can think of as the mathematical logician's view that mathematics is done in natural language or alternatively in some system of signs that functions to abbreviate the words of natural language. A fourth view, that of Philip Jourdain in his little book The Nature of Mathematics, combines the first two. According to Jourdain, It is important to realize that the long and strenuous work of the most gifted minds was necessary to provide us with simple and expressive notation which, in nearly all parts of mathematics, enables even the less gifted of us to reproduce theorems which needed the greatest genius to discover. Each improvement in notation seems, to the uninitiated, but a small thing, and yet, in a calculation, the pen sometimes seems to be more intelligent than the user. Jourdain claims that a good, that is, simple and expressive mathematical notation, although not necessary to the practice of mathematics, enables even the less gifted of us to reproduce theorems. But if so, then a collection of signs in a good mathematical notation does not merely record results as on the documentist view, it can actually embody the relevant bit of mathematical reasoning, put the reasoning itself before our eyes in a way that is simply impossible in written natural language. We saw already in Chapter 2 that even in Greek mathematical practice we find chains of reasoning, for example, that to show that there is no largest prime, that are reported in natural language and make no essential use of any written marks. Such a proof depends, as we noted, not on the capacity to write and read but on the capacity to reflect on ideas. It involves, that is, reason in its discursive use in Kant's sense. Unlike, say, a calculation in Arabic numeration, the proof that there is no largest prime does not embody or show the reasoning but only reports it. Although the words do communicate the argument, one is not reasoning in natural language in this case. It is not the words, written or spoken, that one attends to, not in the way one attends to a drawn diagram in working through a demonstration in Euclid, or to an equation in elementary algebra, or to Arabic numerals in the course of an arithmetical calculation. What one attends to are the relevant ideas, for instance, the idea of a number that is the product of a collection of primes plus 1. The proof can be recorded and communicated in natural language, conveyed by means of it, but the proof is not in the words that are used to convey it do not put the proof itself before one's eyes. The ancient proof that there is no largest prime shows that mathematics is not essentially written. That proof could have been discovered, perhaps was discovered, long before there was any written natural language. And this is in any case something we might have expected. Systems of written signs such as the symbolic language of arithmetic and algebra that have been devised for mathematics were devised for mathematics that already existed. It would be impossible to design such a notation for mathematics without knowing at least some of the mathematics that the notation was designed to capture. But it also seems clear that at least some of the systems of signs that have been devised in mathematics paradigm, among them, Euclidean diagrams, Arabic numeration, and the symbolic language of Descartes algebra, are enormously powerful vehicles of mathematical reasoning. Point 22. Although it is manifestly possible to discover significant mathematical results, that is, solutions to mathematical problems and proofs of theorems, independent of any system of written signs within which to work, it is also evident that such systems of signs are developed in mathematics and can enable results that could not be discovered without them. Systems of written marks seem, then, to be neither essential nor irrelevant to mathematical practice, at least if it is taken overall. Throughout history there have been natural calculators able to identify even very large primes or the solutions to quite difficult arithmetical problems without appeal to any sort of written language. Most of us need the Arabic numeration system, or something comparable, to perform such tasks. Similarly, although various algebraic results were discovered by gifted mathematicians before the development of an adequate symbolism of elementary algebra, most of us can understand those results only when they are expressed in the symbolic language of arithmetic and algebra, only when we can see the reasoning in the formula language. In these cases, mathematics that at first can only be reported, conveyed in natural language together with whatever else seems helpful such as sound effects and drawings, comes later to be displayed in a specially devised system of written signs. It seems furthermore clear that what the systems of signs capture in these cases is not, at least in general, the way the mathematicians themselves were thinking. Natural calculators do not calculate as one calculates in Arabic numeration, albeit somehow naturally. that system was not devised to mimic the reasoning of such people. Point 23 Instead, the system of Arabic numeration provides a kind of rational reconstruction of the mathematics. It shows not how natural calculators reason, how they discover their results, but how the mathematical reasoning itself works, at least in this particular corner of mathematics. It lays out the reasoning as contrasted with some person's reasoning. Point 24. Mathematical languages such as the symbolic language of arithmetic and algebra enable non-mathematicians, and in some cases even mathematicians, to understand mathematics that would otherwise be wholly inaccessible. The point is not merely that the mathematics is harder without a system of signs within which to work, but nonetheless perfectly possible. Such systems of signs in mathematics do not merely make things easier. They make things easier because they embody processes of mathematical reasoning again, not processes of mathematicians' thinking but of mathematical thinking itself. They display how the mathematics works. And if that is right, then we can reconcile Rotman's and Thurston's views. Rotman is right, one can do mathematics, actually perform the reasoning, at least as a public, observable act, only in a specially devised system of written signs. But so is Thurston, in areas of mathematics for which an adequate expressive notation has not yet been devised. Language, that is, natural language, whether written or spoken, supplemented with whatever signs from mathematics seem helpful, is invariably after the fact, serving only to document or communicate results obtained independently. In such cases, although gifted mathematicians will still be doing mathematics, the act will not be public and observable. Mathematicians will not be able to show us how it goes but can only tell us, describe in words, what they have discovered and why it is true. We have been exploring the idea that although mathematical reasoning can only be reported after the fact in natural language, whether spoken or written, that same reasoning can be embodied in a specially devised system of written signs, one that, as Jourdain notes, can require the long and strenuous work of the most gifted minds to be developed. Point 25 The way mathematicians actually write their proofs in current mathematical practice, together with the fact that formalizing such a mathematical proof in standard notation is unhelpful and often unintelligible, provides strong evidence that Jourdain's account of the role of writing in mathematical practice is indeed correct. Our mathematical logic, designed to abbreviate words of natural language, is not a language within which to reason, not a mathematical notation in Jourdain's sense at all. On the mathematical logician's view, the only difference between a proof as formulated by a mathematician in actual practice, on the one hand, and that same proof fully formalized, on the other, is that the former has jumps in the reasoning, whereas in the latter, formalized proof, the jumps have been replaced by small steps that are manifestly instances of the rules of formal logic. On the alternative view now under consideration, a mathematician's chain of reasoning, although it can be reported after the fact in natural language, can be embodied, actually displayed as the reasoning it is, only in a specially devised system of signs. Already in Chapter 2, we distinguished between two different ways in which one might see for oneself in mathematics, either by thinking through the chain of reasoning for oneself or by working it out for oneself in some paper and pencil reasoning. And this distinction in turn allowed us to distinguish between reporting a chain of reasoning in natural language and displaying some mathematical reasoning in a specially devised system of signs, as one does in Euclidean diagrammatic practice, or in a paper and pencil calculation in the positional system of Arabic numeration. Mathematical proofs as they are given today are, as already noted, generally reports of reasoning rather than displays of reasoning. Point 26 That is, instead of giving a chain of reasoning, whether or not one that has gaps or jumps in it, mathematicians describe how the proof goes, or would go were one to work through it. As evidence, Avogadro offers this list of typical descriptive phrases taken from the opening chapter of a well-known undergraduate textbook, Birkhoff and MacLane's A Survey of Modern Algebra. The first law may be proved by induction on n. By successive applications of the definition, the associative law, the induction assumption, and the definition again. By choice of m, p will be true for all km. Hence, by the well-ordering postulate. From this formula it is clear that this reduction can be repeated on B and R1. This can be done by expressing the successive remainders Ri in terms of A and B. By the definition of a prime. On multiplying through by B. By the second induction principle, we can assume P and P to be true. Continue this process until no primes are left on one side of the resulting equation. Collecting these occurrences. By definition, the hypothesis states that Theorem 10 allows us to conclude. Proofs written using such phrases are not themselves the reasoning but instead descriptions of how the reasoning would go were one actually to reason from the starting point to the desired theorem. Thurston suggests that the way mathematicians think is different from the way they write. And as just indicated, this is borne out by the way they actually do write. The proof itself, the actual chain of reasoning, is not given in the writing but only described. And it can, if Thurston is right, be best described using all of the very wide variety of channels of communication that are available in real-time interpersonal communication, not only all the richness and nuance of natural language but also gestures, drawings, sound effects, and whatever else might help to convey the relevant ideas. The language of mathematical logic has, by design, none of this communicative richness and power. Its virtue lies instead in making perspicuous certain logical forms that natural language sentences can exhibit and in codifying rules of inference concerning those forms. It is not surprising, then, that the language of mathematical logic is woefully inadequate as a language within which to communicate mathematical ideas and to describe chains of mathematical reasoning. Nor, for reasons that are not yet clear, is it a good mathematical notation in Jourdain's sense, a notation within which to reproduce results by embodying the reasoning. Again, formalized proofs are unconvincing and generally unintelligible. According to Thurston, actual mathematical reasoning is qualitatively different from the sort of rule-governed symbol manipulation that is involved in a proof in mathematical logic. Mathematicians can and do fill in gaps, correct errors, and supply more detail and more careful scholarship when they are called on or motivated to do so. Our system is quite good at producing reliable theorems that can be solidly backed up. It's just that the reliability does not primarily come from mathematicians formally checking formal arguments, it comes from mathematicians thinking carefully and critically about mathematical ideas. Although one can formalize a mathematical proof in standard logical notation, such a formalization does not seem to capture the mathematician's reasoning, and as Thurston indicates, that is because the mathematician's reasoning is based on mathematical ideas. Rav similarly argues that a mathematician's proof cannot be formalized because it depends on an understanding and prior assimilation of the meanings of concepts from which certain properties follow logically. If this is right, then a formalization in our standard logical notations cannot embody the reasoning because what needs to be expressed in the case of such reasoning is not merely logical form but content, the mathematical ideas that are of concern to the practicing mathematician. But what do ideas have to do with the validity of inference? According to the mathematical logician, the answer is, absolutely nothing. To say that an inference is valid in virtue of form is at a minimum to say that it is an instance or application of something more general, of a schema or rule that applies not only in the given case but also in other cases that are relevantly like it. To use again our earlier example, the inference from Felix is a cat to Felix is a mammal is good, if it is good, because one can infer generally from something's being a cat that it is a mammal. The inference is not good in virtue of being about Felix. Though one does infer something about Felix, the validity of the inference is explained not by reference to Felix but by appeal to a rule, something to the effect that being a cat entails being a mammal. Similarly, the inference from John is in the kitchen or the den and John is not in the den to John is in the kitchen is good, if it is good, because one can infer generally from something's being this or that and its not being that to its being this. The inference is not good in virtue of being about John and his whereabouts. Though one does infer something about John and his whereabouts, the validity of the inference is explained not by reference to John but by appeal to a rule, that known as disjunctive syllogism. Whereas in our Felix example the rule concerns valid inferences that rely on the meaning of cat, In the John example, the rule concerns valid inferences that rely on the meanings of or and not. And just the same is true in all other cases of actual inference, whether material or formal. Any actual inference is an instance of a rule that applies also in other cases. Point 27. Mathematical logic is committed to something much stronger than this, namely, a model theoretic conception of language according to which logical form is opposed to semantic content. One immediate consequence of that commitment is the idea that the Felix inference is not really a valid inference at all. The meaning of cat plays, on this view, an essentially different role in reasoning from the meaning of not or. More exactly, it plays no role at all in reasoning. To write a sentence in standard logical notation is, on this view, perspicuously to display its logical form, where logical form is alone what matters to inference. The particular contents do not, and cannot, come into it at all. Logical contents, such as those given by or and not, are not really contents at all but only form. Contents do not, and cannot, matter to the validity of a proof in language conceived model theoretically. But, again, particular contents do seem to matter in mathematical reasoning. Though any inference is valid in virtue of its form, mathematical reasoning seems to be reasoning from the contents of concepts, from mathematical ideas. If we are to understand how this is possible, we need to keep in mind that although there is a clear sense in which inferences are valid in virtue of their form because they are instances of something more general, of a rule that can be applied also in other cases, it does not follow that language should be conceived model theoretically, in terms of a thoroughgoing distinction between logical form and content, that is, semantic content, content as it matters to meaning and truth. The mathematical logician's view of the mathematician's proofs as merely gappy chains of reasoning seems not to be right, and it seems not to be right at least in part because one does not reason in natural language in the same sense in which one reasons in the essentially written systems of signs that have been developed for mathematical reasoning. Of course, there is a sense in which an English speaker reasons in English, a Chinese speaker in Chinese, and in general that we reason in the natural languages that we speak. But as Kant's distinction between two uses of reason, a discursive and an intuitive use, already indicates, the sense in which one reasons in natural language is very different from the sense in which one reasons in, say, Descartes' symbolic language. In the latter sense of reasoning in a language, one does not reason in natural language at all but only reports reasoning. Current mathematical practice seems to suggest exactly that. 6.5 The Leibnizian ideal of a universal language. We began with the idea that mathematics is done in a natural language, that reasoning is everywhere the same and can be codified in the abbreviations of standard quantificational logic. We have since found reason to call into question not only the assumption that reasoning is everywhere the same but also a constellation of ideas that are generally taken for granted in this logic, that generality, whether in mathematics or in the empirical claims of everyday life, is to be understood quantification ally, that language is to be understood model theoretically, and that meaning as it matters to inference is given by truth conditions. What is the case if a sentence is true? We turn now to an idea that is in some tension with the thought that the reasoning in mathematics is done in natural language, namely, the thought that standard mathematical logic finally realizes the old Leibnizian ideal of a universal language. Nothing, we will soon see, could be further from the truth. As is well known, Frege describes his Begriffsschrift, or concept script, as realizing the Leibnizian idea of a language that is at once a calculus ratiocinator and a characteristica. These expressions have since been employed in a very influential essay in an attempt to clarify some central strands in the history of the development of modern mathematical logic. Because, as is slowly becoming known, these expressions do not mean in that essay what they meant either for Frege or for Leibniz before him, we begin with the Leibnizian idea, at least as Frege understood it. The idea of a universal characteristic, which Leibniz first explores in his dissertation on the art of combinations, goes back at least to Descartes. 28 As Descartes explains in a letter to Mersenne, written on November 20, 1629, in a single day one can learn to name every one of the infinite series of numbers, and thus to write infinitely many different words in an unknown language. The same could be done for all other words necessary to express all the other things which fall under the purview of the human mind. To learn the system of Arabic numeration is to learn to write any natural number, and although such a written numeral will be read, that is, pronounced, differently in different languages. For instance, the numeral 84 is read in English as 84, but in French as 84, it will be written the same way for all. So, Descartes suggests, the same could be done for all the words of natural language. But, he cautions, the discovery of such a language depends upon the true philosophy. For without that philosophy it is impossible to number and order all the thoughts of men, or even to separate them out into clear and simple thoughts. If someone were to explain correctly what are the simple ideas in the human imagination out of which all human thoughts are compounded, I would dare hope for a universal language. The realization of a universal language not only of our ideas of numbers but of all our ideas depends on an adequate analysis of those ideas into their primitive elements, the simples of thought, and hence, Descartes thinks, on the true philosophy. The ways in which words of natural language are formed from sounds and from other words clearly bear no internal, systematic relationship to the ways the concepts or ideas signified by the words are formed from simpler concepts or ideas. But perhaps a system of written signs could be devised in which there was such a relationship. Such a system of written signs would involve simple signs for primitive concepts and complex signs for other concepts that would show in their composition how the contents of those concepts depend on, or can be seen to be built up out of, the contents of the primitive concepts. The crucial idea here is that of showing a content in a composition of signs. The task is not merely to say what is the case if the concept applies, that is, set out necessary and sufficient conditions for its correct application, but to show its content, to display it, much as, I have argued, a drawn circle in a Euclidean diagram displays the content of the concept circle, and as a 2 plus b2 equals c2 displays a relation among arbitrary quantities in Descartes language. Consider, for example, the concept prime number. The content of this concept is, let us say, that no other number will divide it without remainder. But, again, the task is not merely to say what this content is, either in natural language or in some abbreviated version of it, but to show that content in signs, to show it as we show the content of the concept product of two sums of integer squares in elementary algebra. This expressive project is, however, only half the story, as Leibniz clearly saw. A universal language properly speaking has not one but two fundamental, and fundamentally related, aspects. Consider again the positional, decimal system of Arabic numeration. This system of signs not only shows how to formulate the contents of numbers in a systematic way by combining signs for the primitive numbers, 0 to 9, it also provides rules governing the manipulation of signs in an arithmetical calculation. A universal language as Leibniz envisages it similarly would have two fundamental aspects. It would show how to formulate the contents of concepts in a systematic way by combining signs for the primitive concepts, and it would provide rules governing the manipulation of signs in a chain of reasoning. It would in this way be at once a characteristica, a language within which to display the way concepts are formed from other concepts, and a calculus ratiocinator, a calculus of reasoning. As Corte, following Trendelenburg, Gvit, and Exner, puts the essential idea, because structures of expressions in a lingua characteristica characterize structures of concepts, it makes possible to construct a mechanical calculus, a calculus ratiocinator, in which signs could be used as substitutes of concepts, thus turning thinking into calculating. 29. Corte, following Trendelenburg, makes another important observation as well, namely, that the calculus ratiocinator of a proper universal language needs a characteristica in order to express premises from which proofs of its theorems could advance. Corte quotes from Trendelenburg explaining Leibniz's idea. Every proof presupposes definitions. As a matter of fact, the ultimate principles are definitions and statements of identity, i.e., judgments which are proved analytically from the identity of concepts. The important thing is that we form suitable definitions by using sign formulas so that they can form a foundation to the inferring calculus, calculus ratiocinator. What is meant by a definition here is not a set of axioms. The idea that axioms might be treated as definitions is a late 19th century development, not something one might find in Leibniz. For Leibniz, axioms are primitive truths, not definitions. Hence, we need to take the reference to definitions in this passage from Trendelenburg to be a reference to the more traditional notion of definition in which the meaning of a concept is laid out. The claim, then, is that proofs begin with definitions as contrasted with axioms, that is, with explicit definitions. It is definitions, not axioms, that provide the premises of proofs, at least on this view. It is also worth noting that although Kant held in the inquiry that there could be no such thing as a concept script of the sort that Leibniz intended but only an intuition script such as the language of arithmetic and algebra, Kant later seems to have had second thoughts. In a letter to his trusted expositor Johann Schultz written on August 26, 1783, Kant writes, "This and other properties of the table of categories that I mentioned seem to me to contain the material for a possibly significant invention, one that I am however unable to pursue and that will require a mathematical mind like yours, the construction of an ars characteristica combinatorial. If such a thing is at all possible, it should have to begin principally with the same elementary concepts. Perhaps your penetrating mind, supported by mathematics, will find a clearer prospect here where I have only been able to make out something hovering vaguely before me, obscured by fog, as it were." Having, so he thinks, identified the fundamental concepts of the pure understanding through his reflections on the forms of judgment, Kant thinks he has identified the primitives on the basis of which to develop a Leibnizian characteristica. What Kant is clearly finding it much harder to envisage is a way to construct signs and modes of their combination as required fully to realize an ars characteristica combinatorial, that is, a Leibnizian universal language. Point 30. Whether or not Kant took arithmetic to be the model for a universal language, Descartes certainly did, and so did Leibniz. Complex signs for concepts were to be constructed out of simple signs for concepts as signs for larger numbers are constructed out of signs for smaller numbers. Those signs are then to be manipulated according to rules as numerals are manipulated in an arithmetical calculation. Reasoning was thus to be conceived as a kind of reckoning which can but need not be conceived mechanistically. But arithmetic has no definitions, and definitions, we have seen, are critical to the Leibnizian idea. Because they are, it is not simple arithmetic but instead 18th century mathematics that provides a good model of what is needed in a Leibnizian universal language. The primitive signs of the language are the 10 digits, the signs for the basic arithmetical operations, the sign for equality, letters lending generality of content, and parentheses. Familiar axioms set out the basic rewrite rules in the system, and theorems derived from those axioms provide further, derived rewrite rules, for instance, 2 equals a 2 plus 2 of plus b2. We also assume that we have the familiar rewrite rules of the calculus, for instance, that the derivative of xn is nxn, 1. Complex signs for functions are to be constructed out of the primitive signs of the language and set out in explicit identities that provide the starting point for proof. To see more concretely how this works, we consider a proof of what is known simply as Euler's theorem, Ea equals cos x plus I sin x. 31. We begin by defining the trigonometric functions sine and cosine as power series. Sin x equals x, x3/3, plus x5/5, x7/7, plus cos x equals 1, x2/2, plus x4/4, x6/6, plus. This is not how such functions were originally conceived, but given our original understanding of those functions, it makes good mathematical sense to think of them as given in these identities. 32 The signs on the left, the definienda, are simple names for the relevant functions, which are, of course, of antecedent mathematical interest. These same functions are given again in the definientia on the right, but this time through complex, arithmetically articulated collections of signs. Furthermore, because the definientia are complex in the particular ways they are, the rewrite rules of algebra as codified in its axioms and theorems can in principle be applied to them in the course of a problem or proof. Obviously no such rules can be applied to the simple signs on the left because there is no arithmetical articulation in those signs. The expressions sin x and cos x serve merely as labels for certain trigonometric functions. What we want to establish is the truth of Euler's theorem that Ia equals cos x plus I sin x, universally regarded as a paradigm of an interesting and significant mathematical result. One way to prove it is this. We know that the number E is, by definition, the number such that the derivative of x is just x. Given that x is its own derivative, it follows that x equals 1 plus x2/2 plus x3/3 plus x4/4 3/4 plus xn/n plus. And we can see that this must be right because if we take the derivative of the infinite series on the right we will end up with just the same series again. The derivative of the first term is 0, of the second is the first, of the third is the second, and so on. Because there are infinitely many terms, the derivative of the whole will simply be the same series again. If, now, we replace x in this equality with 9, where I is by definition such that I2 equals 1, we get Ia equals 1 plus 9 plus 2 halves, plus 3/3, plus 4/4, plus 5/5, plus. Now we do some standard algebraic manipulations as governed by the axioms and theorems of elementary algebra. Ia equals 1 plus 9, x2/2, 9 3/3, plus x4/4, plus 9 5/5, x6/6. And rearranging things a bit, by collecting together the terms that contain I and separating I out, gives Ia plus I. The two infinite series for our trigonometric functions just pop up when we rewrite as needed. 33 Because the first series is identical with the cosine function and the second is identical with the sine function, putting equals for equals gives us Euler's famous theorem relating the exponential function to these trigonometric functions. As this example illustrates, mathematical identities involving both simple signs and arithmetically complex signs can play a crucial role in a demonstration. Without the simple signs x, sin x, and cos x we would not be able to recognize our result as a result involving the exponential function and the two trigonometric functions, and without the power series with which these three functions were identified, we would be unable to reason our way to the desired result. The example thus illustrates the way in which finding a fruitful articulation of some mathematical notion, one that will enable the proof of some result, can constitute a real mathematical advance. Of course, the simple signs are eliminable in the demonstration in the sense that replacing all instances of them in the course of reasoning with the relevant complex signs will not affect the validity of the reasoning. But equally obviously, doing that destroys the interest of the demonstration insofar as it is no longer possible to see the demonstration as a demonstration involving the exponential and trigonometric functions. What one would end up with in that case would be a trivial identity, one with the same power series on both sides of the identity sign. Euler's theorem is mathematically significant because it reveals a connection between two apparently independent mathematical domains, that of exponential functions and that of trigonometric functions. But we can see this only if we have the identities of the exponential function and of the trigonometric functions with which we began, both the complex signs, the power series, and the simple signs x, sin x, and cos x. By displaying the contents of mathematical notions of antecedent interest in new and mathematically tractable ways in a Leibnizian universal language, identities enable demonstrations involving those notions, and they can do because, as we have just seen, in the identities those contents are displayed in complex signs in ways that enable reasoning. In these identities, both the simple sign and the complex sign designate or mean one and the same thing, they have the same Bedeutung. But, again, they do not express the same sense, they have quite different roles to play in the process of reasoning. As we can think of it, although the two signs, one simple and one complex, have the same meaning in the sense of truth conditions, they do not have the same meaning in the sense of inference potential. Different things follow from the simple and the complex signs precisely because the one is a simple sign and the other is a complex sign with a lot of internal articulation that can be utilized in the proof. We thus have here yet one more instance of an intelligible unity, something that has independently meaningful parts but is also a whole that is not merely reducible to its parts. I have suggested that we think of axioms, for instance, those of elementary algebra, as ascriptions of basic properties to arithmetical operations such as addition and multiplication. Theorems derived from those axioms ascribe further properties to those operations, and both those axioms and the theorems derived from them can then be treated as basic and derived rules governing valid inferences. We have looked at two sorts of cases, one that did not involve any identities of simple and complex signs and another in which such identities have an essential role to play, namely, in the demonstration just rehearsed of Euler's theorem. In both sorts of cases the reasoning is, in principle, fully rigorous. Every step in the reasoning is justified by some antecedently specified rule. But the reasoning is also fully contentful. The formula language of arithmetic and algebra enables the expression of a content in a way that is mathematically tractable, that is, in a way enabling one to reason in the system of signs. It illustrates in this way just how a Leibnizian universal language, one that is at once a characteristica and a calculus ratiocinator, is to work and thereby how a fully rigorous chain of reasoning can be fully compatible with reasoning on the basis of mathematical ideas. Taking our cue from the formula language of arithmetic and algebra as it is employed in the proof of Euler's theorem, we can now ask what would be required of such a language for the practice of reasoning deductively from defined concepts, denken in begriffen, thinking in concepts, that arose in the 19th century. We know that because there was no mathematical language, no system of written signs within which to do this work, proofs had to be reported in natural language together with whatever help could be provided by the formula language of arithmetic and algebra. But it is nonetheless possible to say what such a system of signs would have to do. First, and most obviously, it would have to formulate, set out or display, the inferentially articulated contents of the concepts of mathematical interest in a way that enables mathematical reasoning. And we know that the content must be inferentially articulated, rather than arithmetically articulated as in our Euler example, because we aim to reason deductively from that content. Furthermore, again because the reasoning involved in this case is deductive, the contents of those concepts would need to be displayed in complex signs in a way enabling rules of inference to be applied to them. That is, much as in elementary algebra we introduce a few primitive signs for the basic arithmetical operations, so here we would need to introduce a few primitive signs for the basic logical relations. We would then need to formulate axioms, corresponding to the axioms of algebra, that would set out the basic properties of those primitive logical relations, and to derive some theorems from those axioms. As in algebra, the axioms and derived theorems would then function as the rules governing inferences in the system. Definitions of concepts of antecedent mathematical interest could then be formulated in the system and, as in the proof of Euler's theorem, those definitions could provide the starting point for proofs. The proofs would use the basic and derived rules of inference to proceed step by step from the definitions to the desired theorems. The system would be at once a characteristica insofar as the contents of concepts would be set out in complex signs of the language and a calculus ratiocinator insofar as all steps in the reasoning would be governed by rules, either primitive rules as formulated in axioms of the system or derived rules expressed in theorems derived from the axioms. Freya's Begriffsschrift, we will see, is just such a language, at once a characteristica and a calculus ratiocinator. 6.6 Conclusion. Our aim is to understand the practice of mathematics, both in general and as it has come to be practiced since the 19th century in particular. What we are after is insight into how mathematics works as a mode of inquiry, which requires in turn a cogent account of mathematical truth in relation to mathematical knowledge. and for much of the 20th century it was thought that developments in mathematical logic had provided the essentials of such an account, that what remained was only to secure the foundations. It has become increasingly clear that this is not so. We have here tried to clarify why that logic cannot provide what is needed. The problems do not lie in the rules of inference. Instead, the problems arise because we make substantial metaphysical assumptions in logic, both about the nature of thinking and about the nature of language. It is these assumptions that once made explicit can be shown to be problematic. The model theoretic conception of language, with its notion of a non-logical constant, its conception of generality, and its understanding of meaning in terms of truth, is not obvious. It took many decades and a great deal of hard work on the part of many brilliant minds to hammer out this conception of language. And even now that it has been fully worked out, it is hardly intuitive as an account of language. Technically it has many virtues. Philosophically it has proven a dead end. Mathematical logic does not provide, or even enable, the understanding we seek. Although developments in mathematics in the 19th century seemed decisively to show that Kant's account of mathematical practice in terms of the construction of concepts in pure intuition was wrong, those developments did not show precisely how Kant's account was wrong. One alternative, the less radical, was to think that what was needed to understand mathematical practice was not Kant's account of the intuitive use of reason, but instead something akin to his understanding of logic and deductive reasoning. Although not understood in just those terms, this was the dominant path of philosophers in the 20th century, although not for Kantian reasons. Most work over the course of the 20th century was based on fundamental assumptions that are essentially those we find in Kant, an absolute distinction between logical form and semantic content, and an understanding of meaning in terms of truth and by way of an understanding of quantifiers, of truth ultimately about objects. And one consequence of all this, beginning with Boole's treatment of logic, has been an essentially mechanistic conception of reasoning, an understanding of it as nothing more than the rule-governed manipulation of signs with no regard for meaning. But this idea too has come, over the course of the 20th century, more and more to be called into question. As we have seen, meanings and mathematical ideas seem to be essential in actual mathematical practice. Perhaps, then, real mathematics is not what we can build a computer to do but something only a rational animal can do. To recognize this possibility is to give up the standpoint of Verstand, to adopt instead the standpoint of Vernunfte. Reason. Our aim is to understand our capacity for knowledge of things as they are in themselves, first and foremost in mathematics. And we now have almost all the resources we need in order to achieve this. All that remains is to introduce the mathematical language that Frege devised for the new mathematical practice of reasoning deductively from concepts that arose in 19th century Germany, and to take the needed philosophical lessons from it. We have seen that whereas ancient mathematical practice poses for philosophy the problem of the being of its objects, and early modern mathematics poses instead the problem of the nature and possibility of synthetic a priori judgments, the 19th century mathematical practice of reasoning deductively from concepts poses the problem of the nature and possibility of ampliative deductive proof. The task, in each case, is the same, to understand the characteristic unity, first, of mathematical objects, then, of mathematical propositions, and finally, of mathematical proofs, where this unity is neither an essential unity, the parts of which can be understood only in relation to the whole, nor an accidental unity, the parts of which are fully intelligible prior to and independent of the whole. What we are concerned with, in each case, is an intelligible unity, a whole of independently intelligible parts that is nonetheless not reducible to its parts. Consider, one last time, a Euclidean equilateral triangle, the construction of which is given in the first demonstration of the elements. The triangle is a real whole, one figure, the parts of which are nonetheless independently intelligible. The side, for instance, is a straight line, and straight lines are of course intelligible independent of triangles. But the straight line is also a side, and like the parts of an essential unity, the side qua side is intelligible only in light of the triangle of which it is a side. Similarly, we can think of an analytic judgment in Kant as an essential unity insofar as the predicate is contained already in the concept of the subject, and we can think of an a posteriori judgment as an accidental unity insofar as there is no internal relation between the concept of the subject and the predicate in an a posteriori judgment. Synthetic a priori judgments are different again. They are real wholes in virtue of the necessary relation of the predicate to the concept of the subject, but they also have real, independently intelligible parts. And so it is for the case of reasoning that now concerns us. Where reasoning is merely explicative, a matter of making explicit something contained already in the starting points of the proof, the whole chain of reasoning forms what we can think of as an essential unity. Where the reasoning is instead non-deductive, as in, say, inference to the best explanation, the unity of the whole is only accidental insofar as the steps of reasoning are not intrinsically truth-preserving. In the case of interest, then, we have a deduction, each step truth-preserving, but not a deduction in which the conclusion is contained already in the premises. If we are to understand this, clearly we cannot simply assume a containment model of deduction, as if all deduction were strictly logical deduction. Much as Kant's conception of the synthetic a priori required him to replace Hume's division of all knowledge into relations of ideas and matters of fact with two different distinctions, the analytic/synthetic distinction and that of a priori and a posteriori judgments, so to understand the possibility of ampliative deductive proof, we will see, requires a distinction of distinctions. In place of Kant's division of concepts and intuitions, Frege will put two distinctions, both that of Sinn and Bedeutung, and that of concept and object. That is, much as from Kant's perspective, the ancient notion of a term conflates the logical function of referring with the logical function of predicating, so from Frege's perspective, Kant's division of intuitions and concepts conflates, on the one hand, the notion of an object with that of objectivity, and on the other, the notion of a concept with that of cognitive significance. It is just this distinction of distinctions that we need in order to understand the nature and possibility of ampliative deductive proof. And to show in this way that and how ampliative deductive proof is possible, we will see, just is to show that pure reason has been fully realized as a power of knowing. Pure reason, from being merely a critically reflective capacity, has become the power to know things as they are in themselves. And once we have all this, we will be in a position, finally, to articulate a stable conception of our cognitive relationship to things in the world more generally. To distinguish as Frege does between, on the one hand, the Sinn/Bedeutung distinction, and on the other, the division of concept and object, and properly to understand their relationship one to the other, just is to achieve the standpoint of reason and thereby fully to realize the aspirations of modernity in an intentional directedness on reality that explicitly takes the form of a mediated immediacy, both in our everyday experience of empirical reality and in our scientific investigations into the fully objective nature of that reality. It is fully to realize the power of reason as a power of knowing and finally to understand the striving for truth. 7. Reasoning in Frege's Begriffsschrift. Over the course of the 19th century, mathematics was, for the second time in its long history, fundamentally transformed to become, as it remains still today, a practice of deductive reasoning on the basis of defined concepts. 1 Such a practice clearly does not need any written system of signs within which to work. Indeed, this is evident already in Euclid's Elements, for instance, in the proof that there is no largest prime. But we have also seen that absent such a system of signs the reasoning can only be reported after the fact. It cannot be displayed. Indeed, it is not at all obvious that in such a case there is anything that is the reasoning as contrasted with particular private acts of reasoning on the part of individual thinkers. And insofar as there is nothing that is the reasoning, there is nothing of which it might be asked how it works as reasoning. If we are to understand the new mathematical practice that emerged over the course of the 19th century, we need to be able to see it at work, that is, make it public and observable. And for this we need what, according to Jourdain, any good mathematical notation provides, a means of reproducing theorems in the system of signs. We are already familiar with two such systems within which to reason in mathematics, namely, Euclidean diagrams and the symbolic language of arithmetic and algebra. Gottlob Frege, a 19th-century German mathematician working in the Riemannian tradition, provides us with a third. Frege's Begriffsschrift, or concept script, was explicitly designed as a notation within which to reason deductively from concepts in mathematics. Modeled on the formula language of arithmetic, as Frege tells us in the subtitle of the 1879 Logic, his system of written signs was to do for the newly emerged practice of Denken in Begriffen what earlier systems of signs in mathematics had done. It was to enable one to set out on paper the reasoning that is involved in actual mathematical practice. If we are to understand the practice, we need to learn to read the language that displays it. We have seen that a principal aim of 19th-century mathematics, explicit in, for instance, Bolzano's work, was to show that intuition in Kant's sense has no role to play in arithmetic and analysis. And for Frege, as for many of his contemporaries, banishing intuition from arithmetic and analysis seemed at the same time to suggest that arithmetic is after all a purely logical discipline, that its most basic principles are purely logical and all its concepts definable by appeal only to strictly logical primitives. Point 2. But Frege provides two other reasons as well for thinking that logicism is true. The first concerns the domain of application of arithmetic, the fact that the truths of arithmetic govern all that is numerable. This is the widest domain of all, for to it belongs not only the actual, not only the intuitable, but everything thinkable. If arithmetic, like logic, governs the widest possible domain, then perhaps it really just is logic. Frege's second reason for thinking that logicism is true is the fact that, unlike the axioms of geometry, which can be denied without contradiction, it is not possible in the same way to deny a basic law of arithmetic. Try denying any one of them, and complete confusion ensues. Even to think at all seems no longer possible. Again, it seems natural to conclude that perhaps arithmetic is, then, really logic. Frege's self-appointed task was definitively to show that arithmetic is simply a development of logic, and every proposition of arithmetic a law of logic, albeit a derivative one. But logicism requires more than showing that the fundamental axioms of arithmetic are purely logical. It requires showing as well that there is no such thing as a peculiarly arithmetical mode of inference that cannot be reduced to the general inference modes of logic, and that all concepts of arithmetic are reducible to logic by means of definitions. Indeed, Frege suggests, it is only by such a reduction of the concepts of arithmetic to the concepts of logic that it is possible to fulfill the first requirement of basing all modes of inference that appear to be peculiar to arithmetic on the general laws of logic. In order, for example, to show that the law governing mathematical induction is a purely logical law, one needs to define the notion of following in a sequence by appeal only to strictly logical primitives. Frege's task was to complete such a reduction generally, for all axioms, all rules of inference, and all concepts that appear to be peculiar to the science of arithmetic, algebra, and analysis. Frege's logicist program failed. But what undermined it was not the attempted reduction of the axioms, inference rules, and concepts of arithmetic, algebra, and analysis. What wrecked Frege's logicist program was Frege's attempt to introduce logical objects to serve as numbers. Because he thought he needed logical objects for numbers to be, although in fact contemporary mathematics requires only concepts of numbers of various sorts, Frege introduced an axiom in Grundgesetze, basic law v, that entails that corresponding to every logically permissible concept, that is, to every concept that has sharp boundaries in the sense of delivering a truth value, the true or the false, no matter what is given as argument, there is a course of values, which is an object. Courses of values were to be the logical objects that are numbers. Russell's paradox shows that basic law v leads to a contradiction. There are no logical objects but only logical concepts. Point 3. Frege introduced basic law v in the first volume of his Grundgesetze, and in connection with it also made various alterations to the notation that he had introduced in the 1879 monograph Begriffsschrift. To jettison basic law V is to return to the earlier system of notation, that of the 1879 logic, and to the form of reasoning it supports. Point 4. Our concern here is to understand how reasoning in that notation works. And we will understand this, according to Freya, only if we understand the reasoning of Part 3 of Begriffsschrift. In Part I, Freya introduces and explains his primitive logical signs, the concavity, the conditional and negation strokes, and the sign for identity. He gives a preliminary characterization of the peculiar logical roles of the content and judgment strokes, and indicates the distinctive role his Latin italic letters play in lending generality of content. He also sets out his one rule of inference. Point 5. Part 2 introduces 9 axioms of pure logic, 3 concerning the conditional stroke, 3 concerning the negation stroke, 2 involving the sign for identity, and 1 setting out the fundamental logical significance of Freya's concavity used in the expression of generality. Freya also, in Part 2, derives various theorems on the basis of those axioms using his one rule of inference. As he later indicates, and is in any case apparent in Begriffsschrift, the theorems that are derived in Part 2 are made with an eye to their employment in the derivation in Part 3 of Theorem 133. With a few small exceptions to cater for Aristotelian modes of inference, Freya derives in Part 2 only those theorems of logic that are needed in the Part 3 derivation. 4 definitions are introduced in Part 3 and they provide the basis for Freya's proof of Theorem 133, exhibiting a logical relation among 3 of Freya's 4 defined concepts. If the procedure f is single-valued, and m and y follow x in the f sequence, then y either belongs to the f sequence beginning with m or precedes m in the f sequence. According to Freya, it is this derivation together with the various subsidiary derivations that it involves that are meant to give a general idea of how to handle his concept script. It is not Freya's derivations of theorems on the basis of axioms of logic in Part 2 of the 1879 logic, but instead Freya's derivation of Theorem 133 from his definitions in Part 3 that illustrates how reasoning works in his language. If we are to understand Freya's system of signs, we need to understand this derivation, and how it differs from the derivations of Part 2. 7.1 The idea of a Begriffsschrift. Freya's Begriffsschrift was to be at once a Leibnizian characteristica and a calculus ratiocinator, both, with equal emphasis. We have seen already, at least in outline, what such a language would have to do. It would have to set out the inferentially articulated contents of mathematical concepts in a mathematically tractable way, that is, in a way enabling rigorous deductive reasoning in the system of signs. Freya's language was to do just this, and so to be a language for the sort of mathematical reasoning from mathematical concepts that was then becoming standard. And although Freya at times seems to suggest that the language is equally applicable to reasoning in other contexts or in regard to other sorts of concepts, no such assumption will be made here. The task is to understand Begriffsschrift as a mathematical language, that is, as similar in essential respects both to the language of Euclidean diagrams and to the language of early modern algebra. We saw that Descartes came to read the symbolism of algebra, which for Vede was only a convenient formalism, as a fully meaningful language within which to reason through a metamorphosis in the way he regarded drawn Euclidean figures. Freya, we will see, similarly comes to read equations in Descartes language in a new way and discovers thereby a new kind of language within which to exhibit the contents of concepts. But although both effect in this way a radical transformation in how some inscription or collection of marks is to be regarded, there is also a very significant difference between the two cases. Whereas Descartes learned to do a new kind of mathematics with a new sort of subject matter through learning to see in a new way, Freya had already the new form of mathematical practice of the 19th century. And of course he also had already a mathematician's familiarity with the symbolic language of arithmetic and algebra due ultimately to Descartes. His thought was to achieve something similar to that language for the Denken in Begriffen tradition in 19th century German mathematics, to devise a formula language of pure thought modeled on the formula language of arithmetic. In natural language, there is only an imperfect correspondence between the way words are concatenated and the structure of the concepts. The words lifeboat and deathbed are similarly constructed, though the logical relations of the constituents are different. So the latter isn't expressed at all, but is left to guesswork. Speech often only indicates by inessential marks or by imagery what a concept script should spell out in full. A lingua characterica aut, as Leibniz says, peindre non palle paroles, mais les pensées. And, again, already devised languages of mathematics provide for Freya a model of what is wanted in such a Leibnizian language. The formula languages of mathematics come much closer to this goal, indeed in part they arrive at it. But, as Freya goes on, at precisely the most important points, when new concepts are to be introduced, new foundations laid, it has to abandon the field to verbal language, since it only forms numbers out of numbers and can only express those judgments which treat of the equality of numbers which have been generated in different ways. But arithmetic in the broadest sense also forms concepts, and concepts of such richness and fineness in their internal structure that in perhaps no other science are they to be found combined with the same logical perfection. And there are other judgments which arithmetic makes, besides equalities and inequalities. Introducing new concepts, laying new foundations, making mathematical judgments that do not have the form of equalities or inequalities, in short, doing mathematics in the new style championed by Riemann instead of in the old style of Euler and Gauss, had meant abandoning the formula languages of mathematics, and with them all the virtues they possess. The task was to devise a new mathematical language, more exactly, to extend the existing language in a way that would enable it to deal with the new style of mathematical practice that had emerged in 19th century Germany. The task of a Begriffsschrift, a concept script, is to form expressions for complex concepts out of signs for primitive concepts, and to do so in a way that facilitates rigorous reasoning. In order to achieve this, the formula language of arithmetic must be supplemented with signs for the logical element that will serve as the logical cement binding together the primitive signs available already in arithmetic. It is just this that Freya's own concept script attempts, to supplement the formula language of arithmetic with symbols for the logical relations in order to produce at first just for arithmetic a conceptual notation of the kind I have presented as desirable, a notation that has simple modes of expression for the logical relations that are suitable for combining most intimately with the content. Point 6. I wish to blend together the few symbols which I introduce and the symbols already available in mathematics to form a single formula language. As one builds numbers out of numbers in the formula language of arithmetic, so Freya will build concepts out of concepts in his formula language of pure thought. In Begriffsschrift we use old concepts to construct new ones, by means of the signs for generality, negation, and the conditional. We saw in Chapter 2 that in Euclidean diagrammatic reasoning it is not the definitions expressed in natural language but instead diagrammatic constructions of figures that formulate content in a mathematically tractable way. Assuming only a few primitive constructions as set out in Euclid's postulates of a line between two given points, of a circle given a point and line length, and of an extended line length given some line length, Euclid shows how to construct on that basis other more complex sorts of figures, not only, say, equilateral triangles and squares but also, for instance, cuts of lines in extreme and mean ratio and solid angles out of plane angles. A drawn figure in Euclid serves in this way not as a picture or instance of some geometrical entity but instead to formulate what it is to be this or that geometrical entity, and it does so, we saw, in a way enabling reasoning in the system of signs as scripted by the apodoixis. The system of signs is, in its own unique way, at once a characteristica setting out the contents of concepts in drawn figures and a calculus ratiocinator within which to reason from those concepts. The language of early modern algebra is also, in its way, a Leibnizian characteristica and a calculus ratiocinator, though it is one that is cognitively much more sophisticated than that we find in Euclid. It takes time and practice in the language to learn to see the contents of concepts displayed in collections of signs in this language, even the contents of such simple concepts as that of a sum of a number and its reciprocal, x plus 1/x, or that of a product of two sums of integer squares. In Euclid there are both rules of construction and rules of inference, both of which are involved in any diagrammatic demonstration. In elementary algebra there are, on the one hand, the axioms that provide the basic rewrite rules of the system, and on the other, the theorems one can prove and the problems one can solve given those rules. Whereas in Euclidean diagrammatic reasoning one perceptually reconfigures parts of wholes, in early modern algebra one reconfigures by rewriting, putting equals for equals. We have seen that one can show algebraically that if two numbers are each of them a sum of integer squares then their product is also a sum of integer squares, and that one begins the demonstration by formulating the starting point, two numbers that are each of them a sum of integer squares, in the language thus, A2 plus B2 and C2 plus D2. What we must show is that the product of two such sums is also a sum of integer squares. So we write down the product of our two sums. As we have also seen, one can similarly formulate the contents of important mathematical functions in a tractable way in this language. We saw this in our demonstration of Euler's theorem when it was argued, for instance, that x equals 1 plus x2 2 plus x3 3 plus xn plus. Because the complex sign on the right of the identity sign is formed out of primitive signs in the language, the rules of the language can be applied to that complex sign in a way that is simply impossible in the case of the simple sign on the left of the identity sign. As Freya would put it, although the simple sign on the left and complex sign on the right in our identity have the same designation or bedeutung, namely, some mathematical function, they express different senses. And we know that they express different senses because we had to argue that the identity holds. But in fact we can see already in the notation that the expressions on the two sides of the equal sign express different senses. The mere fact that the sign on the right has a great deal of internal, arithmetical articulation on the basis of which the rules of algebra can be applied, while the sign on the left lacks any such articulation, shows that the two signs express different senses. In our examples from algebra, the content that is formulated is articulated arithmetically, in sums, products, powers, and so on. The content of concern to Freya is instead articulated inferentially, it is content as it matters to inference, not as it matters to algebraic computations, that needs to be expressed in the cases of concern to Freya. It may seem surprising that concepts can have contents that admit of such different sorts of articulation, though having in mind the rich, long history of mathematics will make this seem less surprising. Consider, for instance, the concept rational number. The ancient Greeks had no such concept. Because a number is, for them, a collection of units, what we think of as a rational number is instead conceived as an entirely different sort of entity, namely, as a ratio of two numbers, as two numbers in a certain relation. The early modern notion of a rational number is a notion of a sort of number that can be thought of either relative to whole numbers as a fraction, that is, as something of the form m/n, where m and n are whole numbers, n is not equal to 0, or relative to irrational numbers as decimals that are either finite or repeating. Such expressions formulate rational numbers in a way that is arithmetically articulated, suitable for the calculations that are characteristic of early modern mathematical practice. Freya thinks of that same content as logically articulated. In his presentation of the content of this concept, something, a, is a rational number just in case there is a positive whole number that is a multiple of it, in Begriffsschrift. What we need to understand is how exactly this works. Freya's Begriffsschrift was to be a Leibnizian characteristica in which signs for complex concepts are constructed out of signs for simple concepts, and constructed in such a way that reasoning on the basis of such concepts could be conducted according to determinate rules. Because the form of mathematical reasoning he is concerned with is deduction, that is, the relation of ground and consequent, Freya chooses the conditional as his fundamental logical connective. Freya's three primitive signs for expressing logical content as it figures in mathematical concepts, such as that of a rational number above, are the negation and conditional strokes, and the concavity for the expression of higher-level concepts and relations involving generality. Isolating the primitive logical notions that are needed to serve as the logical cement binding old concepts into new, and devising written signs for them, is straightforward. Much less so is to figure out how it is possible to exhibit the contents of concepts at all. Freya needs not merely to say what a particular content amounts to but to exhibit the inferentially articulated contents of concepts themselves. We know already that a drawn circle in a Euclidean diagram iconically displays the content of the concept circle, that all points on the circumference are equidistant from a center, and hence that one can infer given two radii of that circle that they are equal in length. Similarly, a complex of signs in the formula language of arithmetic displays, for instance, the content of the concept sum of two integer squares, shows what it is to be that in a way enabling calculations, namely, a 2 plus b2. Freya needs, analogously, a way of writing that will display the contents of concepts in a way that supports inferences. The task is not merely to record necessary and sufficient conditions for the application of a concept. What is the case if the concept applies? It is to show, to set out in written marks, the contents of concepts as those contents matter to inference. And to do that Freya needs to invent a new sort of written language, not merely a new system of written marks but a fundamentally new kind of system of written marks. We saw in Chapter 2 that a Euclidean diagram can be variously regarded, that the various points and lines it comprises can be seen now this way and now that, and that this feature of the diagram is critical to an adequate understanding of the fruitfulness of a Euclidean demonstration. A line that is first seen as, say, a radius of a circle is later in the demonstration to be seen as a side of a triangle. In itself the drawn line is neither the one nor the other, but in the context of the appropriate diagram it has the potential to be taken either way. One arrives at a particular geometrical figure by analyzing the diagram. Independent of such an analysis, the drawn points and lines that make up the diagram are not icons of geometrical entities. Drawn points are not, for instance, centers of circles or vertices of triangles, and drawn lines are not radii of circles or sides of a triangle. A particular point is a center of a circle or a vertex of a triangle, and a particular line, a radius or side of a triangle, only relative to a way of regarding the collection of lines and points in the drawn diagram, only relative to an analysis. Freya's concept script, we will see, functions in an essentially similar way. The primitive signs, or collections of them, serve to designate concepts only given a context of use and relative to an analysis into function and argument. Freya's conception of his language, although it is fundamentally similar in certain respects to the conception of a diagram that is needed in Euclidean geometry, is essentially late, possible at all only as a very late fruit of our intellectual development and maturation. It furthermore involves a transformation that is as profound and consequential as that Descartes enacted in founding early modern mathematics. And much as Descartes came to his understanding of the symbolic language of arithmetic and algebra through a kind of metamorphosis in the way he reads a drawn Euclidean figure, so we can achieve a Phrygian understanding of the language of Freya's logic through a kind of metamorphosis in the way we read Descartes' language. It will help to distinguish two stages in the process: first, the transformation itself through which one learns to read the language in a new way, and then the full realization of the power of this new sort of language. In the case of Descartes, the first step is to see a drawing, say, of a square, not as exhibiting a kind of object but instead as exhibiting a certain arithmetical relation among arbitrary quantities, one that can equally well be expressed symbolically, x2. The first step for us is to learn to read the formula language of arithmetic in a new way, not as exhibiting arithmetical relations but as expressing a Phrygian thought and hence as variously analyzable into function and argument. We begin with a mathematical language, that is, a system of written marks within which to do mathematics, specifically, the formula language of arithmetic and algebra. In this system the various signs, the numerals, the signs for arithmetical operations, and so on all have their usual meanings, and in virtue of those meanings, equations in the language serve to display various arithmetical relations that obtain among numbers. Much as the equation a2 plus b2 equals c2 exhibits a certain relation among arbitrary quantities, so we can read the equation 24 equals 16, for instance, as displaying an arithmetical relation that obtains among the numbers 2, 4, and 16.7 in this equation so conceived. The Arabic numeral 2 stands for, or designates, the number 2, the numeral 4 stands for 4, the numeral 16 stands for 16, and the manner of their combination shows the arithmetical relation they stand in. Now we learn to read the language differently, as a fundamentally different kind of language from that it was developed to be. Instead of taking the primitive signs of the language to designate prior to and independent of any context of use, as we needed to do to devise the language in the first place, now we take those same signs only to express a sense prior to and independent of any context of use. Point 8 Only in the context of a whole judgment and relative to some one function/argument analysis will we arrive at subsentential expressions, whether simple or complex, that designate something. Suppose, for instance, that we take the numeral 2 to mark the argument place. In that case the remaining expression, xi4 equals 16, is to be read as expressing a certain arithmetically articulated sense and through that sense as designating the concept fourth root of 16. A concept, in this context, is furthermore to be understood on the model of a function as it is understood by 19th century mathematicians such as Riemann. A concept is a mapping, or as Freya sometimes puts it, a law of correlation, objects to truth values in the case of first-level concepts and lower-level concepts to truth values in the case of higher-level concepts. If now we instead regard the numeral 4 in 24 equals 16 as marking the argument place, the remainder designates the concept logarithm of 16 to the base 2. And other analyses are possible as well. The language is, then, symbolic much as the language of elementary algebra is, but its primitive signs nonetheless function much as the written marks for points, lines, angles, and areas function in Euclid. In the language as Freya conceives it, the primitive signs only express a sense independent of a context of use. Point 9 Only in the context of a proposition and relative to an analysis into function and argument do the subsentential expressions of the language, whether simple or complex, serve to designate anything. Point 10 This is the crucial first step in coming to see how the contents of concepts might be displayed in Begriffsschrift. The first step for Descartes was to learn to see drawn geometrical figures in a new way, as exhibiting arithmetical relations. The second step was fully to realize the potential of this new way of seeing in equations in two or more unknowns, for instance, those that trace the paths of moving points through Cartesian space. In order fully to realize the potential of Freya's new way of reading, we need similarly to go on to consider logically articulated thoughts. We need, that is, two signs for logical relations that are suitable for incorporation into the formula language of mathematics, and in this way forming at least for a certain domain a complete concept script. As already noted, Freya has three primitive signs to serve as the logical cement binding concept words together in the formation of new concept words, namely, the conditional and negation strokes and the concavity. The content stroke is also needed as that to which these signs attach. The conditional stroke is iconic in Peirce's sense, it exhibits one thought as depending, or resting, on another. Exhibits the thought that A is true on condition that B is true, that is, as we will often write it, A on condition that B. The whole formula is true if and only if it is not the case that B is true and A is false. Consider now a simple case involving both the conditional stroke and the concavity. Here we have a complex expression comprising two concept words f(xi) and g(xi), the concavity and the conditional stroke, each of which only expresses a sense independent of the context of a proposition and relative to an analysis. Two analyses are most immediately relevant, namely, this. According to which the formula ascribes the second-level concept universally applicable to the first-level conditional, monadic concept f on condition that g, and this. According to which the formula ascribes the second-level relation subordination to the concepts f and g. On the first reading, what this formula of Begriffsschrift says is that the concept f on condition that g has the higher-level property of giving the value true no matter what the argument, that conditional concept would be correctly applied no matter what object were to be considered. So read, this Begriffsschrift formula does not say that all objects have the property f if g, as does, rather it ascribes a second-level property, the property of yielding the value true no matter what object is given as argument to a first-level concept, from which, of course, the quantified claim about objects follows. On the second reading, the formula says instead that the concept G is subordinate to the concept F, that those two first-level concepts stand in a certain second-level relation. And neither reading is in any way privileged. The one is just as good as the other as a reading of the sentence, much as in the context of an appropriate diagram seeing a line as a side of a triangle is just as good as seeing it as a radius of a circle. Thus, already in this simple example we see how Freya's radically new conception of language enables the formation of concept words. Given the appropriate analysis, we obtain a concept word for the second-level relation of subordination, which takes two first-level concepts as arguments to yield a truth value as value. The fundamental purpose of Freya's concept script is the same as that of earlier mathematical languages, to formulate content in a written system of signs in a way that enables reasoning in the system of signs. More specifically, it is to formulate such content for the mathematical practice of reasoning deductively from defined concepts. Again, the contents Freya aims to display are inferentially rather than arithmetically or spatially articulated. So he introduces primitive signs for primitive logical properties and relations. But once he has done that, he must radically reconceive how those signs function in the context of the language as a whole. Because the task is not merely to record what is the case if a concept applies but to display its content, Freya needs to begin not with concepts but with the contents of whole judgments, that is, free gene thoughts that are a function of the senses expressed by the primitive signs, which can then be analyzed into function and argument in various different ways to give different concept words. A function sign, or concept word, so derived can be highly inferentially articulated, that is, express a very logically complex sense. It nonetheless designates something simple, namely, a concept conceived as a mapping or law of correlation. 7.2 The basics. Anyone who has taught logic, or indeed any rule-governed but non-algorithmic system, knows that it is one thing to know the rules, how to apply them, and another to be able to use them intelligently. In such cases, although one must begin by learning the rules what they do and do not allow one to do, one has facility in the system only when one has acquired a sense of strategy, of what is likely to work or not work given what it is one is trying to do. As strategies remind us, reasoning is not merely a matter of applying rules. It is the capacity to apply them well in a particular context, and this is a skill one learns by practicing, and can improve with further practice. But even strategies do not exhaust the mastery of the mathematician. In mathematics, interesting and significant proofs invariably have a twist, some move, or moves that are surprising, in some way unique, and often altogether wonderful. Freya's proof of Theorem 133 involves such moves, and until we can recognize them as such, we cannot be said fully to understand the proof, or by extension how the language works as a language to enable proof. Point 11 In this section we focus primarily on the rules. In the next we turn to strategy, that is, to a general-purpose strategy that goes a long way in accounting for how reasoning from definitions of concepts goes in Begriffsschrift. In the penultimate section we turn finally to distinctive features of Freya's proof that are not explained by that general strategy, features that alone fully exemplify the power of reasoning from concepts in Begriffsschrift. In Part 2 of the 1879 Logic, Freya introduces 9 axioms and derives on that basis the various theorems that will be needed in the proof of Theorem 133 in Part 3. Much as in early modern algebra, for example, in the demonstration of Euler's theorem, one rewrites formulae according to the rules given in the axioms and derived theorems of that algebra, so in Freya's system one rewrites according to rules given in axioms and derived theorems. And in both cases there is a kind of uber rule that cannot be stated in the system but must instead be presupposed in any application of a rule that can be stated in the system. In algebra the rule is that equals can be put for equals wherever they occur. In Freya's system the rule is that if you have a conditional judgment and know that the condition is met, then you may infer the conditioned judgment unconditionally, that is, detachment. We know that any inference, whether purely logical or not, is an instance of something more general, of a rule that can be applied in other cases. That is, any inference draws a conclusion from some premise or premises according to what Peirce calls a leading principle, where a leading principle is essentially general. Whenever we draw a conclusion, we have an idea, more or less definite, that the inference we are drawing is only an example of a whole class of possible inferences, in each of which from a premise more or less similar to the actual premise there would be a sound inference of a conclusion analogous to the actual conclusion. And as Lewis Carroll famously argues, such a rule cannot be expressed as a premise of the inference. More exactly, if it is so expressed, then another rule is needed to govern the passage from the newly augmented set of premises. In Ryle's words, conclusions are drawn from premises in accordance with principles, not from premises that embody those principles. The rule governing a particular inferential step, that is, the passage from a given judgment or judgments to a conclusion in actual practice, is not expressed in the system, and it cannot be so expressed insofar as it is functioning as a rule. Because the rule governing an inference cannot be expressed in the system, Frege restricts himself in the 1879 logic to only one such rule, namely, this. If one has a judgment of the form A on condition that B and also the judgment that B, then it may be inferred that A. And these must be judgments, that is, acknowledged truths. In Frege's system, one can infer, properly speaking, only from what is true and is acknowledged to be so. What is inferred, the conclusion, is similarly an acknowledged truth. In Frege's system as presented in the 1879 logic, all other rules of inference are expressed as judgments, either as axioms or as theorems derived from those axioms according to Frege's one rule of inference. With one exception, every inferential step in parts 2 and 3 of the 1879 logic involve two premises, namely, a conditional of the form A on condition that B and the judgment that B, and the conclusion that A. We will refer to the judgment that B as the ground of the inference and the conditional premise, the one that has the form A on condition that B, as the bridge. As we can think of it, the conditional premise provides, much as a bridge does for the case of crossing a river, the resources to take one from one judgment, the ground, to another, the conclusion. At least in some cases, we will see, the bridge functions as a kind of a rule licensing the inferential passage from the ground to the conclusion. But although all inferential steps in Begriffsschrift have the same basic form, conceptually, two very different cases can be distinguished. Point 12 In the predominant sort of case, the conditional really does function as a rule. It is something essentially general that applies also to other instances. In other cases the inferential step is merely that of detachment. One has a conditional and also the judgment that the condition of the conditional is satisfied, and so can conclude the consequent unconditionally. Point 13 Frege's derivation of Theorem 5 on the basis of axioms 1 and 2 in part 2 of the 1879 logic, illustrates the difference between these two cases. Frege's first axiom is this. If we think of this formula as a ground, that is, as expressing a judgment or acknowledged truth on the basis of which to draw an inference, there are two different ways we can regard it. First, we can read it as saying that the content A is true on the two conditions that are listed beneath that content and connected to it by conditional strokes, namely, the condition that B is true and the condition that A is true. What we have, that is to say, is the content that A on condition that dash. But we can also read this formula differently, as saying instead that the content A on condition that B is true on the single condition that A, that is, as the content that on condition that A. On the first reading, the formula is trivially true. If both A and B are true, then A is true. On the second, it presents instead an important truth about truth, that what is true unconditionally, that is, on any condition you like. Point 14. But we can also take such a judgment to function not as a truth but as a rule of passage or inference license, that is, as a bridge that can take us from one truth to another. Conceived as such a rule, Axiom 1 licenses a one-premise inference from the judgment that A to the judgment that A on condition that B. For any B you like. Read as a rule licensing inferences. Axiom 1 functions in this way as a rewrite rule much as an axiom or derived theorem of algebra does. Or as we can also think of it, it functions as a postulate does in Euclid. Much as a Euclidean postulate licenses, say, the construction of a line between two given points, or the construction of a circle given a point and a length as radius, so Freya's first axiom licenses the construction of the formula A on condition that B given that one has the formula that A. Freya's second axiom is this. To convince ourselves that this formula is true, that it expresses a thought that ought to be acknowledged as true, we can read it thus: if it is true that A on condition that B and C, and also true that B on condition that C, then it is true that A on condition that C. That is, we read it as about the judgment that A on condition that C, that it is true on two conditions. This is less obvious than is the truth of the first axiom, but nonetheless fairly obviously true. Suppose that we have convinced ourselves that it is true. If we want now to read this Begriffsschrift sentence as an inference license or bridge, we read it instead as the principle that if you have some conditional, here A on condition that B, that is itself on a condition, here C, then you can infer that conditional, A on condition that B, with the condition C instead attached as a condition both on the condition B of the original conditional and on the condition judgment A. Read as bridge. Axiom 2 licenses an inference from a judgment that looks like this to a judgment that looks like this. Conceived as a rule of inference, axiom 2 allows one to move in this way the condition C so that it becomes a condition on both the conditioned content A and the condition B. Much as familiar rules of algebra such as that A equals AB plus AC license rewritings in elementary algebra, so Freya's first two axioms license rewriting a formula in a new way given that one has a formula of the appropriate shape. For example, taking axiom 2 as the ground or premise of an inference, with axiom 1 serving as the bridge or rule of passage, we can, according to that rule, rewrite axiom 2 with an added condition, say, the condition that A on condition that B. This is theorem 3, the first derived theorem of the 1879 logic. Theorem 3 is derived from axiom 2 according to the rule, formulated in axiom 1, that if you have a judgment then you may infer that judgment on any condition you like. That is, although officially the inference is a case of Freya's one rule of inference insofar as Freya substitutes the content of axiom 2 for A in axiom 1 and A on condition that B for B, it is clear that we can also think of this step as an inference from axiom 2 to theorem 3 according to the general rule expressed in axiom 1 that given that one has an acknowledged truth one may infer that truth on any condition one likes. Now we use axiom 2 as the bridge or inference license, with theorem 3 as ground, to infer theorem 4. That is, we move what is in theorem 3 the lowest condition, A on condition that B, onto both arms of the conditional of which it is the condition in theorem 3. Notice that in this case we read the two rightmost conditions on the content A, in theorem 3, as part of the condition judgment in the conditional of which A on condition that B is the condition. To apply the rewrite rule in axiom 2 to theorem 3 as premise, A on condition that B takes the place of C in axiom 2, A on condition that takes the place of B, and on condition that takes the place of A. And this is generally true in reasoning in Freya's Begriffsschrift. To see that and how a given rule applies to some Begriffsschrift formula one must regard that formula in some particular way, regard certain conditions as conditions on a conditioned judgment and others as parts of the conditioned judgment, and different rules will, often, require different ways of regarding the formula. Much as one does in Euclid's system of signs, in Begriffsschrift one must perceptually configure things now this way and now that, depending on what rule one aims to apply. Theorem 4 serves as the bridge from axiom 1 with A on condition that B for A, and C for B to theorem 5. Notice that here theorem 4 is not functioning as a rule, it is not something more general than that to which it is applied, namely, axiom 1, but something less general. We need a special case of axiom 1 here, and so must think of the move from theorem 4 to theorem 5 not as one in which the bridge is functioning as a rule of inference but merely as a case of detachment. We know that the condition on theorem 4 is satisfied because it is nothing more than a special case of axiom 1, so we can detach that condition to give theorem 5. We have just seen that theorem 5 can be derived from axioms 1 and 2, beginning with axiom 2 as ground and axiom 1 as bridge. We derived theorem 3, which then served as the ground, with axiom 2 as bridge to yield theorem 4. Theorem 4 was the bridge from axiom 1 as ground to theorem 5. In this little derivation, then, both axiom 1 and axiom 2 serve once as ground and once as bridge. Because it will help to have a way of visualizing the whole course of reasoning, we introduce the following convention. We write the number of the formula that serves as the ground in an inferential step directly beneath the number of the conclusion of that step and connect the two numerals using a small vertical line. The number of the formula that serves as the bridge for that step in the reasoning is written off to the side, on a level with the number for the ground, and connected to the conclusion using a diagonal line. Using this convention, and marking the axioms with asterisks, the course of the derivation of theorem 5 is as shown in figure 7.1. Figure 7.1 The course of the derivation of theorem 5. That is, reading upwards, the chain of reasoning begins with axiom 2 as ground or premise. The first step is to infer theorem 3 from axiom 2 according to the rule expressed in axiom 1. One then uses the rule expressed in axiom 2 to infer theorem 4 from theorem 3. Theorem 4 serves in turn as the bridge from axiom 1 to theorem 5 insofar as it plays the role of the conditional premise. But again, this inferential step, although formally identical to the first two, is conceptually different. Theorem 4 is not functioning as a rule but instead as a simple conditional, the condition of which is satisfied, as axiom 1 shows. Whereas the first two inferential steps have the form being B entails being A, this is B, hence it is A. The third is a simple detachment, A is true on condition that B is true, but B is true, hence A is true. Our little derivation of theorem 5 is fully rigorous, every step derived from a ground and a bridge according to Freya's one principle of inference. But if that were all one saw in the derivation, one would be missing something. We have already noted an important difference between the first two inferential steps and the third. And there is something else to be seen as well. Think again of the demonstration that the product of two sums of integer squares is also a sum of integer squares. On the way to that result we first derived a 2c2 plus b2c2 plus a 2d2 plus b2d2 according to the rules of algebra. Then we reordered the terms and both added and subtracted 2abcd on the way to the desired result. As far as mere rigor is concerned, each step and each result of a step is as good as any other. But to see only that each step is allowed by the rules is to fail to grasp the point of the demonstration. The point is to reveal a connection between two concepts, that of a product of sums of integer squares and that of a sum of integer squares. The intermediate steps are merely a means to that end and are of no significance in themselves. Just the same is true in the case of the derivation of theorem 5. Although the derivation of theorem 3 is a legitimate move in the system, there is no point to deriving it except in light of what it allows one to go on to do, namely, to derive theorem 4 and on that basis to derive theorem 5. It is theorem 5 that is of interest, and that theorem is of interest at least in part because it expresses an important truth about the relation encoded in the conditional stroke. Theorem 5, appropriately regarded, exhibits the transitivity of the relation designated by the conditional stroke. If A on condition that B and B on condition that C, then A on condition that C. Neither theorem 3 nor theorem 4 has any such intrinsic interest. We know, because Freya tells us in the subtitle of the 1879 logic, that Freya's concept script Begriffsschrift was modeled on the formula language of arithmetic. In the preface of that work, Freya further tells us that the most immediate point of contact between my formula language and that of arithmetic is in the way the letters are used. In the formula language of arithmetic, letters are used in the expression of a kind of generality. They enable the formulation of laws such as that A equals AB plus AC, where such a law relates not any particular numbers but instead kinds or forms of numbers. That is, letters in algebra enable the expression of concepts. For instance, the concept of a product of a number and a sum, a, or the concept of a sum of integer squares, and on that basis enable one to prove that various sorts of numbers are constitutively related. Similarly, in Freya's axioms in Begriffsschrift the use of letters enables the expression of laws about kinds or forms of sentences, that is, concepts such as that of a conditional sentence, and the derivation of relations of entailment between various sorts of sentences. Formulae that express such relations of entailment can, furthermore, often be read also as ascriptions of higher-level properties to lower-level ones. Much as A plus B equals B plus A can be read as ascribing the higher-level property of commutativity to the operation of addition, so, for example, Freya's theorem 5 can be read as an ascription of a higher-level property to the lower-level relation designated by the conditional stroke, namely, the property of transitivity. As one gains facility with the language, one begins to see in this way not only that given steps are valid but also that lower and higher level concepts are expressed in at least some of the formulae of the language, and what they are. The axioms and derived theorems of Part 2 express inference licenses in the form of generalized conditionals. If one has a judgment of a certain form, then one can derive another judgment of a certain form. One can, for instance, reorder the conditions in a conditional involving two or more conditions. Axiom 8 sets out the basic case in which one has a judgment on two conditions that are then switched. Read as a rule licensing inferences. This axiom says that if one has the judgment that A on condition that, then one may infer, rewrite it as, A on condition that. On the basis of axiom 8, Freya also derives various other cases governing the reordering of conditions, cases that involve 3, 4, and 5 conditions. And he shows that one can reorder conditions even in the case in which those conditions are conditions on something that is itself a condition. This rule licenses a switch in the order of conditions in the case in which they are conditions not on a judgment but instead on the condition of a judgment. To see how Freya derives this theorem, consider again theorem 5. We have already seen that we can read this formula as expressing the thought that the relation designated by the conditional stroke is transitive. But we can also read it differently, in particular, as an inference license. Read as a rule licensing a one-premise inference. This formula says that if you have a conditional A on condition that B, that is, the leftmost, bottom condition, then you can attach a condition, any condition you like, to both arms of the original conditional. That is, it licenses inferences of this form. Another way to regard theorem 5 is as the judgment that A on condition that C on two conditions, and hence as a judgment the two conditions of which can be reordered, licensed by the rule in axiom 8, thus. This is theorem 9. What it allows, read as a rule governing a one-premise inference, is an inference from a conditional, here, B on condition that C, to a new conditional both arms of which are also conditionals on condition that dash. Relative to the result of applying theorem 5 as a one-premise inference rule, here everything is switched. The new content, A, is not added as a condition but is instead the condition judgment, and the order of B and C is switched. C, which had been the condition, is now the condition on the condition judgment, and B, which had been the condition judgment, is now the condition on the condition of that judgment. That is, theorem 9 governs inferences of this form. Applying this rule to axiom 8 governing the reordering of two conditions as ground directly yields theorem 10 governing the reordering of conditions that occur in something that is itself a condition on a judgment. Because axiom 8 is, that is, has the form of a conditional, theorem 9 licenses this move from axiom 8 to theorem 10. So far we have considered only one-premise inferences, and officially every inferential step in Freya's system is a one-premise inference. Point 15. But at least some of the theorems Freya derives in Part 2 of Begriffsschrift are more naturally read instead as rules governing two-premise inferences, for instance, Theorem 5. Read as a rule governing a two-premise inference. Theorem 5 is simply the rule we call hypothetical syllogism. Given that A on condition that B and that B on condition that C, it may be inferred that A on condition that C. We have already seen that theorem 9 is just like theorem 5 except for the order of its two conditions, so the same is true of 9 read as a rule governing a two-premise inference. Theorem 7 is just like Theorem 5, except that in place of the condition C there are two conditions C and D. Theorem 7 is thus a variant of the rule of hypothetical syllogism for the slightly more complicated case in which one of the conditionals has two conditions. Theorem 19 stands to Theorem 7 as Theorem 9 does to Theorem 5, the only difference between Theorem 7 and 19 is the order of the two conditions. Theorem 20 governs the case in which one has three conditions that must be carried over into the conclusion. All of Theorems 5, 7, 9, 19, and 20 can function both as rules governing one-premise inferences and as rules governing two-premise inferences. Seen as rules licensing two-premise inferences, they all govern a form of hypothetical syllogism and are distinguished only by the number of conditions they involve. There are three cases, and in principle could be more, that together reveal a pattern that in turn shows something fundamental about the relationship between the rule of detachment and the rule of hypothetical syllogism. Table 7.1 The pattern exhibited by detachment and various forms of hypothetical syllogism. As the progression in Table 7.1 shows, although detachment and hypothetical syllogism can seem quite different as inference forms, we can also see them as deeply related insofar as any conditions on the judgment that B, if there are any, carry over to the conclusion. It is in every case the conditional A on condition that B that is supplying the inference rule or bridge. And because it is, one could not in the same way add conditions to that conditional and still have a rule of the same sort. The premise that A on condition that B is functioning as the major in Aristotle's sense. It provides the rule, the bridge from the other premise as ground to the conclusion. The other premise in each case is what Aristotle calls the minor, it provides a case to which the rule in the major can be applied. We have seen that Theorem 9 enables the derivation of Theorem 10, which licenses the reordering of conditions that occur in the condition of a conditional. Theorem 9 is used in that case as a one-premise rule to transform Theorem 8 into Theorem 10. But Freya also uses Theorem 9, as he uses Theorem 5, to license two-premise inferences. Nevertheless, because he has, officially, only one rule of inference, what is in effect a two-premise inference is actually conducted in two inferential steps, using either Theorem 5 or Theorem 9.16 for reasons that will become clear. It is vital that we understand just what is going on here. We begin with the two premises, A on condition that B, and B on condition that C. What we want to conclude, of course, is that A on condition that C. We cannot, however, do this directly given Freya's one rule of inference. Instead we must, according to Freya's official practice, construct from one of these premises, using either Theorem 5 or Theorem 9, a bridge that will take us from the other premise as ground to the desired conclusion that A on condition that C. We can either use Theorem 5 on the premise that A on condition that B, or use Theorem 9 on the premise that B on condition that C, the results of which would be these bridges. From the first of these as bridge and the other premise, B on condition that C, as ground, we can now derive the desired result, that A on condition that C, and from the second as bridge and the premise that A on condition that B, similarly, the conclusion that A on condition that C follows. It is in just this way that one derives in two steps by forming a bridge, from one of the premises, that will take one from the other premise as ground to the conclusion what might otherwise be achieved in one step according to the rule of hypothetical syllogism. That is, one could also derive the conclusion directly from the two original premises, using either Theorem 5 or Theorem 9 read now as rules governing two-premise inferences. Although in some cases Theorems 5, 7, and 9 really are used as one-premise rules of inference, in other cases it is clear that Freya uses these rules to derive in two steps what is in fact a two-premise inference. Point 17 We see this, for example, in the move from Theorems 52 and 55 to Theorem 57. Although Theorem 9 could have been used to license a two-premise inference directly from Theorems 52 and 55 to Theorem 57, what Freya actually does is first to construct a bridge using Theorem 9 as a one-premise rule, namely Theorem 56, and only then does he derive Theorem 57. Theorem 7, similarly, could have been used as a two-premise inference rule from axioms 28 and 31 as grounds directly to theorem 33 as conclusion, but Freya instead uses theorem 7 to first construct a bridge, theorem 32, and only then derives theorem 33 from 28 as ground. Although in outward appearance all inferential steps in the derivations of parts 2 and 3 of the 1879 logic have one and the same form, in fact, we have seen, important differences can be discerned, both between cases that involve the application of a rule in the form of a bridge and those that are instead instances of the rule of detachment, and between, on the one hand, cases that are presented as two one-premise inferences but can equally well be thought of as single two-premise inferences. And on the other, those that just are one-premise inferences. Putting these two ideas together reveals another possibility as well. We saw that there is a nice pattern connecting the rule of detachment to the rule of hypothetical syllogism that becomes apparent when we consider cases of hypothetical syllogism involving more conditions. In each case there is a bridge of the form A on condition that B. The ground for detachment is simply B. For the most basic case of hypothetical syllogism the ground is instead B on condition that C, and hence, whereas in inference modus ponens the conclusion is simply A, for hypothetical syllogism the condition C must be carried over to the conclusion, A on condition that C. But the ground can also be, say, B on condition that dash, in which case there are two conditions that need to be carried over into the conclusion. In this case, the conclusion is of the form A on condition that. It follows from these two features of inference in Freya's concept script taken together that there can be both cases of hypothetical syllogism that are like detachment, which is the way one might most naturally think of hypothetical syllogism, as involving two mere conditionals that are on equal footing, and cases that in fact involve a rule that is, something essentially general that can be applied in other cases in the bridge. Where A on condition that B is functioning as a rule in what superficially appears to be a straightforward case of hypothetical syllogism, there is an important asymmetry between the two premises. In such cases, one is applying a rule to a formula in order to transform it in some way, but that formula happens to have a condition and this condition must then be carried over to the conclusion. Later we will see cases of just such an asymmetry between the two premises in what superficially appears as a straightforward case of hypothetical syllogism. We have seen that Begriffsschrift formulae can often be regarded in various different ways, and need to be so regarded depending on what rule of inference one aims to apply. One consequence of this feature of Freya's notation is that something very like the phenomenon of pop-up objects that we observed in Euclidean diagrammatic reasoning and again in the proof of Euler's theorem can also occur in steps of reasoning in Freya. Here is a simple example. We start with Freya's axiom concerning the concavity, which expresses the thought that if some concept f has the property of being universally applicable then it can be inferred, for any object you like, that that object falls under the concept f. Now we consider a special case of this axiom with f on condition that g in place of f. Viewed in one way this formula is nothing more than a substitution instance of Freya's axiom. But we can also view it differently, as is made manifest when we reorder the conditions. This rule of syllogistic reasoning, that if some particular thing is g and all g is f, then that particular thing is also f, just pops up when one forms the relevant substitution instance of Freya's axiom. Suppose now that we apply the rule of contraposition. Up pops another rule of syllogistic reasoning, that if a particular object is g but not f, then it follows that some g is not f. Later we will see a case of an expression for a concept popping up in the course of a proof. One draws a certain inference and the resultant formula, suitably regarded, now contains a complex sign for a concept that is integral to the proof. We know that Freya's aim in his little monograph Begriffsschrift was to take the first step in his logicist program of showing that arithmetic is merely derived logic. Ultimately, what Freya wanted to show is that all the concepts of arithmetic can be defined by appeal only to logical concepts and that all laws of arithmetic can be derived on the basis of purely logical laws. What mattered to him, then, was that his proofs be maximally rigorous, that everything on which a proof depends be set out in advance so that it is manifest what it depends on, whether logic alone or also some concepts and/or truths of a special science. Because modes of inference must be expressed verbally, that is, in natural language rather than in Begriffsschrift, Freya employs only one mode of inference in the 1879 logic. All other modes of inference are instead expressed as judgments, either as axioms or as derived theorems. Thus, although one can read various judgments derived in Part 2 as rules governing 1 and 2 premise inferences, they, or more exactly, substitution instances of them, are invariably used as premises in inferences by detachment, that is, they are read as conditionals with only one condition that the ground shows to be satisfied. All other conditions are to be conceived as conditions on the conditioned judgment, that is, on the judgment that is true given the satisfaction of that one condition. And one consequence of this practice is that it can encourage, especially in those antecedently disposed, the idea that reasoning in Begriffsschrift is merely mechanical, that content, ideas, are irrelevant to it. This, however, is false. As Freya repeatedly emphasizes, his concept script is an expressive language just as the formula language of arithmetic is. It formulates content in a way enabling rigorous reasoning. So far we have seen only the barest indication of this. To see more we need to consider the derivations in Part 3 of Begriffsschrift, derivations that begin not with axioms but with definitions of concepts. 7.3 A second pass-through. Because Freya, for the purposes of logicism, allows himself only one rule of inference, every step in any chain of reasoning can appear, and does appear to the unpracticed eye, to be the same as any other. It involves a ground and a bridge, both of which either are or ultimately derive from either an axiom or a definition. Using our earlier convention, we can, for instance, chart the course of reasoning that ultimately yields, say, theorems 48 and 51 in Part 2, both of which are used in Part 3, and also chart the course of reasoning that ultimately yields theorem 133 in Part 3. The results are shown in figures 7.2 and 7.3, respectively, and seem essentially the same. The only difference, aside from the greater length of the derivation of theorem 133, seems to be that the Part 2 derivations begin with axioms, using them now as grounds and now as bridges, and the Part 3 derivation begins with definitions as grounds. In the Part 3 derivation, as in Part 2 derivations, various theorems appear now as grounds and now as bridges. In particular, although Part 2 axioms and theorems are mostly used as bridges in Part 3, there are also steps in which they appear as grounds. As inspection of figure 7.3 reveals, in Freya's derivation of theorem 133, theorems 36, 55, 58, 60, and 63 all occur as grounds. Nevertheless, as we will eventually see, there are crucially important differences to be discerned between any Part 2 derivation and the derivation of theorem 133 in Part 3. As Freya himself says, the proof of theorem 133 is from the definitions of the concepts of following in a series and of many oneness by means of my primitive laws. It is, we will see, Freya's definitions that provide the grounds of the proof of theorem 133, axioms and theorems from Part 2 function in that proof solely as inference licenses, as rules governing the passage from one judgment to another, beginning with the definitions. Once we have proved them, they can be treated in Part 3, where our concern is reasoning on the basis of definitions, as rules of inference of the sort one finds in a natural deduction system. Figure 7.2 The course of the derivations of theorems 48 and 51 in Part 2 of Begriffsschrift. Figure 7.3 The course of the derivation of theorem 133 in Part 3 of Begriffsschrift. In Freya's system, a definition of a concept introduces a simple sign with the stipulation, marked by the double judgment stroke, that that simple sign is to have the same meaning, Bedeutung, as the complex of signs in the definitions. Because the signs in the definitions are already understood, and because the sense of the whole complex sign is a function of the senses of the parts, the sense of the definitions is displayed in the complex of signs that is the definitions. The definiens lays out the inferentially articulated content, the sense, of the relevant concept. Consider, for example, Freya's definition of being hereditary in a sequence. On the left is the definiens, a collection of primitive signs of the language that displays what it is for a property f to be hereditary in the f sequence. On the right is a newly introduced simple sign, although this sign visually has parts, logically it is a simple two-place predicate of the form theta designating the property of being hereditary. Being hereditary in a sequence is thus a higher-level property of lower-level properties and relations. Being a positive whole number, for example, is hereditary in the successor sequence. It follows from being a successor of a positive whole number that that successor is a positive whole number. This is just what the definiens expresses using the concavity and conditional stroke, given that some object D is f and that A is the result of an application of f to D, that is, that f, it can be inferred that A is f, or alternatively, that it can be inferred from the fact that D is f that if f then A is f. Thus, if one knows of some concept that it is hereditary in some particular sequence, then one can infer of any object appropriately related to an object falling under the concept that it too falls under that concept. To apply the concept hereditary in a given sequence to some concept is in this way to issue an inference license regarding that latter concept, what may be inferred given that some object falls under the lower level concept. Point 18. We saw already in section 6.3, that to trace or track truth conditions, what is the case if something is true, is not thereby to trace or track inferential consequences, what follows if something is true. The two notions are different and need to be distinguished. The distinction between them is furthermore crucial to an adequate understanding of what a definition such as that of being hereditary in a sequence expresses in Begriffsschrift, and in particular, the role of the concavity in such a definition as it contrasts with the role of a universal quantifier in a definition in standard mathematical logic. Suppose we write the definiens of Freya's definition in standard notation, namely, thus. This formula states something that is the case if, and only if, f is hereditary in the f sequence, namely, that all objects y that are the result of an application of f to any object that is f also have the property f. The definition so understood sets out necessary and sufficient conditions for something having the property of being hereditary in some sequence. It sets out what is true about objects if and only if some property is hereditary. It does not express an inference license, a rule according to which to reason, but instead a claim, something that is the case, something from which to reason. Consider now a different case, that of being a prime number. Here again we can think of the content of this concept, what it is to be prime, in either of two ways, either in terms of marks, necessary and sufficient conditions, or in terms of the notion of an inference license, what one may infer given that some condition is satisfied. According to the first way of thinking about the content of the concept prime, to say that a number is prime is to say that no other number divides it without remainder. It is, in other words, to make a claim about numbers not equal to our number, all of them, that none divides our number without remainder. The alternative is to think of the concept prime as containing an inference license to the effect that if one is provided another number then it can be inferred that that number does not divide the given number without remainder. To ascribe the property prime to some number is not, on this second, inferential way of thinking, to say something about all numbers but instead to issue an inference license, one that can actually be employed only if some number is given that satisfies the condition in that license. To know, on this way of thinking, that some number is prime is to know that certain inferences involving that number are good. If the condition on the inference is met, then the inference may be drawn. And now we can see as well why a judgment such as that there is no largest prime number need not be taken to show that there are mathematical objects such as numbers. Read quantification ally, that judgment does commit one to there being objects that are prime numbers and indeed infinitely many of them. But if we follow Freya, we will think of that claim as instead licensing an inference, as an expression of the rule that if something is a prime number then it can be inferred that there is another larger than it. As we can also think of it, the judgment is about the concept prime, and ascribes a certain higher level property to that concept. Objects do not come into it at all. Point 19. We have seen that, as Freya defines it, the concept hereditary in a sequence contains, as its content, an inference license, that such and such can be inferred if some condition is met. Point 20. Freya's definition of following in a sequence is essentially similar, though more complex. This latter definition is also, Freya tells us, a paradigm of what he thinks of as a fruitful definition, one that enables a significant proof that extends our knowledge. The definition is this. The question is how to read it. The basic idea of following in a sequence is that one can get to the value y from the value x by repeated applications of the function f. There is, however, no assumption that the function is single-valued, or that it forms a linear chain, as, for example, the +2 sequence does. The chain could branch at various points, that is, have more than one result for some value as argument, and different branches could also merge. The chain, or part of it, could also close in on itself to form a ring. All that is required for y to follow x in the f sequence is that from x by repeated applications of the procedure f1 eventually gets y as value. The task of the definition is to spell out this intuitive idea in a form that is usable in inference. And here again the definition does not merely provide marks, what is the case if the defined concept applies, any more than the earlier definition of being hereditary in a sequence does. It displays not what is the case if the concept applies but instead what follows if it applies. To ascribe this relation of following in a sequence to some pair of objects is to issue an inference license, what can be inferred provided that some condition is satisfied, as Freya's own formulation of the definition in words makes explicit. If from the two propositions, that every result of an application of the procedure f to x has the property f, and that the property f is hereditary in the f sequence, it can be inferred, whatever f may be, that y has the property f, then I say, y follows x in the f sequence or x precedes y in the f sequence. Here again, the definiens contains an inference license, something to the effect that something can be inferred given that appropriate conditions are fulfilled. If two objects m and n are such that n follows m in some f sequence, then if one knows of some heritable property f that it belongs to any result of an application of f to m, one may infer that n is f. Freya's third definition, of belonging to a sequence, is different. Here the definiens does not contain an inference license but is merely truth functional, as is marked by the fact that there are no concavities in the definiens. To say that z belongs to the f sequence beginning with x is merely to say that z either follows x in the f sequence or is identical to x21. The definiens of this definition does not contain an inference license but only states what is the case here, a disjunction, either this or that if the defined concept applies. One might well wonder why Freya would bother to define such a concept. Freya's fourth definition, like the first two, contains an inference license, what may be inferred, given the satisfaction of certain conditions, if, and only if, a function is single-valued. Freya renders it in words thus, if it can be inferred from the circumstance that E is a result of an application of the procedure f to D, whatever D may be, that every result of an application of the procedure f to D is identical to E, then I say, f is a many-one procedure. To say, on this account, that a function f is mignon is not to say something about the objects it relates one to another but instead to say something about the function, that the function has a certain higher level property and hence that certain inferences regarding it are valid. A definition is not a judgment but a stipulation. It does not say, the right side of the equation has the same content as the left side, but, they are to have the same content. And because definitions are stipulations rather than judgments, rules of inference do not apply to them. One needs to make the identity judgment that corresponds to the stipulation. And this, though not a step of inference, is obviously correct. Once one has stipulated that some newly introduced sign is to have the same meaning as some collection of signs that are already in the language, then it is obviously and trivially true that they do have the same meaning, that the relevant identity is true. The reasoning begins with those identity judgments, and the first step is always to transform such identity judgments into conditionals, either with the definiens as the condition or with the definiendum as the condition. Although the derivation of Theorem 133 in Part 3 of Begriffsschrift is from definitions, more precisely, from the identity judgments that are trivially true given the definitions, while the derivations of theorems in Part 2 are from axioms, once we have formed conditionals from those identity judgments, all subsequent steps of both derivations can appear to be essentially similar. Superficially regarded, they are all instances of Freya's one rule of inference. Save for the derivation of Theorem 102 from Theorems 92 and 96 as grounds, with Theorem 101 serving as the bridge. Every step in every derivation, whether in Part 2 or in Part 3, involves a ground and a bridge. In Part 2, all bridges and grounds are, of course, either axioms or theorems derived from axioms. In Part 3, theorems from Part 2 can serve either as bridges or as grounds, as can theorems derived in Part 3. Nevertheless, as already indicated, Freya's axioms and the theorems that are derived from them in Part 2 in fact play an essentially different role in Freya's derivations in Part 3 from his definitions and the theorems derived from them. There is a pattern, or general strategy, discernible in the derivations of Part 3 that is wholly absent from any Part 2 derivation, even very involved ones such as the derivations of Theorems 48 and 51. We need to learn to see this pattern. Think again of the demonstration of Euler's theorem on the basis of three identities regarding the exponential and two trigonometric functions that was rehearsed in section 6.5. That demonstration has three principal elements: the identities with which the reasoning begins, identities that give the functions x, sin x, and cos x also as various infinite sums, the successive preparatory rewritings of the identity involving x, with 9 for x, and the stage at which content from different formulae are combined into one formula by putting equals for equals to give Euler's famous theorem. Reasoning from identities in Begriffsschrift, we will see, involves three analogous elements: the definitions, or corresponding identities, with which the reasoning begins, the successive preparatory rewritings governed by various one-premise rules of inference, and a stage at which content from two different formulae is combined into one formula by means of some version of hypothetical syllogism. We begin with two definitions, which in Freya's notation take the form and, where what is to the left, the definiens, is a complex expression formed from primitive signs, and perhaps also previously defined signs, and what is on the right, the definiendum, is a simple sign newly introduced that is stipulated to have the same meaning as the definiens. Immediately we judge that the relevant identities are true. The first step in the preparation is then to transform both judgments of identity into conditionals, into, for instance, alpha on condition that and on condition that beta. That is, in one the definiens is made the condition and in the other it is the definiendum that is made the condition. Then we transform those two conditionals in various ways according to rewrite rules until they share content. By two independent chains of inferences, we derive, in other words, something like A on condition that, ultimately from the definition of A, and also something of the form on condition that beta, ultimately from the definition of beta, where asterisk is identical to star. Now because asterisk is identical to asterisk we can use hypothetical syllogism to join the defined signs alpha and beta in a single conditional judgment, as mediated by the content that is common to the two conditionals, alpha on condition that beta. This basic process is then repeated until all the signs occurring in the theorem that one aims to prove are appropriately joined. In a derivation from definitions according to the strategy just outlined, two essentially different sorts of moves need to be distinguished. The first sort of move, that made in the stage of preparation, is a one-premise inference, which we can think of as a linear inference because it functions merely to transform one formula, derived ultimately from the identity corresponding to a definition, into another formula. Rules governing such single-premise inferences are rewrite rules to the effect that if you have something of such and such a form then you may infer, rewrite it as, a formula that is thus and so. Such rules are analogous to rewrite rules in algebras such as that A equals AB plus AC. The second sort of move, that in which content ultimately from two definitions is combined by hypothetical syllogism, is a two-premise inference. Such inferences are joining inferences that combine content from two different formulae ultimately derived from two definitions. Much as in a demonstration in algebras such as that of Euler's theorem, we needed both the axioms and theorems of elementary algebra governing rewritings and the general rule that equals can be put for equals, which allowed us ultimately to join the exponential function ia to the trigonometric functions sine and cosine in a single identity. So in the proofs of concern to Freya we need both rewrite rules governing one-premise inferences that serve to transform individual formulae and rules governing two-premise inferences, which allow us to join content from two formulae, derived ultimately from definitions by rewrite rules, into one. Here is an example: the chain of linear inferences that affects various transformations on definition 76 preparatory to the join with formula 74, which is derived from definition 69 by a series of linear inferences, that yields theorem 81.22. The definition, again, is this. The first step is to convert this definition, more exactly the identity judgment that corresponds to it, into a conditional judgment with the outermost concavity removed, theorem 77. That is, we make the defined sign, the definiendum, a condition on the content that is the definiens of the original definition. Now we make various modifications to this formula in a series of linear inferences preparatory to our join. First, we switch around the three conditions, licensed by one of Freya's many reordering theorems, to derive theorem 78. Notice that in order to do this we had to regard theorem 77, derived from the definition, in a new way. In order to see that theorem 77 is a conditional formed from definition 76, we had to regard the lowest condition on it as the condition on the rest of the formula conceived as the conditioned content. But in order to see that we can reorder the conditions as we just did to get theorem 78, we needed to treat everything except f as a condition on f as the conditioned content. And, we have seen, this point applies generally to reasoning in Begriffsschrift. Conditions that are at one point in the reasoning regarded as parts of the conditioned judgment in a conditional are at a different stage in one's reasoning regarded instead as conditions on a conditioned judgment. Now we reorganize the content as licensed by Freya's second axiom to yield theorem 79. That is, we remove the lowest condition in theorem 78 and reattach it to both the condition and the conditioned content of the remainder suitably regarded. The preparation is complete. We assume a similar preparation for the second formula needed in the join, namely, theorem 74. It is easy to see that theorem 74 is derived by a series of linear inferences from the definition of being hereditary in a sequence. We merely make the definiendum a condition on the definiens, remove the concavities, and reorder the conditions. This gives us theorem 74. Notice now that the lowest condition in theorem 79 is identical save for the presence of the concavity in theorem 79 to the conditioned judgment in theorem 74, provided that we regard theorem 74 as having f as the sole condition on that conditioned content. But we know that we can insert a concavity in the relevant place in theorem 74, and hence, together, these two formulae yield, by hypothetical syllogism, theorem 81:23. In this formula the lowest condition, f, derives from theorem 74, ultimately from the definition of being hereditary in a sequence, and the rest of the formula derives from theorem 79, ultimately from the definition of following in a sequence. Notice further that theorem 81 differs from theorem 74 in only one small but crucially important as it will turn out respect, where theorem 74 has as a condition that f, that is, that y is a result of an application of the function f to x as argument. Theorem 81 has instead the weaker condition that y follows x in the f sequence. Theorem 81 shows that heritable properties are inherited not only by the results of applying the function f to things that have the property but by anything that follows, in Freya's technical sense, in the f sequence. We will eventually see that this fact, that heritable properties are heritable also under weakening, that is, not only if f but also if y only follows x in the f sequence, will turn out to be surprisingly important to any really adequate understanding of the proof of Theorem 133 overall. We have just seen that the general strategy of proof from definitions in Freya's concept script is to find a way based on definitions to make joins that combine defined and other signs in conditionals. And we have seen one small example of this general strategy. Now we need to see the strategy working in reverse, that is, how one might discover a proof of some theorem using the strategy. We need to begin, then, with something that seems intuitively to be true given what our signs mean. It seems, for example, obvious given what it means to follow in a sequence that if y follows x in the f sequence and z is the result of an application of f to y, that is, f, then z follows x in the f sequence. If you can get to y from x by repeated applications of f, and z is the result of an application of f to y, then obviously you can get to z from x by repeated applications of f. The task of the proof of this theorem is, in effect, to construct this formula, and the structure of the formula immediately gives us a strategy. We have to get our signs to be joined from somewhere, and the only place is the definitions. So the structure of this formula, in particular, the fact that it involves two occurrences of the defined sign for following in a sequence, once as the conditioned judgment and once as a condition, and also, as a condition, a formula, f, that occurs only in the definition of being hereditary, suggests that we will use the definition of following in a sequence twice, once for the conditioned judgment and once to get the defined sign as a condition, and will use the definition of being hereditary in a sequence once to get the condition that f. Because three definitions are involved, we will need at least two joins. Point 24. Given our general strategy of making preparatory linear inferences followed by joins using hypothetical syllogism, the construction of our theorem to be proved will obviously need the conditional that has the definiendum as the conditioned judgment that we can derive from the definition of following in a sequence. Call this theorem I. We need it because we need to get the defined sign for following in a sequence to the right of the main content stroke, and given our strategy, forming this conditional is the first step on the way to doing that. If now we can prove this, call it theorem 2. Then we can use hypothetical syllogism on theorems I and 2 to derive the desired theorem. For what we have in this formula just is the condition of theorem I, but on two conditions, namely, that y follows x and that z is the result of an application of f to y, which are precisely the conditions in the formula we are trying to prove. In order to derive theorem 2 we will obviously need both the definition of following in a sequence and that of being hereditary in a sequence. And because both defined signs occur as conditions in theorem 2, we will need in particular these formulae, which derive directly from the definitions of being hereditary in a sequence and following in a sequence, respectively. The structure of theorem 4 immediately suggests that we use axiom 2 to transform theorem 3 so that it has a condition identical to the conditioned judgment in theorem 4. That is, from theorem 3, with axiom 2 as the bridge or inference license, we can easily get this, theorem v. And now we can use hypothetical syllogism on theorems 4 and v, though we need to reletter in theorem v, putting y for x and z for y, to give theorem 6. Now we just need to reorder the conditions in theorem 6 to give theorem 2, and add a concavity, and that theorem can be joined with theorem I by a version of hypothetical syllogism to give the theorem we aimed to prove. From the definition of following in a sequence used twice and the definition of being hereditary in a sequence used once, we proved our little theorem in just two joins. The essentials of the proof are set out in figure 7.4. And all that was needed in order to discover this little proof was attention to the particular structure of the theorem we aimed to prove, together with our general strategy for proving theorems on the basis of definitions in Freya's concept script. There are a total of 14 joins in Freya's derivation of theorem 133, one of which joins 3 chains and the rest of which join 2. Figure 7.5, in which most of the linear inferences involved in the derivation of 133 are not shown, highlights the series of joins that take us from Freya's 4 definitions to Theorem 133. 10 of these joins are straightforward joins using some version of hypothetical syllogism, that is, they are licensed by one or other of theorems 5, 7, 9, 19, and 20. This can be seen in figure 7.3 by the fact that just before the join Freya uses one of these theorems to form a bridge out of one of the theorems in the join, a bridge that will take one from the other theorem in the join to the conclusion. Table 7.2 lists these 10 joins, both as Freya presents them in two-step inferences and as two-premise inferences by some version of hypothetical syllogism. Figure 7.4 an example of the general proof strategy when reasoning from definitions. The join of 92, 96, and 100 by Theorem 48 is essentially similar, different only in involving 3 rather than 2 premises, although Freya uses Theorem 48 to construct a bridge out of Theorem 100, one that takes one from Theorems 92 and 96 to Theorem 102. Theorem 48 can be used directly to license the inference from 92, 96, and 100 to Theorem 102. The 3 remaining joins are different. Although in these cases 2 chains are joined, they are not joined by any form of hypothetical syllogism. Consider first the join of 108 and 75 to give 109. That this join is different is indicated already by the fact that both in figure 7.3 of the derivation as given in the 1879 logic and in figure 7.5 of the 14 joins, just the same theorems appear in the inferential step. Here Freya is not, as he does in the cases just discussed, doing in 2 steps what might be done in 1. What is happening here is something different. Theorem 75, derived directly from the definition of being hereditary in a sequence, states that if the condition for being hereditary in a sequence is satisfied by some concept, then one may infer that the concept hereditary in a sequence applies to that concept. Theorem 108 shows that belonging to a sequence satisfies the condition for being hereditary. Hence it is inferred that belonging to a sequence is hereditary in that sequence. The inference is essentially linear, a matter of rewriting a formula that shows that belonging is hereditary, by showing that it satisfies the relevant condition, instead as one that explicitly says this, by using the defined sign for being hereditary, according to the rewrite rule derived from the definition of being hereditary. Of Theorem 133. Freya's 2-step joins. The corresponding 1-step inferences. 1. Derive 80 from 79 via 5, 80 is the bridge from 74 to 81. 179 and 74 yield 81 via 5 as 2-premise rule. 2. Derive 86 from 85 via 19, 86 is the bridge from 73 to 87. 285 and 73 yield 87 via 19 as 2-premise rule. 3. Derive 94 from 93 via 7, 94 is the bridge from 88 to 95. 393 and 88 yield 95 via 7 as 2-premise rule. 4. Derive 107 from 106 via 7, 107 is the bridge from 102 to 108. 4. 106 and 102 yield 108 via 7 as 2-premise rule. 5. Derive 113 from 112 via 7, 113 is the bridge from 104 to 114. 5. 112 and 104 yield 114 via 7 as 2-premise rule. 6. Derive 121 from 120 via 20, 121 is the bridge from 112 to 122. 6. 120 and 112 yield 122 via 20 as 2-premise rule. 7. Derive 123 from 122 via 19, 123 is the bridge from 110 to 124. 7. 122 and 110 yield 124 via 19 as 2-premise rule. 8. Derive 125 from 124 via 20, 125 is the bridge from 114 to 126. 8 124 and 114 yield 126 via 20 as 2 premise rule. 9 derive 130 from 129 via 9, 130 is the bridge from 75 to 131. 9 129 and 75 yield 131 via 9 as 2 premise rule. 10 derive 132 from 131 via 9, 132 is the bridge from 83 to 133. 1083 and 131 yield 133 via 9 as 2 premise rule. The move from theorem 109 to 110 is analogous. Freya derives from the definition of following in a sequence which, it may be recalled, includes the defined sign for being hereditary. What may be inferred given that some concept has the property of being hereditary in a sequence. This is theorem 78. Because theorem 109 says that belonging is hereditary, theorem 78 licenses the move to 110. The move is linear, a matter of rewriting 109 as 110 according to the rewrite rule that is derived from the definition of following in a sequence. The last join is that from 111 as ground, with 128 as bridge to 129. Here Freya uses theorem 51 to construct the bridge out of 127. But it is easy to see that theorem 51, if construed as a two-premise rule, can take us directly from theorems 111 and 127 to 129. As in our earlier cases, Freya constructs a bridge in order to do in two steps according to his one rule something that can also be done in one multi-premise inferential step. Nevertheless, as we will see in more detail later, this is not a case of hypothetical syllogism because although content is joined, nothing is lost in the process. All the original conditions in 111 and 127 reappear in theorem 129, though differently combined. We have just seen that of the total of 14 joins in the derivation of theorem 133, 11 can be accounted for by appeal to the general strategy outlined above of modifying definitions in various ways until two defined, or in some cases other, signs can be joined using some version of hypothetical syllogism. The remaining three joins, resulting in theorems 109, 110, and 129, cannot be so accounted for. Why does Freya proceed as he does in these cases? Of course the steps are valid, and they do get Freya where he wants to go, but relative to our general proof strategy, they seem quite mysterious and unmotivated. And insofar as they do, they suggest that there is something we have not yet grasped about this proof. Before we can see what it is, we need, however, to resolve another issue, that of the part 2 theorems that appear in the derivation of theorem 133 as grounds rather than as bridges. We need to see that had Freya derived the appropriate theorems in part 2, all axioms and theorems from part 2 would function in part 3 as bridges, that is, as inference licenses, never as grounds. And this is just as we should expect. Those axioms and theorems of logic ought to be functioning as principles according to which to reason rather than as premises from which to reason. At least they ought to do so when one is reasoning about some particular subject matter such as the general theory of sequences, as is the case in part 3 of Begriffsschrift. We have seen that in Freya's derivation of theorem 133 on the basis of his four definitions, theorems from part 2 generally function as inference licenses governing the linear and joining inferences that are involved in the general proof strategy we have identified. They function either as rewrite rules, much as the axioms and derived theorems of early modern algebra do, or as some version of hypothetical syllogism, to join content from two different formulae. But, again, in some parts of the derivation of theorem 133 theorems from part 2 appear not as bridges, that is as rules governing rewritings or joins, but instead as grounds, and hence, roughly speaking, as that to which a rule applies. As can be seen in figure 7.3, theorems 36, 55, 58, 60, and 63 all appear in the proof of theorem 133 as grounds. What needs to be shown is that in all these cases Freya could have derived theorems in part 2 that would provide the needed rewrite rules. Point 25. Consider first theorem 55, which is a simple theorem about equivalence. D is equivalent to C on condition that C is equivalent to D. This theorem serves as the ground in the inference from theorem 103 to theorem 104. The fact that 103 is derived in turn from 100 using theorem 19 as bridge indicates that our interest should be focused on the move from 100 to 104, that is, from this to this. Clearly, the only difference between these two formulae is that whereas theorem 100 has z equivalent to x on two conditions, theorem 104 has x equivalent to z on those same two conditions. Theorem 55 cannot, then, be used directly to license the move from 100 to 104. What we need instead is a theorem that says that if you have an equivalence on two conditions, then you may infer that equivalence with the terms reversed on those same two conditions. Because we know from theorem 5, read as a rule governing a one-premise inference, that if you have a conditional you can add any condition you like to both arms of that conditional, applying theorem 5 to theorem 55 and then again to the result yields just what is wanted. Had Freya derived this theorem in part 2, it could have served as the bridge in a linear inference from theorem 100 to theorem 104. Axiom 58 serves as ground in three different inferential steps: in the derivation of 72 from 70, in the derivation of 118 from 116, and in the derivation of 120 from 118. The effect of this step in the first and last cases is to remove a concavity from the main content stroke when it is on two conditions. In the derivation of 118 from 116 the effect is to remove a concavity from the main content stroke when it is on one condition. Here again, then, it would have been easy for Freya to derive on the basis of his axioms the needed rule. Given axiom 58 and theorem 5, treated as a one-premise rule, gives this, which provides the rule for an inference from 116 to 118. Applying the rule in theorem 5 again provides the rule for the cases in which there are two conditions. Freya uses theorem 60 in reordering the conditions in a conditional that has a concavity on its main content stroke and is itself a condition, that is, in the move from theorem 89 to theorem 93. Theorem 60 is this. To derive the rule that we need, we first insert a concavity into the main content stroke between the two leftmost conditional strokes, the scope of which is f on condition that dash, and then use theorem 9 as a one-premise rule to derive our rule. And just the same holds in the last two cases. Suitably modified theorem 63 provides a rule governing the inference from 89 to 91, and theorem 36 similarly provides the rule licensing the inference from 81 or H4F and the conditions suitably ordered, to 83. Had Freya derived these theorems in part 2, it would have been evident that part 2 theorems serve in part 3 only as rules of inference, that is, as bridges, never as grounds. Although, superficially regarded, every inferential step in a Begriffsschrift derivation of some theorem from definitions is the same as any other, and indeed the same as any inferential step in a derivation from axioms, closer inspection has revealed a range of very distinctive features for the case in which the derivation takes its starting point from definitions. First, although in a derivation of a theorem from axioms the axioms serve now as grounds and now as bridges, in a derivation of a theorem from definitions, the axioms and theorems derived from them serve as bridges. That is, they function as inference licenses, rules that allow one to move from the identity judgment corresponding to a definition, in a series of steps, ultimately to the theorem that is wanted. And as we have seen, there are two very different sorts of rules: rules governing linear inferences that merely change a formula in some way, and rules governing joining inferences that combine, by some form of hypothetical syllogism, content from two different judgments. The task of Freya's proof of theorem 133 is to find the sequence of joins that will eventually yield that theorem. And as we have furthermore seen, the structure of a theorem to be proved, in particular the relative locations of the various signs in that theorem, can provide important clues for finding the sequence of joins that is needed. In some cases that is all one needs to consider. In our derivation of Theorem 95, for example, the structure of that theorem, the fact that the defined sign for following in a sequence occurs once as a condition and also as the conditioned judgment, with the only other condition being f, told us everything we needed to know in order to derive that theorem from the relevant definitions. But that general strategy is not sufficient for finding the proof of Theorem 133. Although much of the proof is explained by appeal to the notion of a join that, by some form of hypothetical syllogism, combines content from two different judgments, we have already seen that some steps are not of this form and depend in a quite distinctive way on the definitions. We need to understand what is going on at these points in the derivation. 7.4 Seeing how it really goes. 26. The theorem proven in Begriffsschrift Part 3 is Theorem 133. Which says that if f is a single-valued function and y and m both follow x in the f sequence, then either m follows y or y belongs to the f sequence beginning with m. Given what it means to follow in a sequence and to belong to a sequence, this seems intuitively to be true on the condition that the function f is single-valued. The problem is to prove this theorem, and our general strategy suggests a task of construction. Given the definitions and the rules governing linear and joining inferences, the task is to find a series of joins that will connect together in the required ways all the defined signs that occur in Theorem 133. The general strategy of finding the joins that will relate in the required ways the various defined signs appearing in Theorem 133 is clearly in play in Freya's proof of Theorem 133, at least some parts of the derivation are fully explained in terms of this strategy. But, we have seen, not all are, suggesting that there is also the very particular strategy of this proof, a strategy that seems to depend in some way on the particular concepts, such as being hereditary and following in a sequence, with which it begins. What we are after are the key ideas of this proof in particular, the ideas that enabled its discovery in the first place. We have seen already that of the 14 joins in Freya's proof, 10 of them are or at least appear to be straightforward applications of some form of hypothetical syllogism, and one more, namely, that using 48 to combine content from theorems 92, 96, and 100 to yield 102, although more complex, also conforms to essentially the same pattern. The remaining 3 joins are different. In the inference from Theorem 108 to Theorem 109, we have seen, one makes the transition from a theorem that shows that belonging to a sequence is hereditary in that sequence to one that says that belonging to a sequence is hereditary in that sequence, using the defined sign for being hereditary to predicate of belonging to a sequence that it is hereditary in that sequence. The inference does not have the form of a hypothetical syllogism but is instead by Freya's one rule with Theorem 75, derived from the definition of being hereditary, as the conditional or bridge. The move from 109 to 110 is again according to Freya's one rule, given that belonging to a sequence is hereditary in that sequence it follows, with 78 as the bridge that belonging to a sequence has a certain other property as well. Having shown that belonging to a sequence is itself hereditary in that sequence, we infer, based on a judgment derived from the definition of following in a sequence, that belonging to a sequence has some other property as well. That is what the 2 joins give us. But there is a puzzle here insofar as it is not at all clear why the proof proceeds as it does at this point, what the guiding idea is. How did Freya come by the thought to use the property of being hereditary in this way? The question is all the more pressing once we realize that although superficially a sequence of 2 standard joins, the inferences from 129 and 75 to 131, and then from 131 and 83 to 133, are conceptually more like the sequence of 2 joins just outlined. As in the move from 108 to 109, Freya first shows that a certain property is hereditary in the relevant sequence, and then he shows, using a rule derived from the definition of following in a sequence, that something follows given that that property is hereditary, namely, Theorem 133. The move appears to be adjoined by hypothetical syllogism, and hence just like the other standard joins involved in the general strategy, only because the property that is hereditary is on a condition that must be carried along at each step. Thus at two key points in the proof Freya uses essentially the same strategy: prove that some property is hereditary, then infer something from that fact using a conditional derived from the definition of following in a sequence. We need to understand this strategy. And there is a further puzzle as well. Freya suggests shortly after the publication of Begriffsschrift in 1879 that I now regard it as superfluous to introduce the combination of signs. According to Freya, Theorem 133 is proved from only two of his four defined concepts, namely, following in a sequence and being single-valued. Given that belonging is merely disjunctive, it is not surprising that the definition of this concept plays no essential role in the proof. Did Freya regard the defined sign as superfluous in this case as well? We have no evidence either that he did or that he did not. The concept hereditary in a sequence, by contrast, is clearly important to the derivation, in particular, at the 2 points just noted, though Freya says that the defined sign for that concept is superfluous. The concept belonging to a sequence does not seem to be important in the same way insofar as it does not play any such role in the derivation overall, and yet Freya defines it even though it is a very simple disjunctive property. Clearly there are things at work in the proof that we do not yet understand. The final join only adds to the puzzle. Using Theorem 51, which it is easy to see is functioning in this context as a rule licensing a two-premise inference, Freya joins Theorems 127 and 111 to give Theorem 129. The form of the inference, governed by Theorem 51, is this. If A is true on condition that C and D, and A is true on condition that B, then it can be inferred that A is true on condition, first, that B or C, and also that D. As already noted, this is clearly not any form of hypothetical syllogism because although content is clearly joined, nothing is lost in the inference. All the conditions that occur in the two premises reappear also in the conclusion, though differently arranged. This is also clearly a valid rule of inference, as Freya shows in his derivation of it in Part 2. The problem is to understand how Freya got the idea of making just this move at this point, why it is not merely effective but an intelligent move to make here. Obviously there is a sense in which it is a good move not only in itself but also for the purposes of the proof insofar as it enables Freya to get where he wants to go. And once one has seen how the derivation goes at this point, one will be able to reproduce it. Nevertheless, it seems unmotivated, something Freya just pulled out of the air. And it is of course possible that Freya himself merely stumbled upon the move, and seeing that it worked, used it. But if so, then the proof as a whole is essentially arbitrary at least at some points, and for that reason not fully satisfying as a piece of reasoning. The steps of the proof, each and every one of them, need to be motivated, otherwise, although we have a proof that shows that Theorem 133 is true, we cannot adequately understand why it is true. We need to determine whether there is something that we are missing, some pattern to the proof that will enable all the steps to fall into place. Consider again what we are trying to prove, Theorem 133. Visual inspection of this formula already suggests that our general proof strategy will not be sufficient insofar as we do not have only conditionals here but also a negation stroke, the effect of which is to generate a disjunction. Now we do have a disjunction in the definition of belonging to a sequence. Y belongs to the F sequence beginning with X if either Y follows X or Y is identical to X, but it should be clear that that is not going to be of any help here given that the disjunct in 133 are belonging to a sequence and following in a sequence. The general proof strategy will not give us what we want. We need another. Theorem 133 says that if Y and M follow X in the F sequence, then either M follows Y or Y belongs to the F sequence beginning with M. That is, given the definition of belonging to a sequence, this formula says that if Y and M follow X in the F sequence, then either M follows Y or Y follows M, or M and Y are identical. It will be helpful to have a name for this disjunctive relation. We will say that x and y are connected in the f sequence just if either x follows y in the f sequence or y follows x in the f sequence, or x and y are identical. What we are to show, then, is that if y and m follow x in the f sequence, then y and m are connected. Notice, now, that if a function f is single-valued, and y and m are the result of an application of f to x, that is, f and f, then trivially y and m are connected, because if f is single-valued and f, then by the definition of being single-valued, y and m must be identical. And if they are identical, then obviously they are connected. That is, we start with the identity corresponding to the definition of being single-valued, and derive what in Part 3 is Theorem 120. This formula suggests the beginnings of a strategy involving two related tasks. We need to show that something like this holds not only where x and a are the result of applying f to y, that is, f and f, but also where x and a only follow y in the f sequence, and we need to weaken the consequent property, show that where x and a follow y in the f sequence, not that they are identical but that they are connected in our technical sense. Given that connectedness is a disjunctive property, one of whose disjunct is an equivalence, the latter task should be relatively straightforward. The former seems more daunting. But we do have a precedent for it, given that it is easy to derive from Theorem 74. Which follows directly from the definition of being hereditary, Theorem 81. Theorem 81, we saw, is the result of a standard joined by hypothetical syllogism of Theorem 74 with 79, which derives from the definition of following in a sequence. Furthermore, as already noted, Theorem 81 differs from Theorem 74 only in the topmost condition, the condition that y is the result of an application of f to x, that is, f, has been weakened, replaced by the condition that y only follows x in the f sequence. But that is just what we need to do for the two conditions f and f in Theorem 120, weaken them to the conditions that a and x only follow y in the f sequence. Perhaps, then, the definition of following in a sequence can also be used in these cases as well. Given the definition of belonging to a sequence, it is obvious that if x and y are identical, then y belongs to the f sequence beginning with x. So we can, by hypothetical syllogism, replace the equivalence in 120 with belonging, Theorem 122. And again, because a disjunctive property is weaker than the property that is one of the disjunct, adding the negated condition in order to form our disjunctive property connectedness should not be much of a problem. The real problem, again, is to find a way to replace the conditions f and f with weaker conditions that involve only the notion of following in a sequence. We have already seen that if a property is hereditary, then we can show, using the definition of following, that it is hereditary under weakening. Our thought, then, is to use the property of being hereditary together with the definition of following in a sequence to weaken our two conditions as needed in Theorem 133. We know already that it is easy to show that following in a sequence is hereditary in that sequence using the general proof strategy of making joins by hypothetical syllogism, that is, Theorem 96. And we saw in the derivation of 81 how to use the definition of following in a sequence to replace the condition f, which appears in a condition derived from being hereditary, with the weaker condition of following. Theorem 84 is just a reordering of Theorem 81. What this formula says is that if some property f is hereditary in the f sequence, then that property is heritable even if y only follows x. Because we have shown that following in a sequence is hereditary in the f sequence, it follows that following in a sequence is heritable even where y only follows x in the f sequence. That is, we can use 84 to license the move from 96 to 98:27. As this formula shows, following in a sequence has the property of being transitive. But as we can also think of it, we have, in this formula, weakened the condition, in Theorem 96, that f, to the condition, in Theorem 98, that z only follows y in the f sequence. Now this theorem in fact has no role to play in the proof of 133, As far as that latter proof is concerned, Theorem 98 is a dead end. Nevertheless, Freya includes it, and it gives us insight into a possible strategy for the proof of Theorem 133 insofar as it shows using the property of being hereditary in a sequence and, by way of the definition of following in a sequence, what follows from something having that property one way to weaken a condition from something's being an application of F to its merely following in the F sequence. We have a strategy to try. To use the suggested strategy, one needs first to show of some property that it is hereditary, as we did for following in a sequence. An obvious thing to try to show is that belonging to a sequence is also hereditary in that sequence. Freya shows this in Theorem 108, which, given that he has already shown that following is hereditary and what it means to belong to a sequence, is relatively straightforward to prove. Now at this point Freya could have used the strategy above to show that belonging is heritable even where Y only follows X. This, however, would not advance the proof. What we need to do is to alter the conditions in Theorem 122, not the conditions in Theorem 108. But we will still use the fact that belonging is hereditary. Given that belonging is hereditary in the F sequence, and given this theorem, Theorem 78, which follows directly from the definition of following in a sequence, we can derive Theorem 110. In this theorem, belonging to a sequence is the property F in Theorem 78. Notice now that it gives us another way of replacing the condition F with the weaker condition that Y follows X, namely, when it is a condition on something's belonging to a sequence. That is just what Theorem 110, appropriately regarded, says. Theorem 110 together with Theorem 122 yields, by hypothetical syllogism, Theorem 124. We have managed to replace one of our two conditions of the form F with the weaker notion of following. The problem of the remainder of the proof is to weaken the other condition. And here Freya is especially brilliant. We know what the strategy is: show that some property is hereditary, then somehow use the definition of following in a sequence to weaken the condition that F to that of following. But what property should we do this for? We have already shown that both following in a sequence and belonging to a sequence are hereditary. What further properties are there? The answer is at once simple and elegant: the property of connectedness. If we are going to prove that connectedness is hereditary, we need it in Theorem 124 in place of belonging in the conditioned judgment to which the main content stroke takes 1. This is easily done. First, we introduce the notion of connectedness in Theorem 114. This theorem follows from a standard join of two judgments, both of which derive from the definition of belonging to a sequence. Clearly it is true, if X belongs to the F sequence beginning with Z, then X and Z are connected. Now we can join 124 and 114 by hypothetical syllogism to give Theorem 126. Notice that Theorem 126 is just what we want to prove, except for the fact that we have F. What we want is only that X follows Y in the F sequence. Our strategy for effecting such a change is, again, that of showing first that some property is hereditary, then on that basis, using the definition of following in a sequence, to weaken the condition involving an application of F to one involving only the notion of following. Because this is our strategy, we need to focus not directly on F in Theorem 126 but instead on the condition that M follows Y in the F sequence. If we can somehow transform that condition into the condition that M and Y are connected, that will show that being connected is hereditary in the F sequence. Now obviously we cannot do this directly, simply by adding a condition to that condition. But we can do it indirectly using Theorem 51, if A on condition that and A on condition that B, then A on condition that and D. That is, Freya constructs inferentially the second occurrence of connectedness that is needed to show that connectedness is hereditary. The needed occurrence of the concept of connectedness just pops up when the inference is made. The move, which we will soon walk through step by step, is a delight. We already have the premise that A on condition that dash, namely, Theorem 127 derived from 126 by reordering. Where A is the content that M and X are connected on condition that F, C is the condition that M follows Y in the F sequence, and D is the condition that F is single-valued. What we need to show is that that same content that we put for A, namely, that M and X are connected on condition that F, is also true on condition that Y belongs to the sequence beginning with M. This is trivial to show. We already know that belonging to a sequence is hereditary in that sequence. This is Theorem 108. And we know that we can always add a condition to a judgment, any condition we like, and reorder. So given 108, we know that Theorem 111 is true. From this judgment, and Theorem 127, we derive, by Theorem 51, what is wanted, a theorem showing that connectedness is hereditary, on the condition that F is single-valued, Theorem 129. We further know that if a property is hereditary in the F sequence, then it can be inferred that that property is heritable even where it is not the case that F but only that Y follows X, that is, Theorem 84. But this is not quite what is wanted. There is one more wrinkle. It is a simple fact of logic that a disjunction is logically weaker than one disjunct taken alone. Hence it follows from Theorem 84 that where the property we have shown to be hereditary is disjunctive, as connectedness is, then the following is also true, Theorem 83:28. This is, of course, a rather peculiar case. One would not think of it unless one was working with our strategy of using the fact that some property is hereditary to infer something where the condition F has been weakened to Y's merely following X. But having that general strategy in mind, we know that we will need something like 84 above, and it is not hard to see that what we need in particular is Theorem 83. Having shown that connectedness is hereditary in the F sequence, and using the rule in 83 that shows that if a disjunctive property is hereditary then it is heritable also given weakening to following and only one disjunct, we infer Theorem 133. Figure 7.6 sets out the key moves in the proof. And now it is manifest that although officially 129 and 83 are joined by hypothetical syllogism, that is, the inference looks to be an instance of our general strategy of proving things by hypothetical syllogism, conceptually it is instead a case of Freya's one rule of inference, only with B on a condition that needs to be carried over into the conclusion. Conceptually, what is going on is that connectedness is hereditary, hence by 83 connectedness is heritable on condition that one of its disjunct applies even in the weaker case in which Y only follows X. It is also now clear why the concept of belonging is defined and why the property of connectedness is not. Connectedness is a crucial property in any fully adequate understanding of the proof of Theorem 133, but it is also critical to the proof strategy that connectedness is a disjunctive property, and hence constructible inferentially. It is not in the same way critical to the proof strategy that belonging is disjunctive, and because it is not, it makes things a little easier, though it is hardly critical, to introduce a defined sign for the concept of belonging. The definition of being a single-valued function gave us our template for the proof. Having that definition is, then, not merely useful or convenient, it is suggestive of how to approach the problem of finding a path from Freya's definitions to the desired theorem. The definition of following in a sequence gave us various conditionals that are needed at crucial points to show something that is entailed by some properties being hereditary in a sequence. Clearly that definition is central to the proof. On the other hand, we did not really need a simple sign for being hereditary any more than we needed one for belonging to a sequence. In the end, then, the definitions that are crucial are, just as Freya says, the definitions of following in a sequence and of being a single-valued function. It is a marvelous and elegant little proof. Figure 7.6 The key moves in Freya's proof strategy for Theorem 133. 7.5 Conclusion. I have suggested, following Jourdain, that a good notation of mathematics is one that puts the reasoning before one's eyes, that displays it. One can do mathematics, and in particular the sort of mathematics that involves deductive inference from concepts, without such a notation, but in that case one's reasoning is and must be a private mental act rather than a public, observable one. We also saw in our discussion in section 6.5 of the Leibnizian notion of a universal language, a language that is at once a characteristica and a calculus ratiocinator, what is required of such a notation. Following the model of the formula language of arithmetic and algebra, we determined, first, and most obviously, that the notation must display the contents of concepts in a mathematically tractable way, in a way enabling rigorous reasoning in the system of signs. Because the mathematical practice of concern to Freya involves deductive reasoning from defined concepts, as contrasted both with the sort of algebraic calculating characteristic of mathematics after Descartes and through the 18th century, and with the diagrammatic reasoning of the ancient Greeks, the concepts of concern to Freya must be understood to be inferentially articulated, and their contents must be displayed in a way that is amenable to moves that are licensed by recognized rules of logical inference. Not only must primitive signs be introduced to enable the display of logical relations, axioms expressing basic truths about those primitive notions need to be formulated and theorems derived from those axioms. Those axioms and theorems can then function in the system as basic and derived rules of inference. Because the definitions are formulated using those same signs, the rules of inference can then be applied to them just as the axioms and theorems of basic algebra are applied in reasoning from identities in algebra, for instance, in the demonstration of Euler's theorem. That, we saw, is what is needed in a Leibnizian universal language, and that, we have just seen, is what Freya's language Begriffsschrift provides. Point 29 Begriffsschrift is a language within which to reason deductively from defined concepts. A proof such as that of Theorem 133 in Part 3 of Freya's 1879 logic, written in Freya's Begriffsschrift, displays the reasoning. It does not merely report it but instead puts it before our eyes in a way enabling us to see how it goes, or at least it does for one who has achieved adequate mastery of the system of signs. We saw in section 6.4 that both Rav and Thurston object to formalized proofs written in standard systems of logical notation because they involve the merely mechanical application of rules rather than ideas. And Poincaré, as briefly discussed in section 5.4, suggests something similar. He holds that when you break a mathematical proof all the way down to strictly logical inferences, you lose sight of the mathematics, much as one focused on the cells of which the body of an animal is made up loses sight of the animal. We are now in a position to begin to understand why that is. In thinking about reasoning in Begriffsschrift, we at first focused on the individual steps in Freya's derivations in the 1879 logic, all of which are essentially the same insofar as they conform to Freya's one rule of inference. But then we began to discern a pattern in the proof of Theorem 133 that was absent from the derivations of Part 2, even from the most complex of those derivations. There is, we saw, a general proof strategy at work in reasoning from definitions, one that bears a strong structural analogy to the strategy discernible in our little demonstration of Euler's theorem. And although it could not be shown here, it is not hard to verify that the course of much of Freya's derivation of Theorem 133 is motivated and explained by just this strategy. But not all of it can be so motivated and explained. Indeed, some steps that seemed at first sight to conform to the pattern of the general strategy, in fact, once we see how the proof really goes, ought to be regarded differently, as cases of the strategy that is peculiar to this proof in particular. To find that latter strategy, we had to attend to the ideas of the proof, and in particular, to the concepts of connectedness, being a single-valued function, and following in a sequence. Only by working at the level of ideas, in Poincaré's imagery, at the level of the living, breathing animal, could we come to see what was really going on. And, surprisingly enough, this is true even in the case of pure logic with which Freya is concerned in Begriffsschrift. Point 30. Furthermore, as should by now be evident, it takes real work and devoted practice with the language to come to be in a position readily to see in the system of signs the ideas that are at play in the proof. The point is, in other domains, a very familiar one. Whether one is learning a new language such as German or Greek, a new game such as chess, or a new area of mathematics such as Fourier analysis, one needs to go through a process of training and must practice, and at a given point will be more or less capable. Much the same, we need to recognize, is true in the case of learning to reason in Freya's Begriffsschrift. Being able to see that each step is valid is not sufficient. One has full mastery of the language only when one is able to work at the level of the ideas of the proof as they are displayed in the notation, only then can one be said fully to understand the proof and the notation it is written in. And only then can one see for oneself how the proof actually goes, and so share in the pleasure of its discovery. We have learned the language, or at least enough to understand what it is capable of for the purposes of reasoning from concepts. Now we need to reflect on some of the philosophical ramifications of this language and the form of mathematical practice it puts before our eyes, what this language and this practice have to teach us about the nature and possibility of truth and knowledge in mathematics. 8. Truth and knowledge in mathematics. Our concern is to understand the striving for truth in the practice of mathematics, how this form of inquiry works, and Freya, I have suggested, holds the key, not Freya as he has been understood but Freya as we have learned here to understand him, within the particular historical context of 19th century German mathematics. What Freya alone saw is that the developments in the mathematics of his day reveal not only that Kant's account of truth and knowledge in mathematics in terms of constructions in pure intuition must be jettisoned but that the most fundamental features of the Kantian system were in need of radical revision. Nowhere is this more manifest than in Freya's claim that despite being strictly deductive the proof of Theorem 133 that Freya provides in Part 3 of the 1879 logic is ampliative, a real extension of our knowledge. Kant's division of judgments into those that are analytic, known by logic alone, and those that are instead synthetic, or ampliative, his conception of the synthetic a priori, his account of the distinction between concepts and intuitions, even the very idea of transcendental philosophy, all would need to be wholly rethought in the wake of the newly emerged practice of Denken in Begriffen. It is characteristic of early modern thought, and of contemporary philosophical understanding insofar as it remains essentially Kantian, to be profoundly ahistorical, to turn its back on the past and to build, so it thinks, everything anew from the ground up. The search for foundations, an adequate axiomatic basis on which to build the edifice of mathematical knowledge, that occupied philosophers of mathematics for most of the 20th century, and even some still today, is a paradigmatic expression of this form of consciousness. Supremely confident of its own powers, it fails altogether to realize that the revolutionary changes in mathematics in the 19th century show that its self-understanding is only a moment in a larger process of intellectual maturation and growth. The ahistorical understanding that was born of the revolutionary developments of the 17th century cannot withstand a second revolution. And 19th century mathematicians such as Bolzano and Riemann, we have seen, were well aware of this. They knew that mathematical practice is fallible, that it is not grounded in any firm foundation but involves instead an essentially historical process of growth, maturation, and self-correction. Although a foundationalist conception of knowing is very natural in the context of ancient thought, with everyday experience providing the needed foundation, developments in mathematics in the 17th century raised profound problems for foundationalism. A foundation cannot by its nature be founded in anything else, but how then is it known? The dogmatist holds that it simply is known, the skeptic rightly denies this but can offer nothing in its stead. The right response to the stalemate, Kant saw, was to reject the whole foundationalist picture, to focus instead on the processes of inquiry and the constitutive role played by our capacity for self-correction in those processes. But the point applies, Kant thinks, only to reason in its discursive use. It does not apply to the case of mathematics, to reason in its intuitive use. In the case of mathematics there is a given foundation, as secured by the pure forms of sensibility, on which to erect the edifice of mathematical knowledge. And given the nature of mathematical practice in the 17th and 18th centuries, in particular the role that Cartesian space plays in it, this is not an unreasonable supposition. It is developments in mathematics in the 19th century that show that it is untenable. What 19th century mathematics suggests is that something like Kant's account of reason in its discursive use can, even must, be applied also to the case of mathematics. In Kant's thinking, the capacity for self-correction is closely linked to the theoretical, postulational character of early modern physics, and we hear an echo of this in Riemann and others. Riemann describes, for example, the foundations he proposes as having the status of hypotheses, and his work on the clarification of concepts as philosophical rather than mathematical. But Riemann's mathematical practice, though it is constitutively self-correcting, is not best thought of on the model of early modern physics and Kantian philosophy. It is not reductive and mechanistic, and although there is a sense in which it constructs theories aimed at explaining the appearances or data in this case are earlier mathematical results. We shall need, then, a somewhat different understanding of the capacity for self-correction that is exercised in the mathematical practice of concern to us now from that we find in Kant. We also need a different understanding of the role a written system of signs plays in mathematics, given that, unlike earlier practices, contemporary mathematics is not essentially written. A language such as that Freya developed within which to do this new sort of mathematics is clearly not a necessary condition of engaging in this practice. Indeed, given that one of the principal aims of mathematicians such as Riemann was to free mathematics of the constraints of any and all symbolization, Freya's attempt to devise a system of signs within which to do this work can seem fundamentally misguided, even perverse. Worse, reasoning in Freya's Begriffsschrift seems, as we saw in Chapter 7, to be very like the paper and pencil practices that Kant held to involve constructions in pure intuition and so to involve reason in its intuitive use rather than in its discursive use. How can a self-correcting practice of deductive reasoning from concepts involve an intuitive use of reason? The answer, of course, is that it does not. Again, mathematicians reasoning deductively from concepts do not need a system of written signs within which to work. The practice, as a practice, is purely rational and in this regard essentially different from earlier mathematical practices. It is not qua mathematicians that we need Freya's language, or something analogous, but instead qua philosophers concerned to understand the nature of the reasoning involved. In order to grasp how the reasoning works in contemporary mathematical practice, in order to achieve an adequate philosophical understanding of this practice as a mode of intellectual inquiry, it is essential that it be publicly manifested. The purely internal, mental goings-on of the individual thinker are of no interest to the philosopher. Our concern is instead with the reasoning, and it is this that Freya's language enables, a rational reconstruction in a specially devised system of signs of the course of reasoning that takes one from one's starting points to the desired conclusion. The language, as a system of written marks, is obviously shaped by contingencies of our biological and social makeup, and by our historically conditioned writing practices. The reasoning it displays is not. The reasoning is wholly and purely rational, essentially the same for all rational beings, whatever their biological and social circumstances. Point 1. We saw in Chapter 5 that in becoming purely conceptual, mathematics was to be freed of all accidental and arbitrarily imposed constraints, allowed to develop according to its own inner needs and requirements. Cartesian space within which we first come to understand the notion of a function is revealed to be merely one conceptual possibility among many, and functions first given through their analytic expression in equations are now to be characterized intrinsically through concepts. Those equations, at first taken to be the thing itself, as giving the subject matter of mathematics, are now revealed to be merely facets of what is really real in mathematics. They are the way that mathematical functions first become present to us, available for study, but not what they are in themselves. It is not by way of intuitions but through concepts of reason, Kantian ideas, that we at last come to know mathematics as it is. This, at any rate, is the way Riemann, Dedekind, and others following them thought of their new form of mathematical practice. Our task is to provide an account of how this is to work. Already we have had intimations of how the practice of deductive reasoning from concepts in mathematics, as that practice contrasts with earlier constructive mathematical practices, is the essential first step in dismantling the architectonic of Kant's transcendental idealism insofar as this new practice is not essentially written and does not presuppose space as a given infinite totality of possible positions. The task is to think through what this means, and thereby to clarify how it is that by reason alone one might achieve mathematical knowledge of that which is its subject matter. 8.1 What we have seen. We saw in section 5.4 that Rav distinguishes between a mathematician's proof and a strictly deductive, logical proof, where the former is a conceptual proof of customary mathematical discourse, having irreducible semantic content, and the latter, which Rav calls a derivation, is a syntactic object of some formal system. What Rav calls Hilbert's thesis is the logicist's claim that every conceptual proof can be converted into a formal derivation in a suitable formal system, proofs on one side, derivations on the other, with Hilbert's thesis as a bridge between the two. This bridge, Rav claims, is a one-way bridge. From a formalized version of a given proof, there is no way to restore the original proof with all its semantic elements, contextual relations, and technical meanings. Once we have crossed the Hilbert bridge into the land of meaningless symbols, we find ourselves on the shuffleboard of symbol manipulations, and as these symbols do not encode meanings, we cannot return via the Hilbert bridge and restore meanings on the basis of a sequence of symbols representing formal derivations. Just as Poincaré had argued, to formalize a mathematical proof is to destroy it, at least as a piece of mathematics, it is to cross over a bridge from which there is no return. And as is becoming more and more widely appreciated, this is true in the case of standard mathematical logic. To formalize a mathematician's proof in mathematical logic is to destroy it as a piece of mathematical reasoning. What we saw in the last chapter, and will be explained in more detail below, is that this is not true in the case of Freya's logic. Hilbert's bridge conceived as a bridge to a derivation in Freya's concept script is a two-way bridge. Standard mathematical logic is, we have seen, deeply Kantian in its overall orientation. First, this logic is formal in just the same sense that Kant's general logic is formal, because it abstracts from all relation to any object, it is without content or truth. It furthermore conceives the activity of reasoning as the rule-governed manipulation of signs, something even a mere machine could be built to do. To reason is to follow rules that require no insight or understanding to be applied, a conception that is reinforced by the fact that Descartes knew mathematical practice, unlike diagrammatic practice, has a method that is largely algorithmic. With these developments came also, we saw, a new model of understanding that was resolutely reductive and mechanistic. To understand is to reduce, for example, all of mathematics to set theory. A derivation in this logic is, as Rav says, a syntactic object of a formal system. Freya's proof of Theorem 133, we have seen, is not. Freya's language Begriffsschrift is not a formal system in our sense, it is, and is intended to be read as, a fully meaningful language within which to reason from defined concepts in mathematics. Freya is actually drawing inferences in the 1879 logic, he is reasoning in the language. Much as one reasons in the diagram in Euclid and similarly reasons in the symbolic language of arithmetic and algebra, so one reasons in Begriffsschrift. In all three systems of written signs content is formulated in a mathematically tractable way, in a way that enables rigorous reasoning on the basis of that content. And this works, at least in the case of Freya's language, because by contrast with the primitive signs of mathematical logic, which have their own designation or meaning independent of any context of use, the primitive signs of Freya's logical language only express sense independent of their involvement in a formula and a way of regarding that formula. As a certain collection of lines can be seen to form a particular geometrical figure in Euclid but can also be seen differently, as part of a different figure, so a certain collection of primitive and defined signs in Freya can be seen to form a sign for a particular concept, though it can also be seen differently. As a triangle just pops up when certain lines are drawn in proposition I. One of the elements, So a sign for connectedness just pops up when a certain inference is made in part 3 of Begriffsschrift. As a system of written signs, Begriffsschrift functions in certain respects very like the system of signs that is employed in Euclid's Elements. In other respects, Freya's system of signs functions more like the formula language of arithmetic and algebra. First, and most obviously, the reasoning is not intraconfigurational as it is in Euclid but instead transconfigurational. Steps of reasoning are steps of rewriting just as they are in elementary algebra. And as in that latter practice we can distinguish between two different sorts of steps of rewriting, both what I have called linear inferences, in which some formula is rewritten in some way according to a rule, and joining inferences that combine content from different formulae, by putting equals for equals in algebra and by some form of hypothetical syllogism in Freya's system. And as in algebra identities involving both a simple sign for some concept or function and a complex sign for that same concept or function play a crucial role in the reasoning. A definition in Freya's system is not a mere abbreviation to it is a stipulation but only as regards the Bedeutung or designation of the newly introduced sign. The newly introduced sign is to have the same designation as the complex of signs that forms the definiens. The newly introduced sign, the definiendum, does not also express the same sense as that complex of signs though it would were it functioning merely to abbreviate the complex of signs. Indeed, one can just see that the sense is different insofar as the definiendum is a simple sign and the definiens is a complex sign, one that is highly articulated in ways that can be utilized in one's reasoning. Because the definiens is complex in a way that the definiendum is not, the rewrite rules of the system can be applied to it just as they can be applied to, say, an infinite series as contrasted with a simple sign such as sin x or x. What such identities involving both a simple sign and a complex sign reveal is that we are working in these cases with what we have called intelligible unities, wholes of parts that are nonetheless not reducible to their parts. The simple sign marks the unity of the relevant concept or function, the fact that it is one. The complex sign with which it is identified reveals that that one thing nonetheless has parts that are independently intelligible. Much as a line in Euclid is intelligible independent of, say, triangles but can nonetheless be a side of a triangle, so a primitive sign in Freya, say, the concavity or conditional stroke, is intelligible independent of, say, the concept hereditary in a sequence but can nonetheless be a constituent of that concept. As Freya famously remarks, at least some of his definitions are fruitful, they draw new lines. And that means, as we will see in more detail later, that they are wholes that despite having parts are not reducible to their parts. It has been assumed for over a century that one understands Freya's system of signs when one knows the rules and can see how they are applied in individual steps of reasoning. This we have seen is wrong. Although one begins with such an understanding, to achieve full literacy and competence in the system is to come to see the ideas at work in the proof, how the defined concepts are used to guide the reasoning from the starting point to the desired theorem. It is in precisely this way, by learning to understand the proof at the level of ideas, that we cross back over what Rav calls the Hilbert bridge to the conceptual proof with all its semantic elements, contextual relations, and technical meanings. Poincaré objects to logicism on the grounds that replacing all mathematical modes of reasoning with a series of purely logical steps destroys the unity of a proof that is essential to mathematical understanding. Following Avogadro, we can think of the sort of mathematical understanding Poincaré has in mind in terms of certain sorts of capacities and abilities. A person who understands a proof, as contrasted with merely being able to see that each step is valid, possesses the following three. 1. The ability to respond to challenges as to the correctness of the proof, and fill in details and justify inferences at the skeptic's request. 2. The ability to give a high-level outline, or overview of the proof. 3. The ability to indicate key or novel points in the argument, and separate them from steps that are straightforward. 4. The ability to motivate the proof, that is, to explain why certain steps are natural or to be expected. 5. The ability to indicate where in the proof certain of the theorem's hypotheses are needed, and, perhaps, to provide counterexamples that show what goes wrong when various hypotheses are omitted. If a person can display the sort of understanding that is exemplified in these various ways, then it seems fair to say that they understand the proof. And contrariwise, if they can display such understanding, this shows that there is in the proof the relevant meanings and ideas to be understood. That is, we can use Avogad's criteria to establish that we really have crossed back over Hilbert's bridge. We need to establish that formalizing a mathematical proof in Freya's language, that is, making it fully rigorous and gap-free, does not destroy the mathematics but preserves it, though it does take work to acquire the eyes to see the meanings that are still there after the formalization. And we can do that by showing that Avogad's criteria for understanding are satisfied. To show that the criteria are satisfied will be to show that meanings, the grounds of understanding, are still there in the formalized proof. The first capacity manifesting mathematical understanding is displayed in one's ability to respond to challenges to correctness, fill in details, and justify inferences. Obviously we have that insofar as the first thing one learns in learning to use Freya's system of signs is what the basic rules of inference are as given in the axioms, and how to use those rules to derive various other non-basic rules of inference. All those axioms and derived theorems function in the system as the axioms and derived theorems of elementary algebra function. They are rewrite rules for the cases we really care about, namely, cases of reasoning from defined concepts. Even someone with only the most rudimentary literacy in the system can verify that all the steps in Freya's proof of Theorem 133 are correct. At a more advanced stage of literacy in Freya's language, one is able to see larger patterns, and in particular the general proof strategy for proving generalized conditionals on the basis of certain sorts of definitions, namely, those that contain inference licenses. Already at this stage of understanding one can indicate novel points in the argument, points at which content is joined by hypothetical syllogism, and can separate them from the straightforward steps in which identities corresponding to definitions are merely transformed on the way to a join. Because one has internalized the rules, one no longer needs to write out each step, for instance, steps in which the order of conditions is switched or in which a concavity is added or removed. To be able to apply the general strategy in finding a proof, leaving out the obvious steps, is to satisfy the third desideratum. But we have seen that someone with only this level of understanding will not understand all the steps of Freya's proof. Relative to that general strategy, some steps seem merely ad hoc. Only at the final stage of full literacy can one motivate the central ideas of the proof and explain how in outline it goes. Only at this stage can one recognize that in a fundamental sense the proof begins with a conditional derived from the definition of being a single-valued function and proceeds by transforming that conditional into the theorem that is wanted, that this is the proper overview of the proof as a whole, of its unity as a proof. Someone who has achieved this level of understanding has satisfied the second and fourth criteria on understanding a proof. The final test of understanding is the ability to indicate where in the proof conditions on the truth of the theorem are playing an essential role and to provide counterexamples showing what goes wrong when they are omitted. This we showed for the theorem to be proved. Only if f is single-valued is it true that m and y are connected on condition that both follow x in the f sequence. It is also easy to show for the property of being hereditary in the case of connectedness. Connectedness has the property of being hereditary only on condition that the relevant function is single-valued. Suppose that x follows y, that is, that we can get to x by repeated applications of f to y. If at y there were a branching, with x following down one branch and z, the result of an application of f to y, starting another branch, then we would have x connected to y and f but not that x is connected to z. So the last of Avogad's criteria is satisfied as well. We have satisfied all the criteria of adequacy for understanding a proof and have shown thereby that the proof has content, meaning that is there to be understood. The bridge from the mathematician's proof, which is at the level of the ideas of the proof, to a fully rigorous proof in Freya's concept script is a two-way bridge. The proof can be fully formalized, but even so one can recover the ideas of the proof, how it really goes and how it would have been discovered in the first place. A fully formalized proof in Begriffsschrift adequately understood is not reductive and does not destroy the mathematical meaning of the proof. Point 4. The conception of reasoning and understanding that is the legacy of early modernity and generally accepted still today is, we have seen, reductive and mechanistic. The conception of reasoning and understanding that is required for any fully adequate understanding of Freya's formula language of pure thought is neither. The contents of concepts are not reduced to collections of primitive notions but are instead displayed in definitions as the conceptual contents they are, and those displays are mathematically tractable. One can reason rigorously in the system given those displays. Nor is the reasoning merely mechanical. Indeed, although it is deductive throughout, some steps of the reasoning are not merely by logic, they are licensed by a rule that is neither an axiom of logic nor a theorem derived from such axioms. Instead, these steps are warranted by inference licenses that are derived from a definition. In order to discover a proof in such cases requires insight and understanding, the capacity to see in a definition its potential to provide such rules. The task now is to understand more clearly what all this means and also what it entails for our understanding of truth and knowledge in mathematics, beginning with some reflections on mathematics as a domain of scientific inquiry. 8.2 The Science of Mathematics. We saw in Chapter 5 that in the work of Galois, Riemann, and other 19th-century mathematicians the practice of mathematics was, for the second time in its long history, radically transformed. As was noted in particular in section 5.3, this second transformation furthermore seemed to constitute a second birth of the subject. The whole of mathematics was to be reborn as a purely conceptual enterprise purified of all the contingencies that had hitherto attached to it. Because the world of the mathematician came in this way to be an autonomous realm of meaning subject only to its own internal demands, traditional abstractionist conceptions of mathematical concepts were clearly inadequate to explain the nature of our cognitive access to those concepts. Instead, it was suggested, mathematicians adopted a top-down approach according to which the fundamental notions of the science are to be understood by appeal to higher-order properties. Although the concepts of contemporary mathematics may first be discovered by reflecting on instances, they are to be understood independent of any instances, defined by appeal to their internal constitutive contents and properties. Such concepts, we saw, have the character of Kantian ideas, concepts of reason, insofar as they are wholes of parts that are not reducible to their parts. The task of the mathematician is to analyze these concepts, clarify what exactly their mathematician meaning is, which can then be set out in a definition, and on that basis to prove theorems concerning such concepts. And for this one needs as well, though it is not yet completely clear why, to formulate axioms, basic propositions regarding one's primitive notions. As we noted, both Bolzano and Riemann were explicitly anti-foundationalist and fallibilist about both aspects of this practice. And Riemann was furthermore resolutely historicist about the concepts of mathematics. Only over time, in light of the problems that emerge, do we achieve the conceptions we need in order fully to understand the mathematics we are concerned to understand. We also saw, in Chapter 7, something of how this new form of mathematical practice works insofar as we saw displayed in Freya's concept script just the sort of deductive reasoning from concepts that has been characteristic of mathematical practice since the 19th century. We looked both at examples of proofs of theorems from axioms, for instance, the little proof of Theorem 5 from the first two of Freya's axioms of logic, and at examples of proofs of theorems from definitions, both the proof of Theorem 133 and proofs of some of the subsidiary theorems that are needed along the way. In Freya's system, we saw, there are, first, the primitive signs, which are elucidated in Part I, and the axioms, provided in Part II, setting out the fundamental inferential significance of those signs as well as theorems derived from those axioms. As we furthermore indicated, Part 3 of the 1879 Logic, which introduces definitions and theorems derived on the basis of those definitions, is essentially different insofar as the axioms and derived theorems from Part 2 are now, in Part 3, to be used instead as rules of inference. Again, as Freya himself emphasizes, his proof of Theorem 133 is from his definitions by means of the rules of inference set out in Part 2. What we need now to understand is how this purely conceptual enterprise works as a science, in particular, how it can involve an autonomous realm of meaning to which one's judgments are nonetheless answerable. And for this, it will be argued, we need, as Freya already saw, something very close to the classical model of science first formulated by Aristotle. According to the Aristotelian model, a system of concepts and judgments is a science just if it satisfies the following 6 desiderata. All those concepts and judgments concern a certain domain of being. Among the concepts, some are primitive and the rest are defined by appeal to those primitive concepts. Among the judgments, some are primitive and the remainder are proven as theorems from those primitive judgments. The judgments of the science are true, necessary, and universal. The judgments are known to be true, either directly or through proof. The concepts are adequately known, either directly or through definitions. This model, De Jong and Betti suggest, was in fact abandoned over the course of the 20th century. Among the factors that led to its demise, they list the following: the improved standard of rigor that logic enjoyed after Freya, the restriction to deductive sciences, the discovery of non-Euclidean geometry and the ensuing debate of what geometry, if any, was the true one, pluralism in logic, Hilbert's formalistic turn in mathematics together with debates on the notion of interpretation and meaningfulness of symbolism and the emergence of model theoretical tools in semantics. In short, if one follows the lead of mainstream 20th century analytic philosophy, then one will be led to reject the model. But, we have seen, we need not follow that lead but can instead take the more radical path, opened up by Freya's work, that jettisons not only Kant's forms of sensibility and understanding but even Kant's conception of logic as purely formal and merely explicative. From the perspective of this latter path, the prospects for the Aristotelian model look very different. Euclid's system as presented in the Elements has been, throughout history, the exemplar of a science in the Aristotelian sense. And so it is for Freya. He writes, for instance, in the introduction to Grundgesetze, the ideal of a strictly scientific method in mathematics, which I have here attempted to realize, and which might indeed be named after Euclid, I should like to describe as follows. It cannot be demanded that everything be proved, because that is impossible, but we can require that all propositions used without proof be expressly declared as such, so that we can see distinctly what the whole structure rests upon. After that we must try to diminish the number of these primitive laws as far as possible, by proving everything that can be proved. Furthermore, I demand, and in this I go beyond Euclid, that all methods of inference employed be specified in advance, otherwise we cannot be certain of satisfying the first requirement. This ideal I believe I have now essentially attained. 5. But although Freya adopts this venerable conception of scientific method, he also subtly transforms it. Freya was a logicist, and to be committed to logicism seems clearly to entail a commitment to something like the Aristotelian model of science, insofar as the way to show that logicism is true is by systematically deriving all the basic truths of arithmetic from purely logical laws, and defining all the basic and defined concepts of arithmetic using only purely logical concepts. But one can be committed to the model without being committed to logicism. If logicism is false, then arithmetic is, as, a century on from Freya, it clearly seems to be a science with its own primitive notions and its own primitive laws. But the way to show this, and thereby settle the question of the fundamental nature of arithmetic, is, again, by settling the question of its most basic laws and therefore also its most basic concepts. Freya explains in Logic in Mathematics. Science demands that we prove whatever is susceptible of proof and that we do not rest until we come up against something unprovable. It must endeavor to make the circle of unprovable primitive truths as small as possible, for the whole of mathematics is contained in these primitive truths as in a kernel. Our only concern is to generate the whole of mathematics from this kernel. The essence of mathematics has to be defined by this kernel of truths, and until we have learnt what these primitive truths are, we cannot be clear about the nature of mathematics. The mathematical demand for the utmost rigor, which includes the demand for proof where proof is possible, and the philosophical question of the true character of mathematical knowledge, whether purely logical or grounded in distinctively mathematical truths, results in one and the same requirement. That the fundamental propositions of arithmetic should be proved, if in any way possible, with the utmost rigor, for only if every gap in the chain of deductions is eliminated with the greatest care can we say with certainty upon what primitive truths the proof depends, and only when these are known shall we be able to answer our original questions. Whatever the status of logicism, Freya clearly thinks that the demand for the utmost rigor, and hence proof where proof is possible, which requires in turn the analysis of concepts and the formulation of definitions of them, is a requirement of mathematics as a science. In mathematics we must never rest content with the fact that something is obvious or that we are convinced of something, but we must strive to obtain a clear insight into the network of inferences that support our conviction. Point 6. But it can seem that the model inevitably commits us to something more, not only to rigor in mathematics but also to a false epistemology, in particular, that it commits us to a demand for certainty or infallibility in mathematics. And this seems to have been the way it was understood, for instance, by Descartes and by Kant. Such an understanding is not, as Freya shows, constitutive of adherence to the model. It is perfectly coherent both to take the model to be the standard of scientific rationality in mathematics and to be fallibilist about mathematical knowledge, that is, to take it to be an experimental science, one whose foundations are not given and are never indubitably certain. As we saw in section 5.3, not only Freya but both Bolzano and Riemann hold this pair of views as well. Freya does claim, at the end of the introduction to Grundgesetze, that no one will be able either to produce a better system than his or to show that his principles lead to contradiction, but this is nothing more than an expression of his confidence that he has gotten things right. The test of one's logical convictions, Freya thinks, lies in what one can do with them, and it can always turn out that, unbeknownst to one has gotten something wrong. Russell's discovery of the flaw in Freya's basic law v, however personally devastating to Freya, nevertheless held out for him the promise of being the crucial first step in a great advance in logic. And it did so because, for Freya, the first prerequisite for learning anything is the knowledge that we do not know. For Freya, as for Socrates, the first prerequisite for learning anything is the knowledge that one does not know. Freya furthermore draws an intimate connection between this first prerequisite and the Aristotelian model, at least for the case of mathematics. It is, he thinks, only by adhering to the model and thereby making as explicit as one can just how one understands things to be that one is put in a position to discover that one does not know something one had thought one knew. Freya explains, in evident frustration, with reference to Weierstrass's mathematical work in particular. He was lacking in the first requirement knowledge of his own ignorance. He saw no difficulties at all, everything seemed clear to him, and he didn't notice that he was constantly deluding himself. He did not possess the ideal of a system of mathematics. We do not come across any proofs, no axioms are laid down, we have nothing but assertions which contradict one another. And when on occasion an inference does seem to be drawn from his definition, it is fallacious. If he had but made the attempt to construct a system from the foundation upwards, he could not have failed straightway to see the uselessness of his definition. He had a notion what a number is, but a very hazy one, and working from this he kept on revising and adding to what should really have been inferred from his definition. Without the rigor imposed by the model, Freya suggests, it is all too easy to delude oneself into thinking that one has grasped some concept clearly and distinctly when in actuality one is completely confused. Point 7. It is a very familiar fact of intellectual life that one can think that one understands something clearly and distinctly even though, as one later realizes, in fact one does not. Because one can think that one understands something that in fact one does not, the discovery of a problem that makes one realize that things are not clear, or distinct, can be of immense intellectual value, the necessary first step on the way to a better understanding. And the point applies, Freya thinks, in all domains of science, including even logic. The laws of logic are truths, and what is true independently of our recognizing it as such. We can make mistakes. Of course, in most cases we have no reason to doubt the truth of this or that law of logic, the law of identity, say, that A equals A. Such a law seems to us as manifestly true as anything could be. Because it does, we cannot imagine that it might be false. But, Freya suggests, we can imagine beings who do doubt it, which is to say that we can imagine ourselves coming to have doubts about it, just as Russell brought Freya to have doubts about basic law V. We cannot imagine what those doubts would be. If we could, we would have those doubts. But we can imagine having doubts. As Freya puts the point, the impossibility of our rejecting the law in question hinders us not at all in supposing beings who do reject it. Where it hinders us is in supposing that those beings are right in so doing. It hinders us in having doubts whether we or they are right. Because we have now no doubt at all that the law of identity is true, because we can find no reason whatever to call it into question, we can have no doubt now that we are right to affirm it, and correlatively, that anyone who does not affirm it is wrong. But even so, we can imagine beings who reject the law of identity, which, again, is just to say that we can imagine ourselves coming to reject it on grounds that are as yet unimaginable. Mere conviction in mathematics and logic is not enough. The ground of the conviction must be laid bare by proving what can be proved and by defining all but a handful of primitive terms. Freya furthermore provides us with an account of how it is that we can seem to be clear about something when in fact we are not, and as a constitutive element of that account, a conception of how it is that we can discover our error. Because all our awareness of what is objective is mediated by sense, sin, we can think we have grasped what is in cases in which in fact the outlines of the sense are confused and blurred. We need, then, to distinguish between a concept and our knowledge of a concept, between, on the one hand, the logical and objective order and, on the other, the psychological and historical order. A logical concept does not develop and it does not have a history. If we said instead history of attempts to grasp a concept or history of the grasp of the concept, this would seem to me much more to the point, for a concept is something objective, we do not form it, nor does it form itself in us, but we seek to grasp it, and in the end we hope to have grasped it, though we may mistakenly have been looking for something when there was nothing. Mathematical and logical concepts are something objective that we can grasp and can fail to grasp. Furthermore, because our grasp of a mathematical concept is through an inferentially articulated sense, we can discover by reasoning, by drawing inferences on the basis of the sense of a concept word, at least as far as we understand that sense, that we were after all mistaken about it. The contradictions that we fall into in the course of inquiry are, as Freya explains, due to just such faulty conceptions. Created by treating as a concept something that was not a concept in the logical sense because it lacked a sharp boundary. In the search for a boundary line, the contradictions, as they emerged, brought to the attention of the searchers that the assumed boundary was still uncertain or blurred, or that it was not the one they had been searching for. So contradictions were indeed the driving force behind the search, but not contradictions in the concept, for these always carry with them a sharp boundary. The real driving force is the perception of a blurred boundary. Getting clear on the sense of a concept word through such a process of proof and refutation, inference and counter-inference, just is to come to grasp the concept in its pure form. According to Freya, errors in mathematics are almost invariably due to a lack of clarity about the relevant mathematical concepts. Almost all errors made in inference have their roots in the imperfections of the concepts, that is, in our conceptions, our understanding of the sense. And we discover those imperfections in our understanding by reasoning on the basis of concepts insofar as we understand them, that is, grasp the senses through which they are disclosed. But such a process of reasoning can reveal imperfections only, if the content is not just indicated but is constructed out of its constituents by means of the same logical signs as are used in the computation. In that case, the computation must quickly bring to light any flaw in the concept formation. This is precisely what Freya's concept script enables, the expression of the inferentially articulated contents of concepts in a way that enables rigorous deductive proof and thereby a means to discover the flaws in our understanding of those concepts, and to improve that understanding. Because the aim of proof is, in fact, not merely to place the truth of a proposition beyond all doubt, but also to afford us insight into the dependence of truths upon one another. It is in the nature of mathematics always to prefer proof, where proof is possible. A proof serves to reveal logical relations between truths. That is why we already find in Euclid proofs of truths that appear to stand in no need of proof because they are obvious without one. Indeed, Freya thinks that it is just this that constitutes the value of mathematical knowledge, not so much what is known as how it is known, not so much its subject matter as the degree to which it is intellectually perspicuous and affords insight into its logical interrelations. But of course a proof must start somewhere, not everything can be proved. The task, then, is to make the circle of unprovable primitive truths as small as possible, to discover some small collection of primitive truths from which all the others can be derived. And as Freya notes both in Begriffsschrift, section 13, and in Logic in Mathematics, often there is some leeway here insofar as two different axiomatizations of some domain of inquiry may be equally acceptable. The possibility of one system does not necessarily rule out the possibility of an alternative system, so that we may have a choice between different systems. So it is really only relative to a particular system that one can speak of something as an axiom. In Part I of the 1879 Logic, Freya introduces all the primitive signs of his language, explains his fundamental notions, and sets out his one mode of inference. None of this, as he notes in the opening paragraph of Part II, can be expressed in his language because it forms the basis of all expression in the language. The elucidations of Part I belong, then, only to the antechamber of mathematics, the propaedeutics. They are necessary not to mathematics itself but in order to ensure that a reader has the same understanding of the basic notions of the written system of signs as its author, and here one must of course always rely on being met halfway by an intelligent guess. Point 8 in Part 2 the development of the system properly begins. 9 judgments are presented as the axioms that contain, as in a kernel, all of the boundless number of laws that can be established in logic, and various theorems are derived from them using Freya's one mode of inference. We need to understand just what all this involves. First, axioms, on Freya's view, are truths that are, or should be, immediately evident. They are truths about which we have no doubts, though, again, we can turn out to have been mistaken. Because we need explicitly to recognize the truth of Freya's axioms because inferences can be drawn only from acknowledged truths, we need to grasp the thoughts those axioms express, and in order to do that we need to grasp the senses of Freya's primitive signs. Given, for example, what is expressed by the conditional stroke, as elucidated in Part I, and given what it is to judge, namely, to acknowledge the truth of a thought, it follows that what is true on any condition you like because what is true unconditionally. If, in other words, one has some acknowledged truth, some judgment, then one may infer that judgment on some condition, that is, add a condition to it, any condition you like. Freya's first axiom formulates this valid rule of inference in the form of a judgment. In the same way one needs to grasp the senses of Freya's other primitive signs in order to recognize the truth of his other axioms. For the purposes of proof, all that is granted as known regarding the primitive signs is what is made explicit in Freya's 9 axioms. The axioms codify the fundamental inference potentials that are contained in his various primitive signs. Because they do, various derived rules of inference involving those primitive signs can also be established. Axioms, on Freya's view, are truths that are immediately evident. Definitions such as those Freya presents in Part 3 of the 1879 Logic are different insofar as they are not truths but instead stipulations. What a definition stipulates is that some newly introduced, hitherto meaningless sign has precisely the same meaning as some collection of primitive, and perhaps also already defined, signs. Freya does sometimes claim that the two also express the same sense, that the newly introduced sign is merely an abbreviation for the complex sign used in its definition, but we have already noted that this cannot be right given that Freya also thinks that proofs of theorems from definitions can constitute real extensions of our knowledge. Definitions in Freya's system stipulate sameness of meaning but not also sameness in the sense expressed. Indeed, I have suggested, we can just see that this is so insofar as the definiendum is a simple sign without any internal articulation and the definiens is a complex, richly articulated sign on the basis of which to reason. Now in the Aristotelian model as traditionally understood, definitions seem to have nothing whatever to do with the proof of theorems. There are the primitive and defined terms, on the one hand, and the primitive and derived judgments, on the other, and no indication is provided of any sort of relationship between the two. This is unsurprising given that in Euclid's system definitions belong to the preamble or antechamber, not to the actual system of mathematics. As we have seen, it is not the definitions but instead diagrams that formulate content in a mathematically tractable way in Euclid's system. But proofs in contemporary mathematical practice do take explicitly formulated definitions as their starting points. And Freya's system reflects this. As we saw in Chapter 7, in Part 3 of Begriffsschrift, Freya introduces 4 definitions and proves on the basis of those definitions a series of theorems culminating in Theorem 133 showing a logical relation among 3 of Freya's 4 defined concepts. As Freya shows by example, definitions can enable the discovery of logical relations among concepts by means of deductive proof. Freya's practice suggests that the theorems that are derived from axioms of logic are very different from theorems that are derived from definitions. But the two sorts of derivations are not merely independent of one another, as primitive and defined concepts appear to be independent of primitive and derived theorems in the classical model. As we saw in Chapter 7, in Freya's system, axioms and the theorems that are derived from them provide inference licenses that are needed for proofs that take definitions as their starting points. And this works precisely because the signs that appear in the axioms and theorems are used also in the formulation of the definitions. The content is constructed out of its constituents by means of the same logical signs as are used in the computation. Now in Freya's Begriffsschrift example, even the constituents are strictly logical. All of the primitive notions in the system of the 1879 logic belong to logic. But even were the language to be enriched with the addition of primitive signs of arithmetic, the same would be true. The new arithmetical primitives would require the addition of new axioms codifying the fundamental inferential significance of those primitives. But they would also enable the formulation of definitions of various mathematical concepts such as that of continuity, of prime number, and of being a common multiple, all of which and more are formulated in Freya's concept script together with some signs from arithmetic in Freya's early essay Boole's Logical Calculus and the concept script. Proofs of significant theorems in the new system would begin with such definitions and proceed in accordance with the rules codified in the axioms of the system together with the theorems that are derived from those axioms. There would, then, remain a fundamental division between, on the one hand, axioms and theorems derived from them, all of which function in the system overall as rules governing inference, and on the other, definitions and theorems derived from those definitions. Only the latter sorts of theorems proven on the basis of definitions, can constitute real extensions of our knowledge. According to the model as traditionally understood, a science comprises concepts, both primitive and defined, and judgments, both primitive and derived. No indication is given of the relationship, if any, between defined concepts and derived judgments. Freya's practice, which is essentially that of mathematicians beginning in the 19th century and continuing still today, exhibits a much more complex structure. In Freya's practice, there are, first, axioms setting out the fundamental inferential significance of the primitive signs, as well as various theorems that follow from those axioms by a recognized rule of inference. Then there are the definitions of concepts, which are stipulations that introduce some new simple sign and assign it a meaning that is given in the definiens by way of an inferentially articulated sense. These definitions are, furthermore, formulated using just the same signs as are employed in the formulation of the axioms. And finally there are the theorems that follow from the definitions by means of the axioms and theorems derived from those axioms. A proof of such a theorem on the basis of definitions, and according to the axiomatized rules, is completely rigorous and gap-free. And because it is completely rigorous and gap-free, the proof makes manifest on what the theorem depends and by what means it is justified. In this case, just as Frege remarks in the introduction to Grundgesetze, if anyone should find anything defective, he must be able to state precisely where, according to him, the error lies, in the basic laws, in the definitions, in the rules, or in the application of the rules at a definite point. If we find everything in order, then we have accurate knowledge of the grounds upon which each individual theorem is based. Because everything is made maximally explicit in reasoning in Frege's system, the starting points, the rules governing inferences, and each individual inference from the starting points to the desired conclusion, errors are more easily detected, and where no errors are found, although this is no guarantee that problems will not later come to light, one has very reasonable assurance that the theorem is true and good reason to think one has discovered the nature of its grounds, whether in logic alone or in the basic laws of some special science. It is in just this that the rationality of the endeavor consists. Because it makes everything maximally explicit and hence available to critically reflective scrutiny and criticism, the method gives one cognitive control over the domain of inquiry. And although the method does not guarantee that mistakes will not be made, does not guarantee that what seems to be clear and distinct really is clear and distinct, it ensures as far as possible that such errors as there are will, sooner or later, come to light and be corrected. The practice is both fruitful and maximally robust. It is also non-foundationalist. Not only is it, as mathematics has always been, self-consciously rational, it is purely rational, by reason alone. On the Aristotelian model as traditionally understood, knowledge of the basic concepts and judgments of a science is somehow immediate and certain. Hence, it can seem that a constitutive feature of mathematical practice is the search for indubitable foundations, and as a result, it can seem, giving up the foundationalist enterprise in mathematics is tantamount to giving up the model. Point 10 Frege shows that this is just not so. One can be a thoroughgoing fallibilist as concerns our knowledge of the truths of mathematics, and nevertheless adhere to the model as the exemplar of scientific rationality. Indeed, we have seen, really to take seriously the fact that there is no certainty in mathematics, that one may after all be mistaken on any point, requires that one adhere to the model. Frege rejects the foundationalism of the Aristotelian model as traditionally understood. For him, as for Bolzano and Riemann, mathematics, although a priori, that is, non-empirical, is nevertheless an experimental science whose foundations are not given but instead must be discovered by a process of proof and refutation, that is, self-correction. Axiomatizations and explicit definitions are, on this understanding, not so much the end product of science as a means, a vehicle of discovery. If a contradiction is derived, then one knows that something is wrong, either with one's axioms or with one's definitions, that there is something one has not adequately understood, that one needs to make some corrections. And this requires that Frege modify the classical model in another way as well. Where the model has concepts, primitive and defined, and judgments, primitive and derived, Frege has instead, axioms and theorems of logic, definitions formulated using the same signs as are used in the axioms and theorems of logic, and theorems derived from definitions by means of the rules provided by the axioms and theorems of logic. These three essentially different classes of judgments play in Frege's system just the role that in Kant's thinking is played by the three forms of judgment under the title of relation in his table of the forms of judgment, namely, categorical, hypothetical, and disjunctive judgments. In both cases they are the means whereby one makes explicit one's understanding, and in such a way that confusions can come to light in the form of contradictions. In Frege's modified model, Theorems derived on the basis of definitions are essentially different from theorems derived from axioms alone and must be distinguished from them. This, I have suggested, is something radically new, something that is characteristic in particular of mathematical practice as it emerged over the course of the 19th century and continues today. Although they are not as rigorous in their practice as Freya is and they do not use a formula language of the sort Freya developed, what mathematicians do is to define concepts and derive theorems based on their definitions, showing thereby various logical relations that obtain among the concepts so defined. What Freya helps us to see is in what the rationality of this practice consists. As he shows, the Aristotelian model of science, updated to reflect developments within mathematics, provides a viable and compelling image of scientific rationality by showing, if only in the broadest outline, how it is that we achieve, and maintain, cognitive control in our mathematical investigations. 8.3 The nature of ampliative deductive proof. Freya claims that his proof of Theorem 133 in Begriffsschrift is ampliative, an extension of our knowledge, despite being analytic in Kant's sense, that is, strictly deductive. In section 88 of Grundlagen he further suggests that ampliative proofs involve what he describes as fruitful definitions that by contrast with definitions that merely list characteristics draw new boundary lines. If we represent the concepts by figures or areas in a plane, then the concept defined by a simple list of characteristics corresponds to the area common to all the areas representing the defining characteristics, it is enclosed by segments of their boundary lines. With a definition like this, therefore, what we do in terms of our illustration is to use the lines already given in a new way for the purpose of demarcating an area. Nothing essentially new, however, emerges in the process. But the more fruitful type of definition is a matter of drawing boundary lines that were not previously given at all. What we shall be able to infer from it, cannot be inspected in advance. Here, we are not simply taking out of the box again what we have just put into it. The conclusions we draw from it extend our knowledge, and ought therefore, on Kant's view, to be regarded as synthetic, and yet they can be proved by purely logical means and are thus analytic. The truth is that they are contained in the definitions, but as plants are contained in their seeds, not as beams are contained in a house. In the Longbull essay, the same imagery of drawing new boundary lines is used to distinguish what Freya thinks of as fruitful definitions, and Freya points to his representation of generality as what, in particular, makes possible a true concept formation, one that didn't use already existing boundary lines. Again, Freya indicates that only from such definitions can theorems be derived that extend our knowledge. It is the fact that attention is principally given to the sort of formation of new concepts from old ones, while other more fruitful ones are neglected, which is surely responsible for the impression one easily gets in logic that for all our toing and froing we never really leave the same spot. In both this essay and in Grundlagen, Freya cites the definition of continuity as an example of a definition that is fruitful in his sense. In the Longbull essay he cites as well the definition of a limit and his own definition of following in a sequence. All these definitions involve Freya's sign for generality, his concavity, in their expression in Begriffsschrift. 11 Nowhere does Freya suggest that his definitions of being hereditary in a sequence and being a single-valued function are likewise fruitful, despite the fact that they too involve the concavity in their expression. As we will see, we need to distinguish more carefully than Freya does between different cases, between different levels of fruitfulness. In Freya's imagery in section 88 of Grundlagen, the conclusion of a merely explicative proof is contained in the starting points of the proof as beams are contained in a house. The conclusion is, in other words, already there in the starting points, it is contained in them, needing only to be brought out. In a merely explicative proof the conclusion is, as we can say, implicit in the starting points. All the proof does is to make what is otherwise only implicit explicit. In an ampliative proof, Freya suggests, the conclusion is instead contained in the starting points as plants are contained in their seeds. As a seed has the potential to grow into a plant, so the starting points of an ampliative proof have the potential to yield a conclusion that extends our knowledge. The conclusion of such a proof actualizes that potential as a plant that grows from a seed actualizes the potential of that seed. Whereas in a merely explicative proof what is implicit is made explicit, in an ampliative proof what is potential is made actual. We need to understand what precisely is the difference between these two cases. Freya's remarks about ampliative proof suggest that only proofs from definitions, and in particular from what he describes as fruitful definitions, definitions that draw new boundary lines, can extend our knowledge. It follows directly that none of Freya's proofs of theorems from axioms in Part 2 of the 1879 logic can extend our knowledge. Such proofs only make explicit something implicit in those axioms. If Freya is right, and we will soon see that he is, then it is not primarily the form of reasoning that makes the difference between ampliative and merely explicative proof, but instead the starting point, whether axioms or definitions, though, as we will also see, this can affect in turn the precise nature of the reasoning involved. We have seen that any derivation in Freya's concept script, whether from axioms or from definitions, requires us to regard a formula now this way and now that. Conditions that are at one point seen as conditions on some judgment are at another instead regarded as part of the conditioned judgment. Any derivation also involves the construction of various formulae to take us from something we have, say, axioms 1 and 2, to something we want, such as theorem 5. Both in cases in which the starting point is a collection of axioms and in cases in which the starting point is instead definitions, we can distinguish theorems that are merely a means to some end, as theorems 3 and 4 are, from theorems that are of some independent interest, as theorem 5 is. As the derivation of theorem 5 also reveals, both proofs from axioms and proofs from definitions can require a kind of experimentation to determine not only what rule it is useful to apply but also what it is useful to add as a condition. Axiom 1, we know, licenses adding a condition to a judgment, any condition you like. But one might need to experiment a little to determine that one should add a on condition that be in particular to axiom 2 on the way to theorem 5, and similarly, at various points in the derivation of theorem 133, one needs to add one condition in particular. Hence, in both cases, both in reasoning from axioms and in reasoning from definitions, the reasoning seems to be, at least in some cases, theorematic rather than corollary, all in Peirce's sense. Point 12. Furthermore, although most of the derivations in Part 2 do not, some of those derivations do involve inferences that join content from two axioms, just as Freya's proof of 133 involves inferences that join content from two definitions. In the derivation of theorem 33 from axioms 31 and 28, for example, Freya constructs theorem 32, on the basis of axiom 31, to govern the passage from 28 to 33, but it is clear that we could instead take theorem 7, used in that construction, directly to license a two-premise inference from 31 and 28 to 33, one that joins content from the two axioms. And, finally, axioms can provide inference licenses. So even the fact that the proof of theorem 133 involves using an inference license derived from a definition does not seem in any essential way to distinguish Freya's proof of theorem 133 in Part 3 from the derivations of Part 2. The only principal difference between the two collections of derivations seems to be that the derivations in Part 2 are from axioms and those in Part 3 are from definitions. We need to understand the difference this difference makes. In Part 2 of the 1879 logic, Freya derives various theorems he will need in his proof, in Part 3, of theorem 133. These theorems, and the axioms from which they are derived, function in the latter proof, we have seen, as rules licensing the linear and joining inferences that take us from Freya's definitions to his theorem. And as Freya notes, the theorems that are derived from the axioms in Part 2 were chosen precisely because and insofar as they are needed in the proof of theorem 133 of Part 3, apart from a few formulae introduced to cater for Aristotelian modes of inference, I only assumed such as appeared necessary for the proof in question, that is, for the proof of theorem 133. Although the axioms and theorems of Part 2 are truths on Freya's view, They have, in other words, little intrinsic interest. They are valuable not in themselves but instead for what they enable one to prove on the basis of defined concepts. Independent of a proof such as that of Theorem 133, one would have no reason to derive this rather than that theorem of logic, no reason to start, or to stop, with any particular axioms or theorems of logic. The interest of the sentences of pure logic that we find in Part 2 of Freya's Begriffsschrift lies in the fact that they were adequate for the task that is undertaken in Part 3. An axiomatization of the rules of logic is valuable insofar as it contains, if only implicitly, all of the boundless number of laws that can be established. But neither the axiomatization, nor the theorems that are derived solely on the basis of such axioms by themselves constitute a real extension of our knowledge of the sort that is achieved by a proof from defined concepts. And this is so at least in part because only a derivation based on definitions of concepts can establish that particular concepts such as that of following in a sequence or belonging to a sequence have various logical properties, for example, transitivity, and stand in various relations, such as subordination. There are a number of aspects to this. In the case of a derivation from axioms, whether a very simple derivation such as that of Theorem 5 or one that is quite involved, say, that of Theorem 48 or that of Theorem 51, there is a clear sense in which the conclusion is contained implicitly already in the starting points, the axioms, needing only to be made explicit. In this case, one is merely moving things around and combining and recombining them according to rules. And although the two-dimensionality of the notation enables one to regard a given formula now this way and now that, these various ways of regarding a formula do not reveal any subject matter for logic because any way at all that it is possible to regard the formula is as good as any other. It is definitions that introduce a subject matter, and much as they do in Euclid, definitions in Freya's system enable one to discern, between the primitive parts, on the one hand, and whole formulae, on the other, significant parts of those formulae that are built up out of the primitive signs. A science properly speaking thus involves more than merely primitive and derived truths about various basic notions, such as, in Euclid, points, lines, angles, and areas, or in Freya, negation, the relation codified in the conditional stroke, and the second-level property designated by his concavity. A science needs a subject matter, it involves concepts and judgments that concern a certain domain of being, and it is definitions of concepts by appeal to those same primitives that provide this subject matter. But again, in Euclid's system the definitions belong only to the propedeutic, the antechamber. It is not in the definition but in the diagram that the contents of concepts are formulated in a mathematically tractable way. In Freya's system the definitions themselves formulated in Begriffsschrift are the starting point. We have seen that an axiom of logic is a judgment, a truth. It is, or at least should be, immediately evident, but it is nonetheless a substantive truth that does not go without saying. A definition, we have seen, is not a judgment, it is a stipulation. Such a stipulation does immediately give rise to an identity judgment, but this judgment is one that is, in light of the stipulation, utterly trivial. It is not merely immediately evident as an axiom is, or should be, it is self-evident. It goes without saying. But as we have also seen, although they are trivial in themselves, the judgments that derive from definitions can enable one to discover, by way of proof, logical bonds among the concepts that are designated by the defined signs. In the case of a demonstration on the basis of definitions of concepts, we are not merely joining content in a thought that can be variously analyzed, as is the case in the derivation of a theorem of logic from axioms, we are discovering logical bonds among the particular concepts that are designated by the defined signs. If in Freya's proof of Theorem 133 we were to replace each definiendum by its definians, then we would have a mere theorem of logic, one subject to many, many different analyses. The theorem would not be about the concepts of following in a sequence, belonging to a sequence, and being a single-valued function at all. It would not be a theorem in the theory of sequences any more than Euler's theorem would be a theorem about the exponential and trigonometric functions if the relevant signs were replaced by the various infinite sequences with which they are identified. It is only if we have definitions of concepts that we can forge logical bonds among those very concepts. And, we will see, only in that case can a proof extend our knowledge of those concepts by revealing their logical relations one to another. A definition involves both a complex sign for some concept, the definiens, and also a simple sign for that same concept, the definiendum, and these two signs, simple and complex, although they designate the same concept, express different senses. Thus the mathematical concepts of concern to Freya are, as we argued the figures of Euclidean geometry are, intelligible unities. They are whole of parts that are nonetheless not reducible to their parts. What a proof involving definitions shows is that both these aspects of concepts are essential, both the fact that the concept is one, an irreducible whole, and that it nonetheless has parts. The simple signs, the definienda, are necessary if one is to prove something about the defined concepts with which one begins. One needs the definiendum in order to prove something about the particular concept that is designated by that simple sign. But one needs also the definiens if the needed logical bonds are to be forged. Without the definientia it would be impossible to show that one's various defined concepts stand in logical relations one to another. Only a proof that begins with definitions can show that some logical relation obtains between particular concepts of interest. But it is equally true that only within a proof are definitions of any interest. Because definitions are stipulations, the identity judgments that correspond to them are completely trivial. Only definitions and proofs working together can yield something new. Only within a proof can the peculiar power that resides in definitions by their nature as stipulations regarding simple and complex signs be harnessed in ways that can extend our knowledge. In a slogan, proofs without definitions are empty, merely the aimless manipulation of signs according to rules, and definitions without proofs are, if not blind, then dumb. Only a proof can actualize the potential of definitions to speak to one another, to pool their resources so as to realize something new. But, again, not all definitions are fruitful in the sense of drawing new boundary lines. In particular, definitions that merely list a conjunction or disjunction of marks are not fruitful. Freya's own definition of belonging, because it is merely disjunctive, is not a fruitful definition in his sense. The concept of belonging is not an intelligible unity but only an accidental unity. It is not an irreducible whole of parts but instead a whole that can be reduced to its parts, either this or that. It is convenient to have a sign for belonging just as it is convenient to have a sign for less than or equal to. But nothing new is thereby introduced. Again, no new lines are drawn. Definitions that draw new lines do introduce something essentially new precisely because they draw new lines, which is to say that they cannot be reduced to their parts. What we need to see is that in all such cases the new lines are drawn precisely because and insofar as the concept in question contains an inference license. Consider, first, the concept of a dispositional property such as that of solubility. To say of some stuff that it is soluble is to say that if it were to be put in water then it would dissolve, that one can infer from the fact that the stuff is put in water that it will dissolve. Such a dispositional property clearly cannot be reduced to its parts. In other cases, and in particular in the case of mathematical concepts, the question whether a concept contains an inference license or is instead reducible to its parts is harder to answer. We saw this already in the case of the concept prime. If one thinks of its contents quantification ally, in terms of what is the case if the concept applies, namely, that no other number divides it without remainder, then it appears not to form an intelligible unity, an irreducible whole of parts. Instead it would seem to be a kind of accidental unity, one that is reducible to its parts, that this number does not divide it, and that number does not, and so on. If we instead think of its contents inferentially, in terms of what follows if the concept applies, namely, that if one is provided another number then it can be inferred that that number does not divide it without remainder, then it must be understood as an intelligible unity. So understood, the concept prime is not reducible to its parts, although it has parts, because these parts form an inference license. The whole is no more reducible to its parts than the whole that is the concept of solubility is. And this seems intuitively to be right. That a given number is prime is not an accidental fact about it, the chance convergence of a collection of singular facts about this number and that number. It is necessary that those facts hold, and that necessity is explained by reference to the inference license that, on the Phrygian conception of the concept prime, it contains. Concepts that contain inference licenses draw new lines in just this way, and for just this reason, they are intelligible unities, wholes that have parts but are not reducible to their parts. Because inference licenses are inherently conditional and constitutively general, the contents of all such concepts will be expressed in Begriffsschrift using Freya's conditional stroke and the concavity. Any mathematical concept that contains an inference license will have its content expressed in Begriffsschrift using the concavity and the conditional stroke, for the simple reason that an inference license is inherently conditional and also essentially general, something that can be applied in other cases. But as Freya's own definitions indicate, there are two interestingly different cases. In the case of being hereditary in a sequence and also in that of being a single-valued function, what is defined is a second-level concept. Both the concept hereditary in the F sequence and the concept single-valued take first-level concepts as arguments to give truth values as values. It is not objects that have the property of being hereditary in Freya's sense but instead concepts, and it is not objects but instead functions that are single-valued. And this is directly reflected in the definitions of these concepts, in particular, in the use of the concavity with lowercase German letters. The concavity with lowercase German letters is used to form expressions for second-level concepts, from the simplest, universally applicable formed from the concavity taken alone, through subordinate, which involves also the conditional stroke, to the even more complex concepts of being hereditary and being single-valued. The same is true of the mathematical concept of continuity. The concept of continuity is a second-level concept, the definition of which essentially involves the concavity with lowercase German letters. Point 13. The notion of following in a sequence is different insofar as it is a first-level relation. Assuming that the function is fixed, it takes two objects as arguments to yield a truth value as value. It is in this regard like a concept such as that of being soluble, of dissolving when immersed in water, the definition of which would be expressed in Freya's system of signs using the conditional stroke and Freya's Latin italic letters. To say of some object that it is soluble is to issue an inference license, that if that object is immersed in water then it will dissolve. But the relation of following, unlike the property of being soluble, cannot be defined using a simple conditional together with Freya's Latin italic letters. To understand why it cannot, we need to compare it not with a concept such as that of solubility but instead with, for instance, the logical relation of identity, which is also first level insofar as it takes objects as arguments to give truth values as values. In both the case of identity and in that of following in a sequence, and by contrast with the case of being soluble, the content is articulated in an inference license that concerns not what follows if an object falling under the concept meets some condition but instead what follows if some concept meets some condition. That is, a top-down specification is given, one that is marked in Freya's definition of following by the use of the concavity with an uppercase German letter. To set out the content of the first-level relation of following, Freya invokes an inference license concerning what may be inferred about concepts that satisfy some condition. In the case of identity, because it is a primitive logical notion in Freya's system, the inferential significance of this notion is not given in a definition but instead in an axiom. What the axiom, numbered 52 in Begriffsschrift, tells us is that it may be inferred given that X is identical to Y that any property that belongs to X also must belong to Y. That is, to say that X is identical to Y is to issue an inference license to the effect that it may be inferred from the fact that X has some property that Y likewise has that property, for any property you like. Although identity takes objects as arguments, and hence is a first-level relation, what an ascription of identity licenses is an inference about a concept, provided that a certain condition is met. Similarly, in the case of following in a sequence, to ascribe that relation to a pair of objects is to issue an inference license to the effect that if some lower-level property has a certain higher-level property, then it may be inferred that that lower-level property has some other higher-level property as well. Because in the case of following we are dealing with a definition rather than an axiom, the definiens makes this explicit in the use of the concavity with an uppercase German letter. To say that y follows x in the F sequence, to ascribe that relation to a pair of objects x and y, is to issue an inference license according to which, from the fact that some property of x is heritable, it may be inferred that if that property belongs to any result of an application of f to x, then y must also have that property. Alternatively, from the fact that some heritable property of x belongs to anything that is the result of an application of f to x, it may be inferred that y has that property. Again, just as with identities, the license applies not in the case in which some object satisfies some condition, but instead in the case in which some concept satisfies a condition, that is, falls under another, higher-level concept. To use the license that is contained in the definition of such a concept in making an inference, then, one needs to have already a judgment regarding some particular property that, for the first reading, it is heritable, and for the second reading, it is heritable and belongs to anything that is the result of an application of f to x. Frege does not use this rule in his proof, and it is easy to understand why. There are no objects to which the relation of following might be ascribed, thereby issuing the relevant inference license. One does not, in logic, ascribe first-level properties and relations to objects, but only higher-level properties and relations to lower-level concepts. What Frege does is to derive, in one case from the definition as a whole and in another from a theorem derived from that definition together with the definition of being hereditary, inference licenses regarding being hereditary, what may be inferred not if one object follows another object but if some concept has the higher level property of being hereditary. Having shown that some property is hereditary, the relevant inference is drawn, in one case directly to replace the condition that f with the weaker condition that x follows y in the F sequence, and in the other to derive the theorem that licenses such a replacement. In these cases, and only in these cases, it is a definition that, directly or indirectly, supplies the rule licensing the inference, the rule according to which to reason, as such a rule contrasts with a premise from which to reason. In every other inferential step of the proof of Theorem 133, the rule is instead some axiom or theorem of Part 2.14. In Section 7.1 we distinguished between two forms of reasoning that seem superficially to have the same form, namely, detachment, insofar as in the one case the inference really is by detachment, that is, it is of the form A on condition that B, but B, therefore, A, and in the other it is governed by a rule that although it can be applied in the given case is essentially general, available to be applied also in other cases. Frege's rules of inference, as codified in his axioms and derived theorems in Part 2, are all essentially general in their use in Part 3. Although Frege in his practice employs not the rule itself but instead a particular instance of the rule, which effectively reduces the inference to detachment, we can, as we in fact did, instead treat those axioms and theorems as rules properly speaking, that is, as inference licenses that warrant the particular inferences that are made. And this same point, we saw, applies also in the case of two premise inferences by some form of hypothetical syllogism. In some cases one has a straightforward application of the rule of hypothetical syllogism. If A on condition that B and B on condition that C, then it may be inferred that A on condition that C. But in other cases, the premise that A on condition that B is instead something essentially general, a rule or inference license that can be applied also in other cases. Joins that are made in accordance with our general strategy are instances of the first, straightforward application of hypothetical syllogism. The strategy is to modify the identities corresponding to definitions in various ways until they share content as required by the rule of hypothetical syllogism. What superficially appear similarly to be joins by hypothetical syllogism but involve a theorem derived from the definition of following in a sequence are crucially different insofar as in these cases the major takes the form of a rule that can be applied also in other cases. It is just these two essentially different sorts of cases that explains, we will see, why it is that Freyas singles out his definition of following in particular as fruitful despite the fact that both being hereditary and being single-valued also contain inference licenses. All three definitions involve Freyas sign for generality and hence draw new boundary lines, that is, they are fruitful in Freyas sense. But there are also essential differences between the definition of following, on the one hand, and the definitions of being hereditary and being single-valued, on the other, differences that are reflected in how they can be employed in proof. We have seen that it is important to distinguish between three levels of understanding one might have in relation to Freyas proof of Theorem 133. At the first, most basic level one can discern only the rules that are applied at each step takes the form of a detachment and is merely truth functional. From this perspective there is no significant difference between the derivations of Part 2 from axioms and the derivations of Part 3 from definitions. At the second, more advanced level of understanding one can discern a general strategy in Freyas proof of Theorem 133, one that involves distinguishing between linear, essentially one premise, inferences and two premise joining inferences that combine content from two or more formulae. This strategy, we saw, fully explains the proof that following in a sequence is hereditary. It also, though we did not show this, sufficiently explains the proof that belonging to a sequence is hereditary. But, as we saw, this strategy does not fully explain the proof of Theorem 133. Some steps of that proof do not use hypothetical syllogism to join two chains but instead use the definition of following in a sequence to form an inference license regarding what follows from something's being hereditary in a sequence. Unlike the joins that are explicable by appeal to our general proof strategy, a strategy that constitutively involves definitions, and in particular definitions that are fruitful in Freyas sense, that contain inference licenses in their definitions, but makes no essential appeal to any specific definitions. The inferential steps that involve an inference license furnished by the definition of following in a sequence are possible at all only because that definition contains an inference license in the definitions that concerns not objects but instead concepts. Any definition that involves both the concavity and the conditional stroke in its expression contains an inference license. And any such definition, by contrast with one that is disjunctive such as that of belonging, is amenable to our general proof strategy. Point 15. But again, the definition of following in a sequence is used differently insofar as it provides not a ground but instead a bridge, that is, the needed inference license at certain crucial steps in the proof. These steps that involve inference licenses derived from the definition of following in a sequence thus distinguish the proof of Theorem 133 even from, say, the proof that following in a sequence is hereditary in that sequence, or indeed any proof that proceeds in accordance with the general proof strategy. Should we then say that it is just those steps that enable an extension of our knowledge in the one case, that of Theorem 133, but not in the other, that of, for example, showing that following in a sequence is hereditary in that sequence, which involves only the general proof strategy? In the course of a proof such as that of Theorem 133, the simple, defined signs are needed if what is to be established is to be unequivocally about the concepts of interest, but their definitions are needed if anything about those concepts is to be established. Here, as already noted, we have something new that is made possible only in light of definitions, that is, judgments that involve, on the one hand, a simple sign, the definiendum, and on the other, a complex sign, the definiens, that exhibits the inferentially articulated content of the relevant concept, the sense through which we know it. In this case, and only in this case, content that is derived ultimately from two different definitions, if it can be brought to be identical in the two cases, can be used to reveal a logical bond between the concepts designated by the defined signs. That it is these concepts and no others that are joined is determined by the defined signs,
That they can be joined is made possible by the fact that the contents of those signs are also given in various complex expressions, expressions that are variously analyzable. But we know also that only fruitful definitions that draw new lines, the expression of which require employing the concavity, can be the basis for ampliative deductive proof. Not only the definition of following in a sequence but also Freya's definitions of being hereditary in a sequence and of being a single-valued function would seem, then, to be fruitful in Freya's sense. As marked by the presence of Freya's concavity in their expression, the latter two definitions, like that of following in a sequence, contain inference licenses about what may be inferred given that certain conditions are satisfied. These licenses are not used as such in the course of the proof of Theorem 133, nevertheless, the fact that the definitions have this feature is not irrelevant to the proof. Definitions that contain inference licenses, and so involve the concavity together with the conditional stroke, are alone of a form suitable for use in reasoning according to our general strategy of linear and joining inferences. It is because, in particular, the definitions of being hereditary in a sequence and of following in a sequence take the form of generalized conditionals that our general Begriffsschrift strategy of linear and joining inferences can be applied in this case to show that following in a sequence is hereditary in that sequence. No definition that was not of that form, that did not contain an inference license, could be used to join concepts according to that strategy. Our general proof strategy for Begriffsschrift works only because and insofar as the definientia of one's definitions take the form of an inference license. But again, although any proof from definitions according to our general proof strategy can reveal something interesting about the defined concepts, Freya indicates that his definition of following in a sequence is unlike the definitions of being hereditary in a sequence and of being a single-valued function, that only it is fruitful. And it is Theorem 133 that he says is ampliative, not any of the subsidiary theorems that are proven along the way. But if the proof of Theorem 133 is ampliative in a way that the proof that, say, following in a sequence is hereditary in a sequence is not ampliative, then that can only be because in the latter proof, although essential use is made of the fact that the definientia contain inference licenses, those inference licenses are never used in the proof to license any inferences. Accepting the definition of belonging to a sequence, Freya's definitions in Part 3 do contain inference licenses, as we saw. But, again, only in the case of following in a sequence is such a license used as a license in the proof. And even in this case it is not the license that the definiens contains that is used but instead other licenses that are derived from the definition as a whole. We saw that the definition of being hereditary in a sequence contains an inference license, and because it does, to ascribe that property to some concept is to issue an inference license regarding that concept. To say, for example, that being a positive whole number is hereditary in the successor sequence is to issue an inference license regarding being a positive whole number to the effect that if something is the successor of a positive whole number then it may be inferred that that thing is also a positive whole number. Alternatively, that if something is a positive whole number then it may be inferred that any of its successors must also be positive whole numbers. The concept prime should similarly be construed as containing an inference license according to Freya. To say that a number n is prime is to issue an inference license to the effect that if some number x is not equal to n then it may be inferred that x will not divide n without remainder. 17 In both cases, in order actually to draw the relevant inference, to use the license as the license it is, one needs something on the basis of which to reason. The relevant condition must be satisfied, in the one case by something that is a successor of a positive whole number, and in the other by some number greater than 1 and not equal to n. Nothing like this happens in Freya's proof of Theorem 133. Although he shows that following in a sequence, belonging to a sequence, and what we have called connectedness are all of them hereditary in that sequence, thereby issuing an inference license in each case, no instance satisfying the condition of that license is available as the premise from which to draw an inference according to that license. What does happen in the proof is that something is inferred about the concept that has been shown to be hereditary, and that inference, we have seen, essentially involves the definition of following in a sequence. The rule that provides the bridge that takes one from the claim that some property is hereditary in the F sequence as ground to a conclusion about that property derives from the definition of following in a sequence. Notice further that the other examples that Freya cites as fruitful, namely, that of continuity and of a limit, are not like the definition of following in this regard but are instead like the definition of being hereditary. They are second-level concepts, the definitions of which involve the concavity with lowercase letters. Because they contain inference licenses and hence take the form of generalized conditionals, they can be used in inferences that follow our general strategy of linear and joining inferences. But because the inference licenses they contain concern what follows if some object satisfies some condition rather than what follows if some concept satisfies some condition, they could not be used as Freya uses his definition of following in a sequence in the proof of Theorem 133, they could not supply an inference license for any step in any mathematical proof. But if that is right, then we need to distinguish two cases that Freya does not distinguish. In the one case, the definition, because its definiens has the form of a generalized conditional, can figure in a proof that proceeds according to our general strategy of linear and joining inferences and reveals thereby that various defined concepts have various logical properties and relations. Many proofs in mathematics are of this general form. The other case is more interesting insofar as the definition is supplying not merely fodder for an inference, that is, premises from which to reason, but instead the means of inference, a license or rule according to which to reason. In this case, it will be suggested, there is an especially clear sense in which although the definitions provide everything necessary for the proof, nonetheless, the conclusion is contained in the definitions not implicitly but only potentially, a potentiality that is actualized only by the course of proof. Freya claims that in the case of a fruitful definition, one that draws new boundary lines, that is, contains an inference license, what can be inferred from it cannot be inspected in advance, that here, we are not simply taking out of the box again what we have just put into it. In a derivation involving fruitful definitions that are not used to derive inference licenses but instead merely provide premises for inferences, say, by hypothetical syllogism, there seems to be at least some sense in which what can be inferred can be inspected in advance. Indeed, our general strategy involving linear and joining inferences already suggests this. One can, in that case, simply read off the theorem one is trying to prove at least some of the intermediate steps that will be needed along the way. The problem of finding the path that will take one from the starting points to the desired theorem is not, in light of the general strategy, essentially different from that of finding the proof of, say, Theorem 51 from axioms. There are important differences between the two cases because only in the one case is one proving based on definitions and indeed fruitful definitions and hence can employ the general strategy to show how things stand with those defined concepts. But there is also, as Freya indicates, an important distinction to be drawn between a derivation from definitions that employs only the general strategy and one, like that of Theorem 133, that also uses a definition to derive an inference license that is needed in the proof. Because in the latter case the definitions are not merely supplying the premises for inference but also rules according to which to reason, one cannot in this case just see based on the structure of the relevant formula what may be inferred. Here no general strategy is possible because what may be derived depends in particular on what rules of inference may be inferred from the particular definitions with which one is actually working. In the case of a proof involving inferential steps that are licensed by a rule derived from a definition, although one has already in the definitions everything that is needed to derive the desired theorem, it is in an important sense not merely by logic that the theorem is derived from the definitions as it is merely by logic that one proves a theorem from definitions using our general proof strategy of linear and joining inferences because some steps are licensed not by rules of logic but instead by rules derived from a definition or definitions. The definition in this case does not merely provide the matter for inference, the beams to be combined and recombined. It gives one the power to draw an inference that could not otherwise be drawn, a power that is exercised in the course of the proof, in one's use of the rule actually to draw inferences. It is in just this sense that in a proof such as that of Theorem 133, By contrast, not only with Freya's Part 2 derivations but also with any proof from definitions that requires only our general strategy, the conclusion is contained only potentially in the definitions with which one begins, as the plant is contained in the seed. Only the actual course of proof employing the rule contained in the definition can realize the potential or power that is contained in that definition. Point 18. Perhaps it will seem that this cannot be right given that, as Freya himself says, surely the truth of a theorem cannot really depend on something we do, when it holds quite independently of us. Indeed, Freya makes the remark in the context of a discussion of the status of Euclid's postulates aimed at correcting the misimpression that postulates are somehow essentially different from axioms. A postulate is not to be seen as a rule governing the actual drawing of lines but instead refers, Freya thinks, to an objective conceptual possibility. Our postulate cannot refer to any such external procedure. It refers rather to something conceptual. But what is here in question is not a subjective, psychological possibility, but an objective one. So, Freya concludes, the only way of regarding the matter is that by drawing a straight line we merely become ourselves aware of what obtains independently of us. In a proof, whether in Euclid or in Freya, the truth that is derived obtains independently of the activity of writing, independently of drawing lines in a Euclidean diagram and of writing theorems in Begriffsschrift. Nevertheless, as Freya indicates, the discovery of that truth is not in the same way independent of the activity of writing. Demonstrations extend our knowledge not by creating truths but by showing what can be derived, and hence known, on the basis of given starting points. The possibility of such a showing is an objective possibility. Nevertheless, the showing is needed if we are to come to see what is in this way available to be seen. 19. It is the proof, the actual chain of reasoning, of inferring based on acknowledged truths, that puts one in a cognitive relation of knowing to that which is proved. A related concern arises in light of the status of definitions as stipulations. If a definition is merely a stipulation, then it can seem that a conclusion derived from definitions is not properly speaking an objective truth, or at least not a very interesting objective truth but merely something provable given the stipulation. But this too is mistaken. Although a definition is a stipulation, as Freya says, it is also, along another dimension, something about which one can be right or wrong. One cannot be wrong to stipulate that some newly introduced sign is to have the same meaning as some other collection of signs. But one can be wrong to think that one has in that collection of signs set out the inferentially articulated content of some concept. A concept, which is the Bedeutung of a concept word, is something objective. It is not up to us to decide what concepts there are in mathematics and logic. Because it is not, one's proposed definition can fail to designate any concept. It is, then, a fully objective matter what logical bonds actually obtain among concepts. We can make mistakes, even in mathematics and in logic. In particular, we can think that we have a proof of some theorem when in fact, as we may eventually discover, the conceptions on the basis of which the proof proceeds are flawed. Judgment, conceived following Freya as an acknowledgement of the truth of a true thought, can succeed only if the relevant thought is true, and inference similarly, which aims to acknowledge a truth on the basis of another truth, can succeed only if the ground of the inference is true and the passage is legitimate. But if so, then it can happen that although it might seem to a thinker that a logical bond among concepts has been revealed in the course of a proof such as Freya's, in fact it has not. The possibility, or impossibility, of showing that those bonds obtain is not in any way dependent on the proof, and it is this possibility, or impossibility, that ensures that even deductive reasoning from definitions is answerable to something outside of it. One can extend one's knowledge by deductive reasoning on the basis of definitions because the truth that is revealed in the proof is in this way independent of what we do, both what we do in stipulating in a definition and what we do in drawing an inference as licensed by some definition. Freya claims that his proof of Theorem 133 is ampliative despite being strictly deductive, that is, truth-preserving, and that definitions of the sort that he describes as fruitful can in general provide the basis for ampliative deductive proofs. We have seen that any definition that involves his conditional stroke together with the concavity would seem to count as fruitful in Freya's sense. But we have also seen that there are two very different cases. Definitions of second-level concepts such as that of being hereditary or being continuous involve the concavity and lowercase German letters, and cannot be used in a proof to supply an inference license. They can figure only in proofs that follow something like our general proof strategy. In other cases such as that of following in a sequence, the formulation of the definition requires using instead the concavity and uppercase German letters. Such a definition can thus supply an inference license that can be applied if some concept has the relevant property and hence can be employed in a proof, even in one that is strictly logical or mathematical. Freya's proof of Theorem 133 involves just such an inference license, indeed, more than one, all derived from the definition of following in a sequence. And we suggested that the proof is clearly ampliative for just this reason. Does it follow that proofs that employ only the general proof strategy of linear and joining inferences are not ampliative, that in such cases, for all one's toing and froing one never leaves the same spot? This seems too strong. We need to recognize two different cases, both of which yield judgments that are ampliative despite being the result of purely deductive reasoning. Definitions of concepts that draw new lines, we have seen, are distinctive in having inference licenses in their definientia. Concepts of this sort are intelligible unities, wholes of parts that are nevertheless not reducible to those parts. Any conclusion that is ampliative is likewise an intelligible unity, now at the level of the proposition rather than at the level of a concept. Both conclusions achieved by using our general strategy for reasoning from fruitful definitions and conclusions that also use an inference license derived from a definition are intelligible unities in this sense. They are necessary but not merely explicative. Now we need to apply the notion of an intelligible unity not only at the level of concepts and at the level of the proposition but also at the level of the whole proof. A proof such as that employing only the general strategy of linear and joining inferences is a kind of essential unity, because it employs only laws of logic in moving from one proposition or propositions to the next. There is a sense in which the whole is prior to the parts. The proof as a whole is not an intelligible unity but instead an essential unity. It is just this that gives one the impression that in this case for all one's toing and froing one does not really leave the same spot. The proof, the reasoning, is analytic, even though in light of the definitions, and the way the definitions enable one to join defined concepts in judgments, the conclusion of the proof is ampliative. Only in the case of a proof such as that of Theorem 133 are we dealing with intelligible unities at all levels, at the level of concepts, at the level of propositions, and at the level of the proof as a whole. In this case the conclusion is not merely by logic because some of the steps are licensed not by a rule of logic but by a rule derived from a definition. The step is necessary and truth-preserving, in light of the definition, but it is not analytic in the way that an inference warranted by a law of logic is. The proof is a whole, a unity, because its steps are necessary, deductively valid. But because as some of its steps are not logically necessary, the proof also has real parts. It is not reducible to its parts as for instance a step of inductive reasoning is insofar as in this case the relation between the premises and the conclusion is not necessary, not deductive but it nonetheless has recognizable parts because not all the steps follow by logic alone. The proof is in this case an intelligible unity, a whole of parts that is not reducible to its parts. And that is precisely its charm. Not only does it give one new knowledge in the form of the conclusion, it also gives one a new sort of proof strategy, one that can be tried in other cases. Point 20. 8.4 Freya's logical advance. Natural language, we have seen, is constitutively object involving, sensory, and narrative. The ancient notion of a term, what things are called, further reflects this in its failure logically to distinguish, as we today find natural, between referring and predicative expressions. This is not merely a point about language. The world as it first comes into view is a world of things, paradigmatically living things, with their own proper natures and powers. Relative to this, our first understanding of reality, Early modern mathematics and physics provide a radically transformed vision of the most fundamental nature of reality, and with it the idea of a concept that can be grasped as the concept it is wholly independently of any object to which it might be applied. This transformed vision is furthermore taken to be the truth lying behind the appearances of everyday sensory experience. What we have here distinguished as two profoundly different modes of intentional directedness on reality, namely, that afforded by the natural languages into which we are first acculturated and through which we first become rational animals at all, and that afforded by the symbolic language of arithmetic and algebra first developed by Descartes, were distinguished instead as a false or merely apparent conception of reality as contrasted with the true, mathematically described nature of reality. Thus, it came to seem, as is explicit in Descartes' Meditations, our cognitive access to reality is not by way of perception but by way of thought and acts of will by which we assent to our clear and distinct ideas. Inevitably, this dogmatic rationalism gave way in turn to a Humean skeptical empiricism. And only with Kant were the difficulties resolved, though at a price. We saw in Chapter 4 that in Kant's critical view intuitions through which objects are given and concepts through which those given objects are thought are to be distinguished logically, as singular and general, but also metaphysically, as that to which we are essentially receptive or passive and that with respect to which we are active through the self-activity of spontaneity, and finally ontologically, as matter and form. Kantian intuitions are purely referential and have no descriptive or other cognitive content. And Kantian concepts are merely predicative, they cannot give objects but only provide ways of thinking about objects otherwise given. This distinction is furthermore quite explicitly a posit or hypothesis of Kant's critical philosophy, one that is introduced in order to explain our capacity for knowledge. We are simply told in the introduction, by way of a preliminary, that there are two stems of human cognition, which may perhaps arise from a common but to us unknown root, namely, sensibility and understanding, through the first of which objects are given to us, but through the second of which they are thought. The logical division of representations into intuitions and concepts is not discovered by reflection on thought and language but is instead hypothesized as part of an elaborate theory of cognition aimed at explaining the nature and possibility of our knowledge. Point 21. Kant's problem is to understand the necessary but not logically necessary truths of mathematics and physics, how, in his terminology, there can be synthetic judgments a priori. And as we did in the introduction, we can think of this problem from the perspective of Hume's division of knowledge into relations of ideas and matters of fact. We can understand Kant to be arguing that Hume's division conflates two very different distinctions, that between what is a priori and what is a posteriori, with that between what is analytic, by logic alone and merely explicative, and what is synthetic, not by logic and ampliative. Hume's relations of ideas are a priori and analytic, and his matters of fact are a posteriori and synthetic, that is, grounded in experience. And as Hume argues, knowledge of causal relations cannot be accounted for by appeal to either category. So, he concludes, such knowledge is wholly unjustified, that is, not really knowledge at all. But, Kant responds, although it is true that if a judgment is analytic then it is a priori and similarly true that if it is a posteriori then it is synthetic, it is not true that if a judgment is a priori then it is analytic or that if it is synthetic then it is a posteriori. There cannot be analytic judgments a posteriori but there can be synthetic judgments a priori. And that every event has a cause is a paradigm of a judgment that is synthetic a priori. Such a judgment is not logically necessary, hence not analytic but instead synthetic, but it is nonetheless necessary hence not a posteriori but instead a priori. In any synthetic or ampliative judgment, Kant thinks, one must go outside the concept of the subject to an intuition, whether pure, in mathematics, or empirical, in the case of a posteriori knowledge, in order to determine whether the predicate concept ought to be affirmed of the subject. Point 22. In an analytic, merely explicative judgment, the predicate concept is contained already in the concept of the subject and so must be affirmed of the subject on pain of contradiction. On Kant's account, the idea that a strictly deductive proof might extend our knowledge is utterly incoherent, a manifest contradiction. It is as much as to say that an analytic judgment is synthetic. And yet this is just what Freya claims, that his deductive proof of Theorem 133 is ampliative, a real extension of our knowledge. And just as Kant does in relation to Hume's division of all knowledge into relations of ideas and matters of fact, so we can see Freya doing in relation to Kant's division of all knowledge into analytic and synthetic. As Kant charges Hume with conflating two different distinctions, the analytic/synthetic distinction with the a priori/a posteriori distinction, so Freya reveals that Kant has similarly conflated what must be distinguished, namely, the explicative/ampliative distinction with the strictly deductive/involving intuitions distinction. It is true that if a judgment is merely explicative then it is strictly deductive and indeed by logic alone, and it is also true that if a judgment essentially involves intuitions of objects then it is ampliative. But the converse conditionals are not true. It is not true either that all deductive reasoning is merely explicative or that all ampliative judgments constitutively involve intuitions of objects. There can be no merely explicative judgments that essentially involve intuitions of objects, just as for Kant there can be no analytic judgments that are known a posteriori. But, Freya suggests, there can be deductive reasoning that is ampliative just as for Kant there can be synthetic judgments a priori. Kant's conception of the analytic/synthetic distinction is directly grounded in and made possible by his logical and metaphysical and ontological distinction between intuitions, through which objects are given in receptivity, and concepts, through which objects are thought through the spontaneity of the understanding. To understand Freya's further logical move beyond Kant, as it is enabled by developments in mathematics in the 19th century, we need to see that the Kantian opposition of concepts and intuitions is too crude, that it conflates two essentially different distinctions, that between Sinn and Bedeutung with that of concept and object. Whereas for Kant all cognitive significance, all being for a thinker, is through concepts, and all objectivity, all truth, lies in relation to an object or objects, either as given in sensory experience or merely with respect to their form in mathematics. Freya requires us to distinguish, on the one hand, between cognitive significance and concepts, which are the Bedeutung of concept words, and on the other, between objective significance and objects. As Freya understands it, the Sinn/Bedeutung distinction is orthogonal to that between concept and object. According to him, both concept words and object names both express senses and designate or mean concepts and objects, respectively. He writes in some comments on his distinction between Sinn and Bedeutung. It is easy to become unclear about this by confounding the division into concepts and objects with the distinction between sense and meaning, so that we run together sense and concept on the one hand and meaning and object on the other. To every concept word or proper name, there corresponds as a rule a sense and a meaning, as I use these words. Kant, we can see in retrospect, commits just the error Freya warns against. Kantian intuitions have Bedeutung but, independent of the involvement of concepts, they lack all cognitive significance. Intuitions without concepts are blind. Kantian concepts, correspondingly, express, or even are, free-gene senses, but independent of any object given in intuition they have no objectivity, no Bedeutung. Kantian intuitions are both of objects and the source of all objectivity, and Kantian concepts are at once predicates of possible judgment and that through which things have any and all cognitive significance to a thinker. But as Freya sees, not all objectivity lies in relation to an object and cognitive significance is not merely predicative. On Freya's view, again, both concept words and object names express senses, and so are cognitively significant, and both concept words and object names designate something objective, namely, concepts conceived as laws of correlation and objects, respectively. That not all objectivity lies in relation to an object is evident already in Descartes' mathematical practice. Although our first and most basic cognitive involvement in the world is essentially object-oriented and object-involving, we can and in early modern thought do achieve a fundamentally different intentional directedness on reality, one that is, as has already been suggested, fully realized only in the mathematical practice that emerged in the 19th century. Although Descartes' practice is, in intention, an exercise of pure reason, it is in the contemporary mathematical practice of deductive reasoning from the contents of concepts that we first see how this can be, and as well the respects in which mathematics as a science has always been about concepts rather than about objects. But if that is right, then we need also to draw a distinction that Frege did not draw. Whereas Frege holds that the Sinn/Bedeutung distinction is orthogonal to the division of concept and object, so that both object names and concept words both express senses and designate, respectively, objects and concepts, we will see instead that, although the Sinn/Bedeutung distinction applies to any sort of language, to language as such, the distinction between objects and concepts functions differently. It serves to demarcate two fundamentally different sorts of languages, namely, natural languages and mathematical languages. Point 23. A language in the sense of concern here is not merely a means of recording or reporting something of which one is antecedently and independently aware. Rather, it is the medium of our awareness, that through which we, as thinkers, rational beings, achieve any and all cognitive relation to reality. What Frege enables us to realize is that any such language must involve both sense, Sinn, and designation or meaning, Bedeutung. Language, that is to say, is inherently revelatory, at least in intention. By its nature as language it reveals or discloses something objective, some aspect of reality, Bedeutung. But language can be that, the vehicle of our cognitive awareness, only in virtue of expressing Frege sense. The words of natural language, for example, do not merely stand for or refer to objects and their properties and relations, they are also constitutively inferentially related. To have the use of a word of natural language, to grasp its sense, is not only to be able to apply it correctly, to know which things are called that, but also to be able to reason about such things and in virtue of such reasoning to have second thoughts. We saw already in Chapter 1 that to be rational, to have the power of knowing, is to have the capacity for second thoughts, where a second thought is not merely a change in what one takes to be so but instead a reasoned change of mind. It follows directly that the language into which we are acculturated, and which realizes us as the rational animals we are, must involve both referential relations to things that are called that and inferential relations belonging to the sense expressed regarding what is a reason for what. And although we learn these referential and inferential relations piecemeal in the course of our acculturation into language, eventually, it was suggested, they are synthesized into one whole that embodies a view of reality. The smallest unit of cognition on this account is not an object in its nature, as the ancient Greeks thought, nor is it the judgment, as Kant held. It is the whole inferentially articulated language. But Frege did not discover the Sinn/Bedeutung distinction, as contrasted with that of concept and object, by reflecting on natural language. Nor could he have. Much as the Kantian notion of a concept, as that notion contrasts with that of a Kantian intuition, is made possible by developments in early modern mathematics, so Frege's understanding of the Sinn/Bedeutung distinction as contrasted with that of concept and object is made possible by developments in mathematics in the 19th century. It was those developments that provided both the impetus for Frege's invention of his concept script and the crucial guide to how it must function. And it was Frege's subsequent reflections on the language that he had devised for reasoning from the contents of concepts in this form of mathematical practice that brought him explicitly to realize that the language he devised functions by directly expressing senses, by mapping in signs Frege thoughts that are variously analyzable into function and argument. In Begriffsschrift, and we will see, only in Begriffsschrift, are the Frege notions of sense and meaning manifestly different and distinct. Natural language involves both world referential relations and word inferential relations, and as such embodies a view of the world, of what there is and of how things work in the broadest sense. But there is in such a language no way clearly to demarcate the two. In natural language, sense and meaning are, as McDowell argues, inextricably combined. Point 24. This is due in part to the way the language comes about, due to the fact that it evolves in and through our interactions with salient objects in the environment as the biological and social beings we are. Through those interactions we acquire habits of thought, expectations about what will happen in what circumstances, and these coalesce as reasons as we become rational. Because these inferential relations are between words, more exactly, what they designate, sentences expressing such relations can take the same form as other, merely empirical or factual generalities. The only discernible difference between the two cases appears in the context of counterfactual reasoning or in claims of necessity, and often one just does not know what to say. We know, more or less, what it means to say that as R and must be Bs, that nothing could be an A without being also B, as contrasted with the merely contingent and accidental fact that all as are C. And there are some circumstances in which we have strong intuitions one way or the other, but as the language continues to evolve, what had seemed to be a matter of meaning, that is, an inferential relation codified at the level of sense, can be shown empirically to be false, and what is at first discovered as a matter of fact can coalesce into a relation of ideas. As Quine famously argued, there is no in principle distinction to be drawn here between judgments that are analytic and judgments that are synthetic. The sin/Bedeutung distinction is at work in the language, but not even a notional separation of the two is possible in the case of natural language. And because it is not, no one could discover the distinction that Freya discovered merely by reflecting on this case. The notion of free sense as that through which we are cognitively in relation to something objective, something about which we can have second thoughts, can be discovered only in relation to a very sophisticated and historically late form of mathematical language such as Freya's Begriffsschrift, within which to express senses. The distinction is manifest in Freya's language precisely because what formulae of that language directly map or trace is not truth conditions but inference potential, that is, sense as it contrasts with meaning. But once the notion of sense has been discovered, it can be seen also to apply to the case of natural language. When, for instance, McDowell says that concepts mediate the relation between minds and the world, what he means by concept is free sense. 25 As McDowell reads him, one of Kant's deepest insights is that our cognitive relation to reality is essentially mediated by concepts conceived as free senses. And there is some truth to this. 26 But, again, because in the case of our everyday intentional involvements in the world as enabled by our acculturation into natural language, sense and meaning are inextricably combined, one can discover the notion of sense and its constitutive role in language only in relation to a sufficiently advanced mathematical tradition, one that enables a language such as Freya's in which sense and meaning are not inextricably combined. Only after we have discovered and clarified the sin/Bedeutung distinction for the case of mathematics can we then apply it, as McDowell does, to the case of natural language and see it in play, however inchoately, in Kant's thinking. Nor does a mathematical language such as Freya's differ from natural language only in its clearly distinguishing between sense and meaning. The nature of meaning, Bedeutung, in the two cases is also essentially different. Natural language is, again, constitutively object-involving, sensory, and narrative. It reveals a world of perceptible objects, paradigmatically living beings with their characteristic natures and powers, properties, and relations. It follows directly that the concept words of this language, as much as its object names are object-involving, both sorts of expression snub-nosed, human, and sitting, as much as Socrates and Athens are what things are called. Natural language, that is to say, knows nothing of free concepts, which are laws of correlation arguments to truth values. The words of natural language do not have sharp boundaries to their application, and they cannot be defined on the basis of a few primitive notions in the way that mathematical words can. Natural language does not involve anything like a free concept, and mathematical language, correspondingly, knows no objects but only concepts, laws of correlation that have sharp boundaries, tertium non datur as Freya puts it. Thus, although any language involves both sin and Bedeutung, the concept/object distinction is not, as Freya thought, merely orthogonal to that distinction, but instead marks an essential difference between the natural languages that first realize us as rational at all and Freya's mathematical language that is an essentially late fruit of over 2,500 years of mathematical investigation. And again, one does not actually need Freya's language to do the sort of mathematics for which Freya's language is designed. One can grasp the senses through which mathematical concepts are disclosed without making essential use of any written system of signs, as most mathematicians working today do, and as any of us do insofar as we are able to understand the reasoning of a proof such as that to show that there is no largest prime. The problem for the mathematician is that without such a language it can be extremely difficult to communicate either one's understanding of those concepts or one's course of reasoning to a particular theorem. For the philosopher the difficulty is to understand how the mode of inquiry works, given that, without any written system of signs such as that Freya provides, one cannot see the reasoning at work in a public display. In a well-known letter to Husserl, dated May 24, 1891, Freya presents a little schema according to which propositions express senses, free gene thoughts, and designate truth values, proper names express senses and designate objects, and concept words express senses and designate concepts. And this notion of a concept, as the meaning, Bedeutung, of a concept word, is then related to the notion of an object that falls under that concept. As Freya remarks regarding this schema, with a concept word it takes one more step to reach the object than with a proper name, and the last step may be missing, i.e., the concept may be empty without the concept word ceasing to be scientifically useful. I have drawn the last step from concept to object horizontally in order to indicate that it takes place on the same level, that objects and concepts have the same objectivity. If, as I have suggested, both the concept words and the object names of natural language are object involving, that is, revelatory of objects with their properties and relations, and mathematical language instead discloses concepts with their properties and relations, Freya's schema is not quite right. There are no mathematical, or logical, objects, and the only concepts there are mathematical and logical ones. But there is something right both about the idea that concepts and objects have the same objectivity and about the idea that with concepts it takes one more step to reach the object. The only objects there are empirical objects, or more generally, empirical reality. This reality is directly revealed through the medium of natural language. But as we will see, if only in outline, in Chapter 9, empirical reality is also, though very differently, disclosed through the medium of mathematical language, and this involves two distinct steps just as Freya suggests regarding concepts. The concern of the mathematician is mathematical concepts. The task is to grasp them in their pure form and to understand their various logical properties and relations. Mathematicians do not, qua mathematicians, take the second step to objects, empirical reality. But physicists do, and in 20th century physics in particular, as it contrasts with early modern physics, the mathematics physicists employ directly discloses reality. Mathematicians discover objective truths about mathematical concepts and in so doing discover how things could be. Physicists, using those concepts, discover how things are. Point 27. Although both natural language and mathematical language are revelatory of reality, and as such involve both sense and meaning in Freya's technical sense, they are nonetheless very different insofar as natural language reveals sensory objects together with their properties and relations, and mathematical language directly discloses instead concepts together with their properties and relations, and only indirectly, in physics, discloses objects. This difference is further reflected in, for example, the fact that natural language is inherently narrative while mathematical language is not. Natural language tells of what happens, mathematical language, even in its use in physics, we will see, instead tells of what, in some sense timelessly, is. Natural language also has many words, none of which can be defined in terms of others and all of which are inferentially related to at least some of the others. A mathematical language such as Begriffsschrift by contrast has only a few primitive notions in terms of which all other concepts can be strictly defined. Those defined concepts are furthermore internally inferentially articulated, and it is on the basis of this internal articulation that relations of entailment between different concepts can be proven deductively. But the most significant and fundamental difference between the two sorts of languages, we will see, lies in what we can think of as the relative priority of Sinn and Bedeutung in each, which is in turn indicative of their respective relationships to our receptivity and spontaneity. Natural language is not invented or devised but rather evolves. It merely happens much as the living things that are the fruits of biological evolution merely happen. And any subsequent self-conscious attempts to change it must be taken up by other speakers if they are to succeed. Natural language belongs to no one in particular and answers to no one in particular. It is ours simply in the sense that we experience the world through it, and speak it together, thereby keeping it alive. And because we are in this way passive with respect to it, the reality it reveals has a kind of priority over the sense through which that reality is revealed. That is, as McDowell has argued, because thoughts are in this case object-dependent, where the relevant object is missing, the corresponding free gene thought must go missing as well. It follows directly that a subject may be in error about the contents of his own mind. He may think there is a singular thought at, so to speak, a certain position in his internal organization, although there is really nothing precisely there. Given how profoundly object-involving, world-involving, natural language is and must be, in cases in which we are under an illusion that there is something where there is nothing, the relevant thought is simply not available to be entertained because that thought is object-dependent as it is. In this case, thoughts without content really are, as Kant says, empty, that is, as McDowell glosses, they are not, in that case, really thoughts at all. Our capacity to know reality as it is revealed in and through natural language is an essentially receptive, passive capacity. The situation is very different in the case of mathematical language. First, mathematical language is invented or devised, it is self-consciously created and does not need to be taken up by others as a condition on its having been created. And again, this is a point not so much about any actual written language such as phrases, as it is about the grasp of mathematical concepts through senses that mathematicians can achieve, with or without a written system of signs within which to work. A solitary mathematician can develop important areas of mathematics. Those developments do not wait on being understood by others to be actualized as the mathematical advances they are. Similarly, for more than a century no one other than Freya understood Freya's language, and it could have happened that the earth and all that is on it was utterly destroyed without anyone else ever understanding it. The language would nonetheless be precisely the language that is at point 28. Furthermore, as has been repeatedly emphasized, Freya's language and the 19th century mathematics that inspired it are the culmination of over 2 millennia of intellectual work on the part of mathematicians. We are not, in other words, merely passive with respect to either. 19th century mathematics and a language such as Freya's do not just happen. They require devoted and sustained intellectual work. Freya claims in Grundlagen that often it is only after immense intellectual effort, which may have continued over centuries, that humanity at last succeeds in achieving knowledge of a concept in its pure form, in stripping off the irrelevant accretions which veil it from the eyes of the mind. To achieve knowledge of a concept in its pure form is to get the sense right, and given that we begin with an essentially sensory grasp even of mathematical concepts, a conception of number as a collection of units, of a circle as a two-dimensional plane figure, of addition as putting together, and so on, it takes real intellectual work, and we have seen revolutionary transformations, to rid our conceptions of mathematical concepts of this sensory content. An adequate mathematical understanding, and correspondingly, an adequate mathematical language, one that discloses mathematical concepts as they are, is thus an achievement of the highest order. It is an achievement of the spontaneity, the self-activity, of reason. It follows that in this case the notion of sense has a kind of priority insofar as we can discover in the course of our mathematical investigations that the sense through which we had taken ourselves to grasp some concept is confused in some way or even wholly mistaken. Freya's basic law V is an obvious example. The Begriffsschrift formula for that law does express an inferentially articulated free gene thought, even though, as Freya learned from Russell, it does not designate any truth value, either the true or the false. But it does express a thought. Indeed, it is only because it expresses a thought that one can discover that it designates no truth value. Were no thought expressed, one could not draw the inferences that reveal the problem. The harmony between thought and reality that is always already given in the case of natural language is in mathematics a very hard-won achievement. Developments in mathematics in the 19th century, and the language those developments inspired Freya to create, thus enable in turn a fundamental and profoundly transformative advance in logic, the discovery of the Sinn/Bedeutung distinction, as that distinction contrasts with the concept/object distinction. It is this distinction that we need in order to understand how it is that through the acquisition of language one acquires the eyes to see things as they are, literally so in the case of natural language and figuratively speaking in the case of mathematical language. In both cases, our cognitive access to something objective, Bedeutung, is mediated by our grasp of an inferentially articulated sense, Sinn. But, we have seen, there are also very striking differences between the two cases, beginning with the fact that what natural language reveals is a world of sensory objects with their properties and relations. Mathematical language discloses that same reality only indirectly, through mathematical concepts that are then applied in fundamental physics. What the mathematician is directly concerned with is not objects but instead concepts. Point 29. And in this case there really can be empty thoughts, perfectly contentful thoughts that have no truth values, that are neither true nor false. Thus, for Freya, as for the intuitionist, bivalence fails. One cannot in general infer from the fact that the thought is not true that its negation is true. It is only the negation of thoughts that are themselves false, that is, that have a truth value, and in particular the truth value false, that can be inferred to be true. In Freya's system of signs this is marked by the content stroke, much as affixing the judgment stroke aims to mark a thought as true, so affixing the content stroke to a collection of signs in Freya's language aims to mark a thought as truth evaluable, as having a truth value, either the true or the false. And as one can fail in one's attempt to acknowledge the truth of a thought, so one can fail in one's attempt to acknowledge even that a content is judgeable, that is, that it is true or false. One does so fail in attaching the content stroke to a thought that, like basic law V, is neither true nor false. Point 30. Bivalence fails at the level of thoughts for Freya because he recognizes, at least for the case of mathematics, that some perfectly well inferentially articulated thoughts are neither true nor false. Bivalence nevertheless holds for the case of concepts. Concepts, that is, mathematical and logical concepts, the only sorts of concepts there are, have sharp boundaries in the sense that they settle for every possible object as argument whether the concept applies or not. Hence, to discover in a particular case that we do not know what to say, or worse, that the concept appears both to apply and to not apply, just is to discover that we have not yet grasped the concept in its pure form. To say that the concept is objective is to say that it is there to be grasped, that we can get it wrong, as we may eventually discover, but also that we can get it right. 8.5 The achievement of reason. Freya's formula language of pure thought was not understood and has never before been used by anyone other than Freya. Nor has anyone since Freya attempted, so far as I know, to devise independently a language within which to reason from defined concepts in mathematics. Mathematicians seem, on the whole, to be quite content merely to report their reasoning. 31 In a way this is unsurprising, given that it is part of the self-understanding of practitioners of this form of mathematics that their work should be unconstrained by any particular sort of symbolism. The Kantian opposition of discursive and intuitive uses of reason may also be playing a role insofar as, at least on Kant's account in the first critique, reason in its discursive use can only be reported and is not essentially written in the way that reason in its intuitive use is. That this Kantian division of uses of reason, the one intuitive and the other discursive, has discouraged any attempt to devise a language such as Freya's is further indicated by the vehemence with which mathematicians for much of the 20th century eschewed any and all appeals to diagrams in their work. 32 Of course, the use of symbols was not frowned upon in the same way, but that may well have been because symbols were not conceived constructively, as formulating content on the basis of which to reason, but were instead taken merely to abbreviate words. But although unsurprising, the fact that no one has taken up the task of devising a mathematical language for this new form of practice that first emerged in the 19th century is also significant insofar as it reinforces the idea that this form of mathematical practice really is by reason alone. Even Freya did not devise his language first and foremost as a language for use by the working mathematician. He devised his language in order to show that arithmetic is merely derived logic. As Freya makes clear in the preface of Begriffsschrift, it was the demands of the project of logicism, not those of the new mathematical practice, that provided the impetus for Begriffsschrift. So that something intuitive etwas anschauliches could not squeeze in unnoticed here, it was most important to keep the chain of reasoning free of gaps. As I endeavored to fulfill this requirement most rigorously, I found an obstacle in the inadequacy of the language. Despite all the unwieldiness of the expressions, the more complex the relations became, the less precision which my purpose required could be obtained. From this deficiency arose the idea of the conceptual notation presented here. For the first time in its 2,500-year history, mathematics simply does not need a system of written signs within which to do its work. And the reason it does not is that with this form of mathematical practice the power of reason as a power of knowing is, for the first time, fully achieved. We have seen that Freya's most fundamental logical advance was the discovery of the Sinn/Bedeutung distinction, more exactly, the discovery that we need to distinguish, in a way that Kant did not, between the notion of a concept as the Bedeutung of a concept word and the notion of sense, what is expressed by various expressions in a language, on the one hand, and between the notion of Bedeutung, which is the notion of something objective that is designated by an expression, and that of an object, on the other. But we have seen that we also need to distinguish, as even Freya did not, between natural language, which is revelatory of a world of sensory objects with their natures and powers, their properties and relations, and mathematical language through which concepts, with their properties and relations, are disclosed. Natural language is, furthermore, immediately revelatory relative to mathematical language. Although it constitutively involves free gene sense and is essentially inferentially articulated, it is nonetheless immediately revelatory insofar as it takes no work on our part to have things revealed to us in our experience of the world. In the case of natural language, there is always already a pre-established harmony between the knower and the known, between thought and reality. Although fallible and capable of improvement, our powers of perception, which we have as the rational animals we are, just our capacities to take in how things are. 33 The case of mathematics is very different insofar as it must take, serious intellectual work and real intellectual growth and maturation in order for us, the community of inquirers, to achieve knowledge of mathematical concepts in what Freya describes as their pure form. The power of reason as a power of knowing, unlike the power of perception as a power of knowing, is not and cannot be there from the beginning, a power we have as the rational animals we are. It can only be achieved in historical time through our self-conscious efforts to understand and to know what is there to be understood and known. We have, as the rational animals we are, the power rationally to reflect and the ability to discover on reflection that what had at first seemed true is not really true. This critically reflective power is, however, not in itself a power of knowing because and insofar as it has and needs something given on which to reflect. This does not imply that there is something merely subjective about the whole enterprise as we are wont to think. The pre-established harmony of thought and reality that is enabled by natural language is real, and it follows from that harmony that thoughtful, critically reflective people will mostly, though not infallibly, get things right. McDowell forcefully makes this point for the case of ethics, what is good, in two sorts of naturalism. There is, as he argues, no addressing the question in a way that holds that apparent layout in suspense, and aims to reconstruct its correctness from a vantage point outside the ways of thinking one acquired in ethical upbringing. But the point holds equally for the case of intellectual virtue concerned with what is true in our experience of things. One's eyes are opened both to what is true and to what is good in the course of one's upbringing, both to their value as reasons and to the particular reasons that really are reasons in each case. In both cases, only what McDowell has taught us to think of as a modest account, always already situated in the midst of an understanding of what is true and good, is possible. 34 Reason has in this case no power to discover through its own unaided resources, independent of what is given in experience, either what is true or what is good. In ancient Greek thought, perception provides the principal modality of knowing, and we saw that this is true for Plato no less than for Aristotle insofar as knowledge of the forms is for him a kind of seeing with the mind's eye. Knowledge in both cases is grasp of a thing as what it is, in its nature. And this is so even in mathematics, we saw, insofar as it is constructions that serve as the paradigm of what is known in ancient Greek mathematics. With Descartes, there is a complete reversal. The form of intellection that is involved in Descartes' new mathematical practice becomes the model even for our perceptual engagement with things. But although the power of reason as itself a power of knowing makes its appearance here, it nevertheless still needs something given on the basis of which to be exercised, namely, clear and distinct ideas. And because it does, what in Descartes is held to be a power of knowing becomes in Kant's new form of philosophical practice a power of critique by which to discover the limits of our power of knowing as a necessary corollary of the conditions of the possibility of knowing. Not only does reason have no contents of its own, it is simply impossible on Kant's account of deduction, that is, of purely logical inference that by reason alone one might extend one's knowledge. 35 It is precisely because it is not by reason alone but by reason guided throughout by intuition that judgment in mathematics can be synthetic, can constitute a real extension of our knowledge on Kant's account. The question whether by reason alone knowledge might be possible, whether, that is, reason might itself, as pure reason, be a power of knowing appears, in the wake of Kant's critical philosophy, to have two distinct parts, one regarding the contents of knowledge and another addressed to how by deductive reasoning one might extend one's knowledge as contrasted with merely making explicit something that otherwise remains only implicit. And the two questions are distinct because, it is thought, logic concerns form rather than, as contrasted with, content. Because what concerns only form cannot teach us anything about contents, it is clear on the Kantian conception of logic as formal that deductive reasoning cannot yield anything new that was not contained already in one's starting points, however obtained. The problem of truth and knowledge is completely intractable in the setting in which logical form is set over against content and so truth. 19th century mathematical practice, as is made manifest in a proof such as that of Freya's Theorem 133 written in Begriffsschrift, shows that this Kantian opposition of logical form and content as it matters to truth which is needed in the wake of Descartes' revolution in mathematics in the 17th century has been wholly superseded. As Freya himself says of his proof of Theorem 133. We see in this example how pure thought Rein Denken is able, all by itself, to produce from the content which arises from its own nature judgments which at first glance seem to be possible only on the grounds of some intuition. Concepts and judgments that had seemed to have an eliminable intuitive content are revealed to be purely logical. Both the concepts Freya defines and the means by which Theorem 133 is established belong to reason alone, and yet we have seen that there is a clear sense in which the derivation is ampliative, an extension of our knowledge. The conclusion, Theorem 133, is contained in the definitions not merely implicitly but potentially. Much as an equilateral triangle is potential in a given straight line within the context of Euclid's system insofar as it can be constructed on that line, so Theorem 133 is potential in Freya's definitions within the context of the rules of logic insofar as it can be derived from those definitions, though not solely according to those rules. Because the concepts of fully modern mathematical practice are inferentially articulated in the sense of containing inference licenses as part of their contents, they, at least some of them, have the potential to be used as such in a proof, and this means, as Freya says, that what may be inferred from them cannot be inspected in advance. Not only the definitions we formulate and the conclusions we draw, but even the proofs themselves, we have seen, can be intelligible unities, unities that are necessary without being essential, without, that is, being such that their wholes are prior to their parts. And, I have already suggested, supplementing Begriffsschrift with primitive signs of arithmetic to enable the formulation of the contents of other concepts of mathematics would not significantly change things. In particular, it would not render either the contents or the reasoning any less pure, because and insofar as those primitive signs and those concepts are likewise wholly inferentially articulated. Although we begin, and must begin, with essentially sensory conceptions of concepts in early mathematical practice, over the course of history that sensory content is progressively stripped away until eventually we achieve concepts of reason, what Kant calls ideas. We could not begin with such concepts, but we can, through our intellectual work, our strivings for truth, eventually achieve them. And unlike such ideas as they appear in Kant's philosophy, these ideas are fully contentful. They provide the subject matter for the science of mathematics. The power of pure reason as a power of knowing is a fallible capacity for judgment and inference regarding the inferentially articulated concepts of mathematics and logic. It is a priori in the sense that in order to know in mathematics one cannot rely on testimony, either the testimony of one's own senses or that of another person. One must recognize for oneself, through the use of one's own reason, that a thought is true. One must acknowledge the thought as true in an act of what we have called expressive freedom, and except in the case of an identity judgment corresponding to a definition, one can do this only by way of an inference from something the truth of which one acknowledges by means of a rule that one likewise recognizes to be valid. And one can be mistaken on either or both counts. If one is not mistaken, if all the relevant concepts have come to be known in their pure form through one's grasp of senses that clearly display their inferentially articulated content, and if one has a correct proof, that is, has performed a valid series of inferential steps from the starting points to the theorem, then one's acknowledgement of the truth of that theorem puts one in a cognitive relation of knowing to the truth in question. There is thus both an active and a passive moment in the case of such judgments. The moment with respect to which one is passive is the moment of truth. The thought that one aims to acknowledge as true must actually be true for the judgment, the acknowledgement, to succeed. But the truth of the thought, although necessary, is not sufficient for knowledge. The potential of the thought to disclose an aspect of reality is fully actualized only in one's act of acknowledgement. One must do something, draw the relevant inferences, if one is to achieve knowledge of a theorem in mathematics, or logic. One cannot know what is not true any more than one can see what is not there, but, nor does one know what one only entertains even as very likely to be true. So long as what one has is only a conjecture, one has no knowledge. In mathematics, and in logic, knowledge is achieved by a course of inquiry, and in particular, a proof, starting with adequate, fruitful definitions. To realize that the science of mathematics neither has nor needs any given foundation on which to build is to recognize that it is not the products of this science but instead the practice of it that holds the key to an adequate understanding of how this science works as a mode of inquiry. It is the activities of inquiry, the analysis of concepts, the formulation of definitions, the axiomatization of the rules of inference involving the primitive notions, the formulation of theorems and their proofs that provide the checks and balances that, although they do not guarantee that one will get things right, enable one to improve one's grasp of concepts and correct one's proofs. Because this practice is constitutively self-correcting through the processes of proof and refutation, and judgment is an act of acknowledgement understood as an exercise of expressive freedom, the power to make manifest the otherwise latent structure of reality, successfully to make up one's mind through this critically reflective activity of inquiry is to come to be in a cognitive relation of knowing to the relevant bit of reality. And no matter how confident one is that one has gotten things right, it can always turn out that one was mistaken. The power of pure reason as a power of knowing is, like any power, fallible. It can get things wrong. But it can also get things right, that is, come to know how things are in reality. In mathematics, the reality in question is not, of course, empirical reality, how things actually are, but instead how they could be. For reasons that will become clearer in Chapter 9, the concepts of mathematics, insofar as they are concepts of pure reason, are concepts of how empirical reality can be. As employed in fundamental physics, they reveal how physical reality most objectively is, the same for all rational beings. The concepts of mathematics are not, then, in the world in the way that the entities fundamental physics studies, including even the space-time of general relativity, are in the world. 36 Nor is it correct to describe them as mental entities, though we can, through our grasp of the relevant senses, come to be in a cognitive relation of knowing to them. They are fully objective insofar as they are the possible ways things could most objectively be, the ways any rational being might in time come to recognize as the possibilities of things. We have our account of how reason, pure reason, is realized as a power of knowing over the course of our intellectual history. And I have suggested that this account further enables us to understand how reality, the same reality that is investigated in fundamental physics, is revealed in our everyday perceptual experience. We can now clarify this further by reflecting again on the notion of a power that was invoked in Chapter 1. A power, we said, is a fallible capacity to achieve some end, for instance, in perception to take in, see how things are. Powers, so conceived, are successfully exercised only in propitious circumstances. The ancient Greeks could not quite get this notion of a power into view, at least for the case of knowing, and they could not because they understood the unity of the knower and the known as an essential unity, the parts of which are intelligible only in relation to the whole. Because the relationship of knower and known is in this way constitutive, according to the ancient Greeks, it is unintelligible that one might fail, even if only on occasion, to get things right. As Bernier explains, the problem which typifies ancient philosophical inquiry in a way that the external world problem has come to typify philosophical inquiry in modern times is quite the opposite. It is the problem of understanding how thought can be of nothing or what is not, how our minds can be exercised on falsehoods, fictions, and illusions. The characteristic worry, from Parmenides onwards, is not how the mind can be in touch with anything at all, but how it can fail to be. The notion of a power, say, of seeing or knowing, cannot fail on this conception. It is not through an exercise of the power of, say, sight that one misperceives. The power as a power of seeing is infallible on the ancient Greek view. The point is not merely that seeing is inevitably successful, as of course it is, because if unsuccessful then one does not see but only seems to see. It is that the power to see is inevitably successful. Just as it is not qua doctor that one misdiagnoses a patient, so it is not qua perceiver that one misperceives. The power is not fallible as it is on Rödel's account, and it is not because the unity of knower and known, perceiver and perceived, is taken to be an essential unity. 37. Where ancient thinkers begin with the successful case conceived as an internal constitutive relation between the knower and the known, and then have no way to understand the nature of error, early modern thinkers take mind and world to be only accidentally related. And now it is impossible to understand not the fallibility of our powers of knowing but instead the efficacy of those powers, the fact that despite their fallibility they are powers, and indeed powers of knowing. Knowing requires that there be an internal, non-accidental relationship between the knower and the known, but if mind and world are only accidentally related then there is and can be no such relationship between them. Indeed, the practice of science seems, at this dialectical moment, to show that the relationship is only accidental insofar as the project of science is to understand how things are independent of the contingencies of their appearance to us as the particular sorts of animals we are. But again, if mind and world, knower and known, are only accidentally related then there simply cannot be any such thing as a power of knowing. 38. What is needed to achieve a stable conception of the power of knowing is precisely the further revolutionary transformation we have been concerned with here, the realization that our powers of knowing are constitutively mediated by the free gene, inferentially articulated senses that we grasp with our grasp of language, whether natural language or a sufficiently advanced mathematical language. Because all awareness is ineluctably mediated by free gene senses, whether our awareness of reality as it shows up for beings sufficiently like us or our awareness of reality as it would show up for any sufficiently advanced rational animal, whatever its form of life, we can understand both how we can fail sometimes to get things right and how we can succeed in getting things right. But to understand this, we have seen, one needs to have in view both sorts of language, and to have a clear understanding of their similarities and differences. In particular, we need to see that in the case involving natural language, veridical perception has a kind of primacy over illusory perception. In virtue of our acculturation into natural language, we just do have the power to take in how things are, though we can, in unpropitious circumstances, be mistaken. In the exact sciences we do not just see how things are, but instead must judge all things considered, self-consciously, and critically reflect in the course of our ongoing investigations in order to make up our minds on a matter. And here, because what we are after is not the truth of our everyday lives but fully objective truth, which is the same for all rational beings, it is our failures that have a kind of primacy. And because they do, our powers of self-correction are in this case much more significant and far-reaching. In this case there really is a sense in which everything can turn out to have been wrong. Indeed, this is just what happened when in the 19th century the science of mathematics was reborn, raised anew as a purely conceptual enterprise. We can make sense of this because mathematics has from the beginning involved what we can now recognize to be inferentially articulated free gene senses on the basis of which to reason in mathematics. Neither the ancient Greek conception of knower and known as forming an essential unity nor the early modern alternative in terms of an accidental unity will do. The unity of knower and known is instead yet another instance of an intelligible unity. It is a whole of parts that is nonetheless not reducible to its parts. Much as a side of a triangle in Euclidean geometry is at once a straight line and hence intelligible independent of any reference to triangles, and a side, which is not so intelligible, so a knower is at once an embodied being, a body among others that is intelligible independent of any reference to what it knows and constitutively minded, always already in a cognitive relation of knowing to reality. We are both bodies and self-conscious rational beings, that is, knowers. 39 And we need to keep both in view together, as aspects or facets of one reality, if we are adequately to understand our fallible powers of knowing. We can understand the successful exercise of our powers of knowing only by focusing on the irreducible unity that is the knower and the known. But to understand the failures of those same powers, the fact that they are inherently fallible, we must attend instead to the independently intelligible parts. It is, finally, by attending to the dialectical history we have been concerned here to trace, first and foremost in mathematics, that we learn explicitly and self-consciously to do both these things together. We have learned that the realization of reason as a power of knowing is and can only be achieved in the course of our intellectual history, through our own immense intellectual effort as Freya describes it. Much as nothing could be born a rational animal but instead can become rational only through its acculturation into an ongoing, living language, so no rational animal has reason as a power of knowing save by a course of extensive study within a sufficiently advanced intellectual tradition. One needs not only to be born into such a tradition and acculturated into its natural language but also to become educated. One must explicitly and intentionally learn to do mathematics, and ultimately to do the sort of mathematics that is now the norm in the discipline, if one's own reason is to be fully realized as a power of knowing. And for just the same reason, we can fully understand this practice, and in particular how it is that pure reason can be a power of knowing, purely rational and yet fully contentful, answerable to something objective, only if we have that history in view. Our autonomy conceived independently of our historicity cannot provide what is wanted. Pure reason as a power of knowing is by its nature an achievement of reason, both in the sense that it is achieved by the exercise of reason in the course of our mathematical investigations over the course of history, and in the sense that it is through this historical process of intellectual transformation and growth that reason itself is fully achieved, its potential as a capacity of knowing made fully actual. Reason realizes itself through its self-activity as reason. The realization of reason is self-actualization. 8.6 Conclusion. An adequate philosophical understanding of the science of mathematics is possible only in the light of its historical development, because the practice of mathematics as the purely rational enterprise that it has been revealed to be is possible at all only as the very late fruit of a historical process of discovery and intellectual maturation, one that at once builds on and transforms all the mathematics that had gone before. And as is characteristic of essentially historical processes generally, we can fully comprehend those earlier practices only in light of what mathematics eventually comes to be, in its full and final realization as the rational practice it is. But even this is not enough, as we have seen. If we are to understand current mathematical practice, we must see it at work, see the modes of reasoning it involves and the nature of the concepts with which it is concerned. And in order to do that we need a system of notation of the sort Jourdain describes, a system of signs capable of embodying those modes of reasoning. We need a Begriffsschrift, which, we now know, is just what Freya provides. We can understand current mathematical practice, the nature of that practice as a science, but only by attending to reasoning in the system of signs that Freya provides. As Freya shows by example in his derivation of Theorem 133, a strictly deductive proof can nonetheless be ampliative, a real extension of our knowledge. But such a proof is ampliative only because it is part of a larger system, one that conforms to the Aristotelian model of a science. At least in mathematics, the idea of self-correction is intelligible only in terms of the Aristotelian model. And now we are in a position to see something else as well, how our understanding of this capacity for self-correction also undergoes subtle transformations over the course of history. We know that the capacity for self-correction, for second thoughts as contrasted with mere changes of mind, belongs to us as the rational animals we are. To be rational just is to have the capacity for second thoughts. What is much harder to see is that it is this capacity that is constitutive of the rationality of inquiry in the exact sciences. Kant already had the basic idea, but only with developments in mathematics in the 19th century can we see that in mathematics as much as in natural science is this true. It is only with those developments that our power of reason is finally realized as a power of knowing, because it is a self-correcting power, a power of rational and critical reflection that can call anything into question as reason sees fit, where this furthermore requires the degree of cognitive control that is made possible only because and insofar as one's systematic work approximates the Aristotelian model of a science. It is by making explicit the contents of one's concepts, as far as one understands them, the basic inference patterns on which rest all the other modes of inference at one's disposal, and one's path of reasoning from those concepts to theorems, that one is put in a position to discover one's errors and so to correct them, and thereby to achieve knowledge of things as they are, the same for all rational beings. Over the course of this study, we have distinguished three different modes of our intentional directedness. Our first, and most basic, intentional comportment is that of perceptual immediacy as exhibited in our capacity to take in manifest facts. Objectivity, to this way of thinking, consists in the distinction between an object and one's experience of that object, a distinction that is grounded in the fact that natural language is at once object involving and inferentially articulated. With Descartes' new mathematical practice, a new sort of intentional involvement is realized, though it is one that is hardly intelligible as such. The idea of objective knowledge as an achievement of reason and the expression of our freedom makes its first appearance, but it cannot be sustained because it is as yet wholly unclear how reason could possibly be answerable to what is. Kant sees that knower and known must be internally related, but not how they can be. For him the unity of knower and known must be constituted in a transcendental synthesis. Objectivity on the early modern view lies in the God's eye view, the view from nowhere as it contrasts with the view from here. For reasons that were rehearsed in Chapter 4, our knowledge, by contrast with the knowledge of an infinite being, can only be of things as they appear to us. Developments in mathematics in the 19th century together with Freya's logical advances provide us with yet a third mode of intentionality, that of a fully self-conscious mediated immediacy. Although the mathematical languages that we develop, and the mathematical conceptions we form in these languages, are our own historical products, they are nonetheless revelatory of fully objective features of reality. Objectivity does not lie in the God's eye view, the view from nowhere. Instead, objectivity is what is the same for all rational beings. It is an achievement of reason. With developments in mathematics in the 19th century, developments that were often self-consciously aimed at uncovering the conceptual foundations of various parts of mathematics, mathematical thinking succeeds in breaking free altogether of the bounds of sense. In becoming explicitly conceptual, through reason alone, mathematics becomes pure not only in the sense that it has always been pure, that is, a priori, but also in the sense of being uncontaminated by the contingencies of our biology and social and cultural history. The concepts of mathematics as it is currently practiced are concepts that any sufficiently advanced rational being, whatever its biological endowment and social and cultural history, could discover and understand. In a fully achieved modernity, objectivity is what is the same for all rational beings. This is the truth in logicism, not that mathematics is merely a more developed logic but that it is a purely rational enterprise, the work of pure reason. 9. The view from here. We are each of us born mere animals and become rational, capable of critically reflective thought and of knowledge, only through our acculturation into a socially evolved tradition, a distinctively human form of life. Becoming rational, we also now know, is by the same token to come to have the world in view. And the world as we first find it is rich with significance for us, an organic, meaningful whole within which we have our rightful and natural place. But the world so experienced cannot satisfy the demands of reason. Although we are at home in the perceptible world of change and becoming, our knowledge of this world seems, on reflection, to be somehow partial and essentially perspectival, not a view of things as they really are. Insofar as it is knowledge of merely conditioned being, our everyday experience of the world points inexorably beyond itself to something unconditioned, to things as they are in themselves, the same for all rational beings. And thus a new narrative, that of reason's own becoming, is begun. This narrative of the achievement of reason, its 2.5 millennia long maturation into what is properly a power of knowing, is what we have traced here. It is a story of discovery and growth, revolution and transformation. But it is also a story of failure, in particular, of the failure of recent philosophy to see what was before it in the world historic shift in mathematical practice in the 19th century, which includes also Freya's mathematical practice, and in fundamental physics in the 20th. We have told already of the profoundly transformative developments in mathematical practice in the 19th century, of Freya's extraordinary project of providing a mathematical language for this new form of mathematical practice, and of at least some of the fundamental philosophical lessons about the nature of language and its role in our cognitive involvements in the world that we need to learn from Freya's work. What we have yet to see, even in barest outline, is the role of 20th century developments in physics. As Freya's work, and in particular the language that he developed within which to reason deductively from concepts, enables us to realize, the transformation in mathematical practice that took place over the course of the 19th century realizes a new shape of spirit, the standpoint of pure reason. This standpoint supersedes the sideways-on view of early modernity, and it does so through the realization that the sideways-on view constitutively involves a confusion of two different distinctions, that between Sinn and Bedeutung, on the one hand, and that between concept and object, on the other. So long as these two distinctions are not distinguished but instead conflated as, we have seen, they are in Kant's distinction of concept and intuition, it will inevitably seem that all cognitive significance and hence all awareness is inside, while outside is brute, merely causally efficacious physical reality. it will seem that our self-conscious experience of things is due to the causal impacts on our sense organs, and ultimately our brains, of physical stuff such as light waves and moving particles. Once we have learned to distinguish these distinctions, that conception of our being in the world simply falls away. And if we further recognize that although the sin/bedeutung distinction applies to language as such, that is, to any medium through which reality is disclosed to a rational being, the concept/object distinction instead marks the essential difference between a fully realized mathematical language, on the one hand, and a natural language, which is socially evolved, essentially sensory, narrative, and object-involving, on the other. Then we can begin to understand how and why we need to recognize both of the modes of intentional engagement that they enable. To achieve the standpoint of reason is in this way to recover a sane conception of our everyday being in the world, to understand as, in their way, the ancient Greeks already had that we, as the rational animals we are, have the capacity to perceive and thereby to know things in the world as we first find it. The one significant difference between what we now know of our everyday being in the world and what the ancient Greeks already knew is that we recognize as they could not that this mode of being is not a biological endowment, something we might share with other animals, but instead essentially social, cultural, and historical, that we become self-conscious rational animals only through our acculturation into an evolved public language. Point 1. And we can know this because we, but not the ancient Greeks, have and know ourselves to have also another mode of being in the world insofar as we have the capacity to take up the standpoint of pure reason, to think and so to know things in the world as they are disclosed through the medium of a self-consciously achieved mathematical language. Having learned to distinguish the sin/bedeutung distinction from that of concept and object, we can finally understand how language is the vehicle of our cognitive involvement in the world, how it is that language at once gives us the eyes to see and by the same token the world, reality, a face by which to be seen. But there are, we now know, two very different ways this can work, through the medium of natural language and through the medium of a fully realized mathematical language. The view of reality afforded by natural language, at least by the natural languages of the sort of rational animal that we in fact are, is simply that of everyday life, a view of living beings with their natures and powers and of perceptible things more generally. The view of reality afforded by mathematical language is more complex. What mathematical language directly discloses are concepts, concepts of objects, of properties, relations, and functions, and finally, concepts of mathematical structures, of whole systems of objects in particular sorts of relations. It is these concepts that are deployed in turn in 20th century fundamental physics. Through its work of clarifying the senses of concept words and thereby providing us cognitive access to the concepts those words signify, the science of mathematics provides the language that can serve in turn as the medium of the physicist's cognitive engagement with physical reality. With the rise of early modern mathematics and science we learn to conceive both ourselves and the world around us in a fundamentally new way, and, so it seemed, a better way. The new conception both of ourselves and of the world in terms of the essentially modern notion of a law was to replace the ancient conception. Everyday perceptual experience, which had hitherto been understood as an actualization of our natural capacity to take in things as they are, was now taken to provide only the data for our newly realized capacity for formulating theories of how things really are, theories that were to explain the data that sense experience provides. To the early modern mind, things are not as they appear to be in our perceptual experience. Experience cannot be taken at face value. Our experiences of things are only appearances to be accounted for by what, according to our theories, is actually going on. Not natural language but mathematical language gets things right on the early modern view, not by disclosing how things are, as everyday experience seemed at first to do, but instead by representing it. The theories we formulate in modern, Newtonian scientific practice are representations, models formulated in the language of early modern mathematics that are supposed to correspond to, provide a picture of, what is physically real. A characteristic mark of early modernity is the thought that we must choose between the ancient understanding of being in terms of the notion of a form of life and early modernity's mechanistic understanding of being as a kind of clockwork, whether natural or rational. Much as Aristotle understood even inanimate matter on the model of animate beings, as having its characteristic principle of motion within it as constitutive of its nature as what it is in the nature of fire to go up, of earth to go down, and so on. So we, insofar as we are merely early modern, understand animate being, in particular animal life, on the model of a mere mechanism. As Aristotle understood intellection on the model of perception, so we understand perception on the model of intellection. Point 2. Neither, we ought now to see, will do. We do not have to choose, and we must not choose if we are fully to understand things as they are. Living beings, in particular, cannot be adequately understood as complex mechanisms. As we saw already in Chapter 1, a living being is essentially an instance of a form of life, of a species with its characteristic capacities and powers. Indeed, 20th century fundamental physics seems to show that the reductive, mechanistic understanding characteristic of early modernity is inadequate even as regards inanimate nature, at least as a whole, that is, in our understanding of the cosmos, and in our understanding of the most fundamental nature of matter. Both in special and general relativity and in quantum mechanics we find, we will see, a very different kind of physical theory from that which is characteristic of Newtonian mechanics. Both in special and general relativity and in quantum mechanics, mathematics is not used to construct models of posited underlying mechanisms but instead directly discloses the essentially mathematical structure of the relevant bit of reality. And insofar as the mathematical concepts that are in play in special and general relativity and in quantum mechanics have been stripped of all sensory content, insofar as they belong to pure reason alone, reality as it is revealed in these domains is fully objective, things as they are, the same for all rational beings. 9.1 Einstein's revolutionary physics. To give up the sideways-on view bequeathed to us by early modernity is, among other things, to realize that it is from within the world that we know it. This is of course obvious in our everyday lives, at least it is obvious before the rise of early modern mathematics, physics, and philosophy contrives to convince us otherwise. But it is equally true, we will see, in Einstein's physics. Although in special and general relativity reality is disclosed not sensorily but to reason itself, it is nonetheless disclosed to an essentially embodied rational being, one that is manifestly embedded within the world that is the object of our scientific investigations. What Einstein's revolutionary new physics reveals, so it will be argued, is that having passed beyond the inside/outside perspective of early modernity, we at once recover our everyday being in the world and fully realize our capacity to think, that is, to grasp in pure thought, the most fundamental features of physical reality, in the first instance, the nature and structure of space-time. In special and general relativity we achieve a radically new conception of space and time, and of the ways in which matter and energy interact with space-time, one that supersedes, on the one hand, the Newtonian conception of absolute space and absolute time, and on the other, Newtonian gravitation as a force that acts instantaneously over the distances between massive bodies. Adequately to understand it, we need to remember that the Newtonian conception of space and time that is superseded by Einstein's account is itself made possible only by the profound transformations in mathematical practice first enacted by Descartes. Our everyday conception of space is not that of a container, a totality of relative positions, as it is in Newton's physics, but instead a conception grounded in our experience of objects, landmarks, and of how, as we discover in our journeys through the world, they are arranged relative to one another. And our everyday conception of time is similarly grounded in our experience. Time passes, and as it passes things come to be, grow, and change, and eventually pass away. The time of our lives as the rational animals we are is, as we can think of it, narrative time within which stories, with their characteristic beginnings, middles, and ends, unfold in their own characteristic ways and inexorably toward their end. As things have their proper place according to their natures in our everyday conception of space, so they have their proper time, each its own season in our everyday conception of time. It was only with Descartes' new mathematical language, and as an integral part of that language a metamorphosed understanding of space as an antecedently given whole within which things might but need not be found, that we learned, following Newton, to understand space and time in absolute terms. On Newton's conception of it, absolute space is a kind of container within which material objects are to be found, though, again, the container could have been empty. This conception is furthermore required, Newton argues, in order to explain the fact that although the notion of velocity, that is, of the speed and direction of an object's motion, makes sense only relative to something else assumed to be stationary, the notion of acceleration apparently does not. We feel acceleration, for instance, when, while driving, we step hard on the gas, or on the brake, or take a sharp corner. And clearly other objects, say, a bag of apples laid on the passenger seat, are affected by acceleration, and deceleration, as well. Brake hard and the apples will end up on the floor. But acceleration and deceleration are only changes in velocity. So they ought, like velocity, to make sense only relative to something else. Because in this case the something else clearly cannot be chosen at random, as it can in the case of velocity. What acceleration is relative to, Newton concludes, is absolute space, from which it naturally follows that true motion and rest are likewise relative to absolute space. Of course we cannot determine the absolute velocity or rest of a thing, as we can determine at least the fact of acceleration, though not by how much, relative to absolute space. But once we recognize that absolute space is needed in any case, we know that absolute velocity and rest also make sense. Just the same applies to time, Newton thought. Although we live our lives in the ever-passing present, time, like space, is a kind of absolute container of relative temporal locations, before, during, and after. We cannot know where we are in absolute time, whether near its beginning, if it has one, near its end, if it has one, or some time in between, but we are nonetheless at some time in particular in absolute time. It is this conception of space and time as two independent and absolute relational wholes within which everything happens that would be completely overturned by Einstein, first in special relativity according to which space and time are not two but indissolubly one, and then in general relativity according to which this one space-time is a field that is continuously transformed through its interactions with massive bodies in an ever-evolving cosmic dance. In 1905 Einstein published his special theory of relativity aimed at resolving what he saw as a difficulty with the then standard account of electricity and magnetism due to Maxwell. Much as an object that appears to be at rest to one perceiver, is in motion from the vantage point of another perceiver, so what appears to be an electric field from one vantage point can appear to be a combination of an electric and a magnetic field from another. Depending on the vantage point, and so on whether the system is taken to be moving or at rest, Maxwell's equations yield different answers regarding the electric and or magnetic forces acting on the system. Conceptualized from the standpoint of early modern science, this is no more surprising than the fact that a body that appears to be at rest from one vantage point appears to be moving from another, for, as we have just seen, one distinguishes in early modern thought between absolute and relative space and hence between absolute and relative motion. Because we do not, and cannot, know our absolute location nor from which vantage point things are really moving or at rest, we can measure only relative to some inertial frame of reference, and our descriptions of a moving body will be different in different reference frames. In just the same way, and partly as a result, one's description of the forces, whether electric or magnetic or both, that are acting on a system will be different in different frames of reference. Only relative to absolute space in which the motions of bodies appear as they are in reality could it be determined which forces, whether electric or magnetic or both, are actually acting in the system. Einstein rejects the account. According to him, electric and magnetic fields are not different entities but instead are one and the same, the electromagnetic field as it shows up from different perspectives. There is no absolute space but only relative spaces, that is, various inertial frames within which to make measurements. In special relativity there is no absolute space and no absolute time. What there is instead can be illustrated by the relation between a length of stick suspended in the air and the shadow it casts on the wall and floor. Point 3. Suppose, first, that the stick is suspended from one end so that its length is parallel to the wall and perpendicular to the floor. The shadow the stick casts on the wall will then be the same length as the length of the stick, and there will be no shadow cast by the length of the stick on the floor. Similarly, if the stick is suspended so that it is perfectly horizontal, parallel to the plane of the floor and perpendicular to the wall, then the length of the shadow on the floor will be equal to the length of the stick, and there will be no shadow due to the length of the stick on the wall. At intermediate positions, as we raise one end of the stick towards the vertical, shadows will be cast on both floor and wall by the length of the stick, shadows the lengths of which form the sides of a right triangle, the hypotenuse of which is the length of the stick. Hence, no matter what the actual orientation of the stick, its length can be determined by measuring the length of the shadow it casts on the floor and or wall. The length of the stick equals the square root of the sum of the squares of the lengths of the shadows it casts on the floor and wall. In special relativity, analogously, the elapsed time between two events and the distance between them, although they will appear different to observers in different inertial frames, together determine an invariant space-time interval between the two events. If t is the elapsed time between the two events, as measured in some one frame of reference, and L is the distance between them, as measured in that same inertial frame, then the space-time interval between them is equal to square root, where c is the speed of light and is the same in all inertial frames. Measured distance and measured time are not, then, objective in themselves. There is no answer to the question how long something really is or how much time has elapsed. And the problem is not that we cannot know such facts, it is that the questions simply make no sense in the new framework. Nevertheless, like the shadows cast by our sticks, measured distance and time enable us to determine something that is objective, that is, the same in all inertial frames, namely, the space-time interval. We do not find it odd to think that what happens at different times and the same place when viewed from one inertial frame will appear to happen at different places relative to another inertial frame. But we do find it odd to think that what happens at one and the same time at different places relative to one inertial frame happens at different times relative to another. Nevertheless, this is an immediate consequence of the fact that, as special relativity reveals, the speed of light is the same in all inertial frames. No matter how fast one is moving, whether in the direction of the light's motion or directly away from it, the speed of light is, and is measured to be, precisely the same. It follows that two events that happen at different places so that no matter where a perceiver is relative to those two places it will take some non-zero stretch of time for information about those two events to reach that perceiver will be perceived as differently temporally related by perceivers in different inertial frames. What appears to be two simultaneous events from one vantage point, will appear to be two events one after the other, that is, at different times from one another, from another vantage point. Only events that occur at the same place and the same time will be perceived as simultaneous by perceivers in different inertial frames. In special relativity, space and time are not distinct and separate aspects of reality but instead indissolubly one, and any object's motion through Einsteinian spacetime, though from within an inertial frame will be measured to have both a spatial and a temporal component, is moving through spacetime itself at the speed of light. Hence, the faster one moves through the spatial dimension of spacetime, the slower one must move through its temporal dimension. And at the limit, for the case of something moving through spacetime at the speed of light, that thing must be at rest with respect to time, because all its space-time speed is being taken up within the spatial dimension, there is none left to enable it to move through time. Time does not pass for something traveling at the speed of light. And that is why the speed of light is measurably a constant no matter what one's motion relative to it. As one's own motion relative to that of light increases, one's passage through time slows, and as a result the measured speed of light is from one's own perspective the same as it would be if one were not moving at all relative to the light. Again, because one's total motion through space-time is always at the speed of light. The faster one moves through space, the slower is one's passage through time. To our everyday way of thinking, objects have definite shapes, dimensions, and speeds. There is a fact of the matter how large a thing is, or what the distance is between two things, and a fact of the matter whether a thing is moving or at rest, and if it is moving, how fast it is moving. On the Newtonian view, there is again a fact of the matter what the dimensions of a thing are, and a fact of the matter whether a thing is at rest or moving, and if so how fast. But these facts are not, for the Newtonian, discoverable from our limited perspective. We can measure only from within some inertial frame, which may or may not be moving relative to absolute space. Our view is only the view from here. It is the God's eye view, the view from nowhere, that is the perspective from which things show up as they really are. Einstein's account is very different. According to him, the relative, which we can measure, does not contrast with something absolute, which we cannot measure, but is rather that through which we have access to what is absolute, that is, invariant. There is, on Einstein's theory of special relativity, no absolute space and no absolute time but only space-time. It follows directly that there is no God's eye view to oppose to our own. Our view, the view from here, is the view from nowhere, according to Einstein. It is as embodied knowers limited, finite, perspectival beings in the world that we know things as they are, the same for all rational beings. It is from within reality as it shows up for us finite, perspectival, embodied and embedded beings that reality is knowable and known, not from some mythical outside, or sideways on, or God's eye, view. On Einstein's account according to which a measurement of a space interval together with a measurement of a time interval gives, by way of a simple calculation, a space-time interval that is the same in all inertial frames. A measurement is not a datum to be explained by a theory picturing reality but is instead itself a mode of access to reality. The measurements do not themselves provide what is wanted, by contrast with our everyday measurements, they do not immediately disclose an aspect of the world. But through a simple calculation they do provide a mediated access, not in the sense of data for a theory but immediately. The measurement itself gives us what we want, access to what is, the same for all rational beings whatever the inertial frame they find themselves in. Much as Freya helps us to see that our cognitive access to reality is in every case mediated by a sense, and that different senses can disclose one and the same objective entity, one and the same Bedeutung, so Einstein helps us to see that our access to the bit of reality that is a space-time interval is in every case mediated by a kind of sense, a facet of the real that we grasp through measurement and calculation, and that different senses, that is, different measurements and calculations, in different inertial frames, can disclose one and the same objective reality. What to our first mode of intentional directedness seemed immediate, the capacity directly to measure both space and time intervals, and to our second mode of intentional directedness seemed ineluctably mediated, merely our limited perspective on things, is revealed, in Einstein's special relativity as in Freya's Begriffsschrift, as a mediated immediacy, a mode of access to the real but one that is essentially mediated. In special relativity, electric and magnetic forces are similarly revealed as facets of something fully objective, namely, the electromagnetic field. As Lang explains, there is no fact about whether the magnet is moving and the wires are at rest or vice versa. There is no fact about whether both electric and magnetic fields are present, or only a magnetic field. There is no fact about whether the forces causing the current to flow are electric or magnetic. Rather, the only facts are the relative motions of the magnet and wire, as well as the existence of an electromagnetic field characterized by the invariant quantities, involving both E and B seen from different reference frames. The electromagnetic field appears as different combinations of E and B. Just as it unifies space and time, showing them to be merely aspects of one and the same entity, so Einstein's theory of special relativity unifies electric and magnetic forces by showing that they are aspects of one and the same entity. Einstein's was not merely a new theory about the nature of space and time, and about electric and magnetic forces. It was a new kind of theory, one that Einstein, in 1919, described as a theory of principle as contrasted with a constructive theory. A paradigm example of a constructive theory, according to Einstein, is the kinetic theory of gases, which seeks to reduce mechanical, thermal, and diffusional processes to movements of molecules. According to this theory, when gases appear to expand on being heated, or to exert greater pressure on having their volume reduced, what is in fact going on is that little particles are bouncing off each other, and the walls of the container they are in, with increasing rapidity. Such a theory is a paradigm of Newtonian reductive, mechanistic scientific theorizing. One explains the appearances by positing an underlying reality of particles and forces acting on them. A theory of principle is very different insofar as it does not proceed by positing a theory of entities together with the forces acting on them to explain the appearances, the data, but instead begins with some overarching universal principle from which the account of physical reality is to be deduced. The paradigm for Einstein of such a theory is that of thermodynamics, which begins by assuming that certain types of perpetual motion machines are physically impossible and from there deduces the theory. Einstein's theory, unlike earlier constructive theories, is a theory of principle, one that begins with two assumptions: that the speed of light is the same in all inertial frames and that the laws of physics hold in all inertial frames, and then determines what follows. We can furthermore discern the overall orientation of this new form of physical practice in the way Einstein reconceives certain well-known equations, the Lorentz transformations, not as descriptions of phenomena that are then to be explained by some constructive theory but as themselves directly disclosing objective reality. As Friedman puts the point, Einstein's revolutionary move lies in his interpretation of these transformations as not simply representing special dynamical properties of electromagnetically constructed objects as they move relative to the ether, but rather as constitutive of the fundamental geometrical kinematic framework of what we now call Minkowski spacetime. For Einstein, we might say, the Lorentz transformations change from being properly empirical laws governing a particular variety of force to geometrical kinematic constitutive principles articulating a radically new space-time structure, a space-time structure which, from a classical point of view, is simply incoherent. From within the Newtonian block universe, that is, taking the Newtonian conception of space, time, and motion for granted as the background for our empirical investigation, we discover, by making the appropriate measurements, that the speed of light appears to be the same in all inertial frames. This is, on the Lorentz-Fitzgerald view, merely an appearance, one that is to be explained by the fact that bodies in motion contract in a way that exactly compensates for their motion relative to that of light. That is, the Lorentz transformations are conceived dynamically, the lengths of moving bodies really do change on this view. Einstein, as Friedman notes, takes a radically different view of those same transformation equations. What they reveal, Einstein thinks, is not that the lengths of bodies change as they move relative to the motion of light, but that there is no such thing as the length of a body. Except at the limit in the case of the speed of light, which, we have seen, leaves no room for motion through time. The notion of motion, and with it the notion of the length of a spatial object together with that of a time interval, are all completely relativized. They are not intrinsic properties of things but instead frame relative. Nevertheless, we have seen, measurements of spatial and temporal intervals that are made from within any given frame, though they provide only one perspective on things, do reveal something invariant, namely intervals of space-time. What we had taken to be the real is now revealed to be only a shadow cast by the choice of an inertial frame within which to measure, only a facet or face of what is. Again, from the perspective that Einstein achieves, the absolute is not opposed to the relative, as it is in Newtonian physics, but given through it. It is the view from here, not some mythical God's eye view, that is the view from nowhere, the same for all rational beings. It is furthermore worth remarking that Einstein seems quite self-consciously to adopt the standpoint of reason in the reflections that led him to special relativity. He remarks in the opening sentence of his famous 1905 paper on relativity that Maxwell's electrodynamics as usually understood at present when applied to moving bodies, leads to asymmetries that do not seem to attach to the phenomena, and as Einstein would later explain, the thought that one is dealing with two fundamentally different cases was for me unbearable. The difference between these two cases could not be a real difference but rather, in my conviction, only a difference in the choice of reference point. As Lang remarks, it is hard to avoid concluding that Einstein regarded these asymmetries as supplying a powerful argument against what was then regarded as conventional wisdom. But if they were, then it would appear that the standards of argumentation had somehow shifted insofar as those same asymmetries had not, for Einstein's predecessors, provided any such argument. Unlike his predecessors, Einstein was not concerned only to save the phenomena but also to satisfy the demands of reason itself. Point 4 He does not begin with the various observations and look for an underlying mechanism to explain the appearances, as Lorentz had, but instead begins with a demand of reason, the demand that symmetries be respected. If there is no asymmetry in the phenomenon, there should be no asymmetry in the account that is to explain it. But of course nothing in the phenomenon demands this. The symmetry demand, like its close cousin the principle of sufficient reason, is instead a demand of pure reason only. This time, unlike earlier appeals to the principle of sufficient reason invoked in the context of early modern modes of thought, the demand pays off. According to special relativity, nothing can move through space-time faster than the speed of light. But if so, then Newton's theory of gravity, according to which there is instantaneous action at a distance, must be wrong. So, around 1907, Einstein began to search for a new theory of gravity, and he would find it with the realization that gravity and acceleration are one and the same phenomenon, that what classical physics had understood as a mere coincidence, that the measured effects of gravity and of uniform acceleration are indistinguishable, in fact reflects a fundamental feature of reality. Spacetime, according to general relativity, is curved by massive bodies, and its curvature in turn affects how bodies move through it. Space tells matter how to move. Matter tells space how to curve. And unlike Newtonian gravity, which acts instantaneously, the rate at which space-time is warped by matter is the speed of light. There is no instantaneous action at a distance, but only the rippling effects of massive bodies on the curvature of space that happen at the speed of light. Thus, although in special relativity space-time is absolute and immutable, in general relativity its shape is constantly being changed by the massive bodies in it. As we are now to see, space-time, with its variable curvature owing to the presence of mass and energy, just as the gravitational field. Point 5 Special relativity is merely a special case, that of an empty cosmos in which the gravitational field is everywhere zero. The space-time of general relativity is an evolving structure that is disclosed through Einstein's field equations. And those equations have led in turn to a revolution in our understanding of the life of the universe, one according to which it begins with a Big Bang and is subsequently characterized by the expansion of space-time, that is, the gravitational field. Even the whole cosmos, it now appears, has a story to tell, one that has a beginning, a middle, and an end. There are on this account no forces acting on bodies from the outside such as one finds in Newtonian constructive theories. Indeed, there are no physical correlates of any kind but only mathematically described structures. Einstein's theory is not a model or representation of reality. Instead, the mathematics of Einstein's relativity directly discloses to pure thought a fundamental aspect of reality, namely, the space-time field that is the cosmos. 9.2 The quantum revolution. Einstein's theory and practice, I have suggested, accord with the new mode of intentional involvement, and in particular, the mediated immediacy, that Freya helps us to see is characteristic of the mathematical practice that emerged in the 19th century. Much as mathematicians such as Riemann were engaged in a new conceptual and deductive form of mathematical practice in place of the computational, algebraic methods of Euler and others, so Einstein was engaged in a new sort of practice of physics. And it is one that does not merely use mathematics in theorizing about particles and forces underlying the appearances but instead provides a mathematical account of the structure of the whole of space-time. The situation in quantum mechanics is much less clear, and our discussion of it is, correspondingly, much more tentative, exploratory, and incomplete. The aim is not to provide any sort of an account or even the beginnings of an account of what is going on in quantum mechanics, but only to reflect a little, in light of the account we have developed, on central features of some approaches currently being explored and to provide some indication of a possible alternative. On the conception of scientific practice that is the legacy of early modernity, fundamental scientific advances tend either to reveal hitherto unknown particles and forces that underlie and explain something already known or to expand the purview of our vision so as to embrace ever larger blocks of physical reality. Although we start with the view of middle-sized dry goods afforded by our everyday being in the world, we acquire in the course of our scientific investigations the capacity both to zoom in on ever smaller bits of reality, out of which the bigger bits are taken to be composed, and to zoom out on ever larger expanses of the cosmos, as if seen from further and further away. In neither direction is there any prospect from within the practice, save for those provided by various practical constraints, for the process to reach a natural end. If a stable and intellectually satisfying end is to be reached, in either direction, that will only be because a fundamentally different sort of account has been provided. Einstein's theory provides a different sort of account on the zoom-out side insofar as it eschews the sideways-on view and takes up instead a standpoint within the reality it aims to know. Einstein's practice in physics is that of a limited, spatio-temporally situated observer. As it reveals, it is the view from here, not some mythical God's eye view, that is the view from nowhere, the same for all rational beings. Quantum mechanics similarly, we will see, can be understood as providing something analogous on the zoom-in side, not an account of yet smaller and smaller particles conceived as the ultimate, or at least more ultimate, building blocks of material reality but a new kind of theory aimed at providing an adequate mathematical description of material reality. 6. In quantum mechanics, an isolated physical system such as an electron is characterized by a state function that provides the probabilities of the results of observations, that is, of measurements that can be made on the system. If no measurement is made, then changes in the state function are continuous and deterministic, and are given by Schrödinger's equation. If a measurement is made, say, of the position of some particular electron, then the wave function characterizing that electron collapses, at least in the sense that now, for our system, the probability of its being in the position we found it in is 1, and the probability of its being in any other location drops to 0. And from now on, so long as no further measurements are made, this probability remains fixed as the wave function continues to evolve according to the Schrödinger equation. The mathematics, the Schrödinger equation, provides only predictions, probabilities that the system has this or that feature. These predictions have nonetheless proved extraordinarily accurate. No one has any doubt that the mathematics is right, at least as far as it goes. Even in cases in which we have so far been unable, for practical reasons, to test some prediction of quantum mechanics, it is universally assumed that the prediction will be borne out. Quantum mechanics is the most spectacularly successful theory in the history of science. It is also the most puzzling. The most basic puzzle is due to the form the equation takes, the fact that it provides only probabilities. When Schrödinger first formulated it, he interpreted it classically, as a description or representation of some actual spread out, waving stuff. But that seems not to be right insofar as measurement never reveals such stuff but only one of the possibilities given by the equation. According to Max Born, what the mathematics provides is instead what we can think of as a probability wave, one whose peaks and troughs give not the reality itself but instead the probabilities of the outcomes of various sorts of measurements. There is, furthermore, reason to think that unlike other appeals to probability grounded in our practical inability to work out the actual outcome on the basis of given initial conditions, say, in predictions of whether it will rain tomorrow, the probabilistic character of the wave equation is fundamental, that it in some way reveals, or at least reflects, the true state of things. It is as if, before the measurement is made, the system is in a superposition of states, of all possible outcomes of measurement, that it really is not, before the measurement is made,
determinately in one or other of the states that measurement might reveal. The most famous experiment to show this is the double-slit experiment, in which particles, say, electrons, are one by one fired at a barrier with two slits in it beyond which is a detector. As the mathematics predicts, the frequency distribution of hits on the detector is not the sum of the distributions that would result if each slit were opened separately, but instead that of a wave going through both at once and thus giving rise to a characteristic interference pattern. The mathematics predicts, that is, not two bands on the detector, one for each slit, but instead an array of bands such as would be produced by a stream of waves going through the two slits. Although the particles are shot individually and each hits the detector at one particular location, over time, as many hits are made, the detector shows an interference pattern that is typical not of particles but of waves. This interference pattern strongly suggests that the probability wave that is the Schrödinger equation is somehow real, not merely a reflection of our ignorance as in standard appeals to probability. As Heisenberg showed, the mathematics also predicts a kind of uncertainty, that certain features of the particles are coupled such that knowing, by measuring, about one of them precludes knowing about the other. Indeed, the mathematics tells us, the more precise one's knowledge is of the one, the less precise must be one's knowledge of the other. It is not that we discover empirically, on measuring, that measurement somehow changes the system, that measuring one aspect, say, the velocity of the particle, tampers with the particle so that now some other feature, say, the position of the particle, cannot be determined, even though before the measurement of velocity it was possible to measure instead the position. Rather, the mathematics itself predicts this for such complementary features, and of course the prediction is borne out by our measurements. Finally, and most puzzling of all, the mathematics predicts what is known as non-locality for entangled particles, and again these predictions have been borne out with spectacular accuracy by measurements. Imagine, first, that a particle is split into two particles of equal mass that fly off in opposite directions at the same speed. We can then measure the velocity of one of the two and the position of the other, and thereby apparently determine both the velocity and the position of both particles. One cannot, given Heisenberg uncertainty, measure both the position and the velocity of one and the same particle, but apparently it is perfectly meaningful to say that independent of being measured such a particle nonetheless has a definite position and velocity. And what this shows, Einstein, Podolsky, and Rosen famously argued, is that quantum mechanics is not a complete account of quantum reality, the mathematics insofar as it predicts uncertainty is leaving something out. It was John Bell who took the crucial next step, the one that reveals what is generally interpreted as non-locality. As he discovered, the mathematics predicts, and measurements have since confirmed, that the measurement that is performed on one of a pair of entangled particles affects, apparently, the results of certain measurements on the other no matter how far apart the two particles are when the measurements are made. Brian Greene offers this colorful imagery: entangled particles are like a pair of magic dice, one thrown in Atlantic City and the other in Las Vegas, each of which randomly comes up one number or other, and yet the two of which somehow manage always to agree. Entangled particles act similarly, except they require no magic. Entangled particles, even though spatially separate, do not operate autonomously. A measurement on one particle of an entangled pair seems to affect in a quite determinate way the wave function of the other, even though it is impossible that any information passed between the two. The results of measuring the two particles are correlated, as the mathematics predicts and experiments confirm, despite the fact that the particles themselves seem to be entirely separate. Before the measurements are made on the two particles, there is only some probability of this outcome or that, and yet measuring one seems to affect what one will find on measuring the other. It is as if, when a measurement is made on one particle of an entangled pair, the other knows instantaneously that the measurement has been made and what its result is. We can put this point in terms of collapse: when you measure, say, the spin of the one, thereby collapsing its wave function in a certain way, this instantaneously collapses the wave function of the other in just the same way. This is non-locality, action at a distance.
The mathematics predicts it, and experiments confirm it. Point 7. The mathematics of quantum mechanics provides probabilities of outcomes of measurements that do not seem merely to reflect our ignorance but what is actually going on. It is, again, as if the relevant bit of reality is in a superposition of all possible states prior to measurement, and then the wave function that characterizes the superposition collapses into one of the possible positions when a measurement is made. But if measuring causes a collapse of the wave function in this way, then we need to know more exactly than we generally do just what constitutes a measurement. And as Price explains, what makes the problem so intractable is that to the extent that quantum mechanics claims to be a universal theory, applicable to all physical systems, we should expect it to be applicable inter alia to those physical systems which may be used as measuring devices. If we assume that not only particles such as electrons and photons but also objects such as detectors that are made up of such particles can be in superpositions, then it seems we shall have also to conclude either that an observer can be in a superposition of mental states or that somehow minds affect the collapse, that the collapse occurs precisely at the moment when a self-conscious being comes to be aware of the result of the measurement. There are two key assumptions in play here. The first is the assumption that quantum mechanics is a universal theory applicable to everything, that everything can be accounted for by or reduced to fundamental physics. The second is the principle of psychophysical parallelism, the requirement that, in von Neumann's words, it must be possible to describe the extraphysical process of subjective perception as if it were in reality in the physical world, i.e., to assign to its parts equivalent physical processes in the objective environment, in ordinary space. It is these assumptions that generate the measurement problem, the question when exactly in the chain of events the collapse of the wave function occurs. And once one has that problem, the only way to avoid it is to deny that there is any collapse. And then all that is left to do is to decide on which side of the non-collapse one will set up camp, on the side of measurement and the mind, or on the side of the wave function and the world. The idea that the wave function collapses upon measurement provides a way of thinking about the relationship between the mathematics of quantum mechanics and the measurements we make. Because the mathematics is probabilistic and the measurement effectively settles which possibility is the case, we find ourselves wanting to say that what was originally in a superposition collapses into one definite state. And that, given the assumptions just outlined, leads directly to the measurement problem, which can then be avoided only by denying that there is any collapse, either instrumentally, by treating the mathematics as merely a useful tool of prediction, the measurements alone as real, or many world style, by treating the mathematics alone as real, the measurements relegated to the realm of subjective appearances. As should already be obvious, this whole dialectic arises only because it is assumed that the perspective of science is and must be that of the sideways-on view. Applied to the case of quantum mechanics, the sideways-on view suggests that what is outside is the probability wave evolving according to Schrödinger's equation, and what is inside is what we learn as the result of some measurement. Given this picture, the problem of the collapse of the wave function inevitably gives rise to two opposing positions, each of which is motivated by the manifest defects of the other. There is only the inside and the outside, so only two possibilities: either we are stuck on the inside, or it is as from the outside that we see what is really going on, the appearances on the inside being nothing more than the effects on creatures like us of such a reality. The first is the instrumentalist interpretation, according to which what we know is what we have measured. The wave function does not describe anything but is merely a mathematical tool for making predictions about the outcomes of measurements. Because we cannot know the state of the system except by performing some measurement on it, the question of what the state of the system is before we measure is simply meaningless. The second is the many worlds interpretation, according to which the Schrödinger equation accurately describes reality, the appearance of collapse, the fact that measurements invariably yield only one of the possible outcomes, is taken to be merely subjective, an appearance, not really real. What the mathematics describes is a superposition of states, and that is what is the case. When a measurement is made and, as it seems, the observer finds the system to be in one particular state, what has happened, according to the many worlds account, is that the world, or at least the observer's mind, has split into as many worlds as there are possible outcomes, in each of which the mind observes one of them. The inside/outside conception of mind and world that is the legacy of early modern science, when carried over to the case of quantum mechanics, generates a dilemma, and it is one that is explicit in, for instance, Max Tegmark's defense of the many worlds interpretation. As Tegmark thinks of it, there are two ways to perceive a mathematical structure. On one hand, there is what we will call the view from outside, or the bird perspective, which is the way a mathematician views it. On the other hand, there is what we call the view from inside, or the frog perspective, which is the way it appears to a SAS in it. The frog perspective is that of the Copenhagen and instrumentalist interpretations, and, as Tegmark notes, that of everyday human language. The bird perspective is that of the many worlds interpretation, and of mathematical language. And we simply must choose, he thinks, either the outside view or the inside view, either mathematical language or natural language, either the Copenhagen interpretation or the many worlds, either, as Tegmark puts it, many words or many worlds. As he writes, the reader must choose between two tenable but diametrically opposed paradigms regarding physical reality and the status of mathematics. Paradigm 1, the outside view is physically real, and the inside view and all the human language we use to describe it is merely a useful approximation for describing our subjective perceptions. Paradigm 2, the subjectively perceived inside view is physically real, and the outside view and all its mathematical language is merely a useful approximation. What is more basic, the inside view or the outside view? What is more basic, human language or mathematical language? But we do not have to choose, and we must not choose. We need both the perspective of natural language, the language with which it all begins, and that of mathematical language, which is an achievement of reason, the work of millennia. It is only the sideways-on view of early modernity that leads us to think otherwise, and that view is dismantled with the full realization of reason as a power of knowing. On the Copenhagen interpretation of quantum mechanics, an act of measurement causes the state function, which left undisturbed evolves deterministically in accordance with Schrödinger's equation, to collapse. What had hitherto been a superposition of states collapses into some one state. On both an instrumentalist account and on an Everett-style many worlds account there is no collapse, but there is also no reason to prefer either the inside view of the instrumentalist or the outside view of the many worlds theorist. We need to give up the assumptions that generate the two possibilities. The real problem is the sideways-on view that underlies them. Instead, as in Einstein's relativity theory, we can hold that the measurement gives the relevant bit of reality but only through a facet of it, one way it can show up to embodied and embedded perceiver such as we are. To this way of thinking, the relevant bit of reality is given by the Schrödinger equation, but we have access to this reality only from this or that perspective as constituted by a confirmatory measurement we make. If so, then we are quite like Abbott's Flatlanders, whose experience of a three-dimensional object is of the changing form of something merely two-dimensional. The basic idea is as follows. Imagine a cube passing through a plane and suppose that it can pass through the plane in only three ways, with one face parallel to the plane, with one edge first touching the plane, or with one vertex first touching the plane. If the first of these three possibilities is realized, then from the two-dimensional perspective of the plane a square will appear, persist a while as the cube passes through the plane and then disappear. If instead it is an edge that first meets the plane, then what first appears is a line that then widens until it is a square and then begins to shrink back down to a line, then disappears. And if it is a vertex that first meets the plane, that vertex will become a diamond that grows for a while and then begins to shrink back down to a point before disappearing. These three ways the cube can show up in passing through the two-dimensional plane correspond to the possible outcomes of measurement. It is furthermore easy to work out the probabilities of each sort of outcome given that a cube has 6 faces, 8 vertices, and 12 edges. The cube itself is not in any sort of superposition, nonetheless it is essentially probabilistic, from the point of view of an inhabitant of the two-dimensional plane, what the outcome will be.
What is observed depends on the orientation of the cube as it begins its passage through the two-dimensional plane. The measurement does not cause anything to happen, any collapse, instead it gives what is in fact a facet, one face, of the reality in question. The measurement gives us access to what is real, but only as mediated by our embodied and embedded situation in the world. It confirms that we have gotten the mathematics right, and it is the mathematics that reveals the reality with which we are concerned. In our discussion of Einstein's special relativity, we noted that Einstein does not regard the Lorentz transformations as descriptive of a phenomenon to be explained by a theory of what is really going on, but instead as directly disclosing the relevant bit of reality. As we also noted, what to everyday experience is taken to be the real, namely, time intervals and spatial lengths and distances, are now to be seen as only facets of what is fully objective, namely, space-time intervals. The first is a point about the mathematics employed in relativity theory, the second is about the measurements we make. In order more fully to bring out how we might similarly think in the case of quantum mechanics, it is helpful to consider again the way mathematical notation functions on Freya's view of it, and in particular two interestingly different ways we can think about free gene sense in relation to what is objective, Bedeutung. First, a sense provides a mode of presentation of a thing, what we can think of as an aspect or facet of it. So, to take a simple example, all of the expressions 7 plus 5, 3 times 4, and square root 144 designate one and the same number, but they nonetheless express different senses. Similarly, the sine function, say, can be designated by a certain infinite series. The second way to think about free gene sense in relation to the objective focuses instead on whole formulae and the thoughts they express. Such thoughts, we have seen, can be carved up into function and argument in various different ways to yield subsentential expressions, simple or complex, that designate various objects and concepts. For example, the formula 24 equals 16, as Freya reads it, only expresses a thought independent of an analysis into function and argument. If we take 2 as marking the argument place, then the sentence is seen as ascribing the concept fourth root of 16 to the number 2. If we instead take 4 as the argument, then we are dealing instead with the concept logarithm of 16 to base 2. And if we take the argument to be 16, then the concept is fourth power of 2. Suppose now that we wish to know whether the thought expressed by 24 equals 16 is true. In order to answer that question, we must pick an analysis so as to ask whether the relevant concept gives the value true for the given argument. As we can think of it, we can either interrogate the number 2, asking whether it falls under the concept fourth root of 16, or we can interrogate the number 4, asking whether it is a logarithm of 16 base 2, or we interrogate the number 16, asking whether it is the fourth power of 2. It does not matter which number we interrogate, but we must interrogate one or another in order to answer our question. Now we need to think about the status of objects such as numbers and concepts such as being a fourth root of 16 relative to this conception of the language. Although at first they might have seemed to be what is really real, now they show up only relative to ways of regarding the sense, only from one perspective on it among others. What now appears invariant is the sense, the thought expressed, and also the truth value that is the Bedeutung of the whole formula. The thought conceived one way appears to be about the number 2, but conceived another way it appears instead to be about the number 4, or about the number 16. Independent of any analysis into function and argument, the thought is in a kind of superposition of all possible analyses that is collapsed when we perform our function/argument analysis. The formula 24 equals 16 directly gives the free gene thought, which is not about any particular number, although, again, to interrogate that thought, determine its truth value, we must regard it as being about something in particular. In much the same way, we can think of the equation giving the probabilities of various outcomes as directly giving the reality we are interested in. But the only way we can interrogate it is by measurement. The reality is not given by the measurement or even by a whole collection of measurements, it is given by the mathematics. But because we are doing physics, which is not an a priori science,
the way to interrogate that reality is by making measurements, and in this case, by contrast with that of 24 equals 16, taking one measurement can preclude taking another, as if having once read 24 equals 16 as being about the number 2, one could not go back and see it instead as about the number 4. So measurement clearly changes something. But again, the fact that the mathematics itself predicts this is significant. Much as Einstein does, we can regard the relevant mathematics not as descriptive of some phenomenon to be explained by a theory about what is really going on, but as directly disclosing the reality we are investigating. In our imagery, the mathematics is disclosing the cube of which our measurements provide only glimpses. Again, this should not be taken as a positive suggestion. The aim is only to indicate the kind of possibilities that open up when we self-consciously give up the sideways on view and take instead the standpoint of reason. It provides a way we might conceive the relationship of our measurements and the mathematics of quantum mechanics. On this sort of account, it is the mathematics itself that reveals the structure of quantum reality. So far as it is revealed, the measurements are only confirmatory of the mathematics. But the image also seems to commit us to something more, namely, a hidden variables view of quantum mechanics, insofar as there is in our image a fact of the matter regarding the orientation of the cube, which would explain why it appears as it does on an occasion, only we do not know, before measuring, what it is. But this too, we shall see, can be called into question. The mathematics of quantum mechanics predicts precisely what we find on repeated measurements. For instance, interference in the double-slit experiment, Heisenberg uncertainty, and what appears to be non-locality for entangled particles. What is wanted, in keeping with the overall account we have outlined, is not a constructive, that is, reductive and mechanistic, theory that posits some underlying physical reality to explain the appearances, but instead a way of thinking directly about the mathematics involved, how we should think about what it is revealing to us about the fundamental structure of matter, not what matter is made of but what it is in its own nature. Again, the aim here is not to provide such an account, it is only to begin to alter our understanding of the space of possibilities within which such an account might be sought. And to that end, it will be useful to reflect on the nature of various sorts of temporal processes. Point 8. It is a familiar fact of our everyday lives that we can be doing something, get interrupted, and as a result never finish what was started. Any ordinary instance of making something, say, a cake or a bookshelf or a trip somewhere, is like this. Even in instances in which one is interrupted for some reason and so never actually makes the cake, or bookshelf, or trip, still it is true that one was making a cake, or a bookshelf, or a trip. And the same can be said about various things that non-rational animals do. A bird is building a nest even if the nest does not get built because, say, a hungry cat fatally interrupts things. Such happenings, I will say, occur in narrative time. They are like stories that have a natural end, somewhere they are going, but can be left unfinished. Think now of a stone that has become dislodged and is, as we would say, rolling down some hillside. The stone is stopped by a felled tree halfway down the hill. Was the stone's trip interrupted? Aristotle might say so insofar as the tree impeded the stone's natural motion, but we would not. A stone can roll all the way down a hillside, but if it does not because it is stopped by some such thing as a felled tree, then that was not what it was doing. It was simply rolling and would continue to do so until something stopped it. Similarly, although I can be extinguishing a fire and be interrupted, the rain cannot be extinguishing a fire and be interrupted. Rain can extinguish a fire, that is, it can rain long enough on a fire that the fire goes out. But until it has in fact extinguished the fire, the rain is simply raining, as it happens, on a fire. In this case, as in the rolling stone case, not only can the process not be interrupted, there is no sense in which it was doing that even in cases in which the result comes about. Even if the rain does extinguish the fire, and the stone does roll all the way to the bottom of the hill, we cannot say, even if only retrospectively, that it was doing that all along. Such merely physical processes simply happen, one thing followed by another followed by another. They happen in block time. The two sorts of processes just outlined differ along two dimensions. First, a process in narrative time can be interrupted, though a process in block time cannot. And second, a process in narrative time is teleological, a doing towards some end, while a process in block time is not. In block time, one thing is followed by another, and then another, there is nothing more to it than that. It furthermore seems clear that the idea of a process that can be interrupted but is not teleological is incoherent. If a process is not heading somewhere in particular, then it cannot be interrupted along the way. How about a process that cannot be interrupted but is nonetheless teleological, a doing towards some end? To make sense of this possibility, we need to suppose that although, if it is not completed, one cannot say that it was nonetheless happening, nevertheless, if it is completed, then it is right to say that that was what was happening all along. Having a brilliant career, or a successful marriage, or a happy life may be like this. If the arc of such processes is not completed, one's career starts out brilliantly but then fizzles, one's marriage turns sour and never recovers, one's happiness is destroyed late in life by a terrible tragedy, then it seems right to say that one was not after all having a brilliant career or a successful marriage or a happy life, but only for a time seemed to be. In such cases, the process cannot be going on but get interrupted, as cake making can be going on and get interrupted. If it gets interrupted and remains unfinished, then it was not after all going on. But if it does get completed, then, unlike the case of the rain or the rolling stone, it seems right to say that the process was going on all along, that one was having a brilliant career, a successful marriage, a happy life. And this seems to be true also of evolutionary processes. In the biological case, for example, it seems incoherent to say that some species or other was evolving, coming to be, but that the process was interrupted so that the species never appears. Nevertheless, it seems right to say, once the relevant species is on the scene, that it had been evolving towards what it in fact became. Processes in evolutionary time are such that there is no fact of the matter regarding what is now going on except in the light of what will be, how things in fact turn out. To have been baking a cake, one needs a past of a certain sort, one that involves measuring flour, breaking eggs, and so on, even if no cake eventuates. To have been embarked on a brilliant career, one needs not only a past of a certain sort, one that involves some measure of success or at least promise, but also a future of a certain sort. If no brilliant career eventuates, then one was not after all embarked on a brilliant career. Similarly, for something to have been the evolutionary precursor of some species, there needs to be not only the right sort of past but also the right sort of future, one in which the latter species does come into being. Evolutionary processes thus raise questions that can be answered only retrospectively, not merely because we are ignorant of where they will end up, but because it is not settled where they are going, or even that they are going somewhere, until they get there. In the case of merely physical processes, the rolling stone, say, or a leaf that falls from a tree, we also cannot say where it will end up until it ends up there, but this is due merely to our own ignorance. Classical physics together with all the facts do settle it. Evolutionary processes are not like this. They are instead like processes in narrative time insofar as once they have happened, they exhibit something like a narrative arc, a beginning, a middle, and an end. They are, that is, teleologically structured, though, again, it is only settled at the end of the process that there is such an arc through the process as a whole. We can apply this idea of an evolutionary process to the case of quantum mechanics as follows. As already indicated, it is common in discussions of quantum mechanics to raise the question whether the probabilities that the state function gives are objective probabilities in the sense of giving us information about the system, or whether instead they reflect only our ignorance, until we measure, of what is actually the case. If they give objective probabilities, then it can seem to follow that the state is in a superposition of all the relevant possibilities. If the probabilities are instead a reflection only of our own ignorance, then the system is already in some definite state, one and only one of those possible, only we do not know which. We make our measurement in narrative time. A measurement is a process of setting things up, initiating the experiment, and so on, and it can be interrupted. But we heirs of early modernity expect that the thing we aim to measure is in block time, that it is fully what it is at every moment, and hence that either the system is in a superposition or it is not in a superposition. But now we can see that there is also a third possibility. If we think of quantum processes as processes in evolutionary time, then the either/or, either superposition or ignorance, does not apply. In that case, the process of completing the measurement is what settles how things were before the measurement was made, insofar as what the system is doing before the measurement is made is in part a function of how things end up, that is, the particular measurement that is ultimately made. If quantum processes occur in evolutionary time, then what state a system is in now is a function not only of the past, including past measurements on it, but also of the future, what measurements will be made, how things will turn out. By measuring we thus can bring it about that something in particular was true in the past, in much the way the emergence of some species brings it about that it was the case in the past that the evolution of that species was taking place. On such a view, there is neither a superposition of states nor ignorance. The mathematics provides everything that could possibly be provided prior to any measurement. It leaves nothing out despite being probabilistic, because what it leaves out has in fact not been settled yet. It tells us with what probability this or that future will be realized provided that the appropriate measurement is made, and that just is what is now settled, before a measurement realizes some future in evolutionary time. Point 9. Evolutionary processes do not merely happen in time, whether the flowing narrative time of our everyday lives or the block time of classical physical processes such as stones rolling down hills. They are instead constitutively, profoundly temporal. Their being is in time, and cannot be understood apart from it. As we can think of it, their being is to become, that is, to evolve, not merely in the sense of changing but in the sense of becoming something in particular, the kind of thing that, as it turns out, it was always already on the way to being. And because of this there is in evolutionary time a kind of symmetry between past and future, just as there is in the case of processes in block time. In the case of block time, as contrasted with the time of our lives in which we can know the past but not the future, we can use the past to predict the future, and, at least in principle, the future to predict the past. Either is determined given the other. In the case of evolutionary time, there is again symmetry, only this time it is a symmetry of ignorance, that is, indeterminacy. Until things have in fact turned out some way or other, there is no fact of the matter, either what was or what will be. Perhaps what the mathematics of quantum mechanics is disclosing to us is the reality of quantum processes unfolding in evolutionary time. 9.3 Completing the project of modernity. Our ancient mode of being in the world, as enabled by a socially evolved natural language, reveals a perceptible world of, in the first instance, living beings. It is a world in which we are at home as the animals we are. To the early modern mind, such a self-understanding is a misunderstanding and must be rejected in favor of, on the one hand, a mechanistic conception of nature as the realm of law, and on the other, a conception of ourselves as autonomous, where autonomy is conceived in opposition to nature but at the same time on the model of nature, as self-rule. Our contingency and finitude seem, however, to limit this autonomy. Although, as Kant almost saw, our autonomy is not opposed to but completed by the objectivity of the world, the fact that we are finite beings for whom something must be given in sensory experience ultimately entails, for Kant, that we know only things as they appear to creatures like us, not things as they are in themselves. Our contingency and finitude are, on the Kantian view, incompatible with true autonomy and full objectivity. But as I have argued, we are not only contingent, finite beings but also essentially historical beings, beings whose rationality is fully realized only in time, through a process of maturation, transformation, and growth. And once we see this, we are in a position to come to realize as well that contingency and finitude are not merely compatible with autonomy and objectivity but constitutive of it. Paradoxical as it may at first seem, only a finite being can be fully autonomous, capable of knowledge of things as they are in themselves, the same for all rational beings. It is Freya who provides us with the conception of language as the medium of disclosure of reality that is required in order to understand this. But we also need something more. We need to distinguish, as Freya did not, at least explicitly, between natural language, which is constitutively narrative, sensory, and object-involving, and mathematical language, which is not. And we need to recognize that we do not have to choose between these two sorts of language. We need to realize that if one is more basic along one dimension, the other is more basic along another. Both sorts of language, and the modes of intentional engagement with reality they enable, are needed in any fully adequate understanding of the striving for truth in the exact sciences. The advent of modernity in the 17th century constituted a rupture with the past, a decisive turn away from the old to the new. The task of science, as science came to be understood in the 17th and 18th centuries, was to discover the reality behind the appearances, how things really are given how they appear to us. The developments in the exact sciences begun in mathematics in the 19th century and furthered in fundamental physics in the 20th, I have suggested, take a very different shape. These developments constitute not merely another break, another turn this time away from the merely modern, but instead the full realization of the intellectual aspirations of modernity, though in a hitherto unimaginable way. And at the heart of these developments is Freya's discovery of the logical distinction between the two distinctions, on the one hand, that between Sinn and Bedeutung, and on the other, that between concept and object. It is this logical distinction of distinctions that is, we have seen, the key to a fully adequate conception of truth and knowledge in the exact sciences. Descartes achieved a new mode of intentional directedness on reality through a metamorphosis in his most basic understanding of what is, and as a result learned to distinguish in a way hitherto inconceivable between the sort of meaning we find in the world in our everyday lives and the new sort of mathematical meaning that was disclosed in his new science, Mathesis Universalis. From the perspective Descartes achieves, the ancient view of the world, which just is the view of our everyday lives, is shot through with confusion. In particular, attributes that properly belong, and can belong, only to minds are projected onto bodies, they are taken to belong to bodies as if bodies themselves could be minded. Thus it comes to seem that although we find it natural to take things, an apple, say, actually to have sensory properties such as color the apple, we take it, is itself red in reality it is inconceivable that a mere object could have the very color I experience it as having. In reality, the apple is mere physical stuff and has only the properties that mere stuffs can have, namely, mathematically describable properties. The redness we experience it as having is only a projection, not really a property of the apple at all. This early modern view in which minds, our self-conscious experience and thought of things, are to be conceived in isolation from mere things, including our own bodies, thus gives rise to the sideways on view according to which outside are mere stuffs while inside are meanings. Forgetful of the fact that the early modern view of reality is after all a view and as such fully meaningful to us, albeit in its own distinctive way, it comes to seem that with modernity we achieve a perspective on things that is somehow outside the subject-object nexus altogether, that we achieve, at least in thought, the God's eye view, the view from nowhere. In our becoming explicitly self-conscious of our own self-consciousness, it comes to seem, that is, that our subjectivity is not merely our being towards objective reality, our mode of being in the world, but itself something objective, something somehow in the world in much the way other things are in the world. Subjectivity, consciousness itself, must, then, be available to the scrutiny of science. Somehow consciousness is to be explained in terms of the workings of the brain. The sideways on view, although in fact a metaphysical thesis made possible by Descartes' advances in mathematics, comes in this way to seem to be simply a fact about us, something we have discovered in the course of our empirical inquiries. With modernity comes the idea that it is a finding of science that the sideways on view is correct, that really, as scientists have shown, there is outside only mere stuffs and inside meanings. Outside are causes and objects, inside are norms and concepts. This conception gives rise in turn, as McDowell has shown, to an intolerable oscillation between, on the one hand, an empty coherentism, and on the other, a vain appeal to what Sellers calls the myth of the given. And as McDowell indicates, it is Freya's notion of sense that enables us to dismount from the seesaw. But, I have urged, we need not only that, more exactly the conception of language as a medium of disclosure that it enables, but also to distinguish between two radically different sorts of languages. We cannot merely turn our backs on the practice of science, directly recover a more Aristotelian conception of our being in the world, because we know as Aristotle did not that we are not natural in precisely the way that non-living things are natural. Furthermore, as we also now know, it was a development in science, in mathematics in particular, that provides the resources that are needed to achieve a stable conception combining the insights of the ancient Greeks with those of early modernity. The Phrygian notion of sense comes into view only with the development of a mathematical language of the sort Freya provides, for, we have seen, only in this case is there a clear distinction to be drawn between sense and signification. It is from Freya's mathematical language that we first learn to conceive of language as a medium of disclosure, a lesson that can then be applied also to natural language. But if that is right, then instead of turning our backs on the practice of science and the sideways-on view that it has engendered, we need explicitly and self-consciously to take up that view and transform it from within, by appeal to the self-same disciplines that engendered it, just as we have done here. According to the conception that is enabled by a Phrygian understanding of language, we are, as the rational animals we have become through our acculturation into a socially evolved natural language, always already cognitively oriented on reality. Having learned to distinguish the Sinn/Bedeutung distinction from that of concept and object, we can now understand how language is the medium of our cognitive involvement in the world, how language at once gives us the eyes to see and by the same token the world a face by which to be seen. In place of the modern inside/outside picture, the sideways-on view that conflates Freya's two distinctions, we now have a conception according to which we have two fundamentally different modes of intentional directedness on reality, one that is mediated by natural language and directly reveals aspects of that reality, and another that is mediated by a fully realized mathematical language. In this latter case, one's cognitive relation to reality, we have seen, is not direct but instead occurs in two steps. First, in mathematics, one achieves cognitive grasp of the concepts of modern mathematics, concepts of reason, through the clarification of the senses of concept words. Then in fundamental physics, one employs those concepts in coming to know things as they are, the same for all rational beings. In both cases Phrygian sense is that through which, as the medium or vehicle of awareness, we are in direct cognitive contact with reality. But, again, there are two very different ways this can work, through the medium afforded by natural language and through the medium afforded by a fully realized mathematical language of the sort Freya developed. The view of reality that is afforded by natural language is simply that of everyday life, a view of living beings with their natures and powers, and of perceptible things more generally. The view of reality that is afforded by mathematical language is not like this. What mathematical language directly yields is knowledge of concepts of various sorts of entities. It is most immediately the medium of our cognitive grasp of mathematical concepts. Those concepts are then employed in turn in fundamental physics and enable us to discover how things are, the same for all rational beings. Point 10. Much as Newtonian physics is a necessary stage on the way to Einstein's physics but one that must eventually be superseded, so the sideways-on view, with its meaningless outside and meaningful inside, is a necessary stage on the way to the Phrygian view according to which we are always already cognitively directed on reality. As Newton paves the way for Einstein, so Kant paves the way for Freya. The incoherent inside/outside picture thus gives way to a conception according to which we, now fully modern, must recognize as involving two essentially different modes of intentional directedness, one that we have as the embodied rational animals we always already are, and one that we have achieved through the course of intellectual maturation and growth that has been traced here and has come to fruition only very recently.
And although on the early modern view the exact sciences reveal how things really are as contrasted with everyday experience, which is merely how things appear to creatures like us, this distinction between reality and appearance is revealed, in contemporary science, to be misplaced. As we now can see, the world as it is disclosed in everyday experience is just the world, it is fully real. But our everyday view of reality is a view that is available only to beings sufficiently like us, to beings with our sort of animal life. The view afforded by the exact sciences, because and insofar as it is purely rational, that is, mathematical in a way that is divested of any and all sensory content, is different. It is, in principle, accessible though only in time, through a process of maturation and transformation to any rational being, whatever its biological and social inheritance. The view afforded by the exact sciences is in just this sense maximally objective, the same for all rational beings. But, again, that does not mean that it is in some way more real, as if our everyday view were merely an appearance. To think that the view achieved by the exact sciences is not only more objective but also more real is to fall back into the sideways on view, the incoherent conception of a meaningless outside and meaningful inside. Whether we adopt the everyday perspective of natural language or that of a fully realized mathematical physics, the world is fully meaningful to us, it is the objective correlate of our subjectivity, the reality on which we are intentionally directed, whether perceptually or intellectually. But the world as disclosed in fundamental physics is also inevitably impoverished. Because and insofar as it is the same for all rational beings, whatever the shape of their lives, the only value it can bear is that of truth. The world as disclosed in everyday life is, by contrast, rich with other sorts of value as well, not only truth but also, for instance, moral and aesthetic value. Rational beings with radically different forms of life from our own, owing to their very different forms of life and in particular to their very different ways of perceiving and acting, could find different moral and aesthetic values in the world from those we find. 11 But, again, that does not make those values any less real. The idea that values other than truth are merely subjective impositions is merely another excrescence of the modern inside/outside picture that Freya shows us how to dismantle. The lives of rational animals, precisely because they are the lives of such animals, that is, of rational beings who perceive and act as well as judge, are inevitably rich not only with the value that is truth but also with aesthetic and moral value. Although early modern thinkers were puzzled by this, and reasonably so, we should not be. We should no more expect such values to be absent from the world as it is disclosed in our everyday lives than we should expect them to be present in the world as it is disclosed to pure reason in fundamental physics. The world disclosed in fundamental physics is the world as thought, as grasped in judgment, it is the world as it is the object of contemplation, the same for all rational beings. It is not the world as it is the arena of our actions and perceptions, including our actions and perceptions as practicing mathematicians and physicists. Again, we need both the rich but not fully objective view of reality with which we begin and the impoverished but fully objective view of reality that we achieve through the course of our intellectual inquiries, culminating in a language that is the language of reason itself. On the account we have developed, the concepts of fully modern mathematics that have been developed over the past 2 centuries are concepts of reason. Because they can in turn provide us a view of reality that is fully objective, the same for all rational beings. And they do so, we have seen, directly in the following sense. Whereas in classical physics there is always a physical correlate for the mathematical concepts that are employed, in contemporary physics, there is no physical correlate but only the mathematics. The ultimate natural kinds in science are those of pure mathematics, the ultimate language of the universe is that of the mathematician. Steiner argues that this Pythagoreanism of contemporary physics is profoundly anthropocentric, and hence that its spectacular success is deeply mysterious, even magical. Those conclusions follow, however, only if one thinks, as Steiner does, that mathematics has no proper subject matter of its own, that concepts are selected as mathematical because they foster beautiful theorems and beautiful theories.
Because, Steiner thinks, mathematics, at least as it has been practiced since the 19th century, is merely formal, without content of its own. The only criterion he can discern for distinguishing real mathematics from mere games with constructs is the mathematician's sense of beauty. And then it really does seem to be a mystery how mathematical concepts so identified might be revelatory of fundamental features of reality. But Steiner's is not, we have seen, the only way we can think about the practice of mathematics in the wake of developments in the 19th century. The alternative, Freya's way that we have pursued here, according to which mathematics is properly a science with its own subject matter, does not only not make a mystery of the role of mathematics in contemporary physics, it explains this role. Because and insofar as the concepts of modern mathematics are fully rational, that is, wholly nonsensory, they are precisely the sorts of concepts that can reveal things as they are, the same for all rational beings. That our most objective account of reality is mathematical is, on the account we have developed here, not at all a wonderful gift which we neither understand nor deserve, as Wigner famously claimed. It is precisely what we should expect. 9.4 Conclusion. Early modernity bequeaths to us a puzzle about our knowledge of things as they are that takes the form of an inconsistent triad of claims, that the world is radically mind-independent, that the spontaneity of thought is wholly unconditioned, and that judgment essentially involves rational constraint by what is. What we have since learned is that this triad is not inconsistent, though it must seem so to a thinker such as Kant, who has learned to draw a logical distinction between concept and object, and hence sees the problem, but has not yet learned to make the distinction between Sinn and Bedeutung, on the one hand, and concept and object, on the other, that is required in its solution. It is this latter distinction of distinctions due to Freya, combined with the fact of our historicity, that has enabled us to understand how a radically mind-independent reality and an unconditioned spontaneity are not only compatible but in the end made for each other. Because our spontaneity is unconditioned, because there is for it no given, nothing unquestionable in principle, we can in time develop the language that gives us the eyes to see things as they are, the same for all rational beings. It is in just this way that the radical otherness of the world, its full objectivity, completes the spontaneity of thought, in just this way that the spontaneity of thought and the objectivity of the world form an intelligible unity. As we are now in a position to see, judgment, as the acknowledgement of the truth of a thought, realizes a cognitive relation of knowing between a rational subject and a bit of empirical reality. The power of reason is fully realized as a power of knowing. Although we begin, as the rational animals we are, with a view of reality that is shot through with the contingencies of our particular biological, social, and historical being, we also begin with a yearning for something more, for a kind of knowledge that is not merely partial, limited, and frustratingly perspectival. And in the end we achieve it, not by somehow transcending our limited, perspectival bodily being in the world, but by realizing, finally, that only such a being can know things as they are. Judgment is an act not of productive freedom but of expressive freedom. It leaves everything as it is. To judge truly is to make manifest the otherwise latent structure of reality. But it is only in the end that we can understand this. Only with the realization of reason as a power of knowing can we recognize ourselves as knowers of things as they are, the same for all rational beings. Afterward, in the 19th century, mathematics was transformed to become as it remains today a wholly conceptual enterprise, the work of pure reason. And with this transformed mathematical practice came a new problem for philosophy. Ancient diagrammatic practice had posed for philosophy the problem of the ontological status of its objects, of the being of the intelligible unities that form, so it was thought, the subject matter of the science. Early modern algebraic practice posed instead the problem of our ability to know its synthetic a priori propositions, propositions that are again intelligible unities insofar as they are necessary but not logically necessary. Contemporary mathematical practice poses the problem of its form of reasoning, its proofs, which as at once ampliative and deductive constitute yet a third sort of intelligible unity. Freya solved this problem in 1879. and in so doing he provided the key to any adequate account of truth and knowledge in the exact sciences. The philosophical problem of truth and knowledge in mathematics concerns how mathematics works as a mode of intellectual inquiry into objective truth, and it can be adequately resolved only after that practice has matured into a purely intellectual endeavor. Although mathematics can only begin as a form of inquiry that is dependent on our sensory and motor capacities, manifestly so in Euclidean geometry, but, Kant saw, evident also in the constructive algebraic practice that dominated mathematics in the 17th and 18th centuries, eventually all sensory content is stripped away to reveal a mode of inquiry reliant solely on pure reason. Both the concepts of contemporary mathematics and its methods are purely rational. But knowing that contemporary mathematics is a purely rational enterprise is not sufficient for an adequate conception of mathematical inquiry. One needs also, we have seen, to achieve a conception of judgment as an act of spontaneity, of expressive freedom, that when successful is an exercise of reason as a power of knowing. To judge, acknowledge the truth of a true thought, is to make up one's mind through inquiry, that is, in the case of mathematics, through proof, though, as we now know, proof is a means of inquiry only because and insofar as it is embedded within a practice that conforms to the Aristotelian model of science and hence is constitutively self-correcting. And even this is not yet sufficient. For none of this can really make sense without our having wholly and unequivocally dismantled the sideways on view that we inherit from early modernity. Transformations in the exact sciences in the 17th century required that we embrace the image of the mind as an inner space standing over against a merely causal, normatively inert physical reality, our learning to think of our mindedness in opposition to physical reality, and to distinguish in principle between reasons and causes, was an essential stage in our intellectual maturation. But as we now know, this was, though necessary, only a stage, one to be gone through and then left behind. The natural languages into which we are acculturated at once give us the eyes to see and reality a face by which to be seen, and it follows directly that we rational animals are always already in cognitive contact with reality. But we can come adequately to understand how this can be only by reflecting, as we have here, on the historical unfolding of our intellectual investigations from the first appearance of reason through to its full realization. And here we come to see something else as well, something that, unlike the problem of truth and knowledge in mathematics, or that of the relation of mind and world, the tradition had no inkling of, namely, that what all this historical unfolding was about was reason's realization as a power of knowing. This is something that could not have been foreseen. Only after reason has been so realized is it possible to trace out the trajectory as that of realizing reason as a power of knowing. It happens in evolutionary time. And that is why our account of truth and knowledge in mathematics, of how mathematics works as a mode of intellectual inquiry, has taken the form it has, that of a narrative, a story with a beginning, in the first appearance of reason, a middle, in which reason is transformed in the 17th century, and an end in reason's full realization as a power of knowing in the 19th century. But again, although the 19th century developments in mathematics mark the end of our story, it is those same developments that are what make our story possible at all. Frege designed his concept script as a language within which to reason deductively from defined concepts, and it was in the light of this language that he learned to distinguish the Sinn/Bedeutung distinction from that of concept and object, where this distinction in turn is the key to an adequate understanding of the nature and role of language in our cognitive lives. Only the development of a sufficiently advanced mathematical language can enable us to understand how the acquisition of language makes possible our cognitive relation to reality. Our acculturation into natural language and an essentially social form of life is what first opens our eyes to the world of everyday experience, but it is our acculturation into a sufficiently advanced mathematical language and culture that opens our eyes to fully objective reality, things as they are, the same for all rational beings, and thereby enables us adequately to understand even our everyday being in the world. For the second time in its long history, mathematics was transformed in the 19th century. Physics similarly was transformed, for the second time, in the 20th century. Philosophy was not transformed but has, until now, remained merely Kantian. This story of reason's realization aims to take the first step. What comes after will be for others to tell. One cannot jump over one's own shadow.